Welcome to the Assembly, EVM opcodes, and Formal Verification Smart Contract course. This was previous part 2 or part 3 of the security course, but we decided to branch it off because we do teach a lot of stuff that maybe even security people don't care to know, maybe just advanced smart contract developers want to know, but we figured we'd put it in its own spot. And this course is pretty insane. This course is for those developers and security researchers who want to hit that top 1% of blockchain knowledge. If you take this course, if you go through all the way to the end of this course, at the end of this, you will be able to disassemble smart contracts. You'll be able to learn bytecodes. You will be able to, at the lowest level, understand how to make your contracts more gas optimized because you understand what every single opcode does. Additionally, we're going to teach you how to write your own smart contracts in opcodes. And we're going to do that by teaching you about 2 languages called Yul and Huff. These are 2 very low-level smart contract programming languages that allow us to build insanely gas-optimized smart contracts. As always, on Cypher and Updraft, the approach we take is by doing project-based work. And we're going to be working specifically with 3 projects that might seem like it's a very small course because it's only 3 projects, but we go very deep, very advanced, and we take very different routes to these 3 projects. And then finally, in the second and last sections of this course, we're going to teach you formal verification. If you're here at this course, you should already be familiar with what fuzzing is. Fuzzing is always going to be the step you should take in your smart contracts before you come to formal verification. So if you're here, you should already understand fuzzing. Once you understand fuzzing, once you understand invariants, we can go one step further and do something where we actually formally verify our smart contracts. Fuzzing is incredibly powerful because it does a whole bunch of random stuff to try to break some invariant of our protocol, but formal verification can actually prove if that invariant holds in all cases. And it is an incredibly powerful tool for testing smart contracts. Vitalik actually recently put out a Twitter post where he was excited for AI to actually help write these formal verification tests. And as of right now, a lot of formal verification is a bit of a nice to have, but there are a lot of cases where formal verification has actually found massive critical vulnerabilities. And arguably, I believe that as we make formal verification easier and easier to use, it's going to be the future of testing along with fuzzing for smart contracts. We're going to teach you to use 2 very powerful tools, Halmos, Certora, and we're even going to walk you through some other tools like control by runtime verification. So because this is so level, because this is so intense, because what we're going to be learning is so much harder than a lot of the stuff that's on Updraft, we're going to be throwing away a lot of the funny business. Okay, I can't help myself. I'll probably still sometimes make some bad jokes. If you want to become a top smart contract developer, you need to know this stuff so that when you're doing gas optimizations, you can understand exactly how these works. And a lot of top smart contract developers code assembly in their smart contract for one reason or another. And for you security engineers out there, a lot of the best smart contract security researchers do fuzzing in their private audits and sometimes in their competitive audits as well. But additionally, some of the top smart contract security researchers go an extra step further where if their fuzzing doesn't quite pan out, they go the extra mile and try formal verification. And sometimes in specific scenarios, that's where they'll find a bug. But some of the most important things we're going to be teaching you here is as you get this experience using these tools, you're going to learn when these tools make sense to use, when formal verification makes sense to use, when fuzzing makes sense to use, and so much more. So this is probably going to be the most advanced EVM smart contract course you'll ever take, period. And if you're here, it's because you are already a really good smart contract or Solidity or even a Viper developer at this point, and you're looking to take it to the next step. And that's what we're going to do in this course. We're going to bring you to the next step. So with that, as always, I want to give you a huge thank you for showing up to this course and taking this. This is how we scale Web3. This is how we make Web3 better by us as a collective getting smarter, getting better, getting more powerful when it comes to smart contract development and security. So buckle up, because we got a lot of work to do in this course. As always, let's get started with the best practices. So as always, let's jump into some best practices for this course. Now, whether you're taking this on Cypher and Updraft or on YouTube, there's some links that you need to know about. On any course on Cypher and Updraft, usually the welcome lesson is going to have some links for you to follow along. The most important link is always going to be this GitHub resources link that comes along with the course. because this GitHub resources link is going to have every single link, every resource, everything that you'll need to be good, to be successful in this course. Every single one of these courses additionally is going to come with a discussions tab, which will look something like this. This is where we want you to ask questions, engage with teaching assistants, etc., so that if you have questions about the course, you can come here. Whether or not it's YouTube or Cypher and Updraft, everyone should use this exact same link. If you are watching this on YouTube, if you scroll down into the description, the links for the GitHub will be in the description of the YouTube video itself. The links for the GitHub will be in the description of the YouTube video itself. So for this course, the Assembly, EVM opcodes, and formal verification, I'm building the course as I'm recording it. So if we go to this first lesson here, we can hit this GitHub resources bit, and it'll bring us to the GitHub associated with this course, which is going to have all the projects, all the code bases, all the examples, all the links, etc. in this GitHub. We'll additionally have a lot of them in the written lessons of Updraft as well. And again, I'm building this as I'm recording it. Be sure to click the links at the bottom, which will give you a link to the GitHub discussions. This is where you should ask questions about the course, and the Discord where you can chat with other students. Ideally, all of your technical questions should be in the GitHub discussions so that other students can find them a lot easier and use your conversations to help themselves out. Oftentimes, if you ask a technical question in the Discord, I will push you to the GitHub discussions. Now, importantly, I expect everyone who's taking this course to have some context on how to ask really good questions. But for those who do not, I have some docs in here, how to ask a question, which gives you a rundown of how to ask questions, and then also how to answer a question. I'll leave a link to the lesson in Cypher and Updraft where we go over both of these. Now, this space moves incredibly quickly. And because of that, sometimes we have to make updates to sections because the best practice has changed, the tool has updated, etc. And because of that, on Cypher and Updraft, if you scroll down to any lesson, there will be an updates section. So there will be an updates thing, a little number here. And for example, here we have example update, but in here, it'll give you the context and how to adjust what you're doing, whether you're coding, whether you're doing an audit, etc., so that you can continue to follow along with the video. So all the code should be up to date, but the video might be a little bit out of date, and you'll know that it's out of date because there will be that updates section here. If you find a video that you think is out of date, then be sure to go over to the GitHub discussions and ask a question, because oftentimes the video isn't out of date and there's just something you need to tweak in your code in order to get it right. All of this is to say, use the GitHub repo to your advantage. Use it for discussions, use it for code, use Cypher and Updraft to see the updates, and even in the GitHub repo, there will be a link to Cypher and Updraft talking about the different updates. And additionally, once we do get to the coding portion of this course, it's a good idea to code along with me as I'm explaining things. So having the video up as well as your coding screen is a good idea so you can follow along with me as I'm explaining it. Take breaks. I cannot tell you how many people have tried to rush through these courses and be like, oh, I'm going to finish in a single weekend. Your brain doesn't work like that. Your brain needs time to absorb the information. So take breaks. Maybe every 25 minutes to a half hour, take a 5-minute break. Or maybe you like working in longer chunks. Maybe take a whole hour and then take a 15-20-minute break. Don't try to rush through the whole video in a day. You're not going to retain the information. Go outside, go for a walk, grab some ice cream, get some coffee, go to the gym. Your brain needs time to have the information settle. Maybe every 2 hours, just step away, maybe be done for the day. Work at whatever pace makes sense for you. Everyone's going to have a different learning pace. There is no right speed for this course. I've had people take my courses in 2 weeks, in 3 months, in 6 months. It doesn't matter. Pick a pace that you can do and stick to it. Not only work at your pace, make sure that I'm talking at a pace that makes sense for you. Now, on both YouTube and Cypher and Updraft, there are ways to actually change the speed at which I speak. Here's how you can do it for YouTube. There's a little gear icon in the YouTube video here where you can change the speed of how I'm talking and how fast the video is going. So if I'm talking way too fast for you, then you can slow me down. But if I'm talking too slow, then you can speed me up. And for Cypher and Updraft, it's the same thing. There's this little marker in the bottom right where you can actually change the speed at which I talk or at which the video goes. Additionally, we have a closed captions feature or a subtitles feature. Right now, there's a whole list of different languages that are supported on Cypher and Updraft. If you'd like to add support for your native language, please make an issue or a discussion in the Cypher and Updraft GitHub repo. So make the adjustments you need to make me go the speed you want me to go. And of course, this course is modular. So you can bounce around topic to topic and go to where you want to go. Like I said, go the pace and take the learnings that you want to do. And after every lesson, it might be a good idea to go back and reflect on each lesson to really make sure the knowledge gets ingrained. Repetition is the mother of skill, and we're going to be repeating a lot of smart contract development. Blockchain development and open source development world is incredibly collaborative. So be sure to use tools like, of course, the GitHub Discussions tab, Ethereum Stack Exchange, the decentralized Q&A forum, Piranha, issues on different GitHubs, artificial intelligence, and more. And the reason I'm putting so much emphasis on this, and that I will continue to put so much emphasis on this, knowing where to go for information and how to collaborate with people is often more important than your smart contract knowledge. Because oftentimes you're going to run into issues you don't know how to solve. So we're going to teach you to unblock yourself on this and really anything in life. Plus, syncing with other people in the space makes it way more fun. And additionally, in here, we give some suggestions of some different AI tools or other forums where you can and should ask questions. Being a security researcher and smart contract developer oftentimes is more about knowing where to get the answer than memorizing the answer yourself. Now, for people using this on Cypher and Updraft, this doesn't apply to YouTube. All of these courses additionally come with a written lesson for each one of these courses. So if you're like, wow, that Patrick guy is really annoying and I would rather just read this, well then perfect. We have written lessons for each one of these lessons as well. Although we do recommend you watch the videos as well, because watching these videos can actually give you a lot more context about what something's supposed to look like, what it's supposed to feel like, etc. Now, additionally, just like all of our Updraft courses, each one of these lessons comes packed with a little challenge NFT that you can mint on a layer 2 to actually prove that you learned the knowledge. These are optional challenges, of course. You can use them to actually claim a badge to prove you actually know how to do whatever we were teaching in that lesson or section. Now, for this course, there are a lot of prerequisites. Number one, you need a very solid grasp of Solidity. Ideally, you have a very solid grasp of Foundry. And ideally, you have gone through the security and auditing course on Cypher and Updraft. If you haven't gone through these courses on Cypher and Updraft, that's okay. However, I highly recommend doing the security and auditing course before coming here because we teach you a lot of component skills before getting here. Some of the tools that we're assuming that you already know how to work with are going to be Foundry, VS Code, or some type of text editor, Git, at least knowing how to do Git clones, some basic Unix or Linux terminal commands, GitHub or any cloud Git provider. And if you're on a Windows machine, we assume that you have WSL installed, and that's what you're working with in your text editor. If you don't have these installed, we will have a link in the GitHub repo and in the written lessons of this course to the Cypher and Updraft lessons to actually install these tools so that you can go ahead and move forward. So if you do not have these tools listed on the screen right now installed, pause the video, go download those tools, and potentially, ideally, go back to the different courses that use these tools. We teach you how to use all these tools in the blockchain basics, all the way up to the advanced Foundry, and I highly recommend that as a prerequisite as well. There's a large assumption here that you're not a noob. You've been around the block, and because of that, I'm going to treat you as such. Get ready for a challenge that's going to level you up. So get ready for a challenging course that's going to explode your knowledge from being intermediate to advanced to a top 1% smart contract developer or security researcher. Let's dive into section 1, the horse store. Now, before we move on to Math Masters, I have a little optional video for you to watch, which will actually go over the differences between Viper and Solidity, but under the hood, and what causes the difference in gas that they take. You've just learned a lot about the Solidity compiler just by looking at the opcodes that it puts out. And especially, we've learned about the Solidity free memory pointer. In this video, you're actually going to learn how Viper takes a very different approach to compilers, which makes for some interesting gas trade-offs. So the difference between Viper and Solidity isn't just syntactic, it's also how they operate under the hood. So if you want to learn more about how these different compilers work and how the opcodes that they generate actually are very, very different, then watch this excerpt of Viper versus Solidity and why they have the gas trade-offs that they do. Have fun. Viper or Solidity? Which smart contract language is better? In this video, we will look at popularity, developer experience, gas optimization, opcode use, and gas optimization to compare the languages.
Dodge, duck, dip, dive, and...
We're going to be comparing Viper and Solidity because they are by far the two most popular smart contract programming languages. Additionally, we're going to include Huff and Yul because they are lower level languages that are great to benchmark to. And you can't really fairly assess Solidity without including Yul. The language holy wars on Twitter has fueled a little bit of this debate, but spoiler alert, they're all fantastic languages. Additionally, these languages keep improving over time, and in about a year, this video might be totally outdated. We'll find out. So let's start our smart contract gas smackdown. According to DeFi Llama, for total value locked, Solidity secures about 87% of all DeFi smart contracts. And then next is Viper at about 8%. Curve Finance being a big reason that Viper is up there. So if pure popularity is what you're looking for, you don't need to look farther than Solidity. Now for the next 3 sections, we're going to compare a smart contract that does essentially the same things. It needs to have a private number at storage slot 0, have a function with the read number function signature that reads what's at storage slot 0, and allows you to update that number with the store number function signature. And if you'd like to follow along with all the code here, we have a GitHub repo in the description with all the code that we're going to go through. So here's what the 4 contracts look like. Solidity, Viper, Just by looking at these 4 contracts, we can feel the developer experience of writing in these languages. Just looking at the code, we can see that Solidity and Viper are substantially quicker to write because there's way less code here. This makes a lot of sense as these are higher level languages, while Yul and Huff are meant to be lower level language code. For that reason alone, it's so easy to see why Viper and Solidity have so much more adoption. Higher level languages are generally easier understood by humans with more abstraction underneath the hood, while lower level languages are the reverse of that. They're harder for humans to understand, but you can be more fine-tuned with what you're doing. Now, let's focus on the higher level languages for a second, and I promise we're about to get to gas optimization. I promise we're so close. You can clearly see Viper draws inspiration from Python, and Solidity draws inspiration from JavaScript. So if you like Python, boom. If you like JavaScript, boom. There you go. Now let's talk developer experience tooling. I'm not going to go into tooling too much because the tooling for the high level languages is really good, and the tooling for the lower level languages isn't as good, but still good enough. Solidity definitely comes as a first-class citizen for most popular frameworks, like Hardhat, Foundry, Remix, and Brownie. Viper can be added as a plugin to these, but comes as a first-class citizen to Brownie, ApeWorks, and Titan Boa. Huff and Yul have a little bit less support, but with a Foundry plugin, you're good to go. All right, now let's talk gas. And specifically, we're going to look at the 3 most important parts of a smart contract: the contract creation gas costs, the contract runtime gas costs, and then the metadata as well. Contract creation gas is how much it costs to deploy your smart contract. Runtime gas costs are how much it costs to interact and call functions in your contract. And then metadata is optional data appended to the end of your code. It'll contain things like language, version, etc. Now, before we actually deploy these and see the gas comparisons, we actually need to compile these contracts. Now, there's a lot of different flags we can use to compile them more gas efficiently or less gas efficiently. And I'm sure I'm going to get a ton of comments because I already know some of the ways that I could have made these more gas efficient, but we've chosen just to go with some relatively popular settings for compiling your contracts. And if you want to check out the GitHub repo associated with this, you can see those, or we will put them on the screen right here. And after we compile them, we can now deploy them and see how much gas they consume. Now you'll notice this 5th column here called Sol Yul. Solidity can be combined with the Yul programming language, which again is one of these lower level programming languages, to make your Solidity go faster or be more performant. The idea here is that you get the high level advantages of Solidity while being able to tinker down with the EVM when you need to. As we can see, lower level languages like Huff and Yul are more gas efficient than Viper and Solidity, which makes sense because they're lower level. Viper seems to be a little bit more efficient than Solidity, and Huff and Yul seem to be both more efficient than both Viper and Solidity. Our Sol Yul seems to be the worst by far, but we'll see why that normally isn't the case. Now, before we understand any of these differences of the contract creation code, let's look at the runtime differences. Remember, we're going to be storing a number and reading a number from our contracts, and here are those results. We didn't have data for Yul because I didn't feel like making a Yul Foundry plugin, but I'm sure the gas costs there are going to be similar to that of Huff. Keep in mind, the gas costs here are running a whole testing function. That's why the number seems so much higher than it probably actually is. But we can still see there's a major difference in gas between these languages. Okay, so let's go back to the contract creation. So now we have a good idea of approximately what we're working with here. Now, I gotta warn you, we are about to get really nerdy, like really nerdy. And for this section, it's good to have some understanding of how EVM opcodes work. So I've left a link in the description to the OpenZeppelin Deconstructing a Solidity Smart Contract, which will give you a really good idea of how these contracts work and a lot of the opcodes associated with them. Because yes, we're going into opcodes now. So feel free to pause and take a look at that now. Again, remember, when you compile a smart contract, it's typically split up into the contract creation code, the actual runtime code, and then optional metadata, and then constructor arguments, but we're not going to go into that. Now brace your eyes, because here come the opcodes. In your compiled bytecode, you can typically find the 3 different sections, creation code, runtime code, and metadata, by looking at your bytecode and looking to see what sections are unreachable. This can be a little tricky, but typically looking for return opcodes, the F3 binary, is a good place to start. You can also look for opcodes like 39, which is the code copy opcode, which copies your contract onto the blockchain. And instead of looking directly at the binary, usually it's easier to look at the opcodes instead. Most compilers have an option to output the opcodes instead of just the binary. The Solidity compiler does something really nice for organization and adds an invalid opcode between these 3 sections to make them real easy to locate. Section A is our contract creation code, Section B is our runtime code, and Section C is our metadata. So for our contract creation gas comparisons, we want to focus on our sections A. Now here is the full binary of the contract creation code for all of these contracts. That's it. It's only a few opcodes that make up the contract creation bytecode. We aren't going to go over what every opcode and every piece of binary is doing here, but in the article associated with this video, again, in the description, we go over that for you if you're interested. Instead, in this video, we're just going to focus on what each language is doing differently to make for these gas differences. Now for contract creation, Huff, Viper, and Yul do pretty much nearly exactly the same thing. This list of 7 opcodes just takes your code and sticks it on chain. That's it. Now Solidity takes a slightly different route. And even these opcodes still do approximately what the other languages do. You can still see the code copy opcode here as well. It's all this extra stuff at the beginning that makes the differences in gas. Solidity is doing the following extra work. It's creating a free memory pointer and then checking to see if you sent any ETH when deploying your contract. And remember, these little bits of extra work costs gas. Anything you do extra costs gas. We'll talk about the free memory pointer later. But one of these things that is fantastic is it is checking to see if we're sending ETH with our contract. This is advantageous so that we don't accidentally send some ETH that becomes unrecoverable. We don't lock ETH into our contract forever. Solidity is looking out for us. Interestingly, if you add a constructor to your Viper code and then recompile, you'll get an ETH check in the Viper binary as well. Viper and Solidity looking out for us devs. Now it's these additive checks that are looking out for us are typically what make Viper and Solidity more expensive than Huff and Yul. They're doing some extra work under the hood to look out for us and protect us from doing something stupid.
Pop the hood. Pop the hood.
Yul and Huff, on the other hand, are going to say, hey, we're going to do only what you tell us to do. We're not doing any checks unless you tell us to do some checks. And it's this extra free memory pointer, which is why the Solidity code here is going to be so much more gas expensive. The Viper code after the Solidity and Solidity Yul is going to be the second most expensive because the Viper runtime code is just going to be bigger because it also does a lot of checks that we're going to see in a minute, while Huff and Yul are going to be around the same. Now let's talk runtime code. Remember, for the runtime code, we're measuring how much it costs to store and then how much it costs to read from our contract. And I was able to walk opcode by opcode through this by using Foundry test --debug and then my test function. It's really nice. I highly recommend you try it out. Let's start with Huff, and we'll just look at storing the number 77 by calling the store number function signature. Here are the opcodes for calling store number. The first thing that our contract does is it'll figure out what function to call based on the data that's sent. We send over data associated with the store number function. Then we store the data in the contract. Boom, that's it. Let's see what Viper and Solidity add on here. Viper is still doing those first 2 pieces that Huff does, although it looks like we add 3 checks in here. We make sure we have enough data to call a function. We make sure we didn't send any ETH, and then we make sure we have enough data for a number. These checks make sure that users don't accidentally send some data to our contract that screws it up or locks money in our contract forever. It costs extra gas, but it makes us extra safe. Now let's see what the major difference in Solidity is. We can see Solidity does the same 3 checks, has that additional free memory pointer, and takes a slightly different route on how it sets up the contract and does the checks. So what are the main differences between these languages? Solidity has the free memory pointer. Viper and Solidity both do extra checks on ETH and data size, and they all have slight difference in which opcodes they use to do what. That last piece typically makes negligible gas differences, but it's interesting nonetheless. For example, Solidity uses is0 versus Viper uses XOR, even though they kind of do the same thing, and it doesn't really make a difference. But okay, so what's this free memory pointer? Why does Solidity have it, but not Yul, not Viper, and not Huff? And here's another one of the major differences between the languages: how they manipulate memory. Memory in the EVM is a big array that is alive for the duration of a function. Once the function ends, memory ends. And when you want to put something new into memory, the free memory pointer always points to the end of the memory. So you always know what index you can add memory to. If you want to add memory, check the free memory pointer, add your stuff to where it's pointing, and then update the pointer. This is great since there are data structures like dynamic arrays that we may have to load into memory, and they won't be sure how much memory we need to allocate them. So we need a way to allocate dynamic amounts of memory. Viper does this a little differently. Viper doesn't allow for variables to be of unknown sizes. So it doesn't need a free memory pointer because it always knows exactly how much memory it's going to need to call a function. So instead, at runtime, Viper just allocates the spots where it needs and assigns everything to a position in memory. This is also why Viper doesn't get stack to deep errors, since it's using memory statically as opposed to dynamically. In Viper, there are no dynamic data structures. You are forced to say exactly how big your arrays and how big your objects are, which is why Viper can assign memory statically. Now, this might sound like an advantage, and you'd be like, oh, well, why doesn't every language just do that? Let's look at an example of a trade-off. In Solidity, we can declare a dynamic array with no size constraint. We can always push more items to an array, and when we load the array into memory, our array could be of any size since the array is dynamic, and we need the free memory pointer to know where to put our memory. In Viper, you can have a dynamic array, but you must specify a maximum size. When you load an array into memory, Viper will always know exactly how much memory it needs, so it doesn't need the free memory pointer. This means that Viper can often be more gas efficient than Solidity when it comes to memory management. This can be seen as an advantage or a disadvantage depending on who you talk to. And remember, Huff and Yul don't do any of this, they just do exactly what you tell them to do. Speaking of Yul though, looking at my chart above, working with Solidity and Yul seems to be like the worst option, since at least the contract creation code is so much more expensive. However, we know from bigger projects that this isn't the case. One of the most popular projects that was written as a Solidity version and then as a Solidity and Yul version is the Seaport project. And after a git clone and a few tweaks, we can run our gas comparisons. On average, the function calls performed 25% better on the Solidity and Yul versions, and the contract creation performed about 40% better. That's a lot of gas. Wonder how much they could have saved in pure Yul. Wonder how much they could have saved with Viper. I wonder. And finally, the metadata. Viper and Solidity both append some extra data to the end of our contracts. It's small enough though, and it's only a one-time expenditure, so we're basically gonna ignore it. And if you want to, you can chop it off anyways. Whew, okay. We've gone through a lot here. So I know at the beginning I told you use whatever you want, but it's time for my official recommendation. And my official recommendation for the smart contract language that you should use is whatever you want to use. But seriously, each one of these has their advantages and is worthwhile for production EVM code. And here are my final thoughts on all of this. If you're coding production smart contracts, use Viper or Solidity. They're both high-level languages that will protect you from shooting yourself in the foot by looking at call data sizes and accidentally sending ETH and safe math, and they're just both great languages. So pick whichever one and have fun. Huff and Yul are fantastic languages if you need very specifically performant code or you're looking to learn more about the EVM. I don't recommend using these languages for all your production code. I do think though, they are fantastic to learn and understand. And then finally, understand the memory differences between Viper and Solidity. Again, one of the main differences in our gas costs is going to be this free memory pointer. Keep this in mind when you get advanced and you're looking to understand more of the underlying differences between these tools. Whew, we have learned a lot here. I hope you did too. Now, these languages will continue to evolve and we'll likely continue to see more EVM languages pop up, like Reach or Fei. Fei? I don't know how to pronounce it. And I'm willing to bet a lot of this video might be outdated in a year because these teams are moving so fast building these amazing languages. So huge thank you to both Solidity and Viper teams for building these awesome languages and all the other teams working on fantastic EVM languages and all smart contract languages for that matter. And that's it. Hope you learned a lot. Let me know in the comments section if you learned anything or if you hated the way I compiled my contracts, because I'm sure some of you did, or if when you did some gas comparisons, you found something else. And we'll see you next time. All right, so here we are in our VS Code, our opcodes FV. For this course, I do have GitHub Pilot installed and set to on for this. And I do highly recommend you coding along with an AI extension or an AI buddy. I promise you it's going to make you so much faster. If there is a VS Code extension that is AI friendly, that's not GitHub Copilot, I recommend that as well because Microsoft is kind of dominating right now and that's a little spooky to me. But beside the point. So let's go ahead. Let's open up our terminal. Let's create a new folder. So mkdir one horse store, or whatever you want to call it. And let's open that up like this. And I have an issue in VS Code for why that keeps coming up. Looks like Macs are having an issue as of recording. And now we're in a new folder here. We're gonna do forge init. Of course, you know the drill. Set up our new Foundry project. And great, we have Foundry set up here. So let's pop over to the README, delete everything. And let's set out for our first task, which is gonna be really easy. Write a basic simple storage / horse store contract. And if you want, you can even go right to the GitHub associated with this. And you can just go to src, horse store v1, horse store.sol, and copy this. And you know what? I'm even just going to do that because it's really simple. Let's delete all these. Delete, goodbye. In src, we're going to make a new folder, horse store v1. And in here, new file, horse store.sol. And I'll paste this in here. Now, additionally, if you're going through this code base, we also, in the v1 section, we have this horse store symbolic.t.sol. For this section, we're actually not going to be doing this, but actually in the next section, we're going to come back to horse store to actually set up a real minimalistic symbolic execution or formal verification test. So if you see this in the code base and you're like, what the heck is that? Don't worry about this until the next section, the Math Masters section, where we're going to introduce you to formal verification. So if this is looking like gibberish to you, you need to go back and you need to finish the advanced Foundry section or even the basic Solidity section. This should be very familiar to you. Like I said, we have a storage variable up here, number of horses. We have an update function, a way to update it, and we have a way to read it. So from a Solidity perspective, this is incredibly minimal code. However, if we pull up our terminal and we do forge build, this should work. We get successful. We can now come to the out folder, go into the horse store.json, and I'm actually going to pull up the command palette here with Command Shift P, or you can also do view command palette or whatever it is, or just Google how to pull up the command palette on VS Code. And I'm going to do format document just so that the JSON kind of forms nicely. And then I'm also going to pull up the command palette and do toggle word wrap, which makes it look horrible, but it'll help us a lot. So this is our horse store.json. So this is really the output of our compiler. This is all this stuff. Obviously, we have the ABI. I'm going to minimize that. And then we have the bytecode, which is really what we're going to be looking at. The deployed bytecode, method identifiers, and then some other stuff. There's a whole bunch of stuff in here, but whatever. This bytecode and this bytecode is what we're going to be looking at, both of these bytecodes. And they do something different. If you followed along in Cypher and Updraft, we've kind of told you what the differences in these are, but we'll make it a little bit more clear in a minute. Now, in any smart contract, when it's created or when you send a transaction to it, you're always sending this call data or working with this call data. You're always sending raw bytes, raw data to the blockchain. And if you scroll down into the transaction, you can see, if we just view the original of this transaction, this is exactly what was sent to the blockchain. So when I send a transaction, we're going to have all this call data, right? And this data could be literally anything. We're assuming the smart contract that we send this call data to has a way to process or understand what this call data is supposed to do. And if we look at a contract and we scroll all the way to the bottom, we see all this hex, all this random data down here. It's this random data. It's all this hex that's responsible for processing that call data and governing what the smart contract actually does. It's all of this hex that makes up the different opcodes or the machine readable instructions. Every 1 byte or every 2 characters in this hex essentially makes up an opcode. There's some exceptions when you push raw values in the stack, but we'll talk about that later. We as human beings are terrible at understanding machine level code. We don't really know how 0 and 1s work. We don't know how to work with thousands of transistors at a time. We don't really know how to send instructions to transistors very easily. So when we write code, we write it in what's called higher level languages like Solidity that are more easy for human beings to understand. Machines, however, don't understand Solidity. They understand machine code. At the lowest level, the Ethereum virtual machine is exactly that. It's a machine. And so in order for it to do anything, it needs very specific instructions that tell it, hey, put this data in storage. Hey, put this data in memory. Hey, put this data in the stack. We'll learn about the stack later, etc. And it's all of these, and all of these machine readable instructions are also known as opcodes. So this Ethereum virtual machine that you've heard a lot about before, this magical thing that doesn't really exist, however, it's implemented. So the Ethereum virtual machine is this fake machine that says, okay, when you send data to the blockchain to Ethereum, convert that to, send money, send tokens or whatever. And all of those instructions of the Ethereum virtual machine are in these opcodes for the EVM. So whenever you say, for example, hey, store the number 7 at storage slot 0, there's a set of opcodes that are going to do that. There are a set of machine readable codes. It's all these opcodes combined that make up the EVM. Opcodes are machine readable codes, and it's the combination of all these opcodes that make up the EVM. So the EVM is really just this agreed upon set of opcodes that we say does stuff. It's a virtual machine because there's technically no Ethereum machine. Whenever you run a node, your computer actually pretends to be this stack machine, this Ethereum virtual machine. Don't worry about that too much for now. Opcodes are these very specific machine level instructions. And you can see a list of them if you go to the ethereum.org website. Opcodes are pretty common in computer science. It's also known as instruction machine code, instruction syllable. There's a ton of different words for it. Opcodes in general are very common in computer science as a whole. However, in the smart contracts themselves, these need to be a set of these opcodes. These need to be a set of these machine readable instructions so that when we do send call data, when we do send data to these smart contracts, they have a way to actually interpret the call data and work with the call data. And if we scroll all the way down to the bottom, we can see the actual contract creation code. We can see deployed bytecode, etc. And all of these in the contract creation code and deployed bytecode is going to be opcodes. Typically, each 2 of these digits is going to be so this 60 at the start of this contract, we can actually copy this. And I'm going to go to one of my favorite sites for learning about opcodes, evm.codes. I can paste that 60 in and I can see what the 60 stands for. So the 60 opcode, which again is going to be the hex. So we could do cast to base OX6 dec, which is the 96th opcode, or we could see the binary. This is what the binary of that opcode looks like. So this 60 opcode stands for the push 1 opcode, which is going to place 1 byte item onto the stack. We'll learn what the stack is in a little bit, but there's going to be some familiar opcodes in here like mstore and sstore and sload and mload, right? We've learned about those in the Foundry Flow course when learning about some gas optimizations. So this contract is just this massive set of these opcodes, which essentially tell our machines exactly how to process this call data that gets sent to them. In the Ethereum world, we can actually change or add opcodes through the Ethereum improvement proposals. As of recording, a few months ago, they added the push 0 opcode, which was awesome. So just to recap, in a smart contract is going to be a set of opcodes combined, where in the contract code, every 2 of these hexes stands for 1 byte, and each opcode is 1 byte long, and we can see what each one of these opcodes does. Again, there are going to be some scenarios where it's not every 2, because, for example, we could do like push 4, where we place 4 bytes onto the stack. So we would see like a 63 and then 4 bytes instead of 2 opcodes back to back, right? So, but don't worry about that too much for now. Main thing is, boom, this is an opcode. 60 stands for push 1. 60 stands for push 1. Boom. 60, this is not an opcode. This is going to be how much is going to be pushed to the stack. This is an opcode. 52 is another opcode, which stands for mstore. So lots of opcodes. If this isn't making sense to you right now, it's okay. It will. Okay, now that we've learned about opcodes, we're actually going to go ahead and rewrite our horse store.sol into Huff. Why are we learning Huff? Well, again, if you learn Huff, surprisingly, all of this EVM opcode stuff just becomes easier because it really becomes easy to see how these smart contracts work at the lowest level. So let's go ahead and get started working with and installing Huff. In order for us to install Huff, we need to install the Huff documentation. If you're following along with the course GitHub, if we scroll down into our curriculum, we have a link to the Huff documentation right in the GitHub there. And this is the Huff documentation. You can go ahead and go to the getting started and follow along with the docs here in order to install Huff. I find the easiest way to install Huff is to first install this huff up command. And all we need to do to install it is to run this command, which will download this sh bit and then run bash on it. So I'm going to go ahead and install Huff up by pasting this into your terminal. Great. And after this runs successfully, again, you'll probably need a Linux-like environment in order to do this. You'll get an output that looks something like detected your preferred shell as bash and added Huff to your path. And it'll add this to your bash RC. So you need to run this command first and then run Huff up to install the Huff compiler. Once Huff up is done, you should be able to do huff c -- version and get an output that looks like this. Now, depending on the shell that you're working with, you want to make sure that it actually was correctly added to your bash RC, your bash profile, or your ZCH, or whatever config file that your shell works with. So I want you to go ahead and actually delete your shell by hitting the little trash can or closing out of the terminal or whatever, pulling it back up, and then doing huff c -- version again. If you don't get an output here, but you got an output last time, that means that Huff wasn't correctly added to your bash RC or your bash profile or your ZCH or whatever terminal you're working with's config file. If you're running into issues here, this is a great time to chat with ChatGPT, Google around, figure out exactly what's going on here. If you're not using WSL, you can of course use the Windows installation or whatever installation process you want here. But remember, installing stuff is often the most frustrating part of development work. So don't get too frustrated if it doesn't work right away, and be sure to Google around and ask your AI buddies for help. Or of course, come to the GitHub discussions associated with this course. As we're coding along here, be sure to use the docs as a reference guide as well, because the docs are going to be the most up to date. The docs are incredibly helpful, and there's a whole ecosystem around the Huff code bases. But great, now that we have Huff C installed, we can actually start writing some Huff smart contracts. Let's actually rewrite our horse store in Huff, and rewriting it in Huff will actually teach us how smart contracts work at the lowest level, and will teach us a ton about these opcodes. To get started rewriting our smart contract in Huff, let's go ahead and create a new file. We'll call it horsestore.huff. And what's cool is what's cool about this is because we have these two smart contracts should be exactly the same, this one just written in a different language. When we actually go to write tests, we can write one suite of tests and just apply it to both contracts. This is also known as differential testing. And if done with fuzzing, it's sometimes called differential fuzzing. And it's incredibly powerful for people looking to build code bases in Solidity and then optimize them in a much faster, much more powerful, lower level language like Huff. You write your main smart contracts in Solidity so that they're easier to read, easier to understand, and then you either formally verify or you fuzz them against your gas optimized edition that you actually deployed to the blockchain. But anyways, let's get started working with Huff here. Now, when we work with a Solidity smart contract, let's say we deployed this contract on chain. If I call the function read number of horses, we almost kind of magically get it to return this number of horses. You know, for example, if I had deployed this smart contract, our horse store in Remix, right? I deployed it down here. I do read number. We almost kind of magically get the response 0 back when I call 1 to update the number of horses and rerun. Sorry, that was kind of zoomed out, but you get the picture. When I call read number of horses, I almost magically get this 1 to get returned to us. But when we actually make this call, when we actually make any call, if I actually call update number of horses again in Remix, and we could see this in Foundry too, you know that we actually send, the input that we sent is actually a whole bunch of binary itself, a whole bunch of just data itself. So if I copy this binary of the input of update horse put a little comment here, paste it. It's actually this kind of ridiculous jumble of numbers. When we call update horse number and we add a value here, this data that gets input to the smart contract is called the call data. So this whole thing is the call data. And it's this call data that tells our smart contract, hey, this is what I want you to do. So how does Solidity know that this jumble of numbers tells the EVM, tells our smart contract, hey, update that number of horses? This jumble of letters. So we have two questions here. How did Remix know that when we press this update number of horses to send this exact data string to our smart contract? And then number two, how does Remix even know to update this storage variable with this jumble of binary bytes data? Like, how did this happen? So these are the two questions that we're going to answer now, and we're going to answer them by learning Huff. Let's start by answering this first question. Where did this data come from? Now, if you've taken the Foundry Advanced course, you know what a function selector is. You know we have this update horse number and a uint256. The two of these are the function signature, and we can hash them to make the function selector. So if I do cast sig update horse number uint256, I get this oxcdfea2e or whatever it is, right? Let me actually copy paste this from Remix. So this, as we can see, actually matches the first part of this huge chunk of data that was sent in. So this is what's known as the function selector, right? So when we send this data to our smart contract, we're saying, hey, use the function that has the selector. So this cdfea2e matches right here. So somehow Solidity knows, our smart contract knows, to take the first 4 bytes of the call data and use that to actually pick which function we're referring to. This is actually called function dispatching, and it's something that Solidity does natively for us. So there's no code in here that basically says, if the call data has 4 bytes that match the update horse number function selector, you should call it. It doesn't have that. It does that natively for us when it compiles. Now, instead of update horse number, we did cast sig read number of horses. This would be the function selector, right? And so when we send this call data to our smart contract goes, okay, I'm going to dispatch your function call to read number of horses because that's what your function selector tells me to do. So again, this happens on the back end for Solidity. Solidity sets up this function dispatching for us. But if we're going to write our smart contract in pure opcodes, which essentially is what Huff does, we actually have to write that function dispatcher ourselves. So this is already one of the most powerful things that we can learn right from working with Huff is function dispatching. So again, the flow will look like we send the call data, our smart contract reads our call data and goes, okay, what function selector are you looking for? You're looking for this function. I'm going to route your call to that function. In a way, us sending call data to a smart contract is going to be the same as us calling like a Python script or a JavaScript script. And we need an entry point for our call data to be processed. In Huff, we call that entry point main. In the binary, it'll just take your call data and execute it through whatever binary is there, but we'll talk about that in a bit. And again, I know I'm throwing a lot of terminology at you here, but I promise it'll make sense. Just follow along with me for now. We're going to really dial this in for you. So we need to actually code this function dispatching. So in order for us to have an entry point for our call data, we need to define a function that we're going to call main in Huff. Now, the Huff language does have functions, but for the most part, we're going to ignore functions exist in Huff, and we're just going to work with macros. For all intents and purposes, macros essentially are functions. They're a little bit different. Don't worry about the difference for now. So we're going to write a main function, which will do this function dispatching. And remember, we don't have to do this in Solidity, but we do have to do this in Huff. And importantly, we do have to do this in our bytecode as well. So learning how to do it in Huff will teach us how it's done in the bytecode. So let's get started. So we're going to define macro main like this. Now I am going to put the rest of the syntax for this, but don't worry about what it means quite yet. I'm going to say takes 0, returns 0. So this is how you define a macro, which is basically a function in Huff. Define macro, name of the macro, and then takes and returns. So the takes and returns refer to what it's going to take off the stack and return onto the stack, but don't worry about that yet. Boom, we have our main function. Oops, and sorry, the main macro needs to be uppercase, not lowercase. Now we can even test that this compiles by running huffc on it. So we'll do huffc, src, horse_store v1, horse_store.huff, and we'll get compiling and then no output, which means it compiled successfully. We can actually rerun the command and do -b, and we'll actually get the bytecode associated with just this smart contract. So just this smart contract, just this bit of Huff returns all of this bytecode here, all of these little opcodes. And we're going to come back to what those opcodes mean. But when we do the -b, we get the output of the binary here. Boom, we have a minimal Huff smart contract, which looks like this. And this is the smallest, most basic smart contract you can have, and we haven't done anything really. Now, additionally, I have some syntax highlighting in here. I'm using a Huff extension. So if you're using VS Code and you want to have some syntax highlighting for Huff, install this extension. It'll give you these nice little highlightings here. So we're still in the process of trying to make the function dispatcher, right? We're still in the process of us trying to code this bit that says, okay, if this is your function selector, call this function. But we saw actually when we compile this, we got this output here, but clearly we still haven't coded our function dispatcher. We just coded this main function. So what is this? What is this code doing? Well, when you compile any smart contract, most smart contracts are compiled into 3 or 4 different sections. The contract creation code, the runtime code, and then the metadata, and then sometimes constructors and whatever else the compiler feels like doing. The Solidity compiler does this nice little bit of opcode syntax where it adds a little invalid opcode between the different sections, so it's even easier to tell which section is which. So after contract creation, they pop a little invalid. After the runtime, they pop a little invalid. After the metadata, they don't pop anything because the contract's done. But these 3 sections are typically how a smart contract is created. The first section, or the contract creation part of the code, is what code that tells the blockchain to actually store the smart contract. This first chunk here, even if we have no what's called runtime code, this is still our contract creation bytecode. So when we finish this in Huff, we're actually gonna have 2 sections. We're gonna have the contract creation bytecode, we're gonna have this runtime code, and we're not gonna have any metadata, but we could add metadata if we want. Solidity and Viper natively add metadata to their smart contracts. We'll go through what this contract creation bytecode typically does, but this is a minimalist example of what the contract creation bytecode looks like. All this contract creation bytecode is responsible for doing is taking your smart contract and saving it on chain. Because in order for us to deploy any smart contract, here's an example of a transaction that created a smart contract. In order for us to deploy a smart contract, we send Ethereum some call data. We send it just a huge lump of binary. So in this giant lump of call data, in this giant lump of binary, the first section of this is going to be, yes, this contract creation bytecode. All this usually says is essentially, hey, take the binary after me and stick it on chain. That's essentially all the contract creation bytecode does. And we'll go through the opcodes and how this actually works. But essentially it says, hey, copy the next chunk of code, save it on chain, please and thank you. And that's essentially how the contract creation bytecode works. So even though we have no runtime code, we haven't coded anything, Huff is smart enough to know that we at least need a contract creation bytecode. And even if we compile this Huff smart contract that doesn't do anything, we have this contract creation bytecode here. You can actually typically tell that something is a contract creation bytecode by looking for the code copy opcode. So we talked about opcodes in the Foundry Flow course, but as we know, all these little 60, all these little numbers are referring to some type of opcode. And there's a phenomenal website that teaches us all these opcodes and actually gives us a little playground to try them out and teaches us what they do. But the opcode that actually says, hey, stick this smart contract on chain is going to be this opcode called code copy. So typically if you see this code copy opcode or the 39 opcode, that's an indication that you're looking at the contract creation part of the code base. Typically, you can still have this in the runtime, but if you're looking for a quick litmus test of what section of the code you're in, you can look for this 39. And if we look in here, we do indeed see, okay, so we see F3, 3D, 39. We do indeed see there's a code copy opcode in this contract creation bytecode. So again, we're going to go over what this does in a little bit. Make sense? Okay, let's continue. Now in Solidity, when we're working with variables, Solidity almost kind of magically just knows where to put them. They know magically if it's a memory variable or if it's a storage variable and what variables to kill after a program has ended. So number of horses here is clearly a storage variable. So after a program finishes, it'll keep that value to persist. However, some memory variable, like if I added UN256 hello equals 7, once the transaction to update horse number finishes, this hello variable will be inaccessible. It won't matter anymore. So how does Solidity know what to keep and what to get rid of, and how does it compute all this different stuff? And we have to ask this question in order to answer this question. So I kind of reformatted our questions here because we're getting more and more. And also more importantly, how does the EVM know what to do with this? Does it just stick everything in storage for a little bit and then move it around? Unlike in Solidity will kind of magically say, okay, this call data, I know where to put it, I know what to do with it. But guess what? We are writing Huff code. We are essentially going to be doing the opcodes ourselves here. Now, in order for us to understand what places we can put stuff, we want to take a look at this tweet from a very prevalent smart contract developer in this space, Pascal. And I'll have this image in the GitHub associated with this course. He gave us this image of some of the most important places we can actually store data once transient storage comes into play. Transient storage isn't quite a thing quite yet. Don't worry about that for now. But these are some of the different things that the EVM actually can work with and keep track of. The most important ones that we're going to be looking at are going to be the stack, memory, and storage. There's also obviously the EVM code itself. We have a program counter and available gas. Transient storage doesn't quite exist yet, and it's not super important for what we're going to be covering here. But we are going to focus on the stack, memory, and account storage. So when we're looking to grab this data and work with this data, if we want to do any type of computations, we first need to figure out where do we want to do computations? Where do we want to put this data? So the EVM is what's known as a stack machine. Out of all these places, the cheapest places gas-wise to do stuff is going to be on the stack. And we actually know this because if we go back to this evm.codes website, we have this minimum gas, which gives us a clue as to how much gas each one of these operations are going to do. This add operation, what it does is it takes the first two items on the stack and returns onto this stack data structure the addition of the two of them, and it costs around 3 gas. And if you look for another add opcode, you'll see that the only way to add two things in the EVM world is on the stack. So at some point or another, if you want to add anything, it needs to be on the stack. EVM is known as a stack machine or stack state machine, where most of the operations we're going to be working with are going to be putting stuff on and pulling stuff off of what's called a stack. Now, the stack is going to be the main data structure that we work with when it comes to working with Ethereum. And you can think of it literally as a stack, like a stack of pancakes or a stack of books. Whenever we have an object on the stack, if we push something to the stack, that's when we basically drop it from the top and stick it to the top of the stack. If we want to add a new item to the stack, well, guess what? Same thing. We got to bring it to the top and drop it onto the top of the stack. Now we have an item on the bottom of the stack and an item on top of this object on the stack. If we wanted to get the value in here, let's say this was some 7 let's say this was 100. If we wanted to get to this 7, we would need to first pull off the 100 and then pull off the 7. This is how the EVM works. And this is how we're going to do most operations. So whenever we see any of these opcodes that we're going to be learning about, we can kind of visually represent what they're doing with an object that looks like this. So most of what we're going to be doing is on the stack. Now, the other two important places that we can put and do stuff is going to be memory and storage. Now, unlike the stack where you have to pull things on and off one at a time, memory, you can really stick any variable any place that you want. And at the end of your transaction, poof, everything in there goes away. Storage kind of works the same. You can think of it as a giant array where we can stick data wherever we want, whenever we want. And when the transaction completes, storage persists. However, as we know, as we've learned before, anytime we interact with storage, it's going to be incredibly expensive. If we go to our opcodes, the store opcode, which saves a word to storage, costs substantially more than our mstore opcode, which saves a word to memory. mstore, minimum of 3, store, minimum of 100. So storage is always going to be a lot more expensive. But these are going to be the main places we can work with data. You can think of memory like a giant array. You think of storage like a giant array that persists after the transaction completes. And the stack is literally a stack of pancakes. And the stack is where we're going to do most of our computation and most of our operations. So anytime you want to add stuff, you want to subtract stuff, you want to do anything, you have to do it in the stack. There's sometimes we have to do some stuff in memory, and we'll point those out when we get to them. Now, like we said, there are a couple other places you can actually store data and work with stuff, but for the most part, just think stack, memory, or storage. That's where stuff is. That's where data is going to go. And all of these opcodes, all they essentially do is do stuff to the stack, memory, and storage. That's basically it, with the stack being the most important piece. In fact, right at the top of all these opcodes, you can see this little stack input and stack output. Most opcodes say, okay, A is going to be the top of the stack, B is right underneath the stack, and what the add opcode is going to do, it's going to take the A opcode plus the B opcode and then return on top of the stack A plus B. So if we have a stack here and we want to use the add opcode, we would need to have two stuff on the stack. Well, in order to get stuff on the stack, we actually need to use a push opcode. And there's a whole bunch of push opcodes here. The push opcode has a push and then the number of bytes you want to place on the stack, except for push 0, which always pushes 0 onto the stack. So let's say we called push 1 with a value of 0x01. What we would do is we would push 1 onto the stack, and now this is on our stack with a value of 1. Remember, we're always going to be working with hex data, so 0x01 is going to equal 1. Now, let's say we called push again with push 1, so we're going to push 1 byte code on, and then instead we do 0x03, which is going to equal 3. So now we have 3 on top of the stack and 1 right underneath it. If we came along and said, okay, we want to now do the add opcode, what's going to happen is our add opcode is going to look at the top of the stack and right underneath the stack and say, okay, we're going to add 3 plus 1, and the resulting value on the stack is going to be what the addition of them is. So you can almost think of them being pulled off. Our little add code going, okay, 3 plus 1 is 4. So we're going to do 4 here, 4, boop, and now stick that on the stack. If this is what our stack looked like, if we had 4, maybe 3 at the bottom, maybe 1 here, and we called the add opcode, remember, it only applies to the 2 top on the stack. So essentially it would say, okay, let's take these. 1 plus 4 is 5. So now the data here is going to be 5. Let's stick that back on the stack. And after an add opcode works, this is what it will look like. So that's an example of working with 2 really important opcodes, the push opcode and the add opcode. Push is going to stick stuff into the stack. Add is going to take stuff off the stack. and combine them. And you can read all the different inputs and stack outputs in EVM.codes. They do a great job of that as well. And we'll see in a little bit how opcodes like mstore and store take stuff off the stack, but then stick stuff into memory as a result of what's on the stack. So we'll see that in a bit. How do we make this contract dispatch our call data so that when we send it call data, telling it to update our horse numbers, it actually updates our horse numbers? Okay, let's continue doing that now. So we now know when somebody is going to call our horse store smart contract, they're going to call with something that might look like this, right? They're going to send it this giant lump of data. Let's find the function selector so that we can route it to the code that actually updates the number of horses, which we haven't written yet, but we will. Now that we know that the EVM is a stack machine, and in order for us to do this function selector routing, we need to do some computation on the stack. Let's try to actually get this to work now. Now, just for this beginning part, I'm going to do two things. I'm going to have our little stack over here, and I'm going to push stuff onto the stack to make it a little bit more obvious what's actually going on. But the second bit here is we are going to do a little bit of magic just in the beginning of this main function to do this function dispatching, because there are a couple of opcodes that are going to be a little confusing the first time you look at them. Once again, stick with me. I promise this will make sense as we go back over it. So the first thing that we want to do is we actually want to push 0 onto the stack to do some stuff later. So typically to do that, you would have the push 0 opcode, which would literally just push 0 onto the stack. Boop, like this. In Huff is actually smart enough to know that if you just do 0x00 like this, it's smart enough to say, oh, okay, this is the push 0 opcode, and they want to push 0 on the stack. And similarly, if I wanted to do like push 1, 0x01, if I wanted to push 1 byte onto the stack with the value 0x01, I wouldn't even need to have the push 1 opcode in Huff. Huff is smart enough to know that if I put 0x01, they know that I mean push 1, 0x01, because obviously this is 1 byte long. If I did this, it would be smart enough to make that push 2, because this is, of course, 2 bytes long. So when doing push opcodes in Huff, you just need to put the actual value that you want to push onto the stack. So in our Huff now, when somebody calls this smart contract, and when somebody sends any call data to this smart contract, the only thing this smart contract will do right now is push 0 onto the stack. That's it. And in fact, we can even compile this with huffc, src, horse store v1, horse store.huff. Oh, and let's add the binary. And we can see our code is a little longer than just the contract creation bytecode now. Now, after the F3, after that contract creation code, we now have this 5F, which if we go back to EVM.codes, 5F is indeed, it's the push 0 opcode. So we can see just by adding this push 0 opcode in our Huff, we've added the 5F opcode. And now there's a 5F added into our smart contract. This means that once again, since this is our main function, and since it's the first, anytime anybody says any data to the smart contract, we just push 0 onto the stack. That's it. So this doesn't do anything yet except for push 0 on the stack. But cool. So we're already starting to code with pure opcodes. Very exciting. Okay, what next? Okay, well, somebody's going to send us some call data, right? And they're going to have the function selector embedded in the call data. So we want to actually get their call data. And to get this first chunk, we're going to need to do some operations, right? We're going to need to say, hey, give me the call data, but like only the first 4 bytes. So to do any type of operations, what do? You guessed it, we got to stick it on the stack. And I want you to keep that in mind. Anytime you want to do any operations, you got to stick it on the stack. So if we go back to our EVM.codes, we can look for call data load. And this is the opcode that actually loads our call data onto the stack. So you can even read it in EVM.codes. So what it's going to do is it's going to take a stack input and give a stack output. And the stack input of call data load is why we actually pushed the 0 onto the stack in the first place. So what call data load is going to do is it's going to look at the call data and it's going to grab whatever value is at the top of the stack and use this as the bytes offset. So if this was 1, if we pushed 1 onto here, what our call data load would do is it would look at our call data and go, okay, I'm going to load this call data, but I'm going to ignore the first byte and start from here. We don't want it to ignore the first byte because that first byte includes part of the function selector. So as of now, here's what our stack looks like. And usually when I'm coding, I like to visualize the stack in comments as well. So if I have 0x0, 0x0, which pushes 0 onto the stack, I also like to do these comments where I have like a little brackets and like a 0 in here, which says, okay, at the bottom of our stack is 0. So this little comment here and this image are supposed to represent the same thing. If I were to add like 0x02, I would then do something like this, where I would say 2, 0, where the left side is going to be the top of the stack and the right side is going to be the bottom of the stack. As a stack image over here, that would look like this. So I'm going to keep this commented out for now, but as I'm coding along, this is how in the comments in your code, you can also keep track of what the stack looks like. So I'm going to delete that for now. So since we have 0 on the stack right now, when we do the call data load opcode, and this is how you do it in Huff, you literally just write the name of it. It's just going to put the call data right onto the stack, starting from the 0th byte. So it's going to add the entire call data right onto the stack. And you might be confused. You might be saying, hey, we replaced the 0 with the call data. Like, why did we do that? Well, what happened was we had this call data. We have this call data that's being sent to our smart contract, and we called the call data opcode. And what it did was it says, okay, let's pop off this 0 and let's stick this call data on starting from the 0th. Since if you start from the 0th byte, that's just all the call data. We just said, okay, we've popped off the 0, and now all that's on the stack is the call data, is this big thing right here. So cool. Now we have the whole call data onto our stack here. Great. What's next? Next is the hard part. And if you don't understand this part, that's totally okay. Because what we need to do is we need to lop off all of this, right? Because just this is our function selector. So how do we cut down the call data to just the function selector? We have this huge thing, and we only want this. So how do we cut it down? There must be an opcode that will help us do this pretty easily. So there's a lot of approaches we can take to do this, but one of the easiest and most efficient ones is going to be this SHR. This is where we're going to shift the bits towards the least significant one. And to do this, you need 2 values on the stack. You need a shift number of bits to shift to the right, and the value, the 32 bytes that you want to shift. So this SHR is the right shift for bits. But for the SHR opcode, let's say this is our text. This is our hex here. 0x01, So this is in bytes, of course, right? Each 2 of these, oh, excuse me, let's get rid of that one. This is a byte and this is a byte. And as we know, 1 byte equals 8 bits. So the shift opcode is how many bits to shift to the right. So if we look at this as being 2 sets of 8 bits, we can actually rewrite this. We can use cast if we want. We do cast --2 base, grab this and say bin for binary, and boom, this is it in bits or in its binary. We go 1, 2, 3, 4, 5, 6, 7, 8. This first part represents the 02, and this 1 over here represents the 01, right? If I change this to like an F1, we're going to get a much different value, 0xF102, with, it's going to be a lot bigger, obviously, because that F1 is now going to use all 8 bits. So 1, 2, 3, 4, 5, 6, 7, 8, boom. This is the 02, and this is going to be the F1. Okay, hopefully you're following along with me. If you're not following along with me, play with this cast to base between bin, dec, and hex. So this is the hex, This is the bin. And then what was dec? Dec 6,100, whatever, right? That's the decimal equivalent of that binary. Anyways, so this is the binary representation of this hex. So if we say this is the value that we want to shift, and we want to shift it by 2, well, what are we going to get? Well, we're going to shift off these 2 values here and shift everything else to the right. So now this is going to be our value. 1, 2, 3, 4, 5, 6, 7, 8. This is going to be what's left. And we can pull up cast and see what this is in both hex and in decimals. And we'll put a 0b at the front of this to tell cast this is a binary. But if we take this and we do cast, you can actually do --2 base, or you can actually just do 2 base, paste this in with the 0b to tell Foundry it's a binary. And we say hex, we get resulted with 0x40, which again, if we do the decimal, we get 64. So if we shift over 2 bits, this is 0, 0, 1, 2, excuse me. If we shift over 2 bits, we get 0.40. Let's shift over 2 more bits, right? So let's do 4 bits, right? So that would be 2 more. Copy this, do the same thing, paste it in. Decimal is going to be 16. The hex is going to be 0x10. So what this right shift does is it just pushes the whole thing to the right a number of bits until we're left with whatever is left over. We can actually validate if we did this correct in our heads, right? So we had this 0x012. Let's say we have this 0x012. We want to push it by 4. We said we got what? We got 16. We can actually see that this is correct by trying this out right in our even.codes.playground. So there's this playground tab here where you can actually switch to playing with Yul, solidity, bytecodes, and then opcodes as well. So we're going to go to mnemonic because that's going to be opcodes. SHR needs a value and then a shift. So shift needs to be the top of the stack. So first thing we need to do is we need to push to this onto our stack, right? So we're going to push this onto our stack so that this is now it's on the stack. Then we need to push 1, 4. So we're going to push this onto the stack. We're going to push 4 onto the stack, and then we're going to do a right shift. So when we do this playground here, what's going to happen is we're going to push 0x0102 onto the stack. Then we're going to push 0x04 onto the stack. Then we're going to call SHR, which is going to shift this to the right by 4. And what we're going to be left with is poof, this value shifted to the right by 4. So let's see what this looks like when we actually run this in our playground here. If we click run, and we zoom out just a hair, we have our opcodes up here. And down here, we'll have our stack, storage, etc. It's like there's not really a way for me to keep both in frame at the same time, but I guess we'll have to make do here. So if I want to step into this, we can go opcode by opcode. So first, let's do the push to 0102. Boom, step into it. After that executes, we scroll down here, we now see 102 is now on the stack. So now we're going to push, oops, excuse me, this should be push 0x0, push 0x04. Sorry, let's run that again. 0102, great. Now we're going to push 1, 0x04. Okay, let's run that. Okay, great. Now our stack has 0x04 at the top and 0x0102 at the bottom of the stack. Based off our calculations here, we should return 16. So now let's go ahead and step into it. We get 10 on the stack, and this is the hex here. So if we do cast to base 0x10 decimal, we see we do indeed get 16. So our math here is right, and we've learned how a right shift with all of our bits works. Now, when we do this call data load opcode, the call data load can only put 32 bytes onto the stack. So if this is our call data, again, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 20, 1, 2, 3, 4, 5, 6, 7, 8, 9, 30, 1, 2, 3, 4, 5, 6, 7, 8, 9, 40, 1, 2, 3, 4, 5, 6, 7, 8, 9, 50, 1, 2, 3, 4, 5, 6, 7, 8, 9, 60, 1, 2, 3, 4, 64 of these little numbers divided by 2, since every 2 numbers is a byte, is going to be 32. So this is 32 bytes. And when we call our call data load, it actually puts this onto the stack, not the entire call data. So these last couple of bytes are actually truncated. If we wanted to include these when we actually call the call data, we would increase the offset, right? We would increase the offset so that we could get this. But so when we call data, we only do 32 bytes on the stack. And the reason we're going to do this right shift is because we only want this. We don't want any of this. So what we can do is we can say, hey, let's right shift this whole thing, push it all the way to the right so that this is all that's left. Let's do that now that we learned how the right shift works. Anyways, back over here, we've just put our call data onto the stack. So now our call data is on the stack. Our call data looks like this. We want to shift this so that we only get the function selector so we can finally start doing our dispatch. So what we want to do is, again, back in our right shift opcode, we want to get on the stack the value we want to shift and the amount we want to actually shift it. So we have at the bottom of our stack the value we want to shift, right? We want to shift our call data all the way to the right. So how much do we want to shift it? This is going to be the first 32 bytes of call data is going to be on the stack, right? So this is the call data, or at least the 32 bytes. And remember, since it's only the first 32 bytes, we don't need to worry about this over here. So we're going to need to cut this down to just this. We're going to need to shift all of this to the right. So let's do a little bit of counting again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 30. 1, 2, 3, 4, 5, 6, 7, 8, 9, 40. 1, 2, 3, 4, 5, 6, 7, 8, 9, 50. 1, 2, 3, 4, 5, 6. So 56. So we need to right shift 56. So let's do a little calculating here. 56 divided by 2. So that's 28 bytes. 28 bytes. Or 28 times 8, since 1 byte is 8 bits, or 224 bits. So now there's a lot there, but that's what we need to do next. We need to do a right shift of 224 bits. So let's pull this up. Let's do cast to base 224 hex. That's 0xe0. So we need to do a push 1, 0xe0, but since Huff is smart enough to know that it's just 0xe0, boom, we can just do this. And now on our stack, on top of the call data, we have 0xe0. Now that these two are on our stack, holy moly, we're finally about to do it. We have the number we want to shift on the top, right? 0xe0, we want to shift by that many bits. We have the thing that we want to actually shift. We can actually now do the SHR opcode to actually do this shift. So if I grab this, if we want to even, boom, 0xe0, this is what it looks like now. Now we can run the SHR, which what this opcode is going to do is it's going to take this off, and go, okay, you want to shift this to the right by this much. Great, let's go ahead and do that. And we'll return onto the stack just what's ever left, which is going to be our function selector. So we're going to shift by this many bits, and all that's going to be left on the stack is that. So now we can even just say function selector. And I know this seems like a lot, but really, right, this is just a few opcodes. It's 0x00, call data load, 0xe0, and then a right shift. And just by doing that, we now get the function selector. So now we have the function selector on the stack. And once you have a function selector on the stack, you can now start to finally do some function dispatching. So great job. I know we've gone over a ton already here. So let's do a little bit of a recap of what we learned so far. So first off, we learned a little bit more about the EVM. We learned that there's a lot of different places to store and manipulate data. We have a stack, which is going to be the main data structure we're going to be working with. We've got memory, we've got storage, we've got gas all over the place. We even mentioned there was a program counter, gas available, and some other stuff. We learned that the stack is going to be the main data structure we're going to work with to manipulate data, where we can push data onto the stack, or we can pop data off the stack, but we're always working with the top of the stack. The EVM is built into this list of opcodes, which essentially manipulates the stack and also memory and storage, etc. We learned that when we're working with these opcodes, most of the time we're going to be doing stuff to manipulate data on the stack and store it into memory and store it into storage for one reason or another. In our Solidity smart contracts, whenever we send data to a smart contract, we actually send this thing called call data. Solidity, intelligently enough, when it compiles into opcodes that can understand call data. When it gets call data, one of the first things it has to do is look at this call data and say, what would you like to do? And get this function selector. Once you get the function selector, you can actually route the rest of the call to the function associated with the function selector. We did this ourselves in raw opcodes in essentially Huff by first pushing 0 onto the stack, the call data, 0x-E0, and then doing a right shift. And then what that left us with was the function selector. Essentially, we took this call data, lopped off the end here with our right shift, and all we were left with was, boom, this function selector. Now that we have the function selector, we can use this to say, okay, it's time to route your call to the correct function. We don't have any of the functions defined yet, so obviously we're going to need to do that as well. Now, if we do a little huff C, src, horse store.huff, -b, you should get this to compile and get an output like this. And for now, if you want to play with Huff, you can come to the evm.codes playground. Let's go to the playground here. Let me expand this. You can either do bytecode, where you can literally stick the bytecode in here. You can do mnemonic, where you can do opcodes, but this is a great place to play around with tinkering with opcodes. Foundry has a debug function as well that we're going to play with in a bit, but this is a great place to play with stuff. If you do copy paste the bytecode in here, just remember half of this is going to be the contract creation code. So if we look for this 39 opcode, that we know that that's the code copy. This 3D I already know is actually return F3, F3 is going to be return. So I actually know that the runtime code starts here. And if I wanted to play with this, I could actually just put the runtime code that I created, and we can actually see it does match what we coded. Push 0, call data, push 1, E0, add. Oh, where'd the add come from? Oops, I forgot the C. Oh, okay. Whoops. I forgot the C. Yep. Okay. Right shift. Perfect. And we can see if we were to send this, our call data, we're to copy all of this, stick it into here, get rid of those spaces. Now we hit run. We can now walk through this line by line, and we would see at the end on the stack would just be the function selector. So this is a great place to learn, to tinker, and play around with working and learning about opcodes. All right, so let's keep going. Right now, we have the function selector on the stack. Huzzah! Now we want to route this call to the correct function. In Solidity, when we call update horse numbers, it almost magically just knows what to do. When we're coding in bytecodes, we actually need to tell it that is actually calling to update the numbers or read horse numbers. So we're going to take this function selector and we're going to do a couple of comparisons. We're going to say, okay, now that we have this function selector, we want to jump to the function data associated with the selector. And in this contract, in this Huff, in this horse store, we've got two function selectors. Update horse number and read number of horses. So we're basically going to say if the function selector equals update horse number, then jump to that code, which we haven't defined yet. And then if the F selector equals read the horse number, jump to that code. So let's go ahead and do that. I'm going to get rid of the stack image for a bit, but I'll bring it back when I think it's necessary. So let's do these comparisons. So we have these two function selectors, update horse number and read number of horses. So let's actually compute these with cast, right? So we can do cast sig little parenthesis, little quote, update horse number, UN 256, like this. So this is going to be the function selector for update horse number. So this equals update. And then let's do the read as well. Cast sig paste, oops, little quotes here. Read number of horses. It's going to be this one. So this equals read. So now that we have those, we're going to use these to basically check to see if the function selector matches one of these. We have an opcode that can actually check for matches in evm.codes. In evm.codes, or in our opcodes. In our opcodes, there's one called EQ, which stands for basically equals. And what it's going to do, it's going to look at the top of the stack. It's going to say the left side integer and the right side integer, and it's going to return A equals B, where it's going to return a 1 if the left side is equal to the right side, and then 0 otherwise. So if they match, it's going to be a 1. If they don't match, it's going to be a 0. So what we can do now that we have this function selector on the stack already is we can push this, which is our update, horse number selector, onto the stack. And now on the stack is not just going to be the function selector, but it's going to be the update horse number function selector, and then the function selector. And then we could do the equals. And this will be true if func selector matches. Boom, because it takes 2 inputs and returns 1 on the stack. So on the stack, there's these 2 inputs and it returns true if they are the same. Now that we have whether or not it's true, we want to add a little jump opcode. We're going to say jump to update horse number code if true. And to do this, we actually have 2 opcodes that we can work with. We have a jump and we have a jump if. So the jump opcode just jumps to some other spot in the code. The jump I, which stands for jump if, will jump to some other spot in the code if some condition is met. So the stack input is going to be the counter or the byte offset in the deployed code where execution will continue from, and then B, which is going to be our true or false. So basically, if B is true or anything other than 0, jump to this new program counter. So the program counter is not something we've spoken about, but the program counter is going to be the byte offset in the deployed code. The program counter can be a little bit confusing and a little bit tricky, so we're not going to go over it too deep for now. And because Huff gives us some syntax to make it a little bit easier, but once we compile this, I'll show you what I mean, and it'll make a little bit more sense. So we want to use this jump I, this jump if opcode, to actually jump to the update code base, which again, we haven't defined yet. So the way that we're going to do that in Huff here is we're going to add the program counter to jump to, right? Because the jump if opcode requires the program counter at the top of the stack and then the true false conditional. So we have the true false conditional. So we could either just do like manually add the program counter here, but Huff has some nice syntax. We can actually put some text here, which will define the program counter for a certain macro. So I'm going to do update jump. I'm going to just say update jump here. And what this is going to do now is on the stack, this update jump is going to have the update horse number program counter. And then of course the true false conditional. Before I finish doing this, I'm going to put down here this update jump and this colon, and then this set number of horses. I'm going to explain all this in a second. And then down here, I'll do a little define macro set number of horses equals takes 0, return 0, just like this. Now I just wrote a whole bunch of code, but let me explain it. So we put this update jump here, and what this update jump is since we have this conditional down here, we're basically saying, hey, this update jump keyword is going to refer to the program counter for set number of horses. This syntax here is a little bit of Huff sugar. Update jump refers to the program counter for set number of horses, wherever that ends up getting compiled to be. And right now our set number of horses macro does nothing because we haven't done anything with it yet. But basically now we'll say jump if or jump I, which again is going to take our program number and true false. And so if this is true, if this is anything other than 0, we're going to jump here. Otherwise, we're not going to do anything. So once this jump if happens, we've got nothing left on the stack. And we can even run this again. We'll compile this. C, oops, what did I do? Macro diff set number of horsey, set number of horses. Let's do it now, and boom, and this is our output. Now, if we want to practice, if we want to run this over in the EVM.codes playground, what we can actually do is we can make it even easier. We can do the Huff compiler and do --bin runtime, and this will give us just the runtime code, which is great. So now if I paste this in here, we can actually see pretty much exactly what we just coded in Huff in pure opcodes. We have push, call data, push, right shift, right? This is getting the function selector. Then we have push, which is checking the update function selector. We have an equals, we push that program counter, and then we have a jump if, and then importantly, we have a jump dest. So this is something we didn't talk about quite yet. So when you do these jump opcodes, they can only jump to a jump dest opcode in the code. So if it's not jump dest, you can't jump there. So the jump dest is an opcode which literally just says, hey, this is a valid destination for jump or jump if. When we set this up, this update jump syntactical sugar, we're setting up, hey, set number of horses is now a valid jump destination. So we could have 100% manually done this instead of using the Huff syntactic sugar, right? So what we could have done was we could have said, okay, 0x000f jump if, and then had a jump dest down here, where if this jump dest was at program counter 0xf, this would be a valid jump destination. So, but it's a little confusing to do that when writing in Huff. So this syntactic sugar just makes it a little bit easier, just saying, hey, set this up as a jump destination. Update jump is going to be a valid jump destination, and and the code that's going to start there is going to be whatever code is in the macro set number of horses. So hopefully that makes sense. This is what it looks like when we actually compile it. Obviously, nothing's going to happen after the jump dest because we jump here, boom, nothing happens. So let's actually run this in our playground. With some valid call data in hex here. So if we want some valid call data in hex, we would need to have this at the beginning of our call data, boom, and then we could put, literally almost whatever else we wanted after it. We'll do run, and if we walk through this, we should be able to jump because on the stack is F and true, and boom, we should hit the jump dest. Now, if we don't have the correct function selector, right, this equal will return false. So I just got rid of it in the call data. I'm going to go ahead, run now, step. Once we get to this jump if, we have F and 0. So we have the jump destination, but we have false here instead of true. Now, if we enter we don't jump. However, we still go to the jump dest because that's next in line, right? So we basically just didn't jump and we went to next in line. I guess it's kind of confusing because no matter what, if we jump or we don't jump, the next opcode is the jump dest. So I guess that's not a great example there. But in any case, good job. We have now successfully done a function dispatch for the update number of horses. Good job. But what if they aren't calling the update horse number? What if instead they're calling the read, what is it? The read number of horses. Read number of horses with this function selector. Okay, well, that's easy. We just don't jump, right? No worries. Oh, but our stack has nothing on it, right? Up here, if we don't jump, we now continue with our stack with nothing on it. Oh, well, that's kind of annoying. Well, no worries. We could just run this again and get the function selector again so we could check to this one. We could 100% do that. But what's a lot easier and costs less gas is if once we get the function selector like this, before we do any checking, we actually duplicate it so that there's always a function selector on the stack. It costs less gas than doing all of these. It's one less opcode. And this is where a lot of the optimizations from coding in Huff versus Solidity sort of start to take shape. Solidity might not be as clever as you at doing some of these optimizations. Solidity, maybe it just goes, oh, okay, well, I'm just going to re-get the function selector the way that I got it before. Whereas it might be a lot smarter if instead we just duplicated the function selector. So I'm going to add an opcode here. We're going to add the dupe1 opcode. Oops, we go to evm.codes. Let's see what dupe1 does. It just duplicates the first item on the stack. The input, the top of the stack, is going to be the value to duplicate. And then it sticks on top of that the duplicated value. So now if I go back and I add this dupe1 opcode, all of my comments now need to get updated, right? So if we add dupe1 here, thank you ChatGPT, we're now going to have function selector. And when we add this, the update function selector comparison, the stack is now going to look like boom, function selector. When we do equals, the function selector is going to be underneath that. When we do the update jump, the function selector is going to be underneath that. And then when we do the jump if, the function selector is still going to be on the stack. So now if we don't jump, we still have the function selector, and we can just redo this process. So typically you'll see this setup for checking for function selectors in Huff and actually in Solidity. They'll duplicate the function selector, check to see if it matches another function selector, jump, and then do the same thing all over again. So we probably would, if we had more function selectors, do dupe1 again. But since this is the last one, we can leave it off. So here we are. So now we want to do the same thing, but for read number of horses. We can skip the dupe1 because this is our last function selector, right? So we have the original call data function selector on the stack. So what we want to do is we want to push the read call data function selector on the stack. And now we have the read function selector and then the call data function selector. And we can do the same thing. Let's compare if they're the same. So we have now just true if the function selector matches. We can now create a different jump destination. We'll call it read jump. And now on our stack, we're going to have the read jump, and we're going to have that true false conditional. I should probably do this to make it make more sense. And then after that read jump, we're going to do again a jump if. And if this is true, we're going to jump to the read jump, which we want to go ahead and make a read jump destination. We'll call this one, actually, yeah, thanks ChatGPT, get number of horses. Down here, define macro, get number of horses equals takes 0, returns 0, like that. And the function selector isn't on here anymore, and that's fine because we only had 2 we wanted to compare to anyways. So already, by learning Huff, you've learned how to make a more efficient function dispatcher than Solidity, because Solidity will have an extra dupe opcode here, extra dupe1 opcode, which is going to cost gas. So congratulations, you've just leveled up just by doing this so far. So if we compile this, we should have 2 different jump destinations, one for updating the numbers and one for reading the numbers. So let's go ahead, let's compile this. Again, I'm going to do the bin time or the bin runtime. So this is just the runtime. Let me copy this and we'll paste this once again to the playground so we can really feel what's going on. And wow, look at that. So now we have 1 jump dest, we have 2 jump dests and 2 jump ifs. So it looks like the first one we're comparing for the update, and then we're comparing for the read. So let's go ahead, let's run through this. And again, we're going to be looking at the stack at the bottom, and let's see if once we hit here, it should jump down to here, right? If we pass in the correct function selector. So I'm actually going to copy it so that it should be the correct function selector. And we're going to go ahead and run this. So we do push 0, great. Jump to, yep. Cool, and now we're at this jump if, and here's what the stack looks like. We have a 1A, which is going to be what? This is going to be the program counter or the jump destination. We have a 1, which stands for true, and then we have the original function selector on our stack once we get to this opcode. since this is true, our jump if should jump down to 1A, this valid jump dest, when I hit this step into button. And that's indeed what we see. Perfect. So our code is working the way we want it to work. We're getting valid jump destinations. Our code is compiling. Oh, this is so exciting. We're learning exactly how opcodes work and exactly how Solidity compiles our smart contracts into opcodes. And we're learning even more efficient ways to do it. So I know this is really low level. A lot of this can be confusing. So be sure to stop, pause, ask questions, etc., and tinker with some of these, right? Compile some different contracts, stick it into here, try to play with them, put in different call data values, etc., and see what happens. What will happen if we don't jump? What will happen if we don't jump anywhere? Well, the code will just keep going, right? The code will just keep going, and maybe it'll call whatever the next opcode is. In our case, the next opcode is these two jump dests, which cost gas, right? If we don't get a valid jump destination, we want our function dispatcher to end. We want it to revert. So what's good practice is to add some type of revert statement at the end here so that the code just doesn't continue to execute. And maybe even worse, it executes something you don't want it to execute. So if we do not get a valid function selector in the call data, we want this call to revert. And to do that, we're going to use the revert opcode. So if we go to evm.codes, we look up revert. Here's the revert opcode. It takes two things on the stack, which are going to be the offset and the size. So the offset is going to be the bytes offset in memory in bytes, and the return data of the calling context, and the size is going to be the size of memory to copy. If you wanted to revert with an error code, putting something into memory is how you would actually return with an error code. And this is how you would pick where in memory to actually return the data associated with the error code. For us, we're not going to do an error code. So we're going to say, great, just stick 0 and 0 on the stack and then revert. So on the stack, we would have put 0, 0. And then once we revert, there's nothing else on the stack. And same thing, if we compile this, and now we grab this, we go to our playground, paste it in here. If we run this without a valid function selector, so let's just do like 1111111 or something like that. What should happen is we shouldn't hit these jump dests, right? Because we should hit this revert before we jump here, before we jump to these. If this equals return true, we would jump to this jump dest. We would jump over the revert. But if we don't have a valid jump destination, we're going to run to this revert, which is what we want. So let's practice. We're going to put some dummy data in here. I hit run, step, and then, oh, yep, sure enough, we landed on the revert. If I hit step again, boom, it's done, right? It doesn't go to these jump desks because the call reverts. And even in the little log here, we see revert. And we reverted with no data. So these jump desks don't get executed, and that's what we want. Great job. So we now have a function dispatcher. This is exactly what Solidity does and Viper does and all of our smart contracts do whenever they get a transaction, whenever they get call data. This is the first thing that they do. And later on in this section, when we break down the Solidity bytecode, you'll see that Solidity does this exact same thing, but with a few more opcodes, and you'll see why. Now we're going to do two things to make this a little bit nicer. I've kind of got a lot of comments in here that are making this a little bit difficult to read right now. And this function really isn't that many lines of code, but it looks like it's a ton of lines of code because of how many comments are in here. So I'm going to go ahead and delete most of my comments, but you put the amount of comments in your code base that you want. I'm also going to line up a lot of these jumps as well, a lot of these lines as well, because same reason, I want to make them a little bit easier to read. But yeah, you can do whatever you like to do. This, that, this, beautiful. Cool. See, this is actually what our main function dispatcher looks like, and that's a lot smaller than what it was before. So this one's going to be update number of horses. Bit of syntactic sugar that comes with Huff is actually making these function signatures, these function selectors, a little bit easier to read. What Huff has is this keyword called double underscore, all caps, func underscore sig. And this will actually calculate the function signature for you, so you don't have to manually do it with cast or every single function selector that you're using. What you can do is at the top of your code, you can actually define a little interface. And in this interface, you can write the different functions as how they would be defined in Solidity, and Huff will take those and convert those into function selectors. So we'll do define function update horse number with a uint256, which is going to be non-payable. Like so. So we have to do this non-payable bit in Huff. And then we'll also do define function read number of horses. And since this is a view function, we don't need non-payable, but this will return a uint256. And now that we have this Solidity-esque interface here, we can actually use these with this func sig keyword. So now instead of adding the function selector directly here, what we just do is we do double underscore func sig, and then in here we put update number of horses. So this will take the update number of horses function from our interface and convert it right for us in here. And we can do the same thing for read number of horses. Copy that, paste it in here, boom. And you'll see when we compile this, we can even copy this, paste it into Huff here. Oops, I forgot the B at the end. You'll see it's the exact same code as what we got before. Same function selectors, same everything. It's just a bit of syntactic sugar to make it easier for us to auto-calculate those function signatures. All right, this is great. So now we have our function dispatching. We've got a little interface to make function dispatching a little bit easier, working with our function selectors. Now we have our two main functions that we get to work with. We have our set number of horses and we have our get number of horses. These are going to be the jump destinations for our opcode to go ahead and work with. So let's actually do the set number of horses or update number of horses first. And the reason that we're going to do this one first is because one of the first things that we need to do is we actually need to store this value in a storage slot. So a quick refresher on storage. When we work with storage, we can think of storage as a giant array. A giant array that when the execution of our transaction finishes, it stays, right? And we have variables in our contracts in Solidity that get mapped to some storage slot that stays and persists. Booleans get mapped, favorite numbers get mapped, and they all get mapped in some type of bytes 32 structure. And mappings are a little bit tricky, where the way they work is they have little hashing algorithms that assign their values to a storage slot depending on what slot that array is assigned to. So like, let's say in this example here, my array is at slot 2 in storage. The first value, the value at slot 0 in my array is going to be at kcac 256 of 2 of whatever the value is. So they use a hashing algorithm to put the data of arrays and mappings at slots in storage that are hopefully nobody else is going to use. Constants do not go in storage, nor do memory variables, of course. So when we're working with storage and we want to update storage, we got to do a couple things here. So to set our number of horses, we got to do a few things. We're going to, number one, have to give it a storage pointer or a storage slot. And then number two, call the sStore opcode to store the value. And that's pretty much it. So our set number of horses needs to do these two things. And then once it's in storage, we'll essentially give it a little slot here, which will represent the num of horses, right? And this will permanently be in storage forever at whatever storage slot we give it. And once we do this, and once we write both of these, then we can write some tests that will compare our Huff implementation against our Solidity implementation, and we'll see that they both do exactly the same thing, which will be really exciting. So we're almost there. We're getting actually really close. We're actually almost done with this Huff code base already. Let's set number of horses. Let's update the number of horses here. So let's do that. So in order for us to store this data is we're going to have to use the sStore opcode. So if we look for the sStore opcode, this is the opcode that's responsible for storing data to storage. And once again, it has a stack input here, and it actually has no stack output. So it's just going to pop the first two items off the stack and stick those values into storage. So the first The top of the stack is going to be a 32-byte key in storage, and then the value to store. So the top of the stack is going to tell us where to put this, basically. Are we going to put this at index 1 in storage? Are we going to put this at index 2 in storage? At index 3 in storage? And then, of course, instead of 1, 2, 3, these are going to be bytes, binary here. But where is this number of horses variables going to belong? Slot 1, slot 2, slot 3, etc. And then the value to store obviously is going to be the number of horses that we want to put in here. Actually, we have to do one more thing. We have to get the value to store from call data. And then we have to store it. Sorry. So we have to get a storage slot, get the value the user called to store, and then store the opcode. So on horse store, update number of horses. Maybe they put in like 2, right? We have to say, okay, well, the number of horses storage slot is X. You want to store number 2. Okay, let's store number 2 at storage slot X. Great. So let's go ahead and let's do that. So how do we get the storage slot for number of horses? Well, we could do this a number of ways, right? We could hard code it. We could just say, okay, at 0x, 80 or something, that's going to be where we store this storage slot. And we 100% could do this, but Huff actually makes working with storage a little bit easier. This is another one of Huff's few abstractions that they have. They have this keyword called free storage pointer, where it essentially is just a counter for what storage slots are open. So if we, in our code base here, we scroll to the top, if we define a constant variable, call it number of horses storage slot equals free storage pointer like this, this will just assign number of horses storage slot to slot 0, to whatever slot is open. If we do a new one, number of horses storage slot 2, this would assign it to 1. So this free storage pointer is just a counter essentially, which says, okay, here's the slot that's currently open in storage right now. Because remember, every storage slot is going to be 32 bytes. So number of horses slot, free storage pointer. We could also just say it's 0x00. We could hard code it like that. But when working with storage, it's usually best to use the syntax in Huff. So cool. So now we're saying, okay, in storage, sorry, it actually increments from 0, not from 1. In storage, at slot 0, that's where we're going to put the number of horses. Not slot 1, not slot 2, not slot 576, at slot 0. So anytime somebody looks at this smart contract, looks at storage slot 0, that's where the horse number is going to be stored. And that's exactly how Solidity works. When Solidity sees the first variable in a Solidity contract, it is automatically assigns this to slot number 0. So great. So now we have a storage slot. So we're probably going to want to use this storage slot. Now to reference this storage slot 0 in our code, down in here, we do this syntax like this. We just put it in between these brackets. These brackets here will basically say, okay, I'm going to put onto the stack. It basically is doing a push of this value onto the stack. So I'm going to push that 0, that storage slot pointer. For your notes, you can put number of horses storage slot. You can do 0x00. You can do PTR for a pointer to that storage slot. Whatever you want to do. This is essentially saying at the 0th index, what this number is returning is it's returning the number 0. We're saying, hey, number of horses is at index 0. Great. Number of horses storage slot is 0. So this is just the index in storage where it is, or the pointer of where that value is. And this is where we're going to want to store our data. And if we go back to the store opcode, we're going to need the 32-byte key in storage. Check. We just got that. Now we also need the value, and we need the key on top of the value. So we should do the value first because that's how stack works. So these are actually kind of out of order. Boop, boop. So we actually need to get the value from the call data first so that the key is on top of it. So the question is now, okay, how do we get the value we want to update from the call data? Well, remember in Remix, we grabbed this chunk right here, which was kind of a little demo of what's going to be sent. So again, the first 4 bytes is going to be the function selector. And then the next is going to be the call data associated with the parameters of that function. For us, the uint256. When we did this in Remix, this was the wrong function selector, but if we did this Remix, if I change this to 7, update horses, let me look at the transactions, scroll to the bottom, input here. Let me copy that, show you what that one is. Boom. This is the call data that's going to be returned. Once again, we have the function selector at the beginning, and then all of this is the encoded 7. So this is the hex of the number 7. So everything after the first 4 bytes, these 32 bytes here, is going to be the number that we want to update this to. So how do we do that? Well, we already know how to get call data because we learned about call data load. Call data load, right? So call data load, what does it do again? Okay, the byte offset in the call data is the input, and the output is going to be the 32 byte value starting from the given offset of the data. Okay, great. So if this is our call data, right, because the call data is going to be the same no matter what, it's not going to change, we want to get rid of the first 4 bytes. We would set the byte offset, our stack input, to be the first 4 bytes. Because remember, the function selector is going to be 1, 2, 3, 4 bytes. And the rest of this is going to be the 32 bytes associated with the call. So we just saw that in Remix. Let me actually copy the Remix one because that's using the correct function selector. So what we would do is we'd push 0x04 onto the stack. So essentially 4. And then we would do call data load. And this call data load is going to just add on the, if we called with 7, it's just going to be that 7. So this is going to be essentially the call data minus function selector, or you can just say this is going to be the input value, whatever you want to call it. So now we have the input that we want to actually store, or the value, whatever you want. Then we put the number of horses storage slot on here. So we would have storage slot input. So just storage slot. I like that a little bit better. Storage slot or value. Let's do value. I like value a little bit better. Storage slot and value. Then we can call the store opcode. Because what's this going to do? Again, store. It's going to say, okay, at the top of the stack is the 32 byte key in storage. That's our storage slot. And right underneath it is going to be the value to store. That's going to be our input 7. So we're just going to call store. And then importantly, we're then going to call stop. If you don't call stop here, the code will continue to execute. If the opcodes for get number of horses are right after, it'll also do get number of horses, which kind of would be a waste of gas. And we don't want to waste gas. So we're going to stop here. So the stop opcode costs 0 gas and it just stops the transaction. That's it. It doesn't revert. It's a successful transaction, but the transaction is just done. It's just the end of the transaction. Cool. So this should be a working macro to actually update the number of horses in storage. Well, let's compile this to make sure it actually compiles. It sure does. This is the runtime code. So let me copy the runtime code. Let's bring it over to the playground to test this out. And don't worry, I'm going to show you a better way to test these pretty soon. And now if we look in our opcodes list to the right here, we now have this store opcode at the bottom. Okay, exciting. All right, so let's come up with some valid input data. So this should be valid input call data to update the storage to 7, right? Because we have the function selector for update number of horses. And then the parameter data here is the number 7 encoded. So if I grab that and I stick it into the hex call data of our playground here and then hit run, we now can rip through and see our memory and stack as we do this. And we're going to show you a way to do this in Foundry as well. So let's go ahead and step into this. We kind of already know what some of these are doing. It looks like we're pushing the function selector, we're comparing it, we're pushing the other function selector, we're jumping if, and it looks like we went ahead and jumped, right? That's why we shot down here as I was pressing the buttons, because we've identified a correct function selector. Now we're doing push 4, which is what this push 4 is going to be, this push 4 right here. Then we're doing our call data load, which is going to be this part right here. Push 0, because our number of horses storage slot is actually storage slot 0, right? Push 0. And then we do an store exactly as we just thought. So if we scroll down, right now on the stack is 0, 7, and the function selector. Oh, I guess the function selector is technically on the stack when we do this as well, but that's okay. I didn't put it in the notes here. So 0, 7 in the function selector. So storage slot, value, and then also the function selector. And when we hit next here, it should store that 7 into this little storage bit here. So I'm going to hit next. Now we're at the stop, and we see the value 7 is in storage slot 0. And if we hit next, now that we're at the stop, we've actually ended because stop ends execution. You can see there's actually another jump test after the stop that we didn't go to. And this other jump test is going to be the read number of horses code. We don't want it to read the number of horses. We want it to just stop. We want it to finish executing. So that's why this is here. This stop is actually really, really important because if this next function in your code base was like update number of horses by 2, whenever you update number of horses, it would double it, or it would do whatever this next function is. And we don't want it to do that. So awesome. So we learned after the function has been dispatched, run the function and then stop. And when we decompile the Solidity smart contract, this code right here is nearly identical to what this function is doing in Solidity. These two are doing almost exactly the same things. Solidity has a couple of more guardrails, a couple more opcodes that I'll walk you through in a minute. But essentially, you've just learned how to build a function in Huff and essentially in raw bytecodes. This is so exciting. All right, nice. Let's keep it going. So now we only have one thing left to do. Let's just figure out how to read the number, and then we can write some tests, and I'll show you how to debug Huff a lot better, a lot easier than copying and pasting the output into this playground over here. So final thing, get number of horses. We want to read the number of horses from this storage slot that we came up with up here. So how are we gonna do that? Well, number 1, get the storage slot. Number 2, load the value of that slot into memory, and then 3, return. So there's 2 keywords that 2 opcodes that we're going to work with here, and they're going to be sload. You've probably definitely heard of this before. This is where we load from storage. This is the read from storage. This is a very gas expensive opcode. At the top of the stack is going to be the 32-byte key in storage. This is the index in storage we want to read from, and the output we get from this on the stack is going to be the value stored in that slot. So essentially at the top of our stack, we're going to have the number 0 or the index in storage, or the key in storage, if you will. We're going to run the sload. It's going to pop this off. EVM is going to go, okay, let's look at storage. What's at slot 0? It's the number of horses. Great, let's stick that onto the stack. And that's it. That's how that's going to work. The other opcode that we're going to look at here is actually the return opcode. So this halts execution, returning output data. This is essentially the same thing as stop, except it returns some data. And it returns data from memory, not from the stack. So if we want to return a value to the user, we have to first load it into memory and then return it out of memory with the return keyword. So to add stuff to memory, we're going to use the mstore, which is essentially the same as store, but instead we're going to be using mstore. So it's like memory storage. Because again, you can think of memory as basically the same thing as storage, just a giant array, but the difference is it deletes at the end of the transaction. All right, cool. So first thing, let's get that storage slot. Well, we already know how to do that with this notation here. So this is going to be the key or the index or whatever you want to call it. Then all we have to do with this key is call sload, because the sload, that's all it needs, is the key. So we're saying, hey, at index 0, give us the number of horses. So we go sload. And now on our stack, we have the value. We have the number of horses on our stack now. So now in order for us to return it, we got to stick it into memory first. So this is where we're going to call mstore, which is right here. So mstore takes an offset and a value. So the offset is going to be the offset in memory in bytes. And you can think of this again as kind of like the index in memory. So are we looking at index 0, index 1, index 2, index 3, etc.? But instead of index, it's like the offset in bytes. So, but just, you can kind of just think of it as like the index of memory. So we don't have anything in memory. So we can just say, okay, 0x00. So we're going to stick it at the 0th index in memory, or the 0th offset. So now we have 0, comma value. Now that the top of the stack is the offset and right underneath is the value, we can just call mstore. mstore. And now we pop both of those off. And now we have nothing in the stack, but our memory looks like this now. So this is kind of the hard part of working with opcodes and working with Huff. There's a lot of data structures you will have a hard time keeping track of when you're writing assembly. What's on the stack? What's in memory? What's in storage? What's in this? What's in that? This is why everyone codes in a higher level programming language like Solidity. When you have a ton of stuff in memory, a ton of stuff on the stack, it can get very difficult conceptually for you to keep track of all this stuff. But once we have our value, our number of horses stored in memory, what we can do then is actually return it. And the return keyword takes an offset and a size. So this is going to be the offset in memory. For us, it's going to be 0 because we put it in the 0th slot in memory. And then the size in bytes is actually going to be 20. And that needs to be where? That needs to be below the offset. So we're going to do that one first because that's how stacks work. So the size is going to be how much of the memory data we're going to copy. 0x20 is going to be equal to 32 bytes. 0x20 equals 32 bytes, right? If we do cast to base 0x20 dec, we get 32. So we're going to say, okay, we're going to have something in memory slot 0, which we just stored right before this. It's going to be 32 bytes long because it's just a number, right? That's all we stored. And then we're going to run return. And this again is going to pop everything off the stack, and it's going to return what's in memory. And what's cool is it's going to exit the current context successfully, which again, as you know, it's basically exactly like this in any function, like this keyword right here. And that's it. So let's try compiling this. Great, compiling successfully. So now let's finally stick this into the playground and see end to end how this would work for reading some data. So now we actually don't need the set number of horses function selector. We need the read number of horses function selector. And we actually don't need any other call data other than the read, because in our read code base, we never access any other call data outside of the function selector in our dispatcher. So I know I'm saying a lot of words, but let's paste it in here and let's run it. Let's step through this. And if you want to scroll down and see what the slots look like as we do this, you can do so. So we scroll up, some of our beginner stuff, the SHR that tells me that we're in the function dispatching section. Okay, there's the equals, there's the jump if. We didn't jump, so we're going to compare it to the next one. Here's a second jump if. And if this is wrong, if this function selector is wrong, we are just going to hit the revert. If it's right, we're going to jump down to the section down here. And we sure do. We jump down to the section down here. And we can even see kind of the rest of the opcodes where we're going to push 0. We're going to S load. We're going to load from storage. So after that opcode, if I scroll down, we now see on the stack is 7 because actually, well, this is still actually left over from the last time I ran this. So the playground's really cool where the storage and the contract will actually stay. So I have 7 in there. If you're running this for the first time, you'll probably have 0 in there. But now we've loaded that 7 into our stack. We now need to store it in memory. So after we run this mstore, I'm going to hit step into. So we just ran this mstore. So if I scroll down, we now see in memory, we have the 7 stored here in memory. And now we're going to push 20, push 0, and return, which is going to say, okay, start from 0 in memory and return all 20 bytes, all 32 bytes or OX20 in hex of memory. And boom, that's exactly what happens. So this is incredibly exciting because you just wrote your first Huff smart contract. And in doing so, you learned about a ton of different opcodes and a ton about how the EVM works. Let's do a quick refresher of all the stuff we learned, and then we'll go on and we'll write some differential tests here. We learned every single smart contract, doesn't matter if it's written in Viper, in Solidity, in Huff, pretty much needs to start with a function dispatcher. And this is when you check the call data sent to the smart contract for the function selectors. Once you find a matching function selector, you basically route the call to whatever lump of code is associated with that function selector. We learned about the jump if opcode, where we can jump if some value on the stack is true. We learned how to work with storage slots. We learned how to S-store. We learned how to S-load. We learned what memory was, and we basically just learned how to write a smart contract in raw opcodes. This is fantastic. If you're kind of feeling overwhelmed right now, now's a great time to go take a break, go for a walk, grab a coffee, and come back to this. This is heavy stuff. And the Huff docs do a great job as supplemental information on understanding the EVM, showing pictures, etc. If any of this doesn't make sense to you, tinker with it. Try something else. We are not going to show you the Huff debugger, so you do not need to install HEVM. However, if you like to, feel free to go ahead, try HEVM with the Huff debugger. Although I'm going to tell you right now, you will run into some hurdles installing HEVM, installing potentially Nix, and working with the Huff debugger. Use at your own risk, essentially, and I'm not going to be showing you how to work with it. Instead, we're going to be showing you how to write Foundry tests that work with Huff so that you can basically debug everything through Foundry. Cool? Cool. Okay, well, we are at a phenomenal place. We've learned a ton already. We've built a smart contract in Huff. We have the equivalent solidity over here. And now you can probably see why nobody would ever want to write their smart contracts in Assembly or in Huff. Writing opcode by opcode is a whole lot more tedious than writing a higher level programming language like Solidity. Sure, you might be more gas efficient, but it's kind of 5 times as long to do something that you can do in Solidity in like 2 seconds. But to make sure these two code bases are doing the same thing, we can write some differential tests or some differential fuzzing, etc. And once we write these tests to prove they're doing the same thing, then we're going to break down exactly what's going on in the Solidity code, opcode by opcode. And you're going to see a whole lot of comparisons, a whole lot of parallels to what we just did in Huff. So what we're going to do to get started is we're going to create a new folder in here, and we're just going to call it V1 of our tests. And this is where we're going to write our V1 tests. Now I'm going to make a file called base test v1.t.sol. And this is actually going to have all of the tests that we want for both Huff and for Solidity. We're going to have a Solidity version of the test inherit this one, and a Huff version of the test inherit this one, so that we are 100% sure both smart contracts are running on the exact same tests. You'll see what that looks like in just a minute. So let's go ahead and let's write some tests here. And I'm going to go kind of quick because at this point you should be pretty good at writing this stuff. It's going to be an abstract contract so that when we run the tests, you have to inherit this contract in order for tests to actually run. Base test v1 is test. So feel free to follow along with me, or if you want to just copy paste, you can do that too. But I highly recommend you writing the test, because getting good at writing these differential tests will be really, really helpful for you. So we're going to import horse store. This is going to be the Solidity src horse store v1 horse store.sol. Import test console2 from forge std test.sol. Abstract contract base v1 test is test. Okay, great. We're going to have a horse store public horse store function setup public, and we're going to make this virtual because we're actually going to override this in a bit, and you'll see why. We're going to say horse store equals new horse store. So this is pretty typical of Solidity, but what about for Huff? Well, let's finish writing this. Let's actually just write one test here. We'll say function test read value public uint256 initial equals horse store dot read number of horses. Assert equal should be 0. Equal. So now if we run forge test, this actually won't run. This will do a whole lot of nothing. Why? Well, because we are in an abstract contract. So what we're going to do is we're going to make another one called horse store sulk.t.sol. And this is where we'll do pretty much nothing different. GPL 3 only, 0.8.20, contract horse store sulk is base test v1, import base test v1 from there, and boom. And now that we actually have a contract that's not an abstract contract, now if we run forge test, the test will actually run, ta-da, and it passed. And it's because it's inheriting all the tests from in here, the one test and the setup and everything. Now what we want to do is we want to actually create a new file called horse store huff.t.sol. And we want to put this into v1, excuse me. And I'm actually going to copy paste this one. I'm going to copy paste our horse store sulk. We're going to call this horse store huff. And the only difference that we're going to do is we're going to do a function setup public override. And instead of deploying horse store equals new horse store solidity, this is where we're going to have horse store equals the Huff edition. And this way, both our Solidity smart contract and our Huff smart contract will run on the exact same tests. Pretty badass, right? So in order for us to deploy a Huff smart contract in Foundry, we need to use this Foundry Huff Foundry extension. And you can find a link to this in the GitHub repo associated with this course. So if we scroll down, you obviously need Huff installed, but to install this in Foundry, you just run this forge install Huff language Foundry Huff. So let's come back over here. Let's install this. Oops. --no--commit. And what this is going to do on the back end behind the scenes is whenever we deploy a Huff smart contract, it's actually going to basically run Huff C, blah, 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 the smart contract, paste it into some file, and then Foundry is going to read the binary and use that to deploy a smart contract. So since Foundry is going to run the Huff C command, we have to do FFI equals true. Now remember, anytime you do FFI equals true, you're basically giving Foundry permission to do a whole lot of crazy stuff. So just always keep that in mind whenever you set FFI to true. And then additionally, we're going to need to add some remappings. We're going to say Foundry Huff equals lib/Foundry Huff/src. And now that we have Foundry Huff installed, we're going to import the Huff deployer. So import Huff deployer from Foundry Huff deployer.sol like this. And what we can do is we can actually deploy our Huff smart contract. So you can actually go ahead and read the Huff Solidity codebase if you want to really know how it's working. But I'm just going to pretty much give you the shortcut here. We're going to say horse store equals Huff deployer.config. It's one of the first things you pretty much always have to do. .deploy, and this is where you actually give it the file path of the horse store. So for us, we're going to say string public constant horse store Huff location equals, and the syntax is a little bit weird. It assumes everything's in src, so you don't have to put src, but you do have to put the file path, but without Huff, without the .huff. So it's a little bit confusing, but so no src, horse store v1/horse store. So we're not doing src/, it just assumes it's there. And we're also not doing .huff. It assumes it's looking for a .huff file. So we'll do horse store equals Huff deployer.config.deploy horse store Huff location. And then we have to wrap this all up into horse store like this. Oops, like this. And then we also need to import horse store from base test v1.t.sol. And that's it. And once we have this set up like this, what's going to happen is we're going to run two suites of tests, horse store Huff and horse store sulk, and they're both going to run on every single test that we put in the base test. So now if we run forge test, we should see that test run twice because it's happening in two different folders or two different files. We ran into a bug here. Great. The error was only on the Huff one. So we can actually do forge test -- match path star Huff star -- actually, we can just do that. So this will only run forged tests on the files with Huff and this one test that didn't pass. So let's actually do that again with -1234, and we'll see why I failed here. And we're getting this error not activated. That usually means it's defaulting to the wrong EVM version. So let's do EVM version equals Shanghai in the foundry.toml, and let's run this again, and a pass. So a lot of the Foundry tests actually default to Paris. So we just need to put in, hey, we want to use the latest and greatest, Shanghai, which has push 0, ta-da, and we pass. Hooray. So what did we just prove? Okay, well, we just proved something pretty simple, actually. In our base test, we just proved that at storage slot 0, both of these start with a value of 0. Which is pretty trivial, makes a lot of sense. But we can go even deeper than that. So we can run this same test again. So I'm going to hit up a couple times. And I can also do --mt, or excuse me, --debug, paste the test name, and now run it. And now we'll get popped into the debugger, where we will be able to go opcode by opcode. We would see exactly what we would see if we were calling the smart contract and we wanted to look directly at the bytes data. So pretty cool stuff. You can see at the bottom all the different little commands you can use. So I'm just going to hit J a bunch, which stands for next opcode, and we'll be able to go opcode by opcode in here. Now, kind of got to zoom out a lot for this for you to get a good eye of what's going on here. It might be a little bit small here as you're watching, but yeah, that's kind of just the way it is. But if we kind of scroll down in the code base here, there's a whole lot of setup that the test needs to do that we can kind of ignore. And this kind of is one of the hard parts of working with the debugger in Foundry is you want to get to that call stack of the actual contract. And we can see at the top, the address that we're working with. And when I hit J once more, it looks like this is where we finally start working with our smart contract, our actual test. And that can be kind of tricky to tell when you're actually in the smart contract, but looking at the function selectors here, right? So we see some familiar stuff. We see a push 4, and I know it's kind of really small. We see a push 4 equals push 2, push 4 with some function selectors that we recognize. Now we can pretty easily say, okay, it looks like we're in the right code. It looks like we're making a call to our smart contract. So now, if you wanted, you can literally go opcode by opcode. You can see what's in the stack. You can see what's in memory. And if you run into an issue with debugging a Huff smart contract, you could use the Foundry debugger to actually walk opcode by opcode through. So we can actually even see what this one's doing, right? So we have a call data load. After the call data load, it looks like this is what's in the stack. And I know it's super, super, super small, but it looks like it's just E0, 26, C0, 17. So that's going to be the function selector. And then 0 for the rest of the data. We have the right shift, dupe 1. We're checking if the function selectors match. Jump if. Okay, they didn't match. Okay, we're going to go try the second function selector. Looks like they did match. Great. We're in the part of the code where we're reading the number of horses. We're S-loading it, right? And so right when we do S-load, it's kind of uninteresting because we S-loaded 0 in. But then we load that into memory and then we return, right? And then it's running the rest of the test, which is going to be some like assert equals and stuff. So I know that was really small to see. So instead of doing the read, when we test the update in our tests here, we can put a number that's easier for us to see, like, you know, maybe like 777 or something. So, but okay, cool. So this works great. Test read value works great. Cool. So let's now do function test write value, right? And this is just where we're going to update the number of horses. So we'll say uint256 number of horses equals 777 horse store dot update horse number, because the function selector for the solidity and the Huff is going to be exactly the same number of horses. And then we can say assert equal horse store dot read number of horses should be equal to the number of horses. Now, if we pull up this again, let's run our test again, forge test -- match path Huff -- debug test write value. we'll be able to walk through the opcodes and hopefully we'll be able to spot this, what is it? This 777. So if I pull up a new terminal here real quick, and do cast to base 777 hex, we're looking for a 0x309. That's going to be the 777. So I'm going to zoom out a little bit. Sorry, I know it's super tiny. I'm going to hold down J, and we're going to look for function selectors that match or that 777. Remember, all of these opcodes are like Foundry setup, right? The test has to get set up. The tests have to get called. We're deploying our Huff. We're doing a whole bunch of stuff here. And okay, cool. Looks like we jumped to the contract. There's some function selectors here that I recognize. Okay, cool. So we have a push for equals push to jump if jump dest. It looks like we did indeed jump. And by here in the opcodes at this jump destination, we should be at the set number of horses jump destination right here. So this jump destination here should be the beginning of our set number of horses. Okay, we have a push call data load, push for call data load. That looks pretty promising, right? Push for call data load. That looks good. Then we do push 0 s store. So let's look at our stack right now. So at the top of the stack is 0. The second piece on the stack is going to be 309. Oh, okay. So at the bottom of the stack, we have, it looks like a function selector. And then once we did call data load, it looks like we see 309, which is going to be that 777. So when we called store with 0 and 777, we're basically saying we want to store at the 0th slot, the 777, and then we're going to stop. And that's the end of the call, right? And then we're going to do some asserts. That's going to be what the rest of these opcodes are. So I know that was kind of quick and there was a lot to that. But I want you to play with the debugger a lot, just like we did there, and try to figure out where you are in the execution. Just remember, whenever you run one of these tests, it needs to do all the opcodes associated with the setup, with the getting the values here, with the asserts, etc. Definitely practice using the debugger to actually see, okay, when are we testing 777? Because this will give you the power to actually, read opcodes. So just try to recognize where the 777 is, look for that 309 in those opcodes, and then you can be like, boom, I found it. I'm an opcode wizard, Jesus. But okay, cool. So we've written 2 real minimal tests. I'm just going to leave them like this for now because reading and writing is really all that we're doing. However, if you look at the Git repo associated with this course, we do take a slightly different approach, and you can do whatever approach that you want here. In the GitHub repo here, we actually do a little bit more formal differential tests where we actually deploy the Huff, the Yul, and the Sulk version. And then at the bottom, we basically compare them to each other, which is another way to really just make sure that they're the same. And then we use some fuzzing instead of direct values. So we probably would want to do the same thing here. So we would do UN256 number of horses as a fuzzing parameter, do the exact same thing, right? And now we can just run forge test. And now we'll fuzz both of these contracts so that they are looking good and they look equal. So Sulk looks good, passes everything. Huff looks good, passes everything. So one more thing, in this Huff, we could do some malicious stuff, right? Set number of horses. What if instead of OX4, we put OX2 in here, right? Now we run the tests. They're probably going to fail, right? And sure enough, they do fail, right? Because it's not the correct offset of the call data. We could put the wrong storage slot in the read, right? Same thing. If we run the tests, this is going to fail again. There's lots of ways to very subtly mess this up and fail your tests, and especially lots of ways for your Huff to go wrong or do something unexpected. This is why if you are going to write low-level assembly, low-level Huff, etc., it's highly, highly recommended you use stateful fuzzing, stateless fuzzing, and maybe even formal verification to prove that your Huff, your low-level code, matches your Solidity code. And later on in the course, of course, we're going to teach you formal verification so that you can actually do what we're working with here. But nice. So now you have a good understanding of how these smart contracts work at a binary level. What we're going to do now is we're going to take this Solidity and we're going to crack it open and we're going to go opcode by opcode of this Solidity, and we're going to break it down exactly what it's doing. Now that you've been primed with the huff, this section's actually going to be a lot easier than without the huff, okay? And if you want to see the breakdowns of these in the GitHub repo associated with this course, I've got some written breakdowns of what every single opcode in this is doing for both the huff and the Solidity. And you might be surprised, but the Solidity actually is way, way, way bigger and uses a lot more gas, and we'll explain why there's so many more opcodes in Solidity. So this is the part of the course where we're literally going to be ripping through binary. And it's going to be pretty fun because the whole time you're ripping through binary, whenever you're ripping through binary yourself, you're always asking, what is this doing? What is this opcode here for? And that's kind of the fun of being badass with EVM opcodes. You can start to make fun of compilers. You can start to shitpost about compilers on Twitter. Try to do that as little as possible. There's kind of a meme of gas optimizers who always shit talk compilers, but whatever. This will teach you the low level, how this stuff works. And a lot of smart contract developers do want incredibly proficient, incredibly performant assembly chunks of their smart contracts. And only once you know how to use all of these opcodes will that power unlock for you. So we're going to break down a Solidity contract. We're going to deconstruct it ourselves, and you're going to learn exactly how the Solidity compiler works. So go get a coffee because this part's going to get pretty intense. We're going to do a whole lot of reading. And the main thing we want to ask ourselves is, what is the Solidity compiler doing? Why is this opcode here? And we're going to consistently ask that question. But big check mark to ourselves. We have written the horse store in Huff. Huge check mark. We understood where and why this data looks like this. And then how does Remix know to update the number of horses with this data? Well, we learned that too, because it all is about the opcodes. If you're pumped about just learning this much, this far, this is a great time to jump on Twitter and say, holy hell, I'm learning so much about Huff and the EVM, and tag us, tag Cypher and Updraft, tag me. But yeah, go get a coffee, go get some ice cream, maybe go to the gym, because we're going to get intense by cracking open this Solidity code. Let's do it. All right, and now is the time where we are going to break down all these opcodes in our Solidity smart contract, and then we're going to compare it to the Huff smart contract. So I'm going to go ahead and create a new folder called Breakdowns, where we're going to see exactly what these opcodes do in these smart contracts. So when we compile our horse store.sol and we deploy this in our out folder, we go to horse store.sol, horse store.json. Let's go ahead and let's format this, and let's toggle the word wrap. Let's go ahead and find the opcodes or the bytecode. So here are the opcodes. Here are the opcodes in their binary. And I don't think we have the opcodes in the text in here. Okay, no, we don't have the opcodes in the text in here. That's okay. So what we can do is we can actually copy this, and in our new little breakdowns folder, we're gonna create a new file. We're going to say sulk breakdowns.c++. This isn't really going to be a C++ file, but the syntax highlighting for C++ is going to be really nice. So we're going to just pretend this is a C++ file here. And I'm going to toggle the word wrap. So here is the sulk binary. Now, every two of these is going to be an opcode. So 60, for example, go back to evm.codes, go to 60, that's going to be push 1. So we could 100% break it down opcode by opcode like that in the binary, but that's kind of a huge pain, and I don't want to do that. So instead, what we're going to do is we're going to go back to the playground, paste it in here, switch over to mnemonic, and then just copy everything in here and paste it like that. Boom. Now we have all the opcodes that are going to get deployed. And this is the only time we're going to be walking through these opcodes is for the Solidity. I also have a breakdown of the Huff opcodes, but that's obviously a lot easier because the Huff is basically just opcodes here. But this is the only time we're going to do a walkthrough of the opcodes. But I do recommend that you try to walk through some small contracts of your own after this section and see if you can understand how the opcodes are working yourself. And so let's break down exactly what all of these opcodes do for our Solidity code here. And let's start from the top. So you will see this exact setup in pretty much every single Solidity smart contract that you work with. 60, 80, 60, 40, 52. This right here is going to be the first section of the contract creation code. Remember how we said there's 3 sections, right? There's 3 sections. 1, contract creation. There's 2, the runtime, which is what actually gets stored on the blockchain. And then there's 3, which is the metadata, which often is kind of nothing and just tells a lot about the compiler version that was used and any other metadata that you want to store about the smart contract. So the beginning is always going to be the contract creation code, no matter what, right? Because when we deploy this transaction with all of our data, the entry point to our transaction is going to be the first couple of opcodes, right? So the contract creation code is always going to be our entry point. But why do we always see this push 180, push 140 mstore? What is this doing? Well, this first section that you see all the time in Solidity is something known as the free memory pointer. So if we do the little notations here, what is this doing? Well, it's pushing 0x80 onto the stack. Then what's it doing? Then it's pushing 0x40 onto the stack. 0x80 is onto the stack. And then it's doing an mstore. Okay, well, what does mstore do again? If we go back to evm.codes, mstore, offset value, and it pushes that value into memory based off of the offset. So the top is the offset of OX40 and the bottom is OX80. So let's look at a little example of this that I did at an ETH Denver talk a couple of years ago. So we have this push 80, push 40, and then this mstore. So here's what our memory looks like, and here's our starting stack, right? So memory, as we know, is kind of this giant array. And originally, I was showing you it as a giant array of 0, 1, 2, 3, 4, 5, etc. with like indexes. That's not technically correct, right? Technically, it's an offset in bytes. So it could be 0x01, 0x02, 0x03, etc. 0x20 is going to be the 32 bytes. So if we look at memory as this array of 32 bytes, you know, the 0th slot is going to be 0x0. The first slot after the first 32 bytes is going to be 0x20 because 0x20 is the hex of 32 bytes. So 0x0 is the 0 slot, 0x20 is the first slot, 0x40 is the 4th slot, etc. When we do these opcodes in Solidity, push 80, push 40, mstore, we're pushing 80 on the stack, then we push 40 on the stack, and then we store that 0x80 into the 0x40th position. This 0x40 is always a reserved slot in memory for this thing called the free memory pointer. Why do we need to have memory and storage? Well, stack is restricted in size, memory is much bigger, right? Variables are returned from memory, they're not from the stack. We're always going to have to do stuff with memory. But since we put something in memory here, if we want to put another value into memory, how do we know where we can put stuff in this memory array? So how do we know what parts of memory are free? We need a way to keep track of what hasn't been taken up in memory, right? So here's another setup of what memory looks like and some opcodes, right? So in memory, 0x0 and 0x20, or the 0th index and the first index in a memory array, are usually reserved for hashing stuff, right? So they're usually reserved for precompiles. They're usually reserved for doing some very specific stuff. So you'll find the Solidity compiler pretty much never puts variables in the 0th or the first index of memory. And in this 0x40 or the second slot or whatever you want to call it, it usually puts this 080, which points over to this slot. This 0x40 is known as the free memory pointer. Whatever value in here is the index that has, quote, free memory, right? So what this is saying, if this is your memory setup, 0 is blank, 1 is blank, 2 is 0x80, 3 is blank, 4 is blank. Whenever you want to say, hey, where's there some free memory for me to stick some variables in, you always check this second index or the 0x40th offset of the memory array. This is basically Solidity saying, hey, you can put some stuff over here. This is what's free. This 0x40 in memory in Solidity is special because of the free memory pointer. And that's important too. Only in Solidity, this is important because in other languages, they might not have a free memory pointer. In Huff, we didn't have a free memory pointer. We decided when we were building Huff, hey, we don't need to care about a free memory pointer because we're kind of barely using memory. We never needed to worry about overriding memory or anything like that. So we just didn't use any free memory pointers. Solidity always uses free memory pointers. Now, you can kind of see as I'm flipping back and forth, if at this 0x40 slot, it said 0x60, that would mean that, hey, the free memory starts at this 0x60 instead of the 0x80. Every time we add something to memory, we're going to update this to say, hey, the free memory pointer is now plus 32 bytes, or just point to whatever slot in memory is finally free. We can look at an example of this of, okay, let's say we have a uint256, 2 equals 2. We have a value that we need to store into memory. We need to store this into memory. One of the first things that we're going to do is we're actually going to first load the free memory pointer and basically check at the free memory pointer's location, hey, where's their free memory? If it's 0x80, we know, okay, there's free memory at 0x80. We can put our memory variable 2 in there. And that's exactly what we do in this example. We put OX02 in that location. And then the free memory pointer is then going to update. Now this spot has something in it, so it's no longer free. The free memory pointer is going to say, okay, now the next 32 bytes is where free memory starts, which is at 0x6a, which is the hex of 128 plus 32, whatever that maths out to be. So this is how the free memory pointer works in Solidity. It's always just pointing to where the next available block is. This is actually very different from how Viper works, and we'll see how Viper works in a little bit. To recap, Solidity works with this thing called the free memory pointer. And this free memory pointer is really great because it allows Solidity to always keep track of where in memory they can stick something new. So what they do is they go, hey, this is free. Let's stick something in there. And then let's update this 0x40 to be a new free memory pointer. That's how the free memory pointer works. So whenever you work with Solidity, you are always going to see this being the starting chunk of code. And basically this is just saying, okay, at location 0x40 is 0x80. So you'll see whenever Solidity wants to load something into memory, it's going to first load the free memory pointer. It's going to use that to be the index of the new value that they put in memory. And then they're going to update the free memory pointer. And you'll actually see that in the code as we move along. No matter what, contract creation code, contract runtime code, pretty much will always start with the free memory pointer. Great. Okay, so now we know about the free memory pointer. What comes next? Okay, let's start going opcode by opcode. So what's this chunk do? That's usually a good question when working with opcodes. We can just say, hey, let's go opcode by opcode. What's this chunk do? Well, let's read this, let's annotate this, and let's figure it out. Okay, so call value. Okay, this isn't an opcode we've seen before. Let's go to evm.code, see what this is. What does this do? There's no stack input. It's worth 2 gas. All it does is give a stack output. Value, the value of the current call way. So this call value is checking the message.value and putting that onto the stack. So if you send any value with your call, it'll push it onto the stack here. We don't have a constructor here though. We don't have a payable constructor. How could you put any value into the contract deployment if you don't have a payable constructor? That's weird. Well, okay, so this could be 0, this could be 50, whatever. Okay, then we have a dupe one. We've seen this one before. It means we're going to duplicate it. So message.value, message.value. Okay, then we have an is0. Oh, this is a new one. What does is0 do? Okay, let's go see it. Is0. Stack input is A, and the output is A equals A. 1 if A is 0, 0 if otherwise. Oh, so we have a little Boolean here. So there's an input to the stack and an output to the stack. So it's going to pop message.value off, check if it's 0, and then it's going to return message.value equals 0. And then message.value is still going to be underneath it. So now we have this Boolean of 0 or 1, and we have message.value. Okay, it's still not clear to me what this chunk of code is doing. Let's keep going. So next, all right, push 0x0e. Okay, we know what that does. That just pushes 0x0e. And then we have the rest of the stack stay the same because it's a stack, obviously. Oh, okay. Now we have a jump if. Okay, I need a quick reminder. How does jump if work again? Okay, so the top of the stack input is going to be the counter, and then B is going to be the true false. So 0x0e is going to be the program counter. Ah, okay. And then the next is going to be the true false. Ah, so it's going to jump if message.value does equal 0. And so is there any output to jump if? No, there's no output. So the only thing left on the stack would be message.value. So this, it looks like it's doing a jump. It looks like it's doing a jump if somebody sent some value. So this is saying if someone sent value with this call, jump to the 0x0e program counter / jump test. Oh, okay. So it's saying if the value is 0, we're going to jump someplace. I'm not exactly sure where we're going to jump, but let's keep reading, because I secretly know what's coming next. So if we don't jump, that means message.value is not equal to 0. So we have message.value now, because we just did a push 0. We have a dupe 1, which means we're going to do 0x00, 0x00, message.value. And then, whoa, and then a revert? Well, what's the revert opcode do again? Let's go see, revert. Offset size, so message.value is going to be on the stack and it's going to revert. So we now know what this chunk of code does. The whole thing. We know exactly what this does. So if someone sent value to this call, no, sorry, we don't jump there. Sorry. If somebody sent value to this call, revert. Otherwise, jump to continue execution. So this chunk of code here in our contract creation, we're actually checking to see if somebody sent value with the contract deployment. If somebody did, it'll actually revert. And we can actually see that, right, in our test, in our soak test, in our base test here. If we do a new horse store and we do message.value, we do value of 7 here, it actually doesn't even let us compile because it's saying, hey, you can't put value in with your non-payable constructor. So if you tried to send this transaction, deploy this horse store contract, sending value, it would revert. And our Foundry script doesn't even compile because Foundry's going, hey, that's going to revert always. Don't do that. That's dumb. So cool. And if we wanted to see the jump destination, we could come back here. We could do run with no value. We could jump in here, push, 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 call, 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 jump if. We're at the 0A program counter. What did we say it was going to jump to? Okay, 0xe program counter. Step into, and that's actually the jump test right after the revert. That's kind of the hard part of doing the comments like this. It's a little bit hard to see what the program counter looks like, but the evm.codes playground has it really well. 0e is right here. That's the jump test, and it's actually just right after this revert. So this jump test right here is where it'll jump to. So basically just skips over this revert. So this is the jump test if message.value equals 0. Cool. So now we continue the call. So what was the value before we jumped? Okay, it was message.value. So that's what we're going to start with here too. And oh, we run the pop-up code. So we're just going to go ahead and pop it right off. So we're going to push 0x on. Okay, that makes sense. We're going to dupe it. That's no problem. We're going to push. We know what that is as well. I'm going to do lowercase here just because I want it to match what my opcodes look like. We're going to push 0. We know what that is as well. It's going to look like that. Code copy. Oh, okay. I told you about this opcode, but we haven't actually seen it. Makes sense that we see a code copy because what are we doing? Well, we're copying our code to the blockchain. So what is this code copy? Okay, so it takes 3 stack inputs, destination offset, offset and size, and no input. So we have 1, 2, 3, 4 things on the stack right now. So these 3 are going to get popped off for this code copy. And what do we have? Okay, the top of the stack is going to be the destination offset. So the byte offset in the memory where the result will be copied. So we're actually going to copy this into memory. So byte offset in memory where the result will be copied. So we're going to start at 0. Then what's the next one? Offset byte offset in the code to copy. So we're going to actually start at 0x001b. That's a little weird. Well, what does that mean? Well, this is actually a little bit tricky too, but what this is saying is in all of this code, we're actually not going to copy all of this code onto the blockchain, right? We're not going to copy this stuff at the top, which makes sense. We only want to store the runtime onto the blockchain, right? So this code up here is telling us how to store the contract on chain. And the code later on is going to be how to actually work with the chain. And spoiler alert, this invalid here signals the end of the contract creation section of the binary. So I know from cheating a little bit that this 0x001b is actually pointing to the code down here. This stands for, if we do a little cast to base, decimal is 27. We can actually look at that. And if we do a little counting, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. I might have double counted something. This is the 27th byte offset in the code we need to copy, starting from down here. And then the last bit is the byte size to copy. So OX5A. So we can do a little cast there too. So we're going to copy the next 156 bytes, which should probably just be the rest of the opcodes, right? But we're going to copy this into memory. So this code copy bit is now, we're going to take those three. Our stack is just going to be this, but now our memory is going to be basically like the runtime code, because that's what we just copied into memory with this code copy opcode. Then we're going to do a little push 0. It's going to be 0x00, 0xa5, 0xa5. We're going to return, which is going to return both of these, right? Because return opcode, offset and size, right? So offset, size, and then the invalid opcode doesn't do anything. It just kind of signals to us the end of the contract creation code. So now we know what this does. This basically sticks the runtime code on chain. So we're going to add push 0, and then we're going to return. Remember, the return opcode does what? Return, offset and size of the offset of memory, and then the size in memory. We know that this code copy is 0xa5 long, so we're returning the entire memory, which has all the runtime code, and sticking that on chain as a smart contract. Now, you might be asking a really astute question. The question being, oh, so you're telling me the return opcode actually deploys contracts? It's actually a little bit more nuanced than that. So in EVM.codes, there's actually an opcode called create. And this opcode creates a new contract using the initialization code provided the indicated offset in memory. So you might be going, oh, okay, well then I should probably see the create opcode in this contract creation section. But we don't see that. We just see the return. What's going on here? There's actually another opcode called create2, but same thing. There's no create2 opcode either. We just see the return bit. There's a phenomenal question on Stack Exchange, which asks the exact same question. And the answer basically is there's two ways to create contracts. A contract creating a contract, and a transaction that's created by sending nil in the to field of the transaction. You can read more about the different ways contracts are created in the Ethereum yellow paper, but to save you the trouble, this is essentially the answer. There are a few ways to create a contract. One of them is to be setting nil in the to field of the transaction. If it's a contract, using create or create2. So that's why we actually don't see a create or a create2 opcode in this contract initialization or contract creation code. So that's pretty dang cool. And that's how we deploy a smart contract. These are the opcodes that stick our runtime smart contract on chain. So boom, you now know how contract creation code works. Now, what was mind-blowing to me was the first time I learned all this, I was asking a ton of questions. I said, whoa. Why do we do this free memory pointer thing at all? Wouldn't it be more gas efficient to not do that? And the answer is yes. This would be more gas efficient to do that. Okay, well, what else? Okay, we check for some call data over here. Well, wouldn't it be more gas efficient to not do any of that? Well, yes, it would be. We check for some call value over here, some message.value. would it be more gas efficient then to not do all that? Well, yes. By golly, yes, it would be. So we basically just learned if we added constructor payable, boom, this technically is a more gas efficient smart contract on contract creation because we wouldn't have this check here anymore. And if you want, I challenge you to compile this contract, go check the out, and sure enough, you'll see this section is now missing because adding this constructor payable basically just removes that. And then the rest of this just sticks it on chain. And that's it. You now know, oh my goodness, I can write more optimized code than Solidity. But the thing is, we probably don't want to get rid of this message.value check because this is helpful from a security perspective. What if we fat finger sending $1 million that we'll never get back to this contract? Well, we don't want to do that. So it's good to have these checks in. Yeah, it costs a little bit of gas, but this is like what, 1, 2, 3, 4, 5, 6, 7, 8 opcodes. The 8 opcodes probably isn't going to break the bank. So keep it in there to make you more secure. The free memory pointer on contract creation code, I would argue, okay, yeah, that probably definitely can go. So contract creation code, cha-ching, is done. You've learned a ton so far. So let's keep going. Next. Now we're into the runtime code. All right, runtime code of our smart contract. And as we kind of learned, Solidity is very helpful where it gives us this little invalid opcode to show the difference between sections. But wait, why are there so many invalid codes at the bottom? What the heck is that? Well, we'll come back to that. You'll understand why. But now we're in the runtime code, and this is going to be the entry point of all calls. So in the same way, when we built our huff, we created this main function, right? Where's our main function? Created this main function as our entry point. In Solidity, the entry point is going to just be whatever opcodes are deployed on chain. So for us, since we copied all of this stuff onto chain and not this stuff, this is going to be our entry point, and this is going to be our runtime code. So our code copy, remember, it started from this section, which is going to be our runtime code. Boom, this is now our entry point for all calls. Make sense? Okay, cool. Well, now that you know a little bit more about how Solidity works, this is going to look super familiar. And you can almost just see this and immediately go, okay, this is the free memory pointer. This is setting up the memory pointer so we can work with memory in a little bit. Great. Next, free memory pointer is now set up. Let's go ahead. Let's go opcode by opcode and figure out what the heck these are doing. So we have some call value here. Okay, we know what this does. This gets the message.value. We learned that before. We're going to do a little dupe 1. Okay, we know what that does. Very nice. Is 0. Okay, I know what that does. We're going to say, okay, message.value equals 0. And this is going to be similar to what we did in the contract creation code. But, oh, okay, I recognize this. It's doing the same thing, checking for message.value, but in the contract runtime code. Okay. So now we're going to push 0x0e, message.value equals 0, message.value onto the stack. And now we're going to jump if. So what does jump if take again? Jump if, counter, and B. So what does it do again? Counter is the byte offset, and B is the program counter. So counter, byte offset, counter is the program counter we're going to jump to, and this is the conditional. So we're saying, okay, if message.value is 0, go to 0x0e. Okay, great. We know how to do that. This means that message.value will be left here. So we would jump to 0x0e in the program counter, which is going to be a little bit farther down now because we're in the runtime code here. If message.value equals 0, we're going to jump. And if message.value is not equal is something, looks like we're going to continue. And this looks pretty familiar to us. So let's go ahead. We're going to push 0 onto the stack. It's going to look like that. We're going to dupe 1. And yep, sure enough, we're going to go ahead and revert. So we know what this is doing because we've seen it before. We're basically checking for message.value and if given, reverting. This is a really cool Solidity optimization. So Solidity, basically what Solidity does is it checks all these functions and it goes, okay, are any of these payable? No, that's not payable. No, that's not payable. Okay, I, Solidity, am smart enough to know that no matter what function is called on the smart contract, none of them are payable. And since none of them are payable, whenever anybody sends me a transaction, if they send value, I'm going to revert. So what this is doing is checking the value, checking to see if it's 0. If it is 0, we're going to jump away to someplace else. If it's not 0, we're going to revert. So because I've done this a few times, I know that this is the jump dest of this push one up here. So we're going to say if message.value equals 0, start here. I might even put like a little jump to continue or whatever. So do a little continue. Cool. So I know to jump to continue if message.value equals 0. And that's down here. Okay, nice. We have a jump dest. Cool. So based off the stack, we started with message.value. So that's what we're going to start down here. And okay, all right, we're going to pop it off right away. Thanks, Solidity. Cool. So not sure what this is doing, but I guess we're going to find out pretty soon. Okay, so now we're going to push 0x04 onto the stack. We're going to do a little call data size, which what does call data size do? I don't think we've seen this one before. Okay, call data size, no stack input. Doesn't look like there's a stack input, but there is a stack output, which is going to be the size, the byte size of the call data. Oh, interesting. So we're going to say this is the call data size 0x04. So if somebody sends some call data that's like 0x something crazy like that, the call data size is going to be really big. But maybe somebody sends some call data that looks like this. This is 1 byte, right? So they would say 0x01, right? It's 1 byte big or 8 bits big. What does it do? Byte size of the call data. Okay, so it would be 1 byte long. So call data size 0x04. Okay, so we're getting the size of the call data. Interesting. What are we doing? Less than LT? What? What is the LT opcode? What is that? I got too many opcodes open. I need to close some of these. T. What is that? LT opcode. Okay, LT, which is shorthand for a less than comparison. It has stack inputs A and B and returns A is smaller than B. So it returns a Boolean again, right? If A is smaller than B, it returns a 1. Otherwise, it returns 0. So true, false, similar to that is 0. So is the call data size smaller than 0x04? So call data size is smaller than 0x04. Now we're going to do a little push 30, call data size 0x04. Uh-oh, and we have another jump if. Whoa, so what is this? So jump if, I always forget jump if. Jump if takes 2, takes the counter, and then the conditional. So the counter and then the conditional. So this is going to be left to blank. So we're going to jump to the program counter or the byte offset at 0x if this is true. Oh, so if the call data is too small, we're going to jump. Oh, okay. So what this is doing is this is checking to see if there is enough call data for a function selector. Because how big is a function selector? So Solidity, once again, is pretty smart here. It looks at this code base and it goes, okay, there's no fallback function. So if anybody sends me data and the data doesn't have a function selector, it doesn't have 4 bytes, it's wrong, right? Because all I can do is these 2 functions, and these 2 functions need a function selector. So Solidity is basically saying, okay, if there's no function selector, if the call data is not even big enough to have a function selector, I'm going to jump. And again, from cheating a little bit, I know where this 0x30 is. It's kind of far down here. I believe it's this one, and we could double check to make sure, but I don't really want to. Call data jump. If call data size less than 0x40, go to call data jump. So that's going to be down here. I think that's this one, call data jump. And this starts off with nothing. And of course, this is pretty obvious what it's going to do. It's going to revert, right? 0, dupe 1, 0, 0, and then revert. So this is a revert jump dest. Oftentimes, Solidity is pretty smart. It goes, hey, there's a couple scenarios where we revert without giving any details about the revert. We're going to leave it as kind of a general revert jump destination. Boom, jump, push 0, duplicate the 0, and then revert with nothing left on the stack. If call data is too small, it's going to jump down here, revert, and the transaction is reverted, and that's it. Cool. So now we know what this is doing. So just in this runtime code, we've already learned a ton. We set up a free memory pointer. We check for message.value. Then we check to see if there's even enough call data for a function selector. We didn't code any of that in Solidity. We didn't code any of that in our Huff. Solidity has all this happening under the hood. It's doing this for us. Good person Solidity looking out for us, making sure we don't shoot ourselves in the foot. Thanks, Solidity. But all right, anyways, let's keep going. So we have this next section of code. Who knows where it stops? Let's find out. Okay, so first we're gonna do a little push 0. We love the push 0 opcode. Okay, call data load. We love the call data load. What does this one do again? It's going to take the byte offset in the call data from the stack, and it's going to put back onto the stack the 32 byte value starting from the given offset of the call data. So we're going to take this off the stack, and we're going to say 32 bytes of call data is now on the stack, right? Now we're going to say 0x E0, 32 bytes of call data on the stack. Oh, a right shift. Oh, I remember this. Okay. What does this one do again? I think we might be at the function dispatcher of Solidity. Okay, so we're going to shift the value by whatever's on the top of the stack. Okay, so we're going to shift the 32 bytes call data by 0x E0. So let's do that again. Cast to base 0x E0 decimal 224. Whoa, we've seen this before. So we're going to say, yeah, this is the call data from the 0th bytes to the 4th bytes. We've now shifted, and this is probably going to be the function selector. So by doing this, we got the call data. So we're probably doing the function dispatching in Solidity. Remember, we didn't have to write any of that in Solidity here because Solidity does this all under the hood. However, in Huff, we actually coded our own function dispatcher. So now we're actually going to compare our function dispatcher that we wrote to what the Solidity compiler came up with. That's pretty cool. We're going to compare and see whose is better, huh? So call data load, push 0, the right shift, and now we're going to dupe 1. And so instead of call data 04, I'm just going to say func selector, comma func selector, because we're pretty sure this is going to be the function selector. And whoa, I remember this too. What is this? Oh, this is the update number of horses function selector. And now we're pushing that onto the stack in Solidity. Wow. Boom. Function selector, function selector. This looks super familiar to us now that we've written in Huff. Yep, the equals opcode is going to say, okay, does the func selector equal this bit here? We're now going to push on 34. You probably know where this is going. And then we're going to jump if. Almost exactly the same as our Huff, right? So if the function selector equals the function selector for update number of horses, then we're going to jump to program counter 0x34. If function selector equals update number of horses function selector, then call data jump. I'm going to say set number of horses. And we'll get to that jump in a little bit. So this is almost identical to what we wrote in Huff, right? 0, call data load, 0e right shift, dupe 1, push the function selector equals, then a jump destination, and then a jump if. So if this is us function dispatching for the update number of horses, what's next? Well, what's probably next is going to be the read number of horses. Okay, well, let's find out. So, okay, we do dupe 1. Okay, now we have 2 function selectors in the stack. We're going to do this push here. So this, well, if we go back to our Huff, sure enough, that's the function selector for read number of horses. Oh, look at that though, right? We removed the dupe 1 in our function dispatcher and Solidity still has it. So our function dispatcher is actually a little bit more gas efficient than Solidity's. Nice job, us. Okay, and then we're going to do this equals. So we're going to check if the function selector sent in the call data equals the function selector for read number of horses. And then we're going to push 45. You know where this is going. And then we have a jump if here. So we're basically saying if the func selector equals read number of horses, then we're going to jump to get number of horses. And that's the function dispatcher that Solidity built. Now, what's cool is since this is the end of our function dispatcher. If somebody didn't send us a function selector, we probably should revert. Well, guess what? If the code just keeps going as is, these are the next 4 opcodes it's going to do. So it's going to revert right here if no function selector was set, if no function selector was included. So it'll call jump dest, which, yeah, okay, costs 2 gas, like maybe that's a waste of gas, whatever, but then it'll revert, and that's what we want. Because if it doesn't revert, it would go ahead and actually start executing some code that we might not want it to do. So having this jump destination here after the function dispatching is great because we revert. So this lump of code here, we know what this does. This is function dispatching for read number of horses. And this is going to be dispatching for set number of horses. Ta-da. We're already through more than half the opcodes, and you're doing phenomenally. Let's keep going. But let's go ahead and continue. So now we're at this other jump dest position. This is going to be after we do the function dispatch. This is going to be one of the jump dests, probably one of the jump destinations of one of our function selectors. And we could go back and figure out which one it is, but let's just go ahead and see what this does, and we'll probably figure out what this jump dest is from what it's doing. So this is a jump dest. So this means that we came from this jump if bit or this jump if. So that means we have the function selector. So we're going to push on 43 for some reason. We're going to push on 3F for some reason. And we're going to do this call data size, which we've done before, but let's just double check. Sure enough, this just returns the byte size of the call data. Okay, cool. So again, you know, if we have like function selector and then like a whole bunch of stuff in here, or if we just have the function selector and then nothing, it'll tell us, right? So now we're going to push this. It's a little confusing why we're doing all these pushes onto our stack, but I guess we'll figure out soon. And then we're just going to do a straight up raw jump call. Okay, interesting. So we just pushed a whole bunch of stuff on the stack, and then we're going to do a raw jump. So we haven't done a raw jump before, but all this does is it jumps to the program counter that was most recently on the stack. So we're going to do the jump to the 59 program counter here. And this is going to be way down here. So, okay, I'm going to cheat. So this is the update horse count, or update horse number jump dest 1. So again, I cheated a little bit. I've already looked at all the program counters. This is the first jump destination for update horse number. And we're doing all this stuff here, and then we're jumping. And we're actually jumping way down low here to this one. So this is going to be jump or update horse number jump dest 2. So we start here and then we jump down here. And again, I kind of cheated. I've already looked at the program counters. These are a little bit hard to figure out, but like I said, you could pop them into something like EVM codes and see the program counters on the left over here. So now update jump number 2, where we came from up here, and this is our current stack. So same thing, we jump down here and we have this kind of ridiculous stack. So we're not sure what all these pushes are for, but it looks like we're doing more pushes. No worries. So we're pushing 0, we're pushing 0x20, we're going to dupe 3. Now we haven't done this one yet, but this one's pretty obvious. We're going to duplicate the 3rd item on the stack. So we're going to ignore the top, the second one, and then we're going to take the 3rd one and just duplicate it and put it on the top of the stack here. So 0, 1, 2. So we're going to do like this, take this on the stack, and then put the rest of the stack is going to stay the same. Dupe 5, going to do the same thing. 1, 2, 3, 4, 5. So we're going to do the call data size like this, call data size, and then the rest of the stack. And the stack is starting to get kind of big. I'm actually going to take toggle word wrap off here. Sub, this is one we haven't done yet. So let's grab the sub opcode here. And this is going to be a subtraction operation. So we're going to take the top of the stack and subtract it by the second value in the stack. So we're gonna do call data size minus 0x04. So I'm just gonna take this whole thing, put a little boop, subtraction there instead. So if our call data size was 4 bytes, this would be 0. If our call data is bigger than 4 bytes, this is gonna be, you know, some other number, whatever it's bigger by. We have another new one, SLT. This is a signed less than comparison. So basically we're going to do we're going to compare if A is less than B. And if A is less than B, we're going to do a 1 and then 0 otherwise. So we're going to do the same bit here. We're going to say, we're literally just going to copy this whole thing, paste it in here, get rid of the comma. So this is now call data size minus 0x04 is, excuse me, less than 0x20. So this is actually pretty interesting here, right? We're basically saying, is there more call data than just the function selector, right? Because 0x20 is 32. So if the call data size is 4 bytes, then this is going to be 0 and this is going to be true, right? If the call data size though is a function selector plus data, like a bytes 32, which is what a number would be, then this would be false. So basically we're saying, hey, like, is there more call data than just the function selector right here? And we're doing a little is 0. So remember how is 0 works. Is 0 takes A and then A equals 0. So we're going to basically just say this equals true. And then everything else, I know this is kind of a big one. But basically we're just saying, hey, is there more call data than just the function selector? And I might even just switch this to more call data than selector. More call data than select. Well, it's technically more call data than 32 bytes, but I'm just gonna say more call data than selector. Now we're gonna do a little push 68. And we have all these pushes that we've been pushing on the stack that we're not sure what they do, but I guess we'll find out. And then we have another jump if. Oh my goodness, there's so many jump ifs. So this is where working with Solidity can be a little bit confusing because there's so many jump ifs and there's so many pushes and we're like not really sure why it's doing all these pushes and these jumps and etc. But as we know, jump if, we're going to say OX68. We're going to jump if there's more call data than the selector. So right, instead of this is just going to be what? Jump if returns nothing on the stack. So we're just going to delete these. So basically we're going to say we are going to jump dest3 if there is more call data function selector plus 0x20. So function selector plus some other stuff. So it looks like what this is doing, what this lump of code is doing is check to see if there is a value to update the horse number 2, right? Because a number is going to be 32 bytes. Number is going to be 0x20. 0x20 is the hex form of 32. So we're saying, okay, the total call data should be 4 bytes for the function selector and 32 bytes for a horse number. And that's what this lump of code is checking for. And if it is, we're going to jump to this next section, which again, I kind of cheated and I know where it is. Otherwise, if it doesn't jump, look what we have here. Revert if there isn't enough call data, right? So we have this push 0, which, okay, let me grab this. It's going to be this big thing here now. Boop, boop, boop. We're going to duplicate 1 for some reason. Looks like Solidity is doing, well, doesn't know that it already has these in here, and then it's going to go ahead revert. And this will be what's left on the stack, but it doesn't matter because the call is over because it reverted, right? So this code, we're going to jump to update horse number jump destination 3, but if there's not enough call data, it's going to revert. So this is actually one of the other cool things that Solidity does for us under the hood. Not only does it check for message.value up here at the top here, but it also checks for if there's even enough call data for us to continue execution. So let's go to jump destination number 3. And again, I kind of cheated. I already know where this one is. So I'm going to go directly to it. It's down here. It's actually right after this revert. So this is jump dest number 3. So what's this bit doing? Well, if we came from here, this is what we're going to be working with. So I'm going to copy this, paste this in here, and let's keep going. Okay. So next we have a pop. So it looks like we're getting rid of that 0 on the stack. Then we have a call data load again. So now what does call data load do again? It's going to I and then data I. So we're going to put the call data in here. And as I was filming, I forgot to take off this 0x04. So I'm going to take it off in a minute when I realize my mistake. And since the offset is going to be 4, it's going to ignore the function selector, just grab the data. The data we're going to get sent is like 0x01, 02, 03, 04, which is going to be the function selector, or wait, 1, 2, 3, 4. Yep. And then the rest of the data is going to be the actual data associated with this call. Remember, the call data looks like something like this. So we're starting from the 4th byte. We're starting from here, and we're loading this 32 bytes into memory. So call data of number to update. Cool. So it looks like we're finally pulling in the number to update into our stack. Now we're doing swap 2. Okay, this is another one we haven't looked at yet. Swap 2, A, B, and C. We're basically going to do C, B, A. So we're going to swap A with C. So we have call data, 04 call data size. So we're just going to do call data size, comma 0x4, call data number to update, comma the rest of this stuff. But we're going to do a swap 1 where what we're going to do is we're going to swap the first and second value. So now it's going to be 0x04, call data size, and then the rest of the stack. And we're going to pop. So it looks like for whatever reason, we just needed to pop off this 0x04. So why do we even put this on here? So if we scroll up, we have a jump test here. It looks like we pushed it on up here. Not sure why. Maybe it'll come in handy down here. I don't know. But we're popping back off that 0x04. So this is now what the stack looks like. And we're doing another jump. So essentially what this lump of code did is just grab the call data for updating the horse number and then delete some stuff in the stack. So it's kind of doing both of those. But the important thing is it's grabbing the call data for updating the horse number. And then we're going to jump to jump dest 4, which again, I've kind of cheated and I know is down here. So stay with me. This is right underneath the jump dest 1. So this is jump dest 4. And this is where we can finally run an store to save our value to storage. And we can only now do this now that we've done the function dispatch. We've checked for message.value. And we've checked the call data is long enough. And finally, we've received the number to use from the call data. So now that we're here, okay, let's go back to the bottom of jump test 3. And I know we're kind of all over the place now, but we're just going to copy this. And this is going to be our starting state here. So now we're going to do a push 0. So we're going to do the same thing, just push 0. Now we're finally going to do our store, which if we go here, store takes a key and a value. We're going to push to the 0th slot. What are we going to push? We're going to push the call data size. What's wrong? I just realized my mistake. I forgot. So when we call data load, we're supposed to take off the 0x04 as well as part of that opcode. So whoops, made a bit of an oopsie there. And so the call data size is what's actually getting popped off here. Cool. So now call data is at the top of the stack, or call data is at the top of the stack. Got it. So let's go back to jump dest 4. Great. And so it's not the call data size, it's the call data that's at the top. Okay, cool. Now when we do the store, it's these two. So at storage slot 0, we're going to store the number that we want to update. This is perfect. This is exactly what we want, right? And so store takes a key value, nothing else on the stack. So now our stack just looks like this. I don't know why we've pushed these, but maybe we'll find out in a second. And we have another jump. So we're going to be jumping to this spot here, and their stack is going to now look like this. And because we did that, our swaps are going to be a little bit different. This is now going to be up here. That's going to be here. That's going to be here instead of here. And so then when we jump, this is what's left. You can see as I'm kind of fumbling my way through this, I've even made some mistakes. So not this. And so we're going to jump to the, sorry. And so I need to delete all these 0x3fs that I accidentally kept in here. You can see why this gets kind of difficult for you to keep in your head. But finally, we're going to jump to the 0x3 program counter. And all that's left in here is the function selector. So all these weird pushes that we did up here have basically panned out, right? This was a program counter to jump. This was a way to check for call data size. And then I forget what the 59 was for. Oh, and this was a program counter for this to jump to, right? So all these pushes end up being program counters for us to jump to. So we can say that. Set up jumping program counters in the stack. That's pretty clever of Solidity to have done all that. But so then we're finally going to jump to jump dest 5, which there's only one stop code here. So it's actually right here. This is going to be jump dest 5. And obviously we have a jump dest with our function selector, and then we end execution. So this is great. So we just actually went through the entire stack, the entire list of opcodes for update horse number. And there was a lot of stuff. So let's quickly do a recap of update horse number, all the different opcodes and all the different chunks of code that it set up for us. So once we do our function dispatch, right, way up at the top for set number of horses or update number of horses, it'll jump down to this first chunk of code here. And this first chunk of code is setting up all these different program counters and this call data size check. So this is going to be a program counter. This is going to be a program counter. This is going to be what's used to check the call data is big enough, and then a program counter. Then we go to jump dest 2, which is way down here. And this is where we actually do that check. We check to say, hey, is there enough data in the call data? Is there actually even a number here? Can we even, is there anything to S store? Is there enough data for us to S store something? Then we go to jump dest 3, which basically just grabs the call data for updating the horse number, deletes some stuff on the stack. And now we go to jump dest 4 with that number that we got from the call data. We store it on chain, we store it into storage, and then we jump to jump destination 5 where we stop and we're done. So great. We've just gone through all of the opcodes that are needed to update the number. Now you noticed in our huff, we did a lot less, right? This is all we did. But we did a lot less because A, we did way fewer jumps. We just had everything in one block of code here. So if Solidity tries to get clever with its optimization. Number 2, we didn't do any checks for data size. We also didn't do any checks for message.value. So our huff code was a lot simpler because it did a lot less, had a lot fewer jumps as well. But if we wanted to super optimize our Solidity, super optimize our binary, maybe we just chop off a whole bunch of those checks and we just do it like this. However, I will say checks are really good. We like checks. Checks help us secure ourselves from shooting ourselves in the foot. But now we know exactly what's going on in the hood, under the hood for that function. Let's keep going because there's a whole bunch more that we haven't done yet. So now let's go back to the function dispatcher and let's look for the read number of horses. So that's here, read number of horses. So what's kind of nice is right underneath this final jump dest stop is another jump dest, and this is going to be read number of horses, jump dest 1. And this is going to be the only jump dest for read number of horses, but there's going to be a lot. So we're actually going to go all of this is to return the read number of horses, which looks a little bit different than what we did in our huff, right? This was all of our opcodes. We did a push here, sload, a push, mstore, push, return. So we've got a couple more things in here. We've got a swap, we've got a dupe, we've got an add. What the heck? We're doing so much more in here just to read the number of horses. Well, let's find out what's going on. So what's our starting state from the function dispatch? Well, it's just the function selector. Great. So let's do jump dest, function selector like this. Okay. And now we're going to push 0 for some reason. And then we're going to do a little sload. Okay, cool. So how does sload work again? So this is going to read from storage. You take a key and you return it with the value. So we're going to say at storage slot 0, is going to be the num horses is now on the stack. Cool. So that seems simple enough. Now we're going to do a push 40. Okay. Interesting. Why are we doing a push 40? We didn't do a push 40 in our huff, did we? No, we never did a push 40. Why are we doing a push? Well, I guess let's find out. Now we're doing an M load. Why are we doing an M load? Okay, so the offset. So this is going to read from memory. Okay, in bytes. Okay, so M load, it's going to read. Oh, and it's going to return the value. So this is finally where that free memory pointer is going to come into play. So way at the beginning of this call, that was the first thing we set up. We said, okay, at location, 0x40 is going to be 0x80, right? This is our memory way at the beginning of this. So now that we have this all set up, back down here, we're saying grab load whatever's in 0x40, and that's still 0x80. So remember, this is going to be our free memory pointer that we're now loading into memory. What we need to do in our solidity here is solidity needs to ask, hey, I want to store this variable in memory so I can return it, right? Because when we read number of horses, we need to store it in memory. Where is the free memory? I would like to store this value into memory. So now in our memory, we're saying, okay, at 0x80, there's free memory. And then here's what's on our stack. So now we're going to do a swap 1. We're going to swap these two around. We're going to do a dupe 2. So we're going to dupe that 0x80, comma 0x80. And now we're going to do an M store, right? So how does M store work? M store offset value. So so we're going to duplicate the 2, put it at the front of this, because dupe 2 returns BAB. Yep, AB to BAB. So dupe 2 is now at the top. So now we're going to do an M store, and at location 080, which is the free chunk of memory, we're going to stick the number of horses. So now what does M store? Turn nothing. So this is just going to be, these two are left on the stack. And now in memory, we're going to say at 0x80 is now going to be the num horses. So now 0x80 has stuff in it, right? Remember, what we just did was we just put the number of horses in this spot in memory. Storing the number of horses at 0x80 means now we need to update our free memory pointer to point to the next free section of memory. So we're going to do that. We're going to see 0x20 function selector, and we're going to add, so 0x20 plus 0x80. You can even do like a little cast to base 0x20, 0x80, 32 plus 128 is 160. So 160 going to be 0xa, yep, 0xa0. So now it's 0a0. The function selector, we're going to push 0x40, and now we're going to do M load, which is going to be the offset. So we're going to load what's at, oh, but I guess you'll notice it's solidity is smart enough here to know that it's about to finish, so it doesn't end up calling an M store ever again. So why are we loading from memory, right? So 0x40 is still going to be 0x80, right? M load, just the offset, 0xa, and then the func selector. Then we're going to dupe 1 for, oops, now we're going to duplicate 1 for some reason. So this gets duplicated. We're going to swap 2. So this now goes to the top. We're going to subtract the 2. So we're going to say this minus 0x80, like that. We're going to swap 1 again. So now it's going to be 0x80, like that. And then we're going to return. Okay, so now I see why we're doing this all. So we actually don't end up updating our free memory pointer. Solidity is actually smart enough to know, hey, the call's about to end. I'm never using memory again. I don't even need to do that. But what we do need to do is return from memory those number of horses. So we kind of do a whole bunch of stuff here because at memory spot 0x80, we have the number of horses, and return, how does return work again? It takes the offset and the size. So we're saying at location 0x80 in memory, which again is the number of horses, return a value which is equal to this minus this. So this is what again? Dec 160 minus 128 is what? 32. So basically we're saying right here, return a value of size 32 bytes that's located at position 0x80 in memory, which we know is the number of forces. And then all we have left is the function selector. Good job, Solidity. Okay, and return ends the call stack. So is there any opcodes that we don't have annotated in here? Oh yes, there is a whole bunch of stuff, but I'll get to that in a minute. Is there anything above that that we don't have annotated? No, we have everything annotated. We've gone through all of the contract creation code and all of the runtime code. This is insane. We just learned all of the opcodes Solidity takes for us to return a value from storage. Great job with this. And so you noticed it was a little bit more gas inefficient because in Huff, we didn't deal with a memory pointer at all. We said, hey, anytime we deal with memory, it's pretty much going to be free because this contract doesn't do a whole lot. Solidity doesn't know that. Solidity goes, oof, we always got to check the free memory pointer. Can I stick some stuff in memory? Luckily, to the Solidity developers' credit, they also coded in, hey, anticipate if the call is going to be done, because then you don't need to update the free memory pointer. That would be a waste of gas. So well done to the Solidity devs on that point. Cool. So we're all done with the runtime code. We're all done with the contract creation code. We just have this giant chunk of what the heck at the bottom here. So this is part 3, and this is the metadata of the code. So as you saw in all of our runtime code, never were we able to jump down here. So this is just inaccessible code that can never be reached by any transaction interacting with the smart contract, because all of this doesn't have a valid jump dest and nothing ever jumps down here. So these are some chunks of metadata that Solidity puts in to make it easier to identify what version, what optimization, how this was compiled, etc. And it's this metadata that often tools like Etherscan scan to actually do verification, to actually make sure a contract was compiled the right way, etc. It's not super important for what you're going to be working with, but if you want to learn more about metadata and how it's compiled and how it's built, feel free to jump into the Solidity compiler and check it out. Whew. Oh my goodness. But with this, you have just deconstructed a smart contract yourself. You have just gone opcode by opcode in a Solidity code base and figured out what it does. All of this. And you even know when you see FEs, you know what that stands for. So you know that this was the contract creation code. This was the runtime code. And this is the metadata. We went through the contract creation code, went through all the runtime code. We didn't really go through the metadata, but you know what it is. All this binary you just read and you understood. Now, you, just by doing this, can understand what this contract does, even if you've never seen the Solidity before. That's incredibly powerful. Now, before we get all done with going through opcode by opcode and EVM by EVM, I want to show you one more really cool thing. So we as humans can understand what opcodes do, right? And if you wanted to, you could probably even use your knowledge of opcodes now to reassemble or decompile this. Take these opcodes and actually turn it back into Solidity, right? You see this and you go, oh, okay, that's a free memory pointer. Okay, this is like a check for message.value. Okay, this is setting up some jumps, whatever. Here's our entry point. Okay, cool. You could reassemble this into Solidity. Well, guess what? There's also decompilers out there which try to help you decompile smart contracts. In the GitHub repo associated with this lesson, we can scroll down to some different decompilers that we can check out to try to decompile code. Yes, crazy. We can actually try to decompile code. Yes, crazy. There are tools that actually do exactly that or try to do exactly that. So we're on this DDOB tool here. And if we go to decompiler, we can either add a network address and it'll try to decompile, or we can add some hex bytecode. Well, for us, we can do that. Let's grab our runtime code and let's see if the DDOB decompiler is good enough to decompile this back into Solidity. right? So the solidity for this is pretty simple, right? This is the entire solidity. So we gave it the runtime code. Let's see if it can decompile it, and it'll take a few minutes. Let's see if we can decompile it back into solidity. All right, let's see how it did. So it actually looks like it didn't do too bad here. So we have, okay, function selector, it's public payable, reverts. So, okay, that's pretty good. It's not exactly the solidity we were looking for, but it's saying, hey, there's no fallback function. So cool. Okay, that's pretty good. Now it has function with this function selector, public payable. I think that's wrong. This is good. Require message.data.length -4 is greater than 32. Probably could have gotten rid of that as well. It recognized this was a uint 256. I mean, it could have been a bytes 32 either, but okay, cool. So it looks like this was indeed our set number of horses, right? So it's saying storage position 0 is set to the var argument. That's great. So a little weird, not quite right, but yeah, it essentially got it. And this, it also got, right? This is the function selector of read the number and return storage variable 0. Great. And then finally we have this, where I'm not exactly sure what it's doing, but I think this is it trying to the function dispatcher, which it got a little confused about. So actually it did pretty good, right? I mean, our contract was pretty simple, but it did a pretty good job here. But as you can see, decompiling assembly code is tough. It's not easy. So, but a really cool tool nonetheless, and I expect it to get better and better as AI gets better and better. Heimdall RS is another decompiler that you can use as well, which does some really cool stuff, or disassembly, or however you want to call it. But anyways, okay, we've learned a lot. So let's go over everything we learned in this Sulk breakdown one more time, and then we'll never walk opcode by opcode again, unless we have to, unless we want to do some crazy optimization, unless we're auditing a compiler. There's a ton of reasons why we might want to look at opcodes, but for this course, this is going to be it. If you want to get better at these opcodes, if you want to learn them more, definitely check out evm.codes. It's a phenomenal website which shows you all about the different opcodes. And I highly recommend, if you want to go super crazy mode, you get crazy good at Huff, or maybe you build your own smart contracts in opcodes, whatever you want to do. If you do not feel comfortable in these yet, the more you play with them, the more you use them, the better you will be. But in this, we learned, okay, most smart contracts are compiled into 3 sections: contract creation, runtime, and metadata. This is how most compilers set them up. You can, of course, have a compiler which splits them into as many sections or as few sections as you want, but this is how most of them do it. Huff really just does contract creation and then runtime code. In Solidity, pretty much all code starts with setting up a free memory pointer. We didn't really have to update it too much in this code base because we weren't working with memory a whole lot, but we can see where if we had a lot of memory variables, we would need to consistently update the free memory pointer so that we always knew where memory was free. And this is one of the first things Solidity always does, no matter what. We learned that Solidity at the opcode level has a ton of checks. We check for message.value. We check often for call data being long enough, etc. And we learned in the contract creation code, we basically do this code copy opcode and copy paste all of our code on chain. We learned the runtime code is going to be the entry point for every smart contract. It's going to be very similar to the main function of our Huff code, pretty much exactly the same actually. We learned Solidity does a lot of checks and jumps all over the place with all these checks, checking for call data, message.value, etc. Once it's done a whole bunch of these checks, it enters its function dispatching, where it compares function selectors with the first 4 bytes of the call data given to it by the transaction. We learned it has a bunch of jump destinations to revert. We learned it sets up a whole bunch of jumps, often in its own little chunk there. And we learned about some of the different opcodes and working with the free memory pointer, etc. We literally went opcode by opcode, and we basically manually disassembled or understood what each one of these opcodes is doing. So if you followed along so far, amazing job going along with this. Please be sure to tinker with stuff like, oh, what if I change this to =7? How does that change the opcode? Oh, what if I added a another variable here. UN256 AAA equals 1 or 7. UN256 BB equals 99. How will the free memory pointer be updated if we have those? Please, please, please be sure to tinker with this until your curiosity is satisfied. But whew, okay, we've learned a ton here. Just by doing this, you pretty much are now an opcode savant. Like that's kind of it. There's not that much more to think about when it comes to working with EVM, Solidity, and smart contracts. Except the way mapping and arrays work, it's kind of tricky. Yeah. On a very high level, really, you've learned everything you need to know, right? Every other combination of opcodes is something you can figure out. You know, even things that might seem complicated, like fallback functions or precompiles, etc. All those opcodes are something you can figure out. You can go to evm.codes and work with them. The only tricky thing here that we haven't gone over is going to be precompiles. So let me quickly explain precompiles. So precompiles are addresses in the EVM world that do very specific things. So address 0x0 is going to be the EC recover precompile. So precompiles are basically special contracts that are bundled with the EVM at very specific fixed addresses. They're called from the opcodes just like regular contracts with instructions like call. And there's a gas cost mentioned just purely with the cost of the contract. So basically, if you're working with an EVM chain, there's going to be very specific precompiles, which have inputs and outputs, very specific contracts that allow you to do specific things, right? On each fork, there's often a different precompile, a new one, or remove one. So these aren't opcodes per se, but they are things that you want to keep in mind when you're reading opcode by opcode. And if you're going to decompile a smart contract and you see some hard-coded addresses, maybe they're working with a precompile. And if you see a static call to like a weird one address that's in when you're decompiling or when you're reading opcodes, that's probably a precompile that they are calling. In the security course, we talked a little bit about signature replays, and we talked about some of these precompiled contracts like EC recover, SHA-256, etc. So now we're not going to go through this again, like I said, but if you want, I have the Huff breakdown on the GitHub repo associated with this course. But this was cool. We have horsestore.sol, we have horsestore.huff. So we've learned a couple of different ways we can actually do low-level programming in Solidity. We can do pure binary or opcodes. We can do a low-level language like Huff. We can also do this programming language called Yul. And what makes Yul really special is that it's actually built into Solidity, and you can actually do inline Yul or inline assembly right in your Solidity code. Doing so achieves several goals. We can actually write our high-level Solidity, but for specific parts where we need very specific fine-grained access or we need them to be highly performant, we can actually just write them in Solidity. We can actually just write them in assembly. If we scroll down in the Yul documentation, we can see, if we scroll all the way down, a list of the different commands for the EVM dialect. And this is the list of commands that you can use in Yul or assembly. And it's going to look really similar to what we just did with Huff, right? There's a lot of familiar opcodes in here. We have stop, add, sub, mul. Let's keep going. Equals, is zero, and, or, right shift, left shift, add mod, mul mod, cac256. All of these different opcodes we can use in Yul. And we can do this, like I said, to make more gas efficient smart contracts or just have more fine grained control over our smart contracts. So let's actually rewrite our horsestore.sol into horsestore.yul.sol. So what we can do, we're going to create a new file, horsestore.yul.sol, and we're just going to paste our horsestore code in here. And we're just going to make this pretty minimal, but we're just going to replace the code inside of update horse number and read number of horses with some assembly or some Yul. So when working with Yul in your Solidity, you just put assembly and these little brackets and boom, now we have access to Yul. And simply enough, if we want to do this line in assembly, all this is doing is what? It's basically just an S store, right? We're storing new number of horses into the slot of number of horses. So we can actually just do that right in assembly by saying store number of horses dot slot, comma new number of horses. So this is some cool syntax you can do in Yul. You can do this little dot slot, which will get you slot number 0. Now down here, for reading number of horses, we can do the same thing, but instead we're going to do what? We're going to do an S load. So we can say let, this is how you create a variable in assembly. We'll say num set. So this is how you set a variable in assembly. So num is going to be set to S load number of horses dot slot. So once again, we're calling the S load opcode, and we can go back to EVM.codes to once again see how that works. S load takes a key, returns a value, boom, just like that. And then we're going to do mstore 0 num. So we're going to store. So same thing. We're going to do the mstore opcode, offset value, offset of 0, value of num, and then we're going to return 0, 0x20. Return 0, 0x20. So as you can see, Yul is a little bit different than working with Huff or working directly on the stack. When I called mstore in Huff, I'm expecting these to already be on the stack. In Yul, you almost add them as parameters to the opcode. So mstore says, okay, I need the offset to be at the top of the stack, and right underneath that is the value. In Yul, you just do it like this. So what Yul does is, okay, I'm going to push the number onto the stack first, then I'm going to push 0, and then we're going to do mstore. So it almost abstracts away the stack a little bit for you and turns these opcodes into functions themselves. And how do we test this? Well, you already know how we test this. If we go into our horse store sulk.t.sol, we copy, paste it, we'll create a new test called horse store Yul t.sol. In here, we're going to do the same thing as what we did in Huff. We're going to say function set up, public override. We're going to override it. And we're going to say horse store equals, and let's import horse store Yul from src/horse store Yul.sol. Do we have horse store Yul? Horse store, yep, horse store Yul. So we'll name it horse store Yul in here. Horse store Yul from horse store Yul. So horse store is going to be new horse store Yul, but this obviously won't. Oh, src horse store Yul.sol horse store Yul.sol. Spelling is hard. Great. And it's going to give us an error here saying, hey, you can't actually do that. So this is where we're going to go ahead, make a new horse store.sol. And we're just going to grab these two functions. We're going to do a pragma. We're just going to do an interface to get this to work. GPL 3.0 only, 0.8.20 interface. horse store. Oh, ChatGPT, thank you. So now in our V1, we're going to import horse store from like that. It's going to be an horse store. We're going to wrap this in wrap this in horse store. We're going to wrap this in horse store address horse store like that. We're going to do the same thing for this. Instead of importing horse store, we're going to import horse store sulk. That's fine. For the Yul, we're finally getting there. horse store, comma, horse store. Nice. Okay, and if we did all that right, we should be able to run forge test. I know that was kind of a really quick way, but I basically just created this horse store interface and then wrapped all of our contracts in horse store. All the tests should run exactly the same. They're all being tested on the same interface. And we do indeed see, even with some fuzzing, our Yul smart contracts performed exactly the same. They passed the exact same tests as our Solidity and our Huff. So congrats. You've just written your first little bit of Solidity, and then you've run a differential test for your Yul against it. Now, we're not going to spend a ton of time going through Yul and teaching you Yul because you've kind of learned it already. Just by knowing opcodes, you've essentially learned how Yul works. Most of Yul works really similar to any other programming language, with the biggest thing being kind of down here in this EVM dialect, where these are kind of the most important pieces, these opcodes that are kind of turned into functions. But since you know Solidity, you can always come back to the docs and write some really clever assembly because you kind of now have access to the different opcodes. Coding in raw Yul, pretty much nobody does. And in my opinion, nobody should do this for production unless you want to just be super sick at assembly or Yul for some reason. I don't recommend coding in Yul. And so for this section, this lesson, I'm going to tell you right now, this is 100% optional for you to do. If it's up to me, I would rather you get super good at Huff, because Yul abstracts a lot of stuff away. Huff abstracts just enough that it's easier to use, but you don't lose the feel of working with assembly. Working with Yul, it almost feels like you're kind of fighting with the EVM, the assembly a little bit. That's just my opinion. So this is going to be 100% optional. Take it as you please. So we're not going to build any crazy assembly things here, but we are going to go one step further, because you can do inline assembly, and that's how most people use Yul, but you can also do standalone Yul. Now, Foundry doesn't love standalone Yul. It doesn't love those being in the SRC. So we're going to make our own file here called Yul. We're going to write the entire horse store contract in Yul, and this will give you some great Yul practice. Are you ready? All right, good. Horse store Yul dot Yul. So let's go ahead. Let's rewrite our horse store into completely 100% Yul. So instead of the keyword contract in Yul, the keyword to create a contract is actually going to be object. So we're going to say object horse store Yul like this. And same as Huff, when this object gets deployed, it's going to deploy whatever's inside of our code. So there's another kind of class in here called code. And to get some syntax highlights for our Yul code, I've actually installed this Solidity plus Yul VS Code extension, which is going to give our syntax here some really nice highlights. So that's what I'm using for syntax highlighting here. So in here, actually really similar to Huff, we have to set up our contract deployment. So unlike our .huff code, our Huff code automatically gives us the contract deployment. Unlike that, we actually have to write our contract deployment in Yul ourselves. So the way that we do that is we say data copy 0, data offset. This all makes sense in a second. Runtime, data size, runtime, and then return 0, data size, runtime, like this. This data copy is a bit of a special Yul word. So you'll see there's not quite a data copy function in the opcodes. We have call data copy and then return data copy. So these three functions, data size, data offset, and data copy, are a bit specific to Yul, and they're used to access other parts of a Yul object. The data copy is equivalent to code copy. So this data copy is basically just code copy. And if we look at code copy, it takes destination offset, offset, and then the size. So we're going to stick this in the 0th slot in memory. We're going to start at the runtime object in our Yul, which we haven't created yet. And we're going to copy it for the iteration of the runtime, and then we're going to return it. So obviously, next we're going to have this object runtime, and we're going to add some stuff into it. But now that we have this, what this data copy is going to, just one more time, this data copy is code copy, and it's going to say, go into our code here, grab the object that starts with runtime, which is down here, and grab it up to the size of the object runtime. So it's basically saying grab the whole runtime and stick it into the 0th slot in memory. And then return works just like the return opcode. So it's saying starting from the 0th slot of memory, return all the data associated with the data size. So this is how we actually stick the runtime code on chain. Now compiling straight Yul is a little bit tricky. You do need access to the sulk binary. So you sulk -- version. There's a whole bunch of different ways to install this. So this will be install sulk or installing the Solidity compiler. You can come to the documentation to install it if you want to come here. The way that I like to have it installed, is actually with this tool, Solc Select, because this will help you switch between different Solidity versions depending on what you're working with. So go ahead and install Solc however you feel, because you'll need it for this. Solc -- version. Great. Once you have Solc installed, the way we compile Yul is we're going to do Solc -- strict assembly. We can do -- optimize, optimize runs, whatever you want to do, 2000, and then /Yul /horsestore.yul.yul. Oops. And actually, excuse me, we need the keyword code in here, which code, boom. Let's do that, recompile, -- bin for binary. And you'll get kind of a ridiculous output that looks like this. So I usually like to pipe it into grep 60 to find the line that just has the binary, and that's what this is. So this will be your Yul compiled into binary. Great. So this is what we're going to use to make sure our Yul actually is compiling correctly. So this is our contract creation code. Now we can create our contract runtime code inside of this. So the first thing we're going to want to do is create a function dispatcher, just like Huff, just like we saw in the bytecode. And to do that, we're going to do this switch selector, like so. So this is going to be a switch statement, which we haven't really seen in Solidity. But basically what it says is, okay, we're going to look for the function selector. Now this selector actually isn't a keyword. It's going to be a function that we're going to define in a little bit that will grab the function selector from the call data. So it's saying we're grabbing the selector from the call data, and we're going to do a switch statement. So we're going to have a couple of cases of, hey, what to do in case of X, what to do in case of Y, et cetera, et cetera. So for the update horse number, UN256, horse number, the selector is going to be 0x. Actually, I'm going to copy paste it. It's going to be this one. So we would say if the function selector is this, so we'd say case this function selector, do some stuff. And we're going to define that in a second. If it's, and I'm going to copy paste this, which is the read number of horses. If it's this, so this case basically means if the selector is this, do something else. And then if neither of those hit, the default is going to be to revert. Let's put a little comment down here, decoding functions. And this is where we're going to put some helper functions. So we're going to say function selector returns S. And so S is going to be some variable. This is how we do returns in Yul. And we're going to say S is going to be set to divide call data load of 0. So we're going to load all the call data by this giant number. And if you don't want to write this out, you can copy paste it from the GitHub associated with this course. Yul is a little bit weird. So which is why we're kind of speeding through this. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 30, 1, 2, 3, 4, 5, 6, 7, 8, 9, 40, 1, 2, 3, 4, 5, 6, 7, 8, 9, 50, 1, 2, 3, 4, 5, 6, 7. And this is how Yul recommends you get the function selectors. So similar to like a named return, we don't actually have to return anything here. It just automatically knows to return it as such. Return the S variable. Seems super odd, I know, but this is what we're doing. So we're going to divide the call data loaded by this, and doing so, we surprisingly get the function selector. Cool. So cool. So we have the selector. What do we do in the case it's update? What do we do in the case it's read? Well, let's start with update horse number first. So if we want to update the horse number first, we're actually going to create a new function called store number. And as input parameters, we're going to actually input decode as uint 0, which is going to be another little helper functions down here. So we're going to create this function decode as input offset. So we're setting the offset just automatically to 0 in there. And we're going to return some value. We're going to let position equals add 4 to the mole of offset 0x20. I know this probably doesn't make any sense here, but basically what this is doing is we're getting the offset, multiplying it by 20 by 32 bytes and adding 4. So we're saying where in what position in the call data. So this should be function, and this will be position in call data that we're going to pull from. So we're going to add 4, which is the function selector, to whatever the offset is. Once we have that position in the call data, we can say if the call data size is less than the position times 32 bytes, then we should just revert, right? And this is equivalent to us doing that size check. So we're saying if the call data size is less than the position plus 20, we should revert. So if there's only one piece of call data, it's just going to be 4 plus 20, 24. So the call data should be at least a function selector plus 32 bytes. But anyways, so once we have all that, we can now do v equals call data load position in the call data. So we're loading the position in the call data. That is hopefully going to be the value that we're updating. So we have the store number as an input. We're grabbing the data from the call data for this store number function that we're going to create now. So now below the default revert, we're going to create that function store number, new number. And since it's already been decoded from our call data, we can actually just do an store 0 new number, new number. If we had a lot of memory variables, maybe we're doing something with a free memory pointer. We're not, so we can skip that. And then finally, if we want to read the number of horses, we're going to return uint read number like this. And so we have these two functions to define. Let's first define function read number, which is going to return a stored number. We're going to say stored number is set to sload 0. So we're just grabbing whatever is at the 0th position. And then we're going to use one of our helper functions at the bottom here. We're going to say function return uint v mstore 0, v, and then return 0, 0x20. So this just helps us return it to us. So how would we test this? Well, what we would do is we would run the compiler, POS not found, position column data. All right, well, let's make sure it actually compiles first. And then we would take this, look for the invalid opcode for the 39. I believe that that's what we're looking for. Yep, that's the code copy. What is it, 3F? Where's the invalid opcode? FE. FE is right here. Then we would take all the code after the contract creation. In one of our tests, what we would do is we would say bytes Yul code equals B like this, something like this. And then we would deploy it directly from bytes. I don't want to do that, so I'm going to skip that. However, if you want to go ahead and deploy the Yul code that you compiled and test it, do an equivalence test, do some differential fuzzing, you're more than welcome to do so. And I highly recommend you to do so because you'll learn a lot and it'll be a ton of fun and you'll feel like a badass. So if you want to go ahead and do your differential testing with the Yul code, pause the video right now and have fun. So that's our whole Yul smart contract here. A little confusing, I know, but let's do a quick rundown of what we did, what we built here. So for our Yul, all Yuls start with some type of object with code inside of it. Most of the time, the code section is going to be your contract deployment. And then you'll have another object, which will be your runtime, and you can call it, whatever you want to call it. Inside of our runtime code, the first thing we do is set up our function dispatcher for our two function selectors. If we want to store a number, then what we're going to do is we're actually going to decode as uint. We're going to basically take the call data and get the value that we want to store into storage from the call data, and then simply do an store to do so. If we want to read the number of horses, we're going to first actually read the number from storage, which is just a minimal load. And then we're going to return it as a uint, which is just doing a little mstore and then a return. And then if neither of those function selectors are hit, we're going to revert. Okay, so now we're feeling really good about ourselves. What have we just done? Well, we've written a minimal contract in Solidity. We then took that Solidity and we said, I'm going to rewrite it in Huff, which is essentially us writing it in opcodes. Then we took the Solidity code and we literally went opcode by opcode, teaching us how Solidity actually gets compiled and how these assembly opcodes work at the lowest level. We even looked at a decompiler real quick, which shows us more about how opcodes work. We learned a little bit about the free memory pointer, and we learned about the stack, the memory, storage, etc., and all these little components of the EVM that are important for us to understand the opcodes. We learned about precompiles. We learned about that, oddly enough, there's some precompiled contracts that are deployed on these different chains for doing different bits of math. We wrote some equivalence tests or differential tests for both the Huff, the Solidity, and our inlined Solidity. We wrote some inline assembly in our Solidity, and some of us even wrote the entire horse store smart contract in Yul, which is kind of crazy. And now we're going to kick it up a notch. So we're going to make a slightly more advanced smart contract. So we're going to make this horse store v2, src horse store v2. And this is what this looks like in Solidity. And I'm actually just going to copy paste it into our code base because we're not going to write the Solidity. So I'm going to make a new folder, horse store v2, new file, horse store.sol, paste it in here, boom. And because we're using some OpenZeppelin smart contracts, we're actually going to go ahead and install those as well. So that's going to be forge install OpenZeppelin / OpenZeppelin contracts. We're going to install a very specific version at v 5.0.1 -- no -commit open contracts. Needed an S in there. And while that's installing, we're going to go to foundry.toml. We're going to add a little at OpenZeppelin / equals lib / OpenZeppelin - contracts / forge build to make sure it builds. Looks like I messed up. Oops, this is going to be a horse store. And once we do that, we're also going to grab this iHorseStore.sol, which is a slightly different implementation. iHorseStore.sol, paste it in here. Let's see if I did everything right. Forge build. Okay, cool. Looks like it did. So I know I did a whole bunch of stuff there, but let me just tell you really quickly what your starting point is. So you're going to have HorseStore.sol all set up for you. And then you're also going to have this iHorseStore.sol. And this is going to be our v2, which is a little bit more intense. So we're importing ERC 721s, and our horse store has a mapping, and it has some constants, and it has a whole bunch of stuff in here. So most importantly, all this contract really does is it allows people to mint horses, feed your horse, which just updates a mapping to be the block.timestamp. And then there's a function called isHappyHorse, where if given a horse ID, it returns true if the horse was fed within the last 24 hours. And the reason I want to do this is because we're going to learn about some more advanced huffing. And most importantly, we're going to learn how at a low level, this mapping stuff works. I know a lot of you already know, but we're going to write the huff to rewrite this smart contract. And we can go one step further. So what I want you to do is copy paste this base test v2.sol, which has most of the tests for you already. So let's create a new folder, call it v2, create a new file, base test v2.t.sol, paste the whole thing in here. Then I want you to copy paste the horse store solidity. So we're going to do horse store v2 test, horse store v2 solidity test.t.sol, horse store solidity v2. And then also copy paste the huff. So pretty much I want you to copy paste everything except the actual huff. So horse store v2 huff test.t.sol, paste it in here. And we're going to create in the v2 folder that we just created .huff, which will be blank. So I know the answer key obviously is in here, right? If we go to horse store v2, the answer key is right here. But this is what I want us to do. If we run our test now, forge test, everything should pass except for the huff tests. Everything should pass except for the huff tests. So let's see. Sure enough, all the huff tests fail. So what we're going to do now, and you can even pause the video and try to do this yourself, is we're going to write the huff code for this horse store v2. And it's a little bit more intense because first off, it's an ERC 721. It's got a mapping, it's got several mappings, and there's a whole lot for us to do. So if you want to pause the video, rewrite this in huff yourself, I highly recommend you to do so. Otherwise, we're going to do this together, and this is going to be how we're going to wrap up the section. We're going to get some more assembly, some more low-level EVM practice by rewriting this smart contract in huff and making sure it passes all of our tests. You can see all the tests in here, and I recommend you going through them if you want to get a good idea of what we're even testing for. So we're going to finish up this section by writing horse store v2.huff, getting it to pass all of our tests, and then we're going to be done with the section. And you, my friend, you will have learned so much about opcodes, low-level EVM, low-level assembly, that I will be more than happy to send you on your way and start analyzing bytecode. You will have the power to go to a smart contract that has not been verified in Etherscan and say, you know what? I could figure out what this is doing. And that's incredibly powerful. So let's buckle up and let's rewrite horse store v2 in huff. All right, so now that we've been through this once before, you already know how to get started. Let's go ahead and get started with our define main, or our macro main. Takes 0 and returns. Now this takes and returns is going to be what it takes off the stack and what it returns on the stack. Kind of just like any of the opcodes, right? Any of our opcodes, they take something off the stack and put something back on the stack. So if we wanted to do that, we could do that here. And in this main function, we're going to do pretty much the exact same thing as we did in our v1. So I'm actually even going to just copy paste like so. Boom. First, we're going to grab the call data and give it a little right shift so we can get the function selectors. And now we're going to do a little bit of function selecting dispatching. So let's go to our horse store v2. Let's get the functions that we need. Okay, we need a mint horse function selector. What else do we need? Okay, we need a feed horse function selector. Okay, cool. What else? Okay, we need an is happy horse function selector. And is there anything else we need? Okay, we have a public variable, horse ID to feed timestamp. So whenever you have a public variable in Solidity, this is actually turned into a getter function. So yeah, we actually need that one as well. So we're going to need a horse store, horse ID to feed timestamp like that. Do we have any other public variables? Oh, horse happy if fed. That's a public variable. So we need a getter function for that. And that looks pretty good. So same thing, we know how to do this. We have the function selector up here. We're going to do dupe1 __ func sig. And this is where we put the mint horse function sig, but we know we could do like cast, blah, 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 get the function sig, but we know we can actually just define a little horse store interface at the top to make this a little bit easier. So we're going to define, what is it? Mint horse, non-payable, returns nothing. Define, was it feed horse? Oh, look at that. Oh, define function, excuse me. Function. ChatGPT has already helped me out. Feed horse, not a horse ID, a uint 256. Non-payable returns nothing. Great. What else? Define function is happy horse, uint 256. View, perfect, returns bool. Define function. What else do we need? Horse ID to fed timestamp. That looks good. Define function, oops, define function, very much, and cool. So now what we can do, we can just grab those function signatures right from our interface here. Feed horse equals feed horse jump if, right? This is going to be the same setup as what we did here. Dup1 func sig equals our jump destination and then jump if, since we made a jump destination down here. Oops. Down here, we would say feed horse, and we're going to create a macro called feed horse that we'll define later, and I'll update all these in a bit. So we're going to do the same thing. Dup1. Oh, ChatGPT has got me. Thanks, ChatGPT. Oh, actually, we should do mint horse first. Dup1 func sig mint horse, mint feed is happy, horse to ID T. This is a great reason for using ChatGPT, by the way. Pretty much just gave me all the answers right there, and those look pretty good. Let's see if it's good enough to do this stuff down here. Okay, it looks like it's a little less smart. So feed horse we got. What else we need? We need mint horse. What else? Is happy horse. That. I'm gonna do this horse happy fed within. I like having my jumps lowercase. Horse happy fed within. Horse happy fed within. And those look pretty good. And boom, look at how much quicker this was for us to write now that we actually know how these work, right? We have our main, we do our function dispatching, and ChatGPT, for me, pretty much did most of the writing for me. So cool. So let's get started writing some of these functions here. And then we'll worry about constructors and variables and all that stuff in a little bit. Let's do the feed horse first, actually. Yeah, let's do the feed horse first. Above here, we're gonna do define macro feed horse takes 0, returns 0, because we're not gonna worry about anything on the stack here. And let's actually look at the code and see what this does. Okay, so we have this mapping horse ID to fed timestamp, and this is probably the most important function we're gonna have to do for our learning, because we're gonna learn about the mappings, timestamps, all this good stuff. So we're gonna need to get a block.timestamp. Is there an opcode for working with timestamps? Let's do timestamp. There sure is. It's just called timestamp. It sticks the timestamp onto the stack. So let's go ahead. We'll just do timestamp, and this should mean that on our stack now is the timestamp. Okay. What's next? They're going to send us some call data. They're going to do 0x. And then they're also going to send us what are they going to send us? Horse ID to fed. So, right, it looks like when you feed the horse, it just updates the last time it's been fed. So, and then it's going to give us a uint 256 in the call data. So we know how to get this. So first we're going to do 0x04, and then we're going to do call data load. So this will give us the horse ID and the timestamp. Why? Because when we call data load, we're saying, give us all the call data after the first 4 bytes, which is going to be the function selector. Boom. So we're just going to get the uint 256 here. Next, well, what do we need to do? Well, we have the timestamp. We have the horse ID. So now we need to do what? We need to store, store the timestamp with the horse ID key. So how do we do this? Well, if we look at the Solidity documentation, and we've definitely learned this before, mappings actually work with a very specific algorithm. The value corresponding to a mapping key K is located at kcac 256 h of k dot p, where dot is a concatenation and h is a function that is applied to the key depending on its type. And then there's a whole bunch of math in here. I've gone over this before in the Foundry full course, so I'm not going to go over it again here. But basically, there's some algorithm that we need to use here. Now, I personally don't want to have to write this algorithm out every single time I use it. And guess what? A lot of people thought the same thing when working with Huff. So there's this tool called HuffMate that we can actually use that actually has a lot of these built in. If we go to SRC, we go to tokens, it has an ERC 721 that we're going to use, but additionally, it has utils, data structures, hashmaps.huff. And this is how hash maps or hashing or that algorithm for mappings look like and are used in Huff. And yeah, this looks pretty terrifying, but these are the opcodes that Solidity uses under the hood when it works with mappings or hash maps. And hash maps are pretty complicated. So what we can do is we can install HuffMate and take use of these contracts in here. So I'm going to copy this, forge install huff language / HuffMate, forge install, oops, --no -commit, like this. And now in our Huff, we can actually import the hash map library by doing a Huff import. So we can say hashtag include //lib /huffmate /src /data structures /hashmap.huff. And now we have access to this hash map thing. So now if we open up the hashmap.huff, this is going to make it a lot easier to work with slots, have those algorithms, and we don't have to really think about the algorithms anymore, which is really nice. But for any variable in storage, even if it's a mapping, it still needs some type of storage slot. Hey, we're going to base this algorithm around a storage slot. So what we're going to do is we're going to make a constant. Define constant horse fed timestamp location equals free storage pointer. So this is going to be the storage slot for the mapping. Obviously, the whole mapping is not going to fit into this. The elements are going to follow that hashing algorithm to find their own storage slots, but the mapping needs kind of like placeholder to do the calculation for. So now that we have that, we can access its value like this. And now our stack is going to be like this. And now that we have the location, the horse ID, and the timestamp, if we go back to our Solidity, we're saying, okay, at mapping horse ID fed to timestamp, and the horse ID fed to timestamp mapping storage slot is going to be this location here, updated at index horse ID, or algorithm horse ID with this timestamp. We can do all of that with a macro called store element from keys in this hashmap.huff. So what this store element from keys does, it's another Huff macro. And unlike all the macros we've done, it actually pops 3 things off the stack and returns nothing, right? So it pops these 3 things off the stack, returns nothing. Don't worry about the memory pointer for now, or at all, really, for the portion of this course. But basically, we're gonna call this function get slot from key, get slot from keys, and this is the code that actually says, okay, based off the slot and the key, I'm going to do some hashing to return the slot that this data should go in. So this is the Huff that's responsible for getting us the correct slot with all the hashing and stuff. Once we get the correct slot, we just call store, right? That's it. So we can actually just call that store element from keys, We're just going to pass 0x00 as the memory pointer. That's the free memory pointer. So it's basically, we're passing in, hey, where's their free memory? For us, we're not going to really care about free memory too much at all. So we're just pretty much always going to pass in 0x0. And then now we're going to have nothing, and it's that easy. So we kind of cheated. We kind of made it a little easier using this hashmap.huff. But if you're like, whoa, what the heck just happened? I highly recommend pausing the video, going through this macro, store element from key, and seeing how this get slot from keys function actually calculates the storage slot of a hash map. Because this is exactly what Solidity is doing on the back end underneath the hood whenever we do a mapping like this. And cool. And that's it. And that's our feed horse macro. Great job. All right, next. Let's do this one, horse ID to fed timestamp. I'm going to change this to get horse fed timestamp. So what this is it's simply the public getter function for getting last fed timestamp based on a horse ID. So that's pretty simple. We've done stuff like this before. Let's go ahead and create this macro. Define macro get horse fed timestamp. It's going to take 0. It's going to return 0. And what is this one going to look like? Well, we're going to need the horse ID from the call data. So we know how to do that. 0x04, call data load. And it looks like Copilot's already helping me out here. Horse ID. This is how we get the horse ID from the call data. That makes sense. Then this is the mapping for the horse fed timestamp. So we're going to have that now in the horse ID. And we're going to need to do, instead of store element from keys, we're going to need to load an element from keys. So this is where we kind of do the reverse of what we did for store. So this used that hashing algorithm to store an element. Now we want to load an element. Let's say if there's a macro for this, load element from keys, there sure is. And this does the exact same thing, get slot from keys, but performs an S load as opposed to an S store. So we can do the exact same thing here. So we're going to do load element from keys, free memory pointer of 0x00. And this does what? Takes 2, returns 1, load an element onto the stack from the 2 keys. So what's going to be left on the stack is going to be the horse fed timestamp. Ta-da. Now that we have that on the stack, we're going to need to pop this into memory. So we're going to do 0x00 and then mstore, which does what? It's going to empty our stack. And now memory is going to have at 0x0, it's going to have the horse fed timestamp. And then we need to return. So we're going to say 0x20, 0x00, return. And you'll see that syntax a lot. This says we're going to take 20 bytes starting from the 0th position in memory and return that. So basically we're going to return the horse fed timestamp and we should be good. All right, what's next? Is happy horse. This one is going to be one of the most complicated ones because if we go to the horse store, there's a whole bunch of conditionals in here. So what we got to do, we're going to need to get the timestamp when the horse was fed. We're going to need to compare it to the current block.timestamp minus this horse happy if fed within. And if it's too small, return false. The horse is not happy. Otherwise, return true. So this one's going to be a little bit more complicated and it's going to be even more fun to make. So let's do this. Define macro is happy horse equals takes 0 off the stack, returns 0 onto the stack. So what's the first thing that we need? Well, we're going to need this horse ID from the call data. We know how to do that. 0x04, call data load. And that looks like what? Boom, boom. Horse ID. Nice. Then what do we need to do? Well, we kind of need to do exactly what we did here, right? We need the horse fed timestamp. So I'm actually going to copy this, paste it here, and ta-da. Now we have the horse fed timestamp. Cool. We could have turned this macro into like takes 2, returns 1, where it takes off the stack and returns from the stack. And then we could have just called this macro. I didn't want to do that. So cool, moving on. So we have the horse timestamp. Great. Now we need the actual timestamp. Okay, we can do that. Timestamp. Ta-da. Now we have both of those on the stack. Now we're going to need to be a little bit clever here. We need to do some comparisons here. And I'm just going to do 2 dupe 2s. And I'm going to tell you to trust me, it'll be good. It'll be good for us. So timestamp, horse fed, timestamp, timestamp, horse fed, timestamp. Yeah, just trust me that the 2 dupe 2s are gonna work out here. So what we want to do is we want to subtract horse fed timestamp from the current timestamp. So this actually isn't exactly what we're doing here, but it's going to return, but it's going to end up returning the same result. So we're going to do sub here, and we're going to say, let's take the current timestamp, subtract it from the previous timestamp, like that. And now that we have this, we're going to need to compare that to this horse happy if fed within constant, which we have not defined yet, but we should. So up at the top, we're going to need to define that. Define constant horse happy if fed within const equals, and this is not going to be a free memory pointer. This is going to be a legitimate true constant. And here we have 1 days. Let's pull up chisel, see what 1 days is. 1 days. This is the hex for 1 days that we're going to copy, and we're going to paste it up here. So cool. So this is basically saying if the horse hasn't been fed within a day, it's not going to be happy. And this is the constant that we can use. So we want this constant on our stack because we're going to have to compare it. So back in our isHappyHorse, let's grab that constant. And it looks like I should move these all up by 1 at least. And now on here, on our stack, we have horse happy if fed within const, the subtraction, and then those 2 other variables. Now what we can do, a comparison. So we can go back to EVM.opcodes and look for a greater than or equals to. So there's greater than, sign greater than. There's no greater than or equal to. So we'll have to do a greater than and then an equal to as well. So in here, we'll say greater than. We want to check if this is greater than this. So we'll do greater than. And if we're checking greater than, we're saying basically horse has been fed within 1 day, a true false, like that. And then what we can do is we can say, okay, well, if this is true, let's go ahead and jump. So we can create a jump destination by doing start return true, jump if. And I'm going to make a little jump destination down here, and we'll do some stuff with that in a bit. So jump destination, jump if, and that means that now we're just going to have a timestamp and horse fed timestamp. But we're not done because we checked if greater than, but this is greater than or equal to. So now we also got to check for equal to. So this is why we did these double dupes at the beginning, because now we can just run the equal opcode to see if they're equal. I'm going to do something a little bit cheeky here and just follow me for a second. When we do this start return true jump if the horse has been fed within 1 day, but not at exactly 1 day, we're going to jump down to here, right? And when we jump down to here, we're going to run this opcode of x01 onto the stack here. Remember, 0x01, anything other than 0 is considered true. 0 is considered false. So since the horse has been fed within 1 day, we want to jump to this return true and return true. We could have also duplicated this. There's a whole bunch of different ways we could do that. Now we want to check if it's equal. And remember, if these are equal, it'll be 1. Otherwise, it'll be 0. So on our stack already, for checking if it's equal, it's already going to be correct, right? Like if they are equal, true, that's good. We want that. If not, it'll be false. So we can actually just create another jump destination down here. Oops. Jump destination down here and just jump to it no matter what. So start return 0x00 m store. So this is how we'll store and into memory, and then 0x20, 0x00 return. So a little bit confusing, but basically if it ended up being true, we're not going to check if stuff is equal. We're just going to jump to start return true. We're going to add 0x01 so that we store true into memory and we return true. Otherwise, we're just going to have this in here. We're going to skip over start return true, and what's going to be in the stack is going to be this. So if they're not equal, this is going to be false, and we'll return false, and that's exactly what we want. And when we run a test for this, you'll see that this works, but feel free to come back, play with it, and try to mess it up. All right, cool. So isHappyHorse is done. Hopefully it works right. We'll see when we run the tests. FeedHorse is done. By the way, yes, we know feeding unminted horse is currently allowed. I didn't want to have to give you the extra work of blocking that, but we have not minted a horse. We haven't done the constructor. And did we do this one? And we haven't done that one as well. So let's do that one. This one's super easy to do. We just need to make a public macro for that. We just need to make a macro to return that. So define macro horse happy if fed within equals takes 0, returns 0. This one's really easy. We just do horse happy if fed within const 0x00 m store 0x20 0x00 return. So we're going to get this value right here and then just straight up return that. Cool. And that's all we have to do for that one. All right, now we're going to get to the hard stuff here. The minting and the constructor. Let's start with the minting here. So, although you'll find the minting is actually not that bad once we get some of the ERC20 functions in here. So we're going to create a new define macro mint horse. It's going to take 0. It's going to return 0 as well. And how does this work? Well, okay, we're going to mint the user a horse with an ERC20 token ID equivalent to whatever the current total supply is. And of course, once we mint the horse, we're going to have to increment the total supply. So one of the first things that we're going to need is the total supply. Well, where do we get that? And this, again, is where our good friends at Huffmate actually have all of this for us. However, I will say that working with the ERC 721, Huff isn't perfect at the moment. So I'm actually going to cheat a little bit by, instead of doing an import here, I'm actually going to do some copy pasting. I know, sacrilegious, but it's okay. So we are going to import a few things. First, we are going to import this common errors.huff, and we're just going to update this code base so that it's ERC20'd up. So lib/huffmate/utils common errors.huff. We're also going to import everything in here from nonpayable.huff to avoid some not so pleasant collisions and imports. So we're just going to straight up copy paste this at the bottom of our contract. Cool. We're going to copy this entire interface here and all the events and all the storage slots and the immutable offsets and the ERC20 constructor. And we're just going to copy everything else. And what we're going to do is at the bottom, once again, we're just going to paste. We're going to paste the whole thing. And let's put a little, well, not a little, let's put a really big comment here saying we got these from Huffmate. Imported from Huffmate. And let's make sure this compiles. Huffc /src horse store v2 horse store.huff file not found src utils. Let's try it now. Okay, cool. Horse fed happy within. Oh, it looks like I named horse fed times the location horse happy within horse happy fed within. Sorry, that's what I needed to name it, so I renamed it that. And cool, looks like it's compiling. Nice, that was pretty easy. But so now that we've imported it all, well, imported in quotes a little bit there. Now that we've inherited all the ERC 721 functions, we can now get the total supply, no problem, right? Because we can actually work with all the ERC 721 stuff. And even though I just said we need all the ERC 721 stuff, I forgot that that implementation doesn't have a total supply. So we're going to create our own. Define constant total supply equals free storage pointer this. So the first thing we're going to need to do is we're going to need to get the total supply, like so. Total supply. And we're going to need to mint, and we're going to need to load sload total supply. So now we have the total supply. So the total supply location, sload it. Now we have the total supply. I'm going to do a dupe 1 here. Just trust me that this will be good. This will work out. And then what do we need to do when we do the mint? Well, we got to safe mint it to the message.sender. So we're going to need to get the message.sender. To get the message.sender, there is a caller opcode, which gets the current caller address. So we're going to do caller, which will give us the message.sender, total supply. Then here's why we imported all this. Then we can call the mint macro, which takes 2 off the stack and returns 0. So input on the stack is going to be the 2 and the token ID. Output on the stack is the nothing. So if we go back up to our mint function, we can see, where did I put the mint function? We have the 2 and the token ID on our stack right now. So we can just call the mint macro. And now we just have the total supply on the stack. So this is why we duped one over here, by the way, so that we can have the total supply here on the stack. So now that we've minted, now we want to increment the total supply. So we're going to increment it by 1. So we're going to do 0x01, which will be, which will be 1 total supply. We are then going to do add, which is going to do total supply plus 1. Then we're going to get the total supply location, and we're going to do an store. Pretty much it. So we're going to take this total supply plus 1 value, stick it into the total supply storage location, and then stop. And that's it. And that's our mint function. So I said it was going to be hard, but it's actually real simple because we have this mint macro that came from the ERC721 Huffmate, which pretty much does a lot of the event hashing, logging, invalid opcode, unauthorized, etc. It handles most of the stuff for us so that we can just focus on our horses. So cool. We now have the mint horse done. Now, the only thing we do not have done is our constructor is still not done. So with our ERC721, there's an ERC721 constructor, which I'm not going to go over this. It basically sets up the ERC721 stuff. But what we can do, pretty similar to what we do in Solidity already, is we can say define macro constructor equals takes 0, returns 0, ERC721 constructor, and that's it. Now, because we have the constructor set up like this, we're actually going to need to deploy this a little bit differently than we normally do. So if we go back to our test, I've already kind of set this up for you, so you don't have to worry about this. But the way that we actually deploy this is we do this huffdeployer.config with args, and we add the NFT name and NFT symbol. So this is how you deploy a Huff contract where the constructor has args. And like I said, I've already set that up for you, so you can ignore that. So we're almost done. We're not quite done yet, but if we scroll down into our function dispatcher, we only have our horse store function dispatches. We do not have the rest of our function dispatches, right? We don't have approve or transfer or anything like that. And for this one, once again, guess what we're going to do? We're going to cheat just a little bit. There is an ERC721 wrapper.huff that I'm actually going to cheat, and I'm going to grab. What I'm going to do is I'm actually going to come in here, and I'm just going to copy all the function dispatches from here and copy all the jump stuff. Boop. So once again, we're cheating a little bit, and we're going to put this in our function dispatcher. Yay. So let me go find the main function, and we're going to have to do a little copy paste fun here. Paste. Okay, cool. Looks good. Let's copy this. We need to put these below all of the dispatches down here. Boom, like this. Revert on a failed dispatch. Okay, those all look good. Cool. Let's try to compile this. The huffc. Oh, we're missing macros safe mint. I believe those macros are in here. I think so. Yep, safe mint with data and safe mint. So we're going to copy these last macros, stick them right at the bottom, and try to compile this again. We're missing the mint macro mint. Oh, is that in the wrapper too? Oh yeah, sure enough. Burn and mint were in the wrapper. So we're going to paste those two, and boom, it's compiling. So I think we're done here. Now I know we did a lot of copy paste. We did a little bit of cheating here, but this should essentially be our ERC721 horse store v2 in Huff. Let's try running some tests. Forge test. Pass. And okay, we got some fails. Let's see why we got some fails. Let's run this one. Forge test -mt. Paste that in. 4 V's. See what happened. What did we forget? EVM error revert. Okay, why did we revert? Looks like total supply, static call, reverted. Do we have a total supply? We forgot to add a total supply interface. Do we have a total supply? We don't have, okay, we need a total supply function dispatcher here and a total supply function. So let's do define macro total supply, takes 0, returns 0. This is going to be pretty simple here. We're just going to grab the total supply pointer. We're going to s load it, 0x00 mstore, and then we're going to do 0x20, 0x00 return. And then I think that should be it. And we need a function we have a function dispatcher. We need to add, copy paste this, total supply, and we need to add it to the interface. Total supply, returns you at 256. I think that looks good to me. Let's try compiling it and let's try testing it. I think we should be pretty good. Maybe I'm being, hey, we do look pretty good. Okay, forge, test, and everything passes. So now that everything is passing, one of the coolest things we can do in Foundry is we can do forge snapshot. And this will run all of our tests, but it'll also keep track of all the gas associated with it. So I just ran forge snapshot, and now I have this .gas snapshot file here where we see horse store v2, horse store sulk, horse store v2, and we can do some comparisons in here of the different huff versus solidity. So I'm going to do a little copy pasting here where we have horse store sulk, and one of these is Yul. I don't know which one, but we can compare, okay, horse store huff versus sulk. So horse store huff 7419, horse store sulk 7525, or oh, it looks like this one's a fuzz. So this is what, test read value? Oh, these are both test read value. Boom, boom, boom. So it looks like huff by far is more efficient than solidity and solidity Yul. Okay, well, what about test write value? Okay, so we have these kind of being the two values. Maybe this is the lower, this one of these is the average or the highest or the lowest. I forget, but it looks like even these two values in huff are more gas efficient than that in solidity or solidity and Yul. Okay, let's keep going down. What about horse store v2? Okay, test feeding is 106,119 versus in solidity is, oh my goodness, it's almost 10,000 more gas to do it in raw solidity than raw huff. And you can see why it could be such a good idea to code your smart contracts in huff or in lower level programming languages, because you can get them so much more gas efficient. But keep in mind, we did remove a lot of the safety that we probably shouldn't have, right? We didn't check for message.value. We didn't check for call data. We didn't check for call data size. There were all these checks that we skipped out on the huff, which of course are going to make it more gas efficient, but might not be best practices. Some areas that don't need that level of security, like for example, returning the name, yeah, this would be a great improvement to have in your smart contracts. Look at it's almost 2,000-3,000 gas cheaper in huff than solidity here. We have successfully written a horse store v2 with mappings with ERC20s in huff in very low level, essentially binary bytecodes here. This is hard stuff. And the fact that you got this far, you completed section 1 of the EVM assembly and opcodes course. This is incredibly exciting. Now I know because you've gotten this far, you're obviously no slouch, right? You know a lot about the EVM, you know a lot about Foundry, you know a lot about Solidity, you know a lot about smart contract development, and you just got that much better. So with this, you've actually completed section 1 of the EVM assembly and formal verification course. Give yourself a pat on the back. Now's a great time to go get a coffee, go get an ice cream, go to the gym, but take a break. But before we take a break, we're going to do a quick recap of everything we learned in this whole section, and then especially what we just did. So quick recap. So what did we learn in this section? Well, we learned about a lot of stuff. Even though we probably already knew this, we learned about how the stack and memory work in Solidity. We have a stack, we have memory. When we push stuff onto the stack, we can use the mstore to then store it onto this array called memory. We learned that in Solidity, we have this thing called the free memory pointer, which points to this spot in memory where it says, hey, there's nothing here. And every time it gets updated, we update this free memory pointer. We learned that we can take a smart contract written in Solidity and break it down to the most atomic of its matter. And we learned a great way to write with the Huff programming language. And we learned how to write some smart contracts in Huff. And we learned that if we wanted to write incredibly gas efficient smart contracts, Huff would be a great way to do this. Or Huff is just a great way to learn this low-level EVM. We additionally learned about Yul, where we can do inline assembly in our smart contracts to make them much more gas efficient, or just have access to lower-level code. And with Yul, we learned that you can write inline assembly, but you can also write an entire smart contract completely in Yul or assembly. When it came to our testing, we already learned some clever ways to do differential tests, where two of the same code bases get tested on the exact same code. So we tested our Huff, our Solidity, and Yul all on the exact same tests with very minimal changes to our testing suite. We learned what every single opcode in one smart contract does. And we learned how to do some stack-looking syntax for comments when we're reading opcodes. And we learned how to read opcodes and tell exactly what a smart contract is doing. We learned about a lot of different opcodes and what they do. And we learned about the EVM.code's playground, which is a great place we can play around with opcodes. Another place we can play around with opcodes is going to be the Foundry debugger. We can run forge test --debug and then a test name, and it'll drop us into a debugger where we can go opcode by opcode through any transaction in Foundry. We learned more about building an even more advanced smart contract. We learned that Huff can do imports. And most importantly, we learned how to work with mappings in Huff, or mappings at the lowest level. We got a little bit more comfortable with jump destinations and jumping around. We got pretty comfortable with using the Huffmate to work with keys and work with data. And we built a much, much more complicated Huff smart contract using an ERC721 and this horse thing. And even with the horse thing, we didn't go through this together, but we took that same methodology of doing differential tests with Huff and Solidity, and we applied it to our horse store V2, which was much, much more complex. And still, we were able to find that these two smart contracts were equivalent essentially in their functionality. We learned that smart contracts are separated into contract creation code, runtime code, and metadata. And we learned that if ever we run into a scenario where life or death, we have to tell somebody what a lump of binary does, we can do it. There's going to be times where attackers do not verify their attacking smart contracts. And if it's important enough, guess what? What we can do is even we can break down what those smart contracts have done, what the binary represents, and convert it back to Solidity. There are some disassemblers or decompilers that try to do this for us, but they can be a little rough around the edges. So you now know how to do it manually. We learned about the free memory pointer in Solidity, which is incredibly important. And this will come up even more when we talk about Viper, or if you ever get to Viper. So we learned an absolute massive amount here. And you might still not feel super comfortable with opcodes. That's okay. What I will say though, is a lot of smart contracts are not written in Huff, right? It's too hard to write in Huff. However, there are a lot of smart contracts written with a lot of assembly. And we are going to get more comfortable with assembly in section 2, because there's going to be a lot of assembly in section 2, Math Master. However, in order to really understand the assembly, you really need to understand the opcodes first. So I think one of the best ways to get good at these opcodes is to keep working with Huff. So now is a great time for you to take a step back and convert a minimal smart contract of your own into Huff or Yul or inline assembly or whatever you want to do. Oh shit. That's going to make you so much more comfortable with these opcodes. Huge, huge congrats for getting this far. If you want to go the extra mile, definitely be sure to take this challenge up for yourself. Go get that coffee, go get that ice cream, and we'll see you in the next one. So now that everything is passing, one of the coolest things we can do in Foundry is we can do Forge Snapshot. And this will run all of our tests, but it'll also keep track of all the gas associated with it. So I just ran Forge Snapshot, and now I have this .gas snapshot file here where we see horse store v2, horse store sulk, horse store v2, and we can do some comparisons in here of the different Huff versus Solidity. So I'm going to do a little copy pasting here where we have horse store sulk, and one of these is Yul. I don't know which one, but we can compare. Okay, horse store Huff versus sulk. So horse store Huff 7419, horse store sulk 7525, or oh, it looks like this one's a fuzz. So this is what, test read value? Oh, these are both test read value. Boom, boom, boom. So it looks like Huff by far is more efficient than Solidity and Solidity Yul. Okay, well, what about test write value? Okay, so we have these kind of being the two values. Maybe this is the lower, this one of these is the average or the highest or the lowest, I forget. But it looks like even these two values in Huff are more gas efficient than that in Solidity or Solidity and Yul. Okay, let's keep going down. What about horse store v2? Okay, test feeding is 106,119 versus in Solidity is, oh my goodness, it's almost 10,000 more gas to do it in raw Solidity than raw Huff. And you can see why it could be such a good idea to code your smart contracts in Huff or in lower level programming languages, because you can get them so much more gas efficient. But keep in mind, we did remove a lot of the safety that we probably shouldn't have, right? We didn't check for message.value. We didn't check for call data. We didn't check for call data size. There were all these checks that we skipped out on the Huff, which of course are going to make it more gas efficient, but might not be best practices. Some areas that don't need that level of security, like for example, returning the name, yeah, this would be a great improvement to have in your smart contracts. Look at it, it's almost 2,000-3,000 gas cheaper in Huff than Solidity here. Now, Forge has a great debugger. Tenderly is another debugger we talked about a little bit in the security course. It can do some of the same opcode by opcode debugging, which is absolutely fantastic. And then additionally, we talk about this a little bit in the wallet course. There's this phenomenal tool called MetaDeck. It's a Chrome extension. And if you get it, what will happen is if you go to like Arbitrum scan or Etherscan or anything like that, it'll give you this little risk, fund flow, and these little tags up here. It'll give you some more context on who funded the contract. It'll give you little buttons where it'll bring you over to the DDoB website where you can actually try to decompile it, see what's in storage, etc. And just adds a whole bunch of nice little pop-ups when you're working with Etherscan-like explorers. So really good tools. So take that break, get that coffee, because we're going to go even deeper into assembly, and we're going to finally get introduced to formal verification and symbolic execution. Go get that coffee, go get that ice cream, go hit 315 on the bench at the gym, and I'll see you in a bit. All right, welcome back to the Assembly, EVM opcodes, and formal verification course, previously known as part 2 of the security course. We are in the GitHub repo associated with this course. If you're on Cypher and Updraft, this resource will be on the starter section of the course. And if you're on YouTube, this will of course be in the description of this video. We can now scroll down in here. We can look for section 2, which is going to be Introduction to Formal Verification and Symbolic Execution, the Math Master Audit. So here's the Math Master Audit. Now, this Math Master Audit is hard. This Certora tool, this Halmos tool, a lot of this formal verification stuff is difficult, and this is going to be tricky to work with. I want to make sure that when you're working on this, you're using the GitHub repo to your advantage. All the way at the top, we're going to have a discussions forum, exact same as all of our other courses on Cypher and Updraft. where you can ask questions, connect with your peers, etc. You know how to ask questions on Stack Exchange, jump in the Discord, on Telegrams, on Cypher and Updraft, and I want to encourage you to do so. AI bots are kind of bad at formal verification. Hopefully they will get better, but at the moment, they are not very helpful with a lot of this. So I want to make sure that when you're working with this stuff, you know that it's hard, but you know that when you finish this, you're going to come out the other side an absolute badass with some very, very cool skills that you're going to be able to apply to making code bases more secure. And you're going to have some niche knowledge that very few smart contract developers and security researchers have. So let's take a cruise through this repo to give you an idea of what we're going to be working with. So in our last section, in our horse store section, we actually did a lot of coding. We built a lot of really cool things. In this section, we're back to doing an audit. We're actually going to start on this main branch. We're going to be given this single library, this math master library, and we're going to be doing a little bit of bug hunting. But don't you worry, devs. In the pursuit of squashing out all these bugs, we're going to be building and using a lot of really powerful, really cool tools. Since you all just learned a whole bunch of assembly or low-level Yul, guess what? There's a whole bunch of assembly and low-level Yul in this code base. And the code base we're going to be looking at is actually relatively small. It's this mathmasters.sol, which is actually modified and borrowed from these two phenomenally influential code bases, Solidity and Soulmate. I highly recommend you take a look at them after this course. If you look at them now, you'll get a couple of hints as to where some of the bugs are, so don't look at them quite yet. The purpose of this code base is to have an arithmetic library with operations for fixed point numbers. So basically, this library is intended to make math easier. And if you go into this code, there's a couple of functions. There's molwad, which is equivalent to doing x times y divided by wad. We'll talk about wad in a little bit. There's molwad up, which is x times y divided by wad rounded up. And then we have a square root function, which is kind of this horribly massive assembly chunk of code that we're going to be looking for some bugs in. So that's it. It's just these three functions, but they're super heavily in assembly. And we're going to use our newfound assembly powers to walk through them and look for bugs. And then additionally, we're going to have to use a newfound tool that we're going to introduce in this as well. We're going to be introducing this concept called formal verification and symbolic execution. I am going to introduce you to the Halmos tool, which is a formal verification tool, which will help us find a bug where our fuzzers cannot. Crazy, I know. To do this, we're going to be writing a lot of code, but we're going to approach this as if we are doing an audit. Now, if you haven't done an audit before and you want to learn how to do security, highly recommend you going to Cypher and Updraft, going to the Security Smart Contract Auditing course. Again, there's a huge repo for this on the Cypher and GitHub as well, which will teach you how to go through smart contracts, go through code bases, and do security reviews of the code bases. And if you haven't done an audit before, that's okay. Just focus on the building and the mental approach we take looking for some bugs. But the idea of this is we are actually going to be finding some bugs using building some really advanced, really cool tools. A derivative of this code base was also recently a first flight on the CodeHawks platform, and this was probably one of the hardest CodeHawks first flights out there, but there were some absolutely stellar write-ups that some people did, and it's these first flights that can really give you the chance to practice doing some of these more advanced, more difficult security reviews and really nailing your prowess as a developer and security researcher. So even though the code base that we're going to be looking at is small, we're going to be learning a lot in here. And the answer key to this is in this second branch, audit data. If you ever get lost, if you ever want to refer to the quote unquote answer key, that's going to all be in this audit data branch of the GitHub repo. Now, we are going to approach this the same way we would approach any security review, although somewhat expedited. We're going to be focusing primarily on the initial review. We're not going to do a protocol fixes mitigation review, but we are, of course, going to start with a scoping phase where we just read through the documentation, we read through the contracts, we figure out approximately what this code base is trying to do, we run some tests, and we get a good idea of what this code base is trying to do. And then once we do that, we're going to start smelling out some bugs, and then we're going to write some amazing test suites and use this brand new tool to find these bugs. Formal verification is a superpower very few protocols use. However, the protocols that do use formal verification are the cream of the crop, are the blue chips. Aave is a protocol that I refer to quite often because they are one of the largest DeFi protocols out there, consistently being in the top 3. They use this formal verification tool called Certora. In this lesson, we're going to be introducing you to this Certora tool, which is this incredibly powerful form of verification tool, as well as the open sourced Halmos. We're going to start really easy in this lesson with form verification. And then in our final section in the Bad NFT Marketplace, we're going to be going deeper in Certora and building some incredibly badass formal verification test suites. We're going to teach you why formal verification is so cool, why it's the future of testing, and you're literally going to have a skill that I want to say 0.01% of smart contract developers have. Buckle up, get ready for a phenomenal ride breaking this code base, and let's get started with the initial phase of any smart contract audit, which is going to be scoping it out and getting set up. All right, so we are in our Math Master Audit codebase, and you already know what to do. Let's just go ahead and clone this codebase in our repo. So I'm back in my opcodes FV folder where I can see my horse store in here, and we're gonna go ahead and git clone this Math Master Audit, and I'm gonna open this up in a new VS Code like so, and we're gonna get started just reading through the README. What is this codebase trying to do? So we have the README. I'm going to open it up in preview mode. That logo is so cool. All right, let's give this a little bit of a read. This codebase was inspired by Solidity, Oberon.eth, and Soulmate codebases. Huge thanks to Karma for help on FV with Halmos. I'm probably going to also update this for a couple other thank yous, including to the runtime verification team and, of course, the Certora team as well. Even for me, this was pretty difficult to wrap my head around. Oberon.eth in particular, Mr. Zach, was the one who inspired the specific scenario here so you could really see the power of formal verification and see the power where fuzzing actually won't find our bugs. Anyways, giving out too much information. So here are the requirements. You obviously have Git and Foundry installed. You don't need to have Halmos yet. We will install that together. But okay, cool. Here's the quick start. Looks like I need to update that to be a 2, but let's look at the foundry.toml. Okay, FFI isn't in here. Okay, so I feel pretty safe. Let's go to the makefile, remove install build. Let me do a toggle word wrap. This looks pretty safe for me to call. Remove, cool, install, cool. Okay, great. I can go ahead and run make on this, install all the dependencies. Looks like this will probably run the tests as well. Oh, looks like it didn't actually run the tests. Let's keep reading the README. We ran make. Okay, usage, forge test. Okay, cool. Forge test. Cool. Looks like 7 tests pass. Let's look at forge coverage. Yikes. Okay, that's not great. Let's do a Darren. Let's run a Darren in here. Let's see what a Darren gave for a report here. Solidity pragma should be specific, not wide. Push 0 not supported by all chains. Okay, those are pretty classic issues that are found. Not a big deal. If we go back to the README, we scroll down. Okay, it looks like this is planned on being only used for Ethereum, so we can ignore the push 0 report because that's only because push 0 is supported by Ethereum. And then Solidity pragma should be specific, not wide. Okay, well, we'll address that when we come to it. Okay, so what is this codebase supposed to do? We kind of just blindly ran some tools. What is this supposed to do? Usage, we did that. Okay, I guess there's not a whole lot of abouts in here. That's kind of frustrating. Okay, well, it's just one file here. So let's give this a read. Oh, even right at the top. At notice, we intentionally want to leave this as floating points so others can use it as a library. Oh, okay, so this doesn't have good docs, which I would probably raise as an issue to the protocol. Hey, you need better docs. However, we can see that they're planning on having this mathmasters.sol being a library. And we even see, they're using the library keyword. So actually, this being a floating point is actually correct, right? And when we're doing a review on this, we're going to have to make sure, okay, is the floating point that they're using, are all the versions in here safe based off of these different versions of Solidity? Is it cool for 0.8.3 and above? Will those versions of Solidity work with all the code that's in here? And it looks like we're gonna have to read some of these comments as our documentation. So this is an arithmetic library with operations for fixed point numbers. As I said in the last video, we only have 3 functions. We have molwad up, and then we have square root. So that's it. It's just these 3 functions. We have some notes here we're gonna read in a bit as we flesh out our scoping phase. Okay, that seems pretty good. What else? What do we have for files in here? Okay, we have the tests. We have a base test. Okay, we have a base test in here. And it looks like we have, oh, okay, we're using like a Uniswap square root. This is probably what they're using to compare to their super gas optimized square root. Okay, interesting. A soulmate square root. So it looks like they're probably comparing the square root they do in here to this crazy assembly soulmate square root. Okay, interesting. It looks like all the tests are actually in this Math Masters test. Looks like they have some unit tests. Oh, okay, cool. Looks like they have some fuzz tests. Okay, nice. Got some more unit tests. We have some more unit tests that we might want to read. Why are these tests written as such? Some more unit tests and some fuzz tests that compare the different square root functions to each other. Okay, cool. So it looks like this is actually really interesting, right? So they are comparing this mathmasters.square root function, the square root function that mathmasters implemented, to this Uniswap square root, which we could double check is actually correct, and to this soulmate square root. So there's kind of an assumption that these two square root functions are already correct, which we might want to double check is actually correct. Okay, tests look pretty interesting. What else is in here? Foundry.toml, we got a bunch of fuzz stuff. Okay, cool. Makefile, readme. Okay, they have slither. Let's run slither as well. So it looks like they even have slither in the makefile because I wrote the code base, so I know slither's in the makefile. Okay, slither. Okay, so we can just run make slither and it'll run with the config file. Great. Make slither. Let's see what we got for an output. This is it. We get a real small output here. The first couple of issues are saying, hey, you use assembly. Yep, we know they use assembly. That's kind of part of the reason why this code base exists, because this is going to be a much more gas efficient mathematical library than if they used raw solidity. So cool, we can ignore the assembly usage. And then down here, MathMasters molwad is never used and should be removed. Okay, this is a library, so obviously these are never used, so it's fine. So actually all of Slither's output we can pretty safely ignore. Okay, cool. All right, so at this point, we pretty much know what we're supposed to be doing here, right? And again, maybe it's a good idea to make a .notes file or someplace for you to dump some thoughts. And we know what this code base is supposed to do, right? It's going to be a gas optimized fixed point math library with 3 functions. We're not really sure what these do. We have this molwad thing, molwad up, and then we have square root, which they're all super assembly. We're not really sure what molwad means. Like, what is a wad? Equivalent to x times y divided by wad, rounded down. Weird. Okay, whatever. And then a pretty typical square root function, returns the square root of x. So our job is to see if any of these math functions are wrong. So you know the drill. It's time for us to go line by line through the code base. But before we do that, let's do a quick history lesson on wad, ray, and rad. So in this mathmasters.sol, this mathmasters library, we see a lot of this wad stuff. So what is a wad? Well, you've probably seen this before, but wad, ray, and rad, a little bit of a history lesson here, were introduced in DAppHub/DappTools/the DS test system, which was popularized by MakerDAO, Compound, and a couple other early protocols. You can actually see there's a question on Stack Exchange that also asks this as well. And all it means is just 18 decimal places. It's a token with 18 decimal places. It's a pretty comical interaction here where the person goes, hey, I've not marked your answer as correct because you did not clarify the meaning of the acronym. And then the person follows up and says, it's not an acronym. It's like a bundle of paper, banknotes, or documents, like a thick wad of index cards. So apparently wad is literally just like a wad of numbers. I don't know why it's wad. I don't know why it's ray. I don't know why it's rad, but that's what it is. So if anybody knows why, they want to give a little bit of a history lesson there, please feel free. But yeah, a wad is 1E18, a ray is going to be 27, and then a rad is going to be 45 decimals. So it's a fixed point decimal with 18 decimals. And this is what most tokens actually use when they're calculating decimals. So if you have a token with 18 decimal places, it's using the wad here, and that's pretty much it. So our molwad and our molwad up are going to be both for doing math with a fixed point decimal with 18 decimal places. So that's what WAD stands for. Now, before we even get to the molwad function, right at the top here, we're seeing we're doing 0.8.3. We know that our Darren report actually did point this out. Floating pragmas are bad, but this is a library and it's supposed to be inherited, so that's fine. However, this is one of these things where you kind of just gotta know, or you have to go through your checklist to check for things like this. Version 0.8.3 doesn't have custom errors. So if we actually try to compile this as is, right? If we go to foundry.toml, let's do sulk equals 0.8.3. And now I try to do forge build. We get a fail here. Why do we get a fail? Well, it's because this custom error doesn't exist in that version of Solidity, right? We get rid of this, we go to compile again, forge build, and now we're successful. That'd be another low finding that we would put in the audit report. We're using the wrong version of Solidity here. So that's going to be our first audit finding here. Great job. All right, so now that we know that, we can actually start going line by line and figuring out what this actually does. And here's the beauty of this. This is going to be pretty hard to read, right? Assembly is going to be very difficult to read on your own. Like you saw how long it took us to go opcode by opcode. We kind of have to do the same thing when we're dealing with molwad here. And this is where our testing frameworks make this so much easier, because it can be so time intensive to go line by line through this assembly that it's going to be really important for us to have tools that can help automate this process to make sure it actually works. And formal verification is going to be a tool that'll give us the highest assurance along with fuzzing. But we always want to do some manual review as well. So we have this molwad function, which the docs say right here, it's equivalent to x times y divided by wad rounded down. And we can even go into the test here to look at some examples. If we scroll to the top, oh, that's the base test, mathmasters.t.sol. We go in here, we have molwad and molwad fuzz. It looks like these are the two test functions that we can work with. And we see we have some examples in here. Looks like both of these examples aren't great. So we're kind of assessing the test molwad here. Why aren't these great examples? Well, because these two math out to kind of this nice 1.25, right? There's no rounding really happening. These two, same thing, no rounding. These ones do round down to 0, which is good. So these unit tests aren't great, but this is where the fuzz tests actually come in and make it really, really helpful. Mathmasters.molwad x times y equals x times y divided by 1e18, right? Because this is exactly what we should be getting, just that molwad does it a little bit more gas efficient. Then we have an unchecked conditional here. If x does not equal 0 and x times y divided by x does not equal y, return. So this is basically to say, hey, if you go over a unit 256, we're going to return. We're going to end the test case here. But this looks like it's a really well-written fuzz test so that we can run into some crazy examples there. Okay, so cool. So this, just by having this fuzz test, gives us some assurance that this function is correct, right? Because this doesn't give us a lot of assurance because just 3 examples, but this is saying, hey, out of all these fuzz runs, it's going to be equal here. Hopefully we have enough fuzz runs, but let's go ahead and actually read through this line by line, and we're going to have to break this down a little bit. This is equivalent to require y equals 0 or x is less than a type u56.max divided by y. Okay, interesting, but let's use our newfound knowledge to break this down. So there are a whole bunch of inside parentheses here. Let's just break this out just a little bit so that we can actually see what's going on in here a little bit easier. So, and now we can actually do some stack stuff here. Okay, so we're going to start with not 0, y. So if we come into the Yul documentation for EVM dialect, we can look for not. So not x is going to be the bitwise not of x. Every bit of x is negated. Okay, so we're already getting a little bit hairy here. So unless you're a bitwise god, this might be kind of difficult for you to visualize. So we can actually come to our terminal here into Chisel and try this out. So we'll do Uint56x equals 7, or let's do 0x01. Let's do 0x01 just to demo this. So now if we have x here, we can see the decimal is 1. We can see the output up here. This is obviously the hex for the decimal 1. Now we can do some assembly like this. We could say X is going to be set to, remember this is how you do set in assembly, not X, like that. And now we'll see what X is. So, whoa. So X is this kind of crazy hex up here. Well, what if we do X equals X plus 1 now? Now, X is this number. Oh, well, what if we do X equals X plus 1 again? Uh-oh, you get an overflow. So what this not does is it flips every single bit in the decimal. If you can imagine that number 0x01, this is the hex representation. The binary representation of 0x01 is going to be 0, a whole bunch of zeros and then a 1. So what not does is it flips it. It takes all these zeros, flips them to 1, and then makes this last one 0. So same thing, if we had like 0101 and we did a not to the 0101, we would now have 1010. Basically flips all the binary in that number. So remember, this is the binary representation, this would be the hex representation, and this would be the decimal representation. Not flips everything. When we say not 0, we're really getting this value 0x right? Because if we pull chisel back up, and we need to do X or assembly, X is going to be set to not 0. Oops, I need to close it off. Now we do X, we see it's this huge F thing again. And just to double show you, we'll do U into 56, Y equals 0, Y is 0. Now we'll do that same thing. Assembly, Y is set to not 0, we do Y. So really this not 0 could simply be replaced with this. However, not 0 is a little bit easier to write like this. So, okay, so now we know what this not 0 is doing. It's literally just getting us this 0 F thing here. Cool. Now let's go 1 parentheses up. Next we have the div, which div is going to be what? It's going to be the divide keyword here. So it's going to be equivalent to X divided by Y or 0 if Y equals 0. So this, normally you can't divide by 0, but in assembly you kind of can. But in Yul, you can. If Y is 0, then the response is actually 0. So we're going to divide this huge number by Y here. Let's look at chisel again to see what we would get if we combine these two. And I'll make this a little bit easier. We'll do U into 56, not 0. We'll do assembly, not 0 is going to be set to not 0. And then we'll say Y, because we've already established it, equals like 7 or something. So now we want to do A divided by B, right? Div is going to be X over Y. So let's do that. Let's pull this up. So X is going to be not 0 divided by Y. Let's see what we get. And this kind of crazy number is what we get, right? So this is going to be the output of a division. That's going to be the output of the division that we do here. So, okay, cool. And what we're checking to see here is that this value is GT. What is GT? So GT is going to be 1 if X is greater than Y, 0 otherwise. So we're basically checking, hey, is X greater than this crazy number divided by Y? And is X greater than kind of this crazy number that we did? And remember, if GT returns either a 1 or a 0. So we can do a little bit, another note here. We can say if big num divided by Y is greater than X, this is going to be 0. And if it's less than X, it's going to be 1. So this whole thing just gets us a 0, 1, and then we multiply it by Y. So this is actually really good, right? And here's where it gets a little abstract, but stick with me. So we have this big number, and then we have this greater than. So what we're saying is if X is greater than this division, this big number divided by Y, then we're going to say return 1 or be true. Because remember, 1 is going to be true, 0 is going to be false. Well, it's really anything other than 0 is false, but 1 is true, 0 is false. And we see down here, we have this revert. So we're looking for areas to revert. And we want to revert in this scenario because let's grow up for a bit. Let's pretend the max U in 256 is 10, right? And let's say we get past Y equals 2 and we get past X equals 6. Well, 10 divided by 2 is going to be 5, right? Because 10 is the max U in 256, 2 is the Y. If we then wanted to do a molwad where we multiply x times y, we're basically saying, okay, what's 2 times 6? This 6 is greater than this 5. And because we know 6 is greater than 5, we know that 2 times 6 is going to go past the max U256. So what this conditional is doing is we're basically saying, hey, if we multiply these together, is that going to be too big? If it's too big, we want to revert. So you might be asking, oh, okay, well then why isn't the conditional just this, right? Why are we doing this weird additional multiply by y? Aha, great question. So this is basically the conditional that we want. However, remember, if y is 0, this division is going to return 0. So if we then passed in, x equals 1, y equals 1, or y equals 0, if we do not 0 divided by 0, this is going to return 0. X would be greater than 0. So then we would proceed to x times 0 divided by wad. However, x times y is, if y is 0, is 0. So then we're going to do 0 divided by wad. So this wouldn't work. So we then need to multiply by y to make sure that y is not 0. So basically all we're doing is this is the main check, and then we do this additional multiply to make sure y isn't 0. Because if y is 0, then this is going to return 0. X will pretty much always be bigger than 0. So this is going to say, hey, x is bigger. This is true. We got to revert. But if y is 0, that's okay, right? Because some big number times 0 is going to be 0, and then 0 divided by wad, we don't really care. The answer is 0, right? So 0 divided by anything is going to be 0. So we're saying, hey, make sure this conditional holds unless y is 0. If y is 0, that's cool. 0 times anything in here is going to be 0. So we would go ahead and proceed to actually doing it. Otherwise, this is how this little section here is basically equivalent to doing require y equals 0 or x is less than or equal to type u256.max divided by y. Or that's at least how I'm walking through it. And obviously this might take you a couple tries to go through, right? Doing this assembly written out or in your head can be difficult. And if this doesn't make sense to you, I highly try you giving it a shot, right? Like maybe you go, hey, I don't understand why this multiplies here. Okay, well then let's get rid of that. Let's save. Let's get out of our chisel, right? And let's go over to the tests. Let's do this test molwad fuzz. Let's see if we can forge test -mt, paste it in. See if it'll give us a counterexample where that actually breaks it. Aha, it sure does. If that function is given 1 and 0, it will actually break, right? And that makes sense because if x is 1 and y is 0, right? What happens if x is 1 and y is 0? This reverts incorrectly. We don't want it to revert, right? So we have to have this multiply by y so that it doesn't revert in the case that y is 0. Make sense? So this is actually a really clever way to do this, which in Solidity would be way more gas expensive. So we're doing this very clever assembly here. Great job to the people who wrote this code base. Now let's move on to the revert. So basically we're checking, hey, is y 0 and is x less than the U256 max divided by y, okay? Then we're gonna revert. Okay, cool. And then we zoom out just a hair. We have this comment here saying this should be mol masters mol wad failed. Interesting. And then we're gonna revert like this. So, okay, so we have these two functions here. Let's look at the mstore. Mstore is gonna do, what the heck is that? So P stands for position, V stands for value. So memory, this kind of weird syntax here. So this mstore, what is this weird syntax over here? We can basically just look at this mstore almost exactly like it's an opcode, and these inputs P and V are what would be on the stack. So you can think of it as when we call this mstore, behind the scenes, we're gonna push on these two values in this order onto the stack, and then we're gonna call mstore. And this kind of weird syntax here is basically saying, hey, it's gonna be the offset in memory here. So back in our code base, when we see mstore 0x40, this is saying, okay, we're gonna have memory look like this at 0x40. We're gonna have this value in here. That's essentially all this is doing. We're pushing these two onto the stack and then boom, into the 0x40th position. So it looks like the idea here is that we're actually putting this error into memory so that when we revert, this is the error that we get, right? Again, we can go over to the revert documentation, P and S. You can see it's kind of doing this same syntax as it was doing with mstore. We can also just go to EVM.codes. We could look up the revert opcode, offset size. Okay, so the offset in memory in bytes, the return date of the calling context, and the size is going to be byte size to copy. Okay, so we're starting from, wait, what? 0x1c and 04? Wait, that doesn't make any sense, right? Because, so if we store this value at 0x40, we're saying at 0x40 is this, but we're reverting with the value at 0x1c. So we're saying look in memory this spot, but there's nothing going to be there. So what is going on? So if we go back to the store, we see this weird syntax here. So we see p ... p plus 32 is set to the v. So this little bit of kind of odd syntax is we're saying we're actually going to start at the p. However, we're going to go from p all the way to p plus 32. So we're actually going to fill up the entire 32 bytes with this value. So if we are only putting in this chunk in here, it's actually more like doing a whole bunch of zeros and then this chunk in here. With the mstore keyword, we're not just filling up 4 bytes, we're actually filling up 32 bytes. So you can kind of consider this being zero padded when we use this mstore assembly keyword here. So that means our little error selector here is actually kind of way farther down the line than we thought. But still, this 0x1c still doesn't really make sense, right? If we pull up our cast, we do a little clear, we do cast to base, paste this in decimal. So it says start at the 28th byte and then grab the last 4 bytes. Oh, so this is basically saying, okay, well, if memory looked like this, x00, and there were, and then we had 0x000 ... and then this, right? This chunk being 32 bytes, that's how we would grab these last 4 bytes here. We would start at the 28th byte and then just grab the last 4 bytes if this was 32 bytes long. Hopefully I'm making some sense here because there's a lot of bytes and stuff going on. Let's do a little recap of why this looks so wonky. So when we start with this code here, right? We start right before we execute either one of these. Let's see what our memory looks like, right? Our memory, we haven't done any mstores or anything. We've done some moles. We've done some greater thans. These are all stack things, right? We haven't done any mstore. So our memory should be empty, right? Here are the first 32 bytes. We have 0. We have nothing in any slot in memory, right? Each one of these blocks represents a byte. 0x20 is going to be the 32th byte in memory, right? So if we do cast to base 0x20, we're going to get 32, right? So this is the 32nd position in memory. Same thing between the 33rd or 0x21 and 0x40 or 64. And then same thing between, should be 41, the 65th or 0x41 and 0x60, which this is going to be the 96th byte in memory. Whole thing is blank, right? There's nothing in here. However, when we call this mstore and this value here, we figure, oh, okay, well, we're going to go to the 0x40 position, which is right here, and we're going to stick this value into that, right? Remember, every 2 digits is 1 byte. So we have 1 byte, 2 byte, 3 byte, 4 bytes. Okay, so 0x40 will be BA, 0x41, C6, 42, E5, 43, right? Oh, okay, so that's what the mstore is going to do, but that's actually not quite what's going to really happen. And let me show you exactly what I mean. This mstore actually doesn't start it at 0x40, it actually pads it. So if we go back to Yul, the mstore says, okay, p ... p plus 32 is equal to v. What it means is instead of just adding this directly at 0x40, we're going to fill up from 0x40 to 0x60, we're going to fill up 32 bytes with this value by 0 padding it. And I'll show you exactly what I mean by that. So if we go back to mathmasters.t.sol, we can even write a little function test mole revert, where we try to make sure this reverts. And we can just do this by doing mathmasters molewad. We'll do type uint256.max, and we'll test this by just by adding the max value of these. This should revert because in here we're doing all these checks to make sure that it's less than type u into 56.max. And if they're both too big, this should revert, right? So I'm going to take this forge test --debug and paste this in here. And by doing this, we're going to open up the debugger, and I got to zoom way out. And I'm so sorry I have to zoom way out. Hopefully you'll still be able to see this, but I'm going to hold down J until we get to the part where we do this function, and we should be able to kind of see it by looking at the opcodes. Aha, okay, I see right here. There's a push 4, and I know this is super small. There's a push 4, but that's the exact opcode that we have in our math masters right here. So it looks like we are at the correct place where we're actually doing, and we see that once I hit J, that's what enacts it. We see that now that is on the top of the stack. Press J again, which will put the push OX40. Now when we call mstore, you'll see it does push our value into 0x40, but it kind of pushes it all the way at the end here in the 0x40. So if we ever want to access this value, we need to first jump over the first 28 bytes and then get to this. So this is how these mstores work. You can almost think of them as padding these chunks of 32 bytes. So when we mstore 0x40, we're putting this in at the 0x40 position, but we're kind of padding this all the way to the right. So back in our written here, instead of it looking like that, our memory is really going to look like this. Boom. Where it starts at 0x40, but it starts by putting a 0 here, a 0 here, a 0 here, and a 0 here, aka doing nothing because they all default to 0, a 0 all the way, and then the last 4 bytes, it puts our value. So if we ever want to get just this, we would need to skip over all of this stuff beforehand. If we accessed 0x40 and grabbed the 32 bytes from it, we would get a ton of zeros and then the last 4 bytes. But a lot of times it makes sense just to go directly to the last 4 bytes because that's all we want. And we know the rest are just zeros, right? So it doesn't make sense to grab the whole 32 bytes here. So, okay, so it's a little bit weird that we're putting it at the 0x40th position, but it looks like the revert would be correct because this is saying, okay, grab 0x1c and go 4 bytes, right? So if we look at memory, 0x1c would be here and it's saying go 4 bytes. So it'd be like 1, 2, 3, 4. Huh, that's kind of odd. So shouldn't these be placed up here? So if we grab we grab these, shouldn't these be up here instead? If they want to have this revert code output, it looks like this is correct, but it looks like they're putting this data in the wrong spot. And wait a minute, 0x40. I recognize 0x40. Hold on. 0x40 is usually reserved for the free memory pointer. What? And if we go back into the Forge debugger, I'm going to hold down J. Hopefully it's a little bit bigger for you here. You can see right before we call that mstore, we actually look in memory at 0x40 where the free memory pointer is, and we do indeed see there's an 80 in here already. And when we call mstore, we actually override the free memory pointer. Ah, why are we doing this? This is such bad practice. So it looks like just doing this, we found an issue. At audit, this is probably going to be low because we're going to say this will revert with a blank message. Because in memory, when we actually do this revert, we're reverting from up here, but there's nothing in here. So it's going to be blank, right? So this revert is just going to revert whatever's in here, which is nothing. And if you want to go for some extra credit, you can even do a little test mul revert and put the, the vm.expect revert with the actual revert code if you wanted to do that. Quick recap. So for some reason, we're putting this value in memory, we're overriding the free memory pointer, and then we would do a revert with this data. However, we're grabbing from the wrong place. So one of these is wrong. It's probably this one. This probably should be this instead. We don't want to override the free memory pointer. And then if we say, okay, let's mstore at the 0th position, put this in here, then what's going to happen is then these values would correctly be in this position, right? We're going to say, okay, let's start from 0 and let's put this in here. Let's put this value at the 0th position. At the 0th position, we 0 pad it. So we're going to have a whole bunch of these zeros in here. 0, 0, 0, 0, all the way down to the end. And we put the last 4 bytes at the end right here. That way, when we revert, we say, let's start from 0x1c and go 4 bytes. So that's 0x1c, 1, 2, 3, 4. Boom. That's exactly what we want to revert with. This is the revert function selector. Okay, cool. So we found an issue. This will revert with a blank message. We don't actually revert. And we could also be even like at audit, why are you overriding the free memory pointer? You absolute mad, insane person. But we can do one more thing. So nice work. But you know what? Now that we're here, we're doing a lot of hex code stuff. Let's just double check. This is supposed to be the function selector for this error. Yeah, even errors have function selectors. So if I pull this back up, I can do cast sig, paste this in here. Oh my goodness. This isn't even the right function selector. Oh my goodness. At audit, wrong function selector. It should be this, right? Because I don't know where they're getting this value from, but this is the correct function signature. But if this is what they're looking for, this is wrong. So this could be low, this could be informational. It sounds like they probably wanted to do this, but they're doing some other weird function selector here. So this would also go in the audit report. So there's a whole bunch of stuff wrong with just this line right here, but it looks like this line is actually correct. Okay. So we figured out, okay, they are doing some cool, good stuff up here. We're reverting in specific scenarios. They were reverting really weirdly and kind of wrong, but it's all right. We've spotted it out just using our wonderful mind's eye and understanding of assembly. And finally, we do the actual math here where we multiply x times y, right? Mul, if we go back to the Yul here, this is just going to return x times y, okay, x times y. And we know it's not too big because we did this check over here. We know it's not going to overflow. And then finally, we divide by WAD, which if we command click it, it looks like WAD is correct. It's 1E18. It's an internal constant. Great. So div, as we already know, div just does x divided by y. So this looks good. And then z here, I believe z is defined up at the top. So z is returned. So this looks pretty good to us. So other than this weird oddities with the issues here, this function looks pretty good to us. But in this process, you see, it was kind of difficult for us to walk through this, right? And this is where methods like formal verification, which we're going to go through later, are actually going to help us out a lot. And if we wanted to, of course, we could double check this and spot check this, but this looks good to me. I probably would do some double checking and spot checking, but great job walking through this assembly. Let's move on to Mulwad up. And sorry, originally I added this extra OR opcode in here. I was going to add another bug, but then I decided it was kind of a pain in the ass to add this other bug and it didn't really teach you anything. So I got rid of it for this video, so you don't have to worry about that. So hooray. If you see the OR on the video at any time during this recording, just ignore the OR. It was from a previous version of the course, which I have removed. So great, let's go to Mulwad up and let's do the same thing. So we're doing the same, we're doing x times y divided by WAD, but we're rounding up this time. When we rounded down, we didn't really have to do too much. And let me just undo all that. We didn't really have to do too much because just when we call this div here, it automatically cuts it off, right? If we did 100 divided by 108 or 109, this would be like 0. Something or other. So that would automatically round down to 0, right? Whenever you do division in Solidity or with fixed point math, it pretty much just cuts off the decimal and automatically rounds down. However, it doesn't automatically round up, right? So this is if we want to do, okay, let's say we did 3 divided by 5, we would want to round this up to 1 because this really equals what? 0. Let's pull out the calculator. 3 divided by 5, it's 0.6, right? This equals 0.6, and we want to round this 0.6 up to 1. Let's walk through this line by line and see if we can figure it out. So first, let's open these up just to get a better idea of what these are actually doing. Okay, and we'll start here. Not 0 divided by y. Oh, we've seen this before. This is like oxfff divided by y. Okay, this actually looks nearly identical to what we did up here. And we can actually even compare and look at the two. And it looks like this initial part is pretty much exactly the same as what's up here. So because of this, we can just skip this over and we go, oh, we know what this does already. And then we have the M store and the revert. We already know at audit, this is wrong for a bunch of reasons, right? This is the free memory pointer. This is the wrong function signature, a whole bunch of reasons that this is wrong down here. So, okay, cool. We can skip over this part. And now we get to this weird part. Okay, we have this weird conditional stuff. Okay, let's pull this out and let's see what this is doing. Okay, so first we have this is zero conditional thing based off of this stuff in here. So let's try this out. So we're saying z plus x. So we're saying z plus x divided by y. What the heck is z? Z starts off as 0. So we're saying, okay, 0 plus x divided by y. Okay, so that's kind of odd. 0 plus x divided by y. Okay. Sub minus 1, because we have sub 1. Okay. And then we're saying, is this 0? 0 plus x divided by y. So if x over y is 1, 0 plus 1 is 1, minus 1 is 0, then we're going to add 1. Okay, weird, but we might put like a little e, adding 1 to x if 0 plus x divided by y minus 1 equals 0. Huh, I don't really know why we're doing that, but sure, okay, whatever. Then we're going to go down here. Okay, we have a lot more stuff. Let's break this out so we can have a better understanding of what this is actually doing. Like this. Okay, so we're going to start multiply x times y, mod the wad. So this is like x times y, mod 1e18. So this is getting the remainder. Getting the remainder, okay. And first off, we're checking if it's 0. So checking if it divides evenly, right? Because if the remainder is 0, right? If this is 0, that means it divides evenly. And then we're checking if that is 0. So this kind of looks weird, is 0. But if mul mod is 0, right? If this returns 0, that means false. So we want to do an is 0 to check if that's true. And then another is 0 to check if that's false. So a little confusing there, but basically we're saying, hey, is this 0? Yes, no. Hey, is this 0? Yes, no. And then, hey, is 0? Yes, no. So basically this is just saying, hey, if it divides evenly, then get a 0 and add it to whatever the result is. If it doesn't divide evenly, just add 1 to whatever the result is. So that's pretty much all this is doing. Saying, hey, add 1 if the result has a remainder. That's pretty much all this is doing. Oh, okay, cool. But why are we doing this weird chunk up here? This doesn't make any sense to me. This does make sense to me. I understand this, but I don't understand this. Well, let's look at the tests. Test mul watt up, test mul watt up fuzz. Does this pass? Huh. Forge test -- MT. Test mul watt up fuzz. Looks like the fuzz does pass. So this is where I'm going to have to check out this test mul watt up fuzz, because is this correct? Like I don't understand why we're adding this 1 here. So let's look at this. This looks pretty similar to what we did above. It says we want to skip the case where x times y would overflow, since 0.8.0 checks for overflows by default. We cannot just multiply x by y or this could revert. Instead, we ensure x or y is 0 or that y is less than or equal to the maximum. Okay, cool. That makes sense to me. We have this conditional here, x times y equals 0. If yes, return 0, else return x times y minus 1 divided by e to the 18 plus 1. And this is where maybe I take some time to go through this, but like looking at this looks correct to me. And here's where I want you to start questioning your fuzz tests, because this does pass, but maybe just didn't do enough runs. So if we go to foundry.toml, we take this and we crank it up to 100,000. Now we rerun this. Let's see what happens. Oh, we found a counterexample. If these two numbers are included, we get the wrong result. Well, let's write a unit test with these two values. Let's do function test mul wad up unit like this, public unit 256. What is it? X is that, Y is that. X equals this. Y is going to be this value. And then let's just do result like this. So what should this be if this is going to round up? So let's do this times this. We should get by 1, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Should get this as a value where if we round up, this should be like a 7.5, right? Or 7.4999999. Let's see if what we get. Console.log result. Console2. Forge test dash mt, paste it in, dash 1, 2, 3 these to see the console log output. Oh, we get this value. So it's actually a lot bigger than we wanted it to be, because it should be like 7.4999999 or something, right? But it's like 7.5 with a 9 at the end. Yeah, that seems wrong. Maybe it's related to this weird additional line. I don't know. Let's get rid of that. Let's run this test again. Oh, looks like this is the real answer. That's what it looks like rounded up. Well, what if we do UN256 result down equals mathmas.molwad x comma y console.log result down. Let's see what rounding down looks like. Aha. So this looks correct to us. Looks like my calculator is actually could use a little bit of tuning. I need to use a scientific calculator because it took off the ending inputs, right? It took off the 1 and the 0. So I guess a lesson here is make sure you know your tools, right? My calculator is screwing us over a bit here. But so we got this is what rounding down got us. So rounding up, since we only want to go up by 1, got us this, which is correct. This rounded way the heck up. So it looks like we were adding this extra 1 in here for no reason. And we didn't catch it with our fuzz testing because we didn't do enough fuzz testing. And here's where we run into our first thing that I really want to drive home for you. Fuzz testing is absolutely phenomenal and should be the first step in everybody's test suites. And especially if you're doing an audit or a security review, you want to run fuzz tests. And usually, if you put enough runs in there, you're going to find most of the outliers. However, there will always be a question mark in your brain if there are any bugs left. With fuzzing, you can never be 100% certain that this case always holds. Because maybe there was an example where it only would have worked with this many fuzz runs, and we might have to wait weeks of our fuzzer running for us to actually find a counterexample. Fuzzing will 99.99% of the time catch your bugs. It'll catch your outliers, but it won't be 100%. And that's where form of verification is going to come in. So, but in any case, looks like we found a bug here, right? This is going to be at audit. It's going to be a high. This line is wrong and not needed. So I'm kind of teasing you along to this form of verification thing. But it looks like, okay, we found an edge case with test molwad up where it's not actually rounding up correctly. And we found a unit test case where it indeed doesn't round up correctly. So we found an issue with this one. We can add, hey, at audit, this line is wrong and not needed. The rest of this looks pretty good. So we can continue moving on with our lives. To the last and final function, the square root function. Now, there is a lot of stuff to this function, and doing a square root in Solidity is difficult, and doing it in Assembly is even more difficult. If we look in the mathmasters.t.sol, we go to the base test, we see at the top we have this uni square root, where it's based off of Uniswap, where they do this bit of math here to get the square root. It's got this while loop where they basically keep checking for stuff and keep updating x while x is less than z, and then once that is no longer wrong, it looks like, okay, let's ship whatever z is. And as you can probably tell, doing while loops in Solidity is very gas inefficient. So this is going to be a very gas inefficient function. However, in our math masters, we're doing this square root purely in assembly. So we're going to massively cut down on the potential time it takes to actually get this. And the math that this is using is based off of the Babylonian method for calculating the square root. So you can actually read about this in Wikipedia and all of the math that goes behind it. I'm not going to walk you through the actual math here. If you want to pause the video and actually get a good understanding of how this math actually works, you're more than free to do so. And you would, of course, then be more than free to walk through all this assembly, knowing what you know, because you know what all of these keywords do, right? You know what this does. Okay, we're setting Z to be 181. Why 181? Well, that'll be something in that Babylonian methodology of finding a square root. You know what left shift is. You know what less than is. You know what OR is. It's the bitwise OR. You know what mul is. It's multiply. You know what add is. You know what div is. Sub is. You know what everything in here does, but we're not sure if this actually gets us what we want. Let's look into the fuzz tests and let's scroll down and let's see what they have for testing here. Okay, so cool. So they have this test square root where they have picked some specific values. We would want to double check that these are actually correct. I'm not going to do that in this video. You can, of course, pause a video, and during an audit, I would also check this as well. And then we also have these two functions down here, which are going to be key to solving whether or not this function is correct. So we have this test square root fuzz uni and this test square root fuzz soulmate. So this first one, it looks like we're doing some differential testing here. We're testing our mathmasters.square root compared to this uniswap square root function, which again is in our base test, right? So there's some assumptions here that this is actually the correct square root function. If you want to pause the video and take some time to figure out if this really does return the right values, you can go for it. I'm not going to walk you through that process, but for now, I'm just going to assume that this is correct, right? So if we give this 9 though, it should return 3, right? Then we additionally have this test square root fuzz soulmate, where we compare mathmasters to this soulmate square root, which is also defined in the base test. So this soulmate square root is actually, you can click the link here to see where it's from. It's from the transmissions 11 soulmate GitHub repo, this fixed math.lib, which is what inspired solidity, which is what this whole thing is based off of. But they took a different approach doing the square root function. They also did this Babylonian method. However, they did some is zero, less than shifts. They did some different assembly. So what's happening in our math masters is we're doing all of this stuff instead of all of this stuff, right? And it looks like the second half is actually pretty much the same, right? Math masters looks like the second half is pretty much the same as the soulmate one. A couple things going on here. So number one, we have a function called square root written in assembly, which we need to verify is actually correct. And then for a test suite, we have two fuzzes. We have two fuzz tests. One compares it to the Uniswap square root function, and one that tests it to this soulmate implementation. And if we run our tests, now that we just figured out, our fuzzers might not be so reliable after all, if we go to our foundry.toml, let's not make the runs that big. If we do this many runs and we do forge test, we're gonna have to wait a lot longer because we have a lot more runs, but let's see if we get an error. Okay, we don't get an error here. Okay, well, what if we make it even more? Go ahead and run that. Now I'm gonna tell you here, no matter how many fuzz runs you put in, unless you put it in for like infinity and you get like crazy lucky, it's highly unlikely you're going to find the edge case here. But there is an edge case. There is an issue here. So let's cancel this. Let's go back to this. So we could run this for infinity. We could say, hey, we're pretty sure there's no bug here, but we would never be 100% sure. And with a math function like this, we really want to be 100% sure. Is there a way we can have much higher assurance that these are actually correct? And for this function in particular, I'm going to tell you, I'm first going to teach you the harder way, and then I'm going to teach you the thing that would tip you off in an audit. So we're going to teach you two things. Number one, the harder way, with formal verification. And then we're going to teach you the tip, the hint that should have tipped you off. So we're going to teach you both these, the harder way first, and then the hint. So now guess what? I get to introduce you to this concept called formal verification. And formal verification is going to help us solve whether or not this function is actually correct. Now, to get started with formal verification and symbolic execution, we're going to watch this video excerpt. Now, I will say, if you do not understand everything in this video, that's okay. Using the tools is going to help you learn and help you really see what's going on. The biggest difference to know is that fuzzers will try to do random stuff, whereas formal verification will try to mathematically prove or disprove one property about your system. A square root function does or does not do what we want it to do. So let's jump in. Formal verification is the act of proving or disproving a given property of a system using a mathematical model. Symbolic execution is one technique used for formal verification. Symbolic execution explores different paths in a program, creating a mathematical representation for each path, or more plainly, converting your code to a set of mathematical expressions. Is this the silver bullet for your auditing journey? Let's get froggy. I had the absolute pleasure of interviewing Trail of Bits head of engineering Jocelyn and security engineer from Trail of Bits as well, Troy, about fuzzing, testing methodologies, and importantly, formal verification. I have links to the full interviews with both of them in the description. And in this video, we're going to summarize a lot of that and focus on what formal verification and symbolic execution actually are. But to do that, we need a quick refresher on some of the testing methodologies that we use in Web3. If you haven't seen my invariant testing video, be sure to watch that first before coming here. And to really understand this, you do need at least a high-level understanding of Solidity as well.
What tools do we have in our toolbox to have high assurance about our program?
Layer 1, the unit test.
Obviously, you have unit tests, which is you do a very specific thing like this function does this. And then you start looking at things like test code coverage, like statement and branch coverage. And I think that's kind of the bare minimum.
The absolute bare minimum in security is a unit test. For example, if this is our Solidity and we have a set number function, which should set our number variable to whatever new number is, a unit test would be able to catch this. And if we're using Foundry, we could get an output that looks like this. Some assertion failed, and we can go see our test and see that when we call set number to my number, we assert that we get what we want. And if that breaks, cool, our unit tests have saved us. Foundry, Hardhat, Apeworks, Truffle, Brownie, and all the most popular frameworks have unit tests built in. Layer 2, the fuzz test.
Fuzzing is where you take random inputs and run them through your program. So you have to define things in your code that you always want to hold true.
And fuzz testing is the new bare minimum for Web3 security. Because I decree. And as Troy said, you need to understand the property or invariant of your system to do fuzzing. Once you have your property defined, you throw random data at your system in order to break that property. If you find something that breaks it, you know you have an edge case that you need to refactor your code to handle. For example, if I have a function like do more math, and I know that this function should never return 0, I can throw a whole bunch of random numbers in here to try to get it to return 0. I can have a fuzz test that looks like this, which passes in a whole bunch of random numbers and tries to assert that we never get 0. And we can see from our fuzz test, it was able to pick a random number in order to break our invariant or property. Now, like I said, we recently did a video on fuzz testing or invariant testing, and I highly recommend everybody watch that video because I decree it. Foundry, Echidna, and Consensus Diligence Fuzzer are some popular fuzz testing tools. Okay, what's next? Layer 3, static analysis.
So the things that we've been discussing, unit testing and fuzz testing, are dynamic testing, which dynamic just means like you're actually doing something.
Dynamic analysis is when we run or we execute our code. In unit and fuzz tests, we do exactly this. We are running our code to try to break it. In static analysis, we just look at our code or have some tool look at our code. For example, this code here has a classic reentrancy vulnerability in our withdrawal function. If we run a static analysis tool like Slither, it'll automatically detect, hey, you have a reentrancy vulnerability. And this is great for very quickly picking out very specific parts of your code that are known to be bad practice. Some popular tools for static analysis are going to be Slither, created by the Trail of Bits team, and even the Solidity compiler could be considered a static analysis tool. So now that we have a little bit of a backstory on some of the popular layers of testing and keeping ourselves secure, let's jump into formal verification and symbolic execution now. Layer 4, formal verification.
So on a high level, formal verification is going to be the act of proving or disproving a given property of the system. This is usually done through a mathematical model of the system and the property.
There's that word again, property. You're seeing that almost no matter what you're doing in your testing, you need to understand the properties of your system. And right there, Jocelyn gave us some of the keys between fuzz testing and formal verification. Fuzz testing tries to break properties by throwing random data at your system, whereas formal verification tries to break properties using mathematical proofs. And there are many different ways to do formal verification, such as symbolic execution and abstract interpretation. For this video, we're going to focus on symbolic execution, as that's one of the most popular ways currently done in Web3.
Symbolic execution is then one of the techniques that you can use to do formal verification. Symbolic execution on a high level is going to be a technique where you are going to have your program and you are going to try to explore the different paths of the program. For every execution path, you are going to create a mathematical representation.
Additionally, if you want to learn more about symbolic execution outside of Web3, I left a link in the description to an MIT OpenCourseware video, which does a great rundown of symbolic execution. Now, let's look at Jocelyn's example of using formal verification and symbolic execution. Let's say this is our function that we want to do formal verification on, and we're going to do symbolic execution to do formal verification. Well, let's go back to what formal verification actually is. Formal verification is the act of proving or disproving a given property of a system using a mathematical model. So the first thing we need to do is figure out what we want to prove or disprove. For our demo, we should say our invariant is this should never revert. And that's what we're going to try to prove or disprove. Now, this might seem like a silly example, but you can imagine that this was a function called withdraw money, and you want users to always be able to get their money out, which would seem like a much less silly example. Symbolic execution is going to be creating a mathematical formula for this function f from our code. We're going to convert this function to a mathematical/logical representation of every execution path from our code. Once we have a set of math functions, we can push those into a solver, which will tell us if a property is true or false, or if our invariant is true or false. When we talk about the different paths of our function, we can imagine, okay, one path that our function can take is going to be a plus 1 being returned. That's going to be one of our paths. But we can also imagine that a plus 1 is actually going to overflow and therefore revert. If we pass in the maximum uint256, a plus 1 would revert. So that would be a second path that our function could take. And a symbolic execution tool would find this second path for us programmatically. And then, of course, convert these to a set of mathematical expressions. This set of mathematical expressions might look something like this: a and also not a. Imagine if you ask somebody, can this set of mathematical expressions be true at the same time? The answer would obviously be no. It is impossible for both a to be true and a to be false. This is what our solver is going to figure out for us, but with much more complicated expressions than this. In our example, the solver is known as a SAT solver or an SMT solver. And there are many different types of solvers, but I'm not going to go too deep into that right now. Running our symbolic execution tool, we would see two paths. Our first path going to be if we give it the maximum size of a uint256, we try to add 1 to it, the function will revert. Solidity doesn't allow you to add 1 to the maximum size of a uint256. The other path is anything lower than the max size of a uint256, we'll just add plus 1 and then return. So those are going to be our two paths. Path 1, a is not 2 raised to the 256 minus 1, and then a returns normally, and a is 2 raised to the 256, and it reverts. However, instead of A, B, C, not A, etc., our symbolic execution tool will give us an output that might look something like this. Now, what you're seeing on screen is an SMT lib language. And it's a language specifically made for working with these solvers to solve our mathematical representations of our code. I'm not going to go over too deeply what this is doing, but you can consider this just a list of Boolean expressions, kind of like A and not A, and if A, therefore B, and A, B, and C, etc. Now, if you take this code and paste it into a tool like Z3 or run it locally on your machine, it'll give you an output that looks something like this: SAT and SAT. This first SAT is saying they were able to find an input for path 1, and they were able to find an input for path 2. They were able to satisfy the Booleans in those different paths. Since it was able to satisfy an input for path 2, and we know that path 2 reverts, we know that this invariant is now broken, because our invariant is it must never revert, and our mathematical representation said, hey, I've mathematically proven that there is a scenario where path 2 is executed and your function reverts. So SAT here means we mathematically proved that this invariant breaks. Now, I manually created this SMT lib list with the help of ChatGPT. However, symbolic execution tools like Manticore, HEVM, and even the Solidity SMT checker can give you this SMT output. But all those tools come with a Z3 built in, so they'll even just skip this step and just give you, hey, is my invariant broken or not? Even the Solidity compiler itself can do this entire process behind the scenes. Explore the paths, convert the paths to a set of Boolean, and check to see if those paths are reachable or not. Using the Sol compiler, we can run with model checker engine, and we can look for an overflow in small sol.sol. And if we run this, you'll see the Solidity compiler was able to do symbolic execution to find out, hey, if I add the maximum unit 256 as an input to here, you're going to get an overflow and that function is going to revert. Now, obviously reverts are pretty easy to find, but we could even add assert a does not equal 1, rerun this, but instead of overflow, look for asserts, and we would see that, again, it was able to mathematically find an input to break our assert or our invariant. Said if you add 0, you're going to get 1. Asserts are what you're going to use if you want to use more complicated and more specific symbolic execution rather than just overflow or underflows. A tool like Manticore will also give you an output with the revert, as well as a much more hyper-specific list of SNT lib that it's inputting into its Z3 solver. So a lot of stuff just happened here. Let's recap. We built some Solidity. We understood our invariant, and the next two steps happened at the same time with Solc or Manticore. We used a symbolic execution tool like the built-in one to Solidity to create a set of Boolean expressions that represent every execution path of our code, and then we dumped them into a solver like Z3 to see if our property could be broken. Just by running this one function, Solidity was able to do all those steps behind the scenes for us. We go through a full walkthrough of this example with the interview with Jocelyn, so be sure to check that out as well if you want to learn more. And don't be afraid if this seems a little bit complicated. Be sure to ask questions, leave comments in the descriptions, and leave a like as well. And hopefully I'm going to clear this up for you.
Sometimes the solver might not be able to solve the equation too. Like if the equation is too complex, you usually provide a timeout to the solver just because if you have to invert hash function, good luck to do that with the solver.
Well, so you're saying this isn't a silver bullet for auditing? Like any technology, even formal verification and symbolic execution, abstract interpretation, these are not a one-size-fits-all approach. Using symbolic execution can run into something called the path explosion problem, where there's too many paths for a computer to explore in a reasonable amount of time, and a solver would never be able to finish.
How practical is it to take all these steps? How hard is this to really do?
So there are a couple of things to consider. The first one is that this specific technique, symbolic execution, has a couple of limitations. As you're going to explore the different paths of the program, there is a problem which is called the path explosion problem, which is basically if you have so many paths to explore in the program, it's going to take forever. If you have an infinite loop, this technique requires significant effort to be used. You need to understand how they work and you need to understand their limitation and how to help them. And also significant effort to be maintained. At the end of the day, I think what really matters are the properties. If you want to know if a bug can occur and if the property can be broken, you don't necessarily need formal method for that. And you can use a further, which is way easier to use and provide like kind of the same type of value. Something that is sometimes difficult for people is really to understand how to create this property and how to create invariant for themselves. If someone wants to learn a bit more, we have this website. It's called securetrack.com, where we go over a lot of guidance and best practices, and among other, we have tutorial on how to use Echidna, how to define invariant, how to think about properties.
There's a high skill requirement to using these tools effectively at the moment. People are working on making them easier and easier, like the built-in Solidity SMT checker. However, as Jocelyn's been saying, sometimes a sufficiently powerful fuzzer is all you need. And if you combine a fuzzer with a symbolic execution backend, the fuzzer can pick better random numbers based off of the symbolic execution. And maybe you can find all the answers you need without having to do a formal verification test suite. And the most important piece here is that even this isn't a guarantee your code is bug-free. All it does is mathematically prove your code does that one specific thing correctly. I'm hoping as AI takes off, doing a lot of this will become much easier. And I guess we'll have to see. But the takeaway from this is that you should become a stateful fuzzing wizard. Thanks all for watching. Be absolutely sure to go watch the interview with Troy and Jocelyn, links in the description, and we'll see you next time. Now, that's a lot of information to take in. So to get started really feeling what this formal verification looks like, we're going to go back to this SC exploits minimize side tangent for a bit, where we're going to actually write some formal verification tests, see some formal verification tests, and then, of course, compare them to fuzzing. For those of you who don't know, this is a repo dedicated to minimize smart contract exploits, different ways to test for them, different ways to look for them, different remix examples that you can play with, and then of course the different form of verification and variants that we're going to be working with. So what we're going to do is we're going to go ahead and clone this repo to get started. Now I am going to go back to my opcode FV folder to actually do this. And I'm going to git clone it in here, but you can of course clone it wherever you want. And we're going to be here for a little bit, and I do want you to code along with me. So I would love it if you would clone this and open this up in your text editor as well, because we're going to be here for a little bit. I've opened up this folder, zoom in a little bit, and let's see what we're working with. So in our test folder, we have this folder called invariant break. And this is where we're going to be comparing fuzzing and formal verification. So we have stateless fuzz, we have a stateful fuzz, we have the handler fuzz here, and then we also have a couple different forms of formal verification. So let's go to the README just to make sure that we're going to install everything correctly. Okay, we want to run the make command. This is going to install Foundry. Of course, you'd want to look at foundry.toml to make sure FFI isn't on in here. It's not. Hooray. We're installing everything. We're compiling everything. All right, cool. And this warning is expected because we're showing that self-destruct is actually bad. But great. So what we can do is we can actually go to SRC and scroll down in here to invariant break and check out this readme.md. So this readme in here is going to talk about different invariants, some different videos, and some different types. We have stateless fuzzing, which you should know about, stateful fuzzing, which we should know about, stateful fuzzing with a handler, which you should know about, and then finally, form of verification down here, which you can actually read to learn more about form of verification if you want some more written explanations. This will, of course, additionally be in Cypher and Updraft. Like I was saying before, we're not going to learn the SMT language, but essentially whenever we run a form of verification tool, we convert all of our solidity or all of our form of verification writings into this SMT lib, which then gets dumped into this SAT solver. For now, I would say ignore learning all this. Just kind of think of the form of verification as compiling down to this black box that just tells you if it's true or not. If you really want to learn the SMT lib and all this low level stuff, you're absolutely more than welcome to do that on your own. The pros of form of verification are we can be 100% sure that a property is true/false. The cons here, as you'll see, is it can be very difficult to set up. It actually doesn't work in a lot of scenarios. The tools can be very slow, and it can give you a false sense of security that there are no bugs. Formal verification can only protect against one specific property, and if you code it wrong and you think you're good, well, then you can think that you're actually protected when you're really not. So let's get started though by doing a little refresher here. So in our SRC, we have this stateless fuzz catches.sol. So in here, we have this function doMath, which all it does is it says, if my number equals 2, return 0, else return 1. And we have some variant, this should never return 0. At this point, you should be able to tell, okay, if I throw enough random stuff at this, we'll eventually find my number equals 2. We'll find this edge case where it returns 0, and boom, we've broken our invariant, right? So this is pretty easy. We can write a stateless fuzz test form. So if we go in tests, invariant breaks, stateless fuzz catches test.t.sol, we can run this test here, forge test --mt, paste it in, and you'll see it'll pretty quickly find the bug, right? Input is 2, boom, bug found. So cool. So fuzzing is the best and we don't need to go any farther. Okay, well, not so quick. This is what I like to call like level 1, stateless fuzzing. Okay, let's move up to level 2, stateful fuzzing without a handler. Okay, so we have this new contract here, stateful fuzz catches, where our invariant is do more math again, should never return 0. Okay, pretty simple. However, stateless fuzz will actually never catch this issue. If we look at this do more math again, we see it takes an input and we go, hey, we can still use stateless fuzzing on this. We can just throw a whole bunch of random stuff at do more math again. Well, stateless fuzzing actually won't catch the issue here. In order for this to return 0 and break our invariant, we actually have to call this function change value. So a stateful fuzz is a better solution here. And we can actually see that if we scroll down to our tests. Let's go to stateful fuzz catches.sol. We scroll down in here, we can actually see if we try to do a stateless fuzz, ready? Forge test --mt, paste this in. This is the version of a stateless fuzz, it'll pass, right? And even if we go into foundry.toml, we can kick this up to as high as we want. It will never ever find a counterexample here. But if we scroll down, we can look at the state full fuzz example, right? It's going to make a whole bunch of different calls to this contract. It'll call change value, do more math again, and it'll eventually find the invariant break where it returns 0. We do forge test --mt, paste this in here. Oops, sorry, I got rid of it. State full fuzz catches. That's this one right here. And boom, we find a path here. Now, Foundry kind of went crazy with the path here, but we found a path, right? Essentially, all it needed to do was call change value and then do more math again, right? But it gave us kind of this wild output. Why? Well, this was the first sequence that it found, right? It only ran like 3 times and it found the sequence. So it found the sequence pretty quickly. So, okay, hey, Patrick, I hear what you're saying about formal verification, but fuzzing still seems like it's the bee's knees. Well, okay, well, there's some areas where our stateful fuzzing, just an open stateful fuzzing like this, isn't good enough. And we're going to have to narrow down our random environment. And this is, of course, where using a handler comes into play. So if we scroll back up to our examples, get rid of these, we go to the handler stateful fuzz catches.sol. We have this invariant. Users must always be able to withdraw the exact balance amount out. We have kind of this more complex contract in here. If we scroll down to handler stateful fuzz, we go to invariant fail.t.sol. If we scroll down in here, this test invariant break hard, this is an example of stateless fuzzing, which of course won't find it. And then even if we run our stateful fuzz testing, it still won't find an edge case because there's just way too many possible inputs. You can go ahead and uncomment this and run this to give it a try. But this is where our invariant.t.sol comes in. This uses a handler, of course, which cuts down on our number of inputs to just these 3 or 4 different functions that we can call, and it'll find the bug. If we run this invariant, if we run this test here, pull this up, forge test --mt, paste this in. And it's going to take a lot longer because there are a lot more scenarios it needs to walk through. After a while, it does indeed find a scenario where it breaks. Again, the sequence is kind of wild. And if you break this down, it's only a few function calls that actually breaks it, but we do find the actual issue. So you might be saying, hey, Patrick, I hear what you're saying about this formal verification thing, but it looks like fuzzing is the bee's knees. What are you talking about here? But all right, finally, let's move to our formal verification example where fuzzing fails. But I do want to just remind you that fuzzing most of the time will find your bugs. 99.999% of the time, fuzzing is probably all you need. But there's that 0.0001% of the time that it doesn't find your bug that terrifies us. Because guess what? Oftentimes, that 0.0001% of the time is the bug where somebody can steal all the money out of your protocol. So whereas fuzzing can find bugs right away, fuzzing does not give you the assurance that you're 100% scot-free. Formal verification can give you the assurance that a single property is 100%. Now, there's a link to this tweet by Zach Obrunt where he goes over how he actually ran into a scenario where even when he cranked the Foundry fuzz runs up to a crazy number, it still didn't find the bug until he cranked it even farther. This would have been an example where he could have saved hours and potentially days of headache by just doing formal verification. He was pretty sure there was a bug, but he couldn't prove it. So we had to just keep iterating, where formal verification found the bug, but everyone else just assumed it was good because a ton of fuzz runs were passing. Definitely check this out if you want to see a real scenario where the fuzzer was saying, hey, this is good, and formal verification would have caught it. The Certora tool additionally has a number of case studies where they were able to find really bizarre edge cases that could have potentially broken massive protocols and stolen all of the money out of these massive protocols. So be sure to check out Certora as well if you want to see more cases where formal verification actually found these crazy edge cases and saved a protocol from being destroyed. There's a phenomenal lecture by Certora's CEO, who, as a formal verification expert, gives us his walkthrough of what formal verification is and what it looks like. If you want to learn more about formal verification, highly recommend you pause and watch this video. A link to this will be in the GitHub associated with this course. So let's look at an example here where a fuzzer might give us the false impression that there are no bugs. And we actually saw a little bit of an example of this in the Math Masters. Our fuzzer originally said, hey, your code is good. It was only when we increased the number of runs that we actually found a counterexample. However, one could argue that we got lucky that our fuzzer actually found the counterexample in the number of runs we gave it. There's a chance that even if we give it 1,000,000 runs, that wouldn't be enough, right? So we go into our SRC, we go into this formal verification catches.sol file. We see an example that I've used in the past, and it is this horrifying monstrosity of a code base. We changed it so that, first off, we said, okay, anytime you see the word add, that's actually going to be a subtraction. Anytime you see the word div, that's going to be addition. Every time you see mul, that's going to be division. And then sub is multiplication. So we already see some nonsense. So these are going to be some functions for the different integers. However, these different functions are actually also wrong. So we said using add as subtraction. However, add wraps up an int and then divides. So none of this makes any mathematical sense in the history of math. This is absolutely cursed code. And the purpose of doing this was just to make it harder to manually audit. You might be saying, hey, Patrick, no realistic code base would ever have something as stupid and ridiculous as this. And to that, I would counter with, you probably haven't read the make or die code base yet. Subtle dig at the naming conventions that they use. Anyways, then we have the actual contract. And we have a bunch of storage variables with variables all named slightly the same, but not. And then finally, we have our wonderful function called hellfunc with our invariant that this function must never revert. And it just does absolutely nothing that makes any type of sense and would make any manual auditor cry. Now, yes, okay, you could probably realistically do some manual auditing in here, and because we only have so many numbers, but the gist is this is supposed to represent a function that's really ridiculous to manually audit. The square root function that we're going to go back to really is kind of ridiculous to manually audit, but it's all good. This is going to work as a perfect example here. This is what we want to test for. And if we scroll into our formal verification bit, we have this code base where fuzzing fails. We don't need to do stateless fuzzing in here because there's nothing that can access or change state. We only have one function, so we can use a stateless fuzz for this. So pretty simple. The invariant is this function must never revert. So we have a test here, which calls it, and then we just assert that the function didn't revert, right? Pretty simple. Let's run this test. And it says it passed. Now, of course, in founder.toml, we could probably bump the number of fuzz runs up to a number where it eventually does find the counterexample. But for the sake of the course, let's pretend that, we tried 10 million bazillion runs and it wasn't able to find. That is what we're going to be working on here. Now, to get you started, we're going to watch another little excerpt where we do a little bit of a formal verification speed run, and this will show you approximately what using each one of these tools looks like. So let's go ahead and watch that. Formal verification is the process of turning your code into math. You can sort of think of it as unit tests on roids. And for the longest time, this skill was solid off to the gigabrains of Web3. But now, the tools are becoming more and more usable. It's important we get better at formal verification, because if you mess up your smart contract, you lose $500 million. So I'm going to show you 3 formal verification tools that we can use very easily to demonstrate formal verification skill. I have specifically crafted this function to be hell for any manual auditor and would give even Milo Truck a heart attack. First off, it uses adds for subtractions, divisions for additions, multiplications for divisions, subtractions for multiplications. And then we have functions which wrap our integers, a function add, which actually divides, even though add up here says subtract, and all of these functions are wrong. But you think that's bad? Right in the function, we actually have a few variables, number, which all look very similar, but are all slightly different with a slightly different number. And then finally, we have our function hellfunc with an invariant. This function must never revert, which just does all types of nonsense. So as an auditor, to figure out where this function reverts, you could 100% walk through it manually, but I'm going to show you where formal verification is a much better way. First off, let me show you that fuzzing actually doesn't catch this. So we have a test here where we're just doing a static call to this function, and we're asserting that the function does not revert. So if I run this test in our terminal here, with 250 runs, we actually do not catch the issue. In fact, if we go to our Foundry TOML and bump the number up to 1,000 and then we rerun the test, we still don't catch the issue. Our first formal verification test is going to be with Halmos, where we can actually take that exact same Foundry fuzz test that we just run and just slap Halmos on top of it, and it'll run formal verification on that Foundry fuzz test. We just run Halmos -- function and the name of the fuzz test that we want to do formal verification on, and Halmos is going to automatically convert this into math and then solve. And boom, after maybe about 20 seconds, we get the counterexample. We get the counterexample where the number 99 is actually the issue, and this is correct. Our formal verification was able to find the bug. Next, control. The test looks exactly the same as the Halmos / Foundry test. The only addition is we've added this KEVM.infinite gas cheat code. To run control, we first need to build all of our contracts with recompile with a K and then prove it. So we're going to run that. And while this is running, it might be a good idea to go get a coffee or go for a run.
A few inches later.
Once it's built, we can run the control prover, which again, you might have to go take a nap for. Then after you run the model, you can actually view the nodes and view the models and look into where it failed or where it passed. And then finally, Certora. For Certora, we actually have to take a step back and use a special language called CVL, designed specifically for formal verification. We create a rule / invariant saying healthfunc must never revert. We add some requires to tell Certora to not randomize storage. We say, let's call this function and assert that it never reverted. We then can run this Certora command with Certora run, and we're going to get this beautiful output with a UI to actually show us what happened in this formal verification run. And oh, job completed. View the results here. Oh, we found an error. So let's go ahead and click on this and let's see what this looks like. In the Certora UI, we can click on this. We can hide a lot of these issues here, and we can go right to the variables and see, number 99 causes to fail. We can click on the exact run that it used right here and see why it failed and see, yeah, sure enough, 99 is the issue. Thank you for finding this for us, Certora. You can find all the code for this in the Cypher and SC exploits minimized. Go to test, variant break, formal verification, and see the Halmos, control, and Certora, and then additionally the where fuzzing fails and doesn't catch this. This was a speed run of formal verification. You now can tell your friends you have the mathematical power to convert code into math. We've shown that fuzzing fails or doesn't give us enough assurance. Let's finally move on to formal verification. And in this code base, we have a couple different examples. I'm going to be showing you two of the tools, Halmos and Certora, and then some of the trade-offs of each of them. Now, I'm not going to show you control simply because the API for Halmos is basically the same. Halmos is a lot faster, and installing and waiting for control to run can take a really, really long time. But huge shout out to the runtime verification with helping me understand a lot of the formal verification stuff that we're teaching here. So definitely recommend you check them out after taking this course if you want to use the control formal verification tool with your code bases or with your audits. Now, so that you can actually write these along with me, what I want you to do is I want you to select all of these, the Certora folder, Halmos, and control, and then delete all of them. And we're going to write these formal verification suites one at a time, starting with Halmos. So let's go ahead and get started. We're in our invariant break formal verification folder. Let's create a new file in here called Halmos test.t.sol. And this is where we're going to write all of our code for Halmos to actually formally verify whether or not our code has an issue. The cool thing about Halmos is most of Halmos is actually going to be regular solidity and works really, really well with Foundry. So you'll notice we almost don't do anything different. So we're going to go ahead and we're going to import test from forge.std test.sol. Contract Halmos test is test, like this. And then we need to import the file we want to do formal verification on, of course. So we're going to import formal verification. Oops. I'm just going to open it up and copy the name because I named it this horribly long name. Okay, formal verification catches like this from .. /src/ invariant break / formal verification catches. That's all. Let's do a little toggle word wrap. Okay, cool. Now we're going to have this formal verification contract FVC. We'll do a function set up like this, public, and then we'll just say FVC equals new form of verification catches. Thank you, GitHub Copilot. And so all this is doing, as we know, is just deploying this contract so that we can call that HELFUNC function. Now down here, we're going to write a test. We're going to pretty much write the exact same test that we did for Foundry. The way Halmos works is that requires are going to be considered preconditions. So if you have like a require X, Halmos will say, okay, assume X about the run. So you can't run like assume X, like, right? Like this would be valid Foundry, but not Halmos. And there's a lot of little quirks like this to keep in mind when working with Halmos. For Halmos, all it cares about is asserts. So if you say assert X, this is all Halmos cares about. If you do not have an assert, all it wants is asserts. So you must have an assert. But we could write function, test, blah, 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 whatever. I like to do function check and then like the name of my form of verification, just because having check at the beginning tells me, okay, this is different from the Foundry test suite. This is a formal verification test instead. So I'm going to do test HELFUNC doesn't revert Halmos. And then same thing, we can add, a uint, let's do a uint 128 num, just so that we don't add too big of a number, public view, almost the exact same as what our fuzzing looks like so far, right? So this normally in Foundry is going to be fuzzing. So in Halmos is going to take this num, compute it to a mathematical symbol, and you'll see what I mean in a second, and use that to come up with some equation to prove or disprove what we want to do here. So now we're going to say bool success, comma, equals address FVC static call abi.encode with selector hvc.helfunc.selector, comma num. And this is how we call our HELFUNC function with num as an input and get whether or not it passed right here. And then we're just going to say assert success. And that's it. Now we do have to install Halmos, but this is your entire Halmos test. Crazy, right? It looks just like Foundry. So what Halmos is going to do, unlike what Foundry does, is Foundry goes, okay, random num1, random num2, random num3, and so on and so forth, and just keeps trying random numbers, okay? What Halmos does is Halmos goes, okay, let's convert this HELFUNC function into some math expression. So you can almost think it like f of x equals not revert, which sounds crazy. And this is why Halmos might take a little bit longer than running a fuzzer or running with Foundry. And since this is what our invariant is written in this check here, it's going to look for a mathematical proof that the function will or can revert. And this is kind of the black box magic of using formal verification, is that essentially under the hood, this is what they're going to do. And it takes some time of tinkering with these tools and playing with these tools to really understand, okay, where is this not going to work? What are the limits of using this tool? Because as we said earlier, it's not a silver bullet. It doesn't just work everywhere. Now to get started with Halmos, we can come to the Halmos documentation and we can scroll down and we can actually get started here. Now, as you can see right away, we have some tooling you might be less familiar with. We see pip install Halmos. So in order for you to work with Halmos, you do need Python installed. I'm not going to go through the Python installation with you here because it can definitely be, because like I always say, installing tools is one of the most difficult challenges in all of software engineering. There are tons of videos and tutorials out there that will teach you how to install Python. And it might take you a while to install Python, but I highly recommend it because there are a lot of tools, Slither included, that only Python works with. You'll know you have Python installed if you can run python 3 -- version, get an output like this. Python usually comes installed with pip. If pip works, and you can see if pip works by running pip 3 -- version as well. This again is where AI buddies come in great help because AIs are great at helping debug why your installations aren't working. I additionally highly recommend you Windows users install Python in this WSL environment because otherwise you're going to run into a lot of weird stuff. Get Python installed in a Linux-like environment so that you can use these tools. Once you have Python installed, you can run pip install Halmos, Or the way I prefer to do it is pipx install Halmos. Pipx is a tool that puts packages in their own virtual environments so they don't clash with other environments. That's a whole nother concept. But if you want to not run into a lot of weird installation stuff, I highly recommend you install pipx and install Halmos with pipx as opposed to with pip. But that's just my take. Again, installing pipx is another thing you have to install. So this can be kind of a pain in the butt. But if you install Halmos with pipx, personally, I think you will have a better time. It might be a little tough to install pipx for you. I'm actually going to install it here with pipx install Halmos. Again, pip or pipx, both work fine. I prefer pipx. Now I can do a Halmos -- version, and we'll get an output that looks like this. Again, please be sure to use their GitHub if you run into issues, their community, their Discord, etc. If you run into issues with Halmos. The A16Z team and the Halmos team are incredibly responsive and great to work with. So now that we have Halmos installed, we can actually run the Halmos command on this test, which again looks pretty much exactly like the fuzz test. To run it, we can do Halmos -- function and then paste the name of our Foundry function. And you'll notice that you're actually going to be sitting here waiting for a bit. Why? Well, here's one of the cons of formal verification. They take a lot longer to run. Although this was actually crazy fast. So this was our output here saying, hey, there's a counterexample. If we put 99 in here, it actually reverts. And we can now write a unit test where we just copy paste this whole thing, paste it in here. Instead of num like this, we could say test like this. We'd say uint256, or excuse me, uint 128 num equals 99, because that was the counterexample it gave us, like this, 99. And we can now run this unit test with the counterexample that it gave us. Forge test -- mt, paste that in there. And we see reason panic assertion failed. This did not succeed, it actually failed. And if we go back to the actual code base, we scroll around in here, we'll see there's this tiny little bit of code right here where it checks if a number is greater than 88, does a little unwrap, +3, does some division stuff, and the bug's over here. So if we comment these out and we rerun the test, it should actually pass now because we've removed the bug. Ta-da, and it sure does. So Halmos was able to formally prove that this invariant doesn't hold. And if we do Halmos -- help, we can see a ton of different flags that you can actually run with Halmos. It's because when doing this mathematical conversion, it's literally taking this function, converting it to math, and then trying to prove. And same as working with like a handler, maybe we want to restrict all the different inputs it needs to think about, or how long you want to wait for. A common input that you might use for your solver is to increase the timeout. There's a 1,000 second default timeout assertion. If this takes longer than 1,000 seconds to solve, move on. And a lot of times if you're going to run Halmos, you're just going to crank this up way higher so that it takes plenty of time to actually run through this code base and solve it. The Halmos code base has a really cool getting started guide where it teaches you about working with Python, writing a setup function, some other ways to actually work with Halmos, some easier examples as well. And it also talks about using this SVM cheat code, which is a symbolic cheat code that generates a new symbol of type uint256. So in our example here, we have uint256 num as a fuzzing input parameter. What this really does, since we ran it with Halmos, is it uses this num as a symbolic parameter. When it creates this math equation on the back end, it uses this num thing. Now, Halmos is really cool because of how quick it is to use, how easy it is to use with Foundry, and how powerful it is for a free tool. However, it still has its limitations. There's some assumptions that gas isn't an issue. It isn't as flexible as a tool like Certora, where we're going to go over later. It doesn't give you a UI, and there's a lot of information that can be a little bit difficult to extract from Halmos. But I love showing Halmos because of how easy it is to write some of these simpler assertions here. Once we get more complex, that's when we're going to move to like a Certora, where we have a lot more flexibility because we have a whole nother language. But congratulations, you've learned Halmos and how to write a very minimalistic Halmos form of verification, right? It looks almost exactly the same thing as a fuzz test in this example. However, it's converting this assertion to a formal set of Booleans, a formal mathematical expression, and then trying to solve. So even though it kind of looks the same, what's going on under the hood is completely different. I highly recommend you play around with Halmos, especially with this example, to see if any of your theories work or not. Okay, well, what if we did require success? Would that pass? What if we tried to use some SVM? What if we said like svm.create uint256 or whatever the API is, num or something like that, right? Play around with it, tinker with it, and then once you feel like you've tinkered enough, let's move on to getting introduced to Certora. So now that we've gone through the Halmos example, which was a real quick foray into formal verification, let's now move over to Certora. So Certora is a cloud formal verification tool and one of the sponsors of this course as well. And two of the biggest benefits about Certora is the fact that you can run these incredibly long processes in the cloud. You have way more flexibility with the Certora prover, and we additionally get a whole new language to write our formal verification proofs. We use the Certora verification language, or the CL as it's often abbreviated, and it allows us to make very fine-grained invariants and rules for working with our smart contracts. And it doesn't just do unit tests or fuzzing tests, but it mathematically proves every one of our rules or invariants about our protocol. Like I said, this still isn't a silver bullet. However, it will give us that assurance that a fuzzer cannot. A fuzzer can give you 99.999% assurance. This is the final 0.0001% to make sure that we don't have that issue or that bug. So to get started with Certora, we're actually going to get started for free, and we actually have to sign up. Certora runs on this freemium model where you can run the Certora for free up to 2,000 minutes per month. So we're going to go ahead and sign up. And if you could do me the biggest favor, like I said, Certora is one of the sponsors of this course. If you could just click this link, Certora sign up here. This is our affiliate link. It'll tell Certora that you actually learned about Certora through Cypher and Updraft. And if you like these tutorials, this would help support us to keep making more tutorials in the future. So please go ahead, click the link from the Certora sign up page to tell Certora, hey, Cypher and Updraft taught me, brought me here. Thank you so much. It would help us out an absolute ton. And this link is in the Assembly EVM opcodes GitHub repo associated with this course. There's this, if we go to the section 2, the Math Master, click the Certora sign up. That'll tell them that we are the ones who got you signed up, and that would be phenomenal. So go ahead and get signed up. Once you're signed up, you will have to check your email for a verification link to get verified. And once you click it, you'll get a little pop-up, email confirmed. Close this window and check your email for login details. And in your email, you'll get an email that looks like this with a temporary password and a Certora key. So this is your Certora key, just like an Alchemy API key or Infura. You don't want to share it. Obviously, you want to reset your password. And this is the API key that we're going to be using whenever we run the Certora prover. So we're going to grab this, and we are going to pop into our VS Code here. We're going to go back to the opcodes.fv. We are going to create a little .env and just paste this in here for now. As you know, I hate .env files, so just put this API key someplace safe. Luckily, it is not a private key. There's no funds associated with it, so it's not the end of the world if it gets leaked. But ideally, you don't show this to anybody. Then we can go ahead and click the login button, and we will actually log into the prover itself, where we put our email and password, and you'll be prompted to create a new password. And then you'll be signed into the prover that looks a little something like this. There's a whole lot of nothing here, of course, because we haven't run any jobs yet, but we will very soon. So now that we're signed up, we have our API key. Let's go ahead and let's write our first Certora formal verification proof in the CVL language. Now this is going to be a minimal one, a minimal example with this hellfunc function still. Then this is still going to be this minimal one from this hellfunc function. But once we learn how to use the Certora prover, we're going to go back over to Math Masters, use our newfound Halmos and Certora prover powers to actually formally prove that there's a bug in that square root function. So let's go ahead, let's get started writing this formal verification test suite for Certora. And if you want to, the Certora documentation also brings you through some tutorials if you want to follow along with them, and everything you need to know can be found in the documentation associated with Certora. And to get you started, we're actually going to give you almost the exact same setup to run Certora formal verification tools as some of the giant protocols like Aave use to run these. Typically, they have a Certora folder at the root of their project, and they have at least a specs folder and some other folders depending on what they need. We can go over harness and scripts in a little bit. But for us, we're going to go ahead and we're going to go down away from SRC into the invariant break formal verification folder, create a new folder called Certora. Like I said, normally this will actually be at the root of your project, but for this one, we're going to have it in this invariant break folder. Now to get started with Certora, the most important thing is going to be one of these specs. So you see this specs folder in Aave, it has this atoken.spec, and it's got a whole lot of stuff in here. These spec files are where we're going to write our invariants and our rules, and I'll explain what these are in a minute. So for us, one of the first things we're going to do is we're going to create a new spec folder where we're going to write our first spec. Our first spec, we're going to create a new file called fvcatches.spec, like this. And to get these to have some really nice syntax highlighting, you get this little fun thing if you're using VS Code. There's a Certora verification language extension. There's also a Certora IDE. I'm just using the extension here, which formats and adds syntax highlighting to our .spec files, which is really nice. So in here, sort of like how we did with Halmos, where we defined a function to actually test, to actually formally verify our code base, this is where we're going to define a rule or invariant to formally verify our smart contract. Now, unlike Halmos, Certora actually uses its own formal verification domain-specific language called the CVL language, or the Certora verification language. We use this language to write our formal verification rules in our .spec files. You'll see that the CVL language is very similar to Solidity with some additions. So let's just write at the top what we want to do. Well, we want to test the invariant here, hellfunc must never revert. That's all we want to do. We have this Solidity code base. We want to prove this hellfunc must never revert. How do we write that out in Certora to actually test this methodology? And as we're working with this, we're going to be running the Certora prover to see how it handles different inputs, and so that we can learn more about the outputs and how it actually works. So if you go to these Certora documentation, we're in one of these specification files. There's a whole lot of stuff that we can define, but the two most important ones are going to be our invariants and our rules. And these are slightly different, and we're just going to get started with rules. So rules are the main entry points for the prover. A rule defines a sequence of commands that should be simulated during verification. So a rule can be thought of do X, Y, and Z and prove A. So that's what a rule is going to be, and that's what we're going to start with. Whereas an invariant is slightly different. Invariants describe a property of the state of a contract that is always expected to hold. So invariants are actually a keyword in Certora. So whereas our invariant that the hellfunc must never revert is an invariant, we can actually write this invariant as a rule or an invariant in Certora. So a little bit confusing, but this is our invariant. In Certora though, it says if you do a bunch of stuff in a row, that's going to be a rule, whereas an invariant is just going to be some property that must never revert. So an invariant is a little bit simpler, where it just says at any state in the contract does X hold, or I should say does A hold. So they can be seen as really, really similar, and you'll see as we kind of play with them that they are a little bit different. But basically anytime you want to have some preconditions and you want to do some stuff to check if something works, it's a rule. And anytime in Certora, you want to say, hey, does total supply only go up? Is the total collateral greater than the minted amounts? Just one single thing that you can look at anytime in the lifespan of the contract, does it hold? According to Certora, that is an invariant. For rules, rules are like, okay, if it's Tuesday and it's raining, X should always be 7. Technically, that's an invariant, but to Certora, that's a rule. So hopefully that makes sense. Invariants are kind of one property, one state that we're checking. A rule can be conditionally, this property should hold. So hopefully that makes sense. But we're going to focus on the rule to start with. So the first thing we need to do is we need to, tell our spec about the contract we want to formally verify. So how do we actually even do that? So we haven't written anything yet, but our code base needs to know, hey, this is the contract that we want to actually work with. And this is where we're going to create our second folder called the conf. Now, when you actually run the Certora prover, and we'll install this in a bit, you're going to use this Certora run command, and you can do all these input parameters. I'm not exactly sure what they are, but it's like file, blah, 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 whatever. We don't want to have to write 100 commands on the command line. So we just add all these flags that we want to use into a comp file. So we create a new file called fvcatches.conf. And this is pretty standard for most Certora projects as well. They have some type of configuration file with all the parameters that they need. So in here, we're just going to say, okay, files are going to be, and we have a little list of the different files that we want to pass to our spec. So the only file that we want to pass is ./src/invariant break, because we're going to run this from the root directory. So we do ./src /formal, oh boy, I spelled this right, verification catches.sol, like that. There's going to be a whole bunch of other flags that we put in here, but this is how we get started. Then we have to tell Certora what we actually want to verify. So we have this verify keyword, where we're going to say, we want you to verify formal verification catches. So we put formal verification catches, we put a little semicolon here, and we say, we want you to verify formal verification catches, and we say what spec we want it to verify on. So we do ./test/invariant break /formal verification /Certora/spec /fvcatches.spec. Hopefully I spelled everything right. And if not, we'll find out very soon. There's going to be some other commands we're going to add in here as well. But with just these two lines, we're saying, hey, these are all the files that you need to know about. And this is the file that we're verifying, this form verification catches.sol, and we're verifying it with this spec. So now we know that we can write our first rule. So we just use the rule keyword, and we'll say the health func must never revert, right? Because that's our invariant. And similar to like a Foundry test, we have input parameters. Similar to a fuzzer, we say, okay, uint 250 or uint 128 num, like this. Boom. So we have our rule, health func must never revert, and we're saying no matter what number we use as an input parameter, this health func should never revert. And remember, because this is formal verification, it's not going to throw a bunch of random numbers. It's actually going to turn this number into a symbolic expression, which conceptually is hard, but just remember, it's going to take our code, convert it to math, and this number is like some x plus y equals z or something, right? So this is going to be turned into a mathematical expression. So we want to say, no matter what number we use, health func must never revert. How do we actually figure out if something reverts? So similar to Halmos, Certora works with the assert command. So if I say assert true, like this, full semicolon, this should pretty much pass because it's trivial and really dumb. But I'm going to leave this as our rule for now because we're going to run this just to show you what an output will look like. So let's go ahead and test running our very stupid rule, assert true, that should pretty much always be true no matter what. So we're going to come to Certora, and we want to install the Certora CLI. And there's a link to this in the GitHub repo associated with this course, but we want to install the Certora prover package. It's this pip install Certora-CLI like this. Again, it is a Python package, very similar to Halmos. Ta-da, surprise, surprise, like I was saying, you pretty much are going to need Python. You're going to need pip3 to work with these Python packages because Certora is also a Python package. Like I said, I prefer to install my stuff with pipx, but you can use pip3 if you like, whatever you want to do. So for me, I'm going to run pipx install Certora CLI like that, but you can run pip, whatever you want to do. Like I said, I prefer pipx because it puts the Certora CLI in its own isolated virtual environment. Now that we've installed the Certora CLI, we've given our shell access to these three commands: Certora EQ check, Certora mutate, and Certora run. So now I should be able to do Certora run --help and get a crazy output that looks something like this, right? Or better yet, Certora run --version. And this will give us the version edition of the Certora run CLI. And that's the most important thing that we need. Now that we have the Certora CLI installed, we need to now export our Certora key as an environment variable. So to do that, we can just run this command, export Certora key equals, and then put your key. So we can do export Certora key equals like that. Now this has to be a Linux-like environment like WSL, macOS, Linux, etc. in order for this to work. You can also do like vim.env and then export Certora key equals like this. Right, quit it, and then do source.env. Those work as well. Just remember, every time you delete your shell, you're gonna have to rerun this. You'll know you've done it right if you can run echo $Certora key, and you see your key is printed out to the terminal like that. Once you have the Certora CLI installed and you have your key as an environment variable, you'll also need to install Sulk Select. This is something I talked about before. Sulk Select is a wonderful tool from Trilobits that allows you to switch between Solidity versions and gives you access to the Sulk command line command. I have my Sulk Select once again installed with pipx. And if you run Sulk Select --help, you'll get an output that looks like this. This is so that when you run your Certora CLI, it runs with a specific Solidity version. Right now, if I do Sulk --version, I get 0.8.20, but I could do Sulk Select, use 0.8.7 like this, and it will switch to 0.8.7 because I already have it installed. If you don't have installed, you would need to do Sulk Select install, maybe like 0.8.23, and it'll install it. And then you can use 0.8.23. If you don't have it installed, it'll say, hey, I don't have it installed. You need to install it. So I'm going to switch back to Sulk Select, use 0.8.20 so that our Certora CLI uses 0.8.20 for all of its runs. You can also use the Sulk binary. However, I highly, highly recommend doing Sulk Select. That way you can easily switch between Solidity versions when you're working with this or any other tool that needs the Sulk compiler. Absolutely love Sulk Select. Step 5, we already have that set up. Great. So now that we have everything set up, if you're following along with the docs, we actually have this running the Certora prover where it gives you all this stuff. You can run your Certora prover, all your commands right through the command line. However, we're going to do everything through the comp file. So what I'm going to do, I'm going to pull up the terminal. Now that we have our fvcatches.conf and .spec. So we're going to do Certora run./test invariant break formal verification Certora fvcatches.conf. So you just do Certora run and then your config file, and that's all you need. What's going to happen is we're going to connect to the Certora cloud provider, and we're going to get access to this URL, which we can click, open up, or command click and open up, or copy paste, or whatever you want to do. And we will see our formal verification of this rule happening in the cloud. And after we wait a little bit, we'll see what the output looks like. And after we give it some time, we'll see this is the output that we actually get. So let's do a little walkthrough of what we're seeing on the screen here. So we have our rules, which we can see in the tab in the top left. And we can see the different rules that have passed and their status in the rules section. We see a little check mark here because our health func must never revert was indeed verified. If we click on our actual spec, we can see the actual spec that was used to verify this run. We can see the different files that were run in this as well. For us, we only had formal verification catches.sol, and we had our fvcatches.spec, our conf, and then of course the run.conf, which is essentially going to be the same as our actual conf, but Certora just basically added this process EMV in here. So we have rules, the different files that were sent here. We can see our contract call resolutions, which there was nothing for this, and we can see the actual contracts. There's only one contract in here, formal verification catches with one method. Typically, when you have a rule like this, you can expand the call trace to see what happened in the call or what happened in the rule. But since ours is just assert true, nothing happened. It just said, okay, assert true. Yeah, that passes. So, so not a great use of a run here, but I just wanted to show you what it looks like when you do get a run and do basically like a sanity check. Okay, let's just see what happens when we do a run at all. So this is what the UI looks like. We'll see what a real run looks like in a second, but glad we did that sanity check. And this is what you should see in the terminal output. Okay, cool. Now, the other thing is writing this kind of massive terminal command is going to be a huge pain in the butt. So what we're going to do is we're going to open up the makefile and we're going to scroll down in here. And there's already this Certora keyword in here. So since this is in our makefile, we should just be able to run, instead of that whole thing, we should just be able to run make Certora like this, and it should submit our job and connect to the server and everything. So this obviously is going to be blank again, so I'm not going to run it, but since we have it in our makefile, we can just run make Certora and we will be good to go. Okay, cool. So now that we have figured out how to do just the basics of a rule, let's actually write this rule so that it makes sense. Now on variant here is the hellfunc must never revert, right? So right here, obviously we need to run our hellfunc. So the question is, how do we run our hellfunc? Or how do we tell Certora, hey, in your mathematical craziness in the background, you need to symbolically express running the hellfunc? Well, what we can do, we're going to add a methods block to tell Certora about the different methods that we have. Now, technically, you don't even need a methods block. Certora will be smart enough to know what functions you can call. But if we want to be a little bit more explicit, let's go ahead and create a methods block. And in here, we're going to create a function, hellfunc, uint 128, hellfunc, external, returns uint 256, env free. And this looks real similar to a Solidity interface, except for we have this weird env free keyword. So in the Certora documentation, we see there's the documentation for this method block, which tells us about these methods. And this is considered a non-summary declaration. And there are two types of method or function declarations that you can make, non-summary or summary. For now, just assume that summary declarations aren't a thing and assume that the methods block is almost the exact same as an interface in Solidity. It just tells us what functions are and what they do. The only additional piece that these add is this env free thing. So following the returns clause of an exact method entry is an optional env free tag. Doing this has two effects. First, calls to the method from the Certora verification language do not need to explicitly pass an environment value as a first argument. And secondly, the prover will verify that the method implementation of the contract being verified does not depend on any environment variables. So basically this means there's no message.value, the message.sender doesn't matter, etc. The environment at which this function being called doesn't matter. So now that we have that, we could say hellfunc, we call hellfunc with number like this, and we could get our uint 256 response. And if our invariant was like, hey, this must always be 0, we could say like assert response equals 0. And this would be our whole rule, right? This would be a great example of a simple invariant, but it's not. Our invariant is that it must never revert. So we actually want to do this a little bit different. We're going to do hellfunc at with revert and put a number here. And we're going to say assert last reverted equals false, like this. So this last reverted is a keyword in Certora where it's updated every time a Solidity function is invoked. So basically, anytime you run a Solidity function in Certora, last reverted will be updated with if it reverted or not. So since our rule or our invariant is that hellfunc must never revert, boom, this should be good enough. Okay, we're gonna run hellfunc with revert and it should never revert, right? Boom, this is it. So go ahead, Certora, do your thing. Turn this into math. So let me ask you a question. If we run this, do you think it'll work? Well, let's give it a whirl. Let's give it a try. Let's run make Certora. We'll get the output. We're gonna have to wait a little bit, but let's see what happens after we run this. Get our little job. Let's go see it in the UI, and we'll wait a little bit for it to finish running. After a little bit of time goes by, this is what we'll see. So we'll see, we get a little executed here, and we'll see we have a check mark for this env free func status check, and then a health func must never revert that actually is failed or violated. So whenever we add that env free keyword, we get this env free func status check where Certora actually says, okay, you don't want to use env. I got to prove that nowhere in this function you use an env. And then we have our health func must never revert check. Now, we actually know from Halmos that the answer to this, let's pull this back up, formal verification catches. The answer to this is actually going to be 99. If we scroll down in here, there's that weird area. Okay, I can't find it right now. But we know that 99, right? We know 99 is the counter example. So we know 99 is the counter example. Let's go back to here. What we can do, go back to rules. Sorry, click this rule, go back to the right, either call resolution or variable. And let's go into the call trace. I can actually close the spec as well. And we can see in either our variables or our setup, we can see in the call trace the different steps it actually took to get this failure. So first they set up some global state, then they do a whole bunch of setup, then they actually try to make the call and check the assertion. So for the global state, something interesting happens right away. So we see this number 0 is havoked. And havocking is actually something really important that happens in Certora. In some cases, the Certora prover should assume that some variables can change in an unknown way. For example, an external function on an unknown contract may have an arbitrary effect on the state of a third contract. In this case, we say the variable was havoked. So for us, simply because down here we have these storage states, Certora goes, hey, these aren't immutable, these aren't constant. We do some weird stuff in this code base. These could potentially be changed by interacting with an external contract. So since these could be changed, Certora just assumes they could be changed to anything, and it does what's called, it havocks them. It basically says, okay, well, number could be pretty much anything. So I'm just going to set it to 0 for this run. Even though in our code, we set it to 10, Certora says, okay, I'm going to set that to 0. That's what it did for this global state to get this set up. Then we do this setup here, which we can kind of skip this. This is where this is just some basically boilerplate setup. But then finally, we have this form verification.health func number equals 99. So it actually reverts with number is 99. And we do know that this is the output case. And typically you're just going to want to scroll down to why did this revert if it reverted? Or you're going to want to walk through the call trace to find why some variable got changed in a way you didn't expect it to. Oftentimes, variables getting havoked is going to be one of the most important things to look for. Remember, if Certora is unsure that a variable can change in any way, it will assume that variable can change in any way. And we see we got a revert case on line 76. So if we go down in our code base to line 76, we see that this is the error that it's giving us. So since it havoked number to be 0, so 0 is less than 3. Okay, cool. What is number normally? It's normally 10. So it's saying it havoked number to 0, and then this broke with 99. So we know our edge case is 99, so we might kind of erroneously think that this is correct. However, there's an issue here. It havoked this number to be 0 when it really is 10. So this line normally never hits. So since Certora assumed that these storage variables could be changed in any way, it went ahead and said, okay, well, I'm going to change this to 0. And if I change this to 0, this line hits and the number 99 as an input variable reverts. So even though we got the right revert number, we got the right revert number for the wrong reason. And this is why reading this call trace is so important. And then we can see, finally in the assert, last reverted equals false. We can see the global state of storage, formal verification catches, number, NUMBR was havoked to be 0. And that's how I was able to find this edge case. We can even see on the right side for variables, rule parameter, number was passed in as 99, and that's what caused this to fail. So even though it got the right answer, it got the right answer for the wrong reason, right? It set this to 0 and boom. So we don't want Certora to havoc our storage here. We want Certora to run as if storage cannot be changed, right? Because as we know, storage cannot or should not be changed. And if you don't know if storage cannot or should not be changed, we'll actually teach you later on how to prove storage variables can't be changed or aren't changed. But for now, we actually need to tell Certora, hey, you need to assume the starting state. So in Foundry, we usually do something like vm.assume, x equals y. We do v.assume, like number is like greater than 7 or something like that. In Certora, we can require as a precondition just about anything. So we can say, okay, preconditions are whatever we want using, same as Halmos, the require keyword. If we wanted to say, okay, we need to require that these storage variables are as they are in here, what we would do is we'd say require current contract. This is how we refer to the contract that's being verified. .numbr equals 10. Boom, like this. So number equals 10. And then we do the same thing for all of these storage variables. Now it might seem like, oh man, that kind of sucks. We need to like rewrite all of our storage variables essentially. Most of the time you won't have to do this because storage isn't usually initialized like this. But since we have all these wild wanky calls using these libraries that are outside the contract, Certora assumes that these can be updated to be anything. So this is why we have to do these requires in here, and then we'll just require all of them. So this should be 3 equals 3. Oops, current contract number, current contract dot, oop, is that smart? Is that what it is? Nope. Number, well, let's just copy paste. Mumber is 7. Okay, what's next? Numbor is 2. And then Nambir is 10. So now in our preconditions, we're saying, hey, assume storage is as it is. Don't move it. All right, great. So what do we think now? Do you think this will pass now? Got a hint for you. The answer is no. But let's go ahead and run it anyways. Let's see what happens. What are we missing? What could we possibly be missing here? So now that we have storage set up correctly, is there a way to make this function call revert? Well, let's see what Certora can find out. Is there a way for this to revert? It must never revert. Certora, what do you got for us? So now that this is run, we do indeed see the same 2 checks here. If we go to rules, we can see that the env func static check passed, which of course it did, but our health func must not revert failed again. And if we look over to the variables on the right side, it's still with 99. Okay, but why did it fail this time? Let's go through the call trace once again to see what actually made this fail. I'm going to pull the call trace out a little bit. So, okay, this time global state. Okay, storage state. Great. All of these numbers were havocked. However, we went ahead and required that they were certain numbers, right? So even though it havocked them to be forced to be whatever we told them to be. So cool. So the starting global state is actually correct now. This is what we want, right? The setup just does a whole bunch of stuff in the background. We have all of our requires here. Awesome. And then we call the formal verification catches.healthfunc with revert. It did indeed revert, but why did it revert? Let's scroll in here. Why did this call revert? It's saying on line 21, there is an issue. So, okay, so let's go over to here, line 21, which is actually way up here on this unwrap thing. So something called multiply, which caused this subtraction to fail. So it said A was 0 and B was 1 when it called it. And then before that got called, it said evaluating branch condition defined on form verification catches line 105. We go down to 105 down here. Aha, this is indeed the line it fails on. So it was able to successfully find the bug. Excellent. Well done. Certora found the bug. It proved that 99 is a counterexample. And we now, just like that, have a successful spec here written to prove that healthfunc does indeed revert sometimes. So, awesome. Now let's go back up to this healthfunc. So now that we know we have a scenario where this actually reverts, it's correctly finding the 99, it's correctly finding the right line where it reverts. What if healthfunc wasn't ENV free? What does that actually look like? So let's see what healthfunc not being ENV free looks like. So let's call this again without the ENV free. If you actually run this, you get an error saying, hey, error in spec file, could not type expression, missing environment parameter to non-ENV free function. So basically, if you do not have that ENV free keyword here, when you call this healthfunc, the first parameter needs to be the environment. And so you would do env e like this, and you would pass e into your function call like so. So this env is actually a type in the CVL. CVL has a lot of special types. It has kind of all the UNT256, Boolean, etc. you'd expect in Solidity, and some special types. env stands for environment, right? And like I was saying, it's the message sender, message value, block number, timestamp, base fee, blah, 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 etc. Anytime you call a function that's not ENV free, like since we got rid of not ENV free here, we have to provide the ENV to it. And this is where we could say, like require env or e.message.value, or what is it? e.message.value equals 0 or something like that. So if we add this environment in here, we remove the env free. Let's see what actually happens when we add this environment variable. Just a quick summary here. If you don't have that env free keyword, Certora will go, hey, you need to pass an environment here. So we pass the environment as the first parameter to any function call. So if I call this now, you should have a good idea that this will actually fail. Now that this is finished, we don't have that static function check anymore, but this is still reverted. And let's take a look as to why in the call trace. So we can see it reverted with number equals 4. Number is 4. That was the input. Why did it actually revert with number with 4? Why did this call revert? Okay. C, line 32, informal verification catches. Okay, let's go to this, line 32. Where is that? 32. Okay, that's the actual contract. Nice. We see some local variables over here. We see a little dump. Safe math narrow, message.value equals 0, 0. Revert. Oh. So it's a little dense here, but essentially we added e.message.value equals 13. This healthfunc is a non-payable function. So simply because we added a message.value, this reverted. Since it reverted, our spec said, hey, I found a way for it to revert. Just add a value in message.value and boom, it automatically reverts. So sometimes we're going to have functions that are not ENV free, but we're going to want to say, hey, this isn't ENV free. We know, but we want to ignore message.value. So what we could say is, once again, require e.message.value equals 0. And the reason that we have to do this require here is anytime you initialize a variable, either in the body of the rule or as a parameter in the top of the rule, it actually doesn't matter where you put it. Certora is going to try to havoc those variables to break your invariant or your rule. So anytime you initialize a variable in Certora, just know Certora is thinking, how can I havoc this? How can I randomize this? How can I get an input for this value to destroy whatever rule or invariant that you have? In this case, for E, Certora goes, I know if I put a message.value in the environment, then since it's a not payable function, the transaction will revert. Boom, I found a way. Certora is always looking for ways to break your invariants and your rules, which is good, which is what we want it to do. And Certora will take any technicality and any route it can to get there. So adding a message.value will get it to revert. So we need to say, yeah, we know that's Certora, but don't havoc E to have a message.value just in this case. But anyways, now let's rerun this and rerun this. So even though this isn't ENV free, we have an ENV, but we're saying, hey, don't let message.value be anything. And we can run this again and see if we get past that error and actually back to the 99 being the true condition where it's actually an error. and you're going to get used to waiting for Certora as you play around with this. All right, now that this is finished running, we can walk through it and actually see why this one failed. Hopefully we get the same number. We do indeed see in the variables, number is 99. We required e.message.value equals 0. We see that this reverted. And if we walk through it, we do indeed see that it failed on that same line 105 on that conditional. And it has correctly found our edge case because we have a beautifully written spec. So basically, now that you know that hellfunc, that a env free function definition up here is the same, or well, and like this, is the same as basically saying enve require e.message.value 0, message.sender doesn't matter, blah, 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 etc. So this is our very minimalist spec. Now in the comp, there are a lot more parameters that we usually like to add. And I'm going to add a couple of them in here. I'm going to add wait for results. We're going to say all, and you can find in the documentation, you can find what all of these parameters actually do. This will wait for the cloud job to complete and display the log and results in the meantime. We want to also add rule sanity. We're going to make this basic. And this is also from the CLI. This enables sanity checking for rules. This will actually help us kind of get rid of silly rules. So if you do rule sanity basic, and we were to put back in here, like rule high, like this, assert true. If we push this up to the Certora prover, Certora would say, hey, I'm not going to run this rule because this is like always going to be true. So this is kind of a dumb rule. And it would actually say, it would tell us that this is a bad rule because it's just obviously a tautology. So rule sanity basic, and you can see all these different outputs in the CLI or the config file documentation. We're going to do optimistic loop. This is going to be true. And this is something for loop. It basically unrolls loops when you have like a for loop or a while loop or something. So whenever we have loops in your code that are getting a counterexample labeled loop unwind condition, you can run this. Or if you're working with really big loops and you know that they're not going to cause issues, this is kind of like saying, hey, like we're optimistically unrolling the loops. And then oftentimes you'll see like message verification of FVC or whatever the name of your contract is. So now if you're following along with the GitHub in here in the Certora folder, you'll actually see that we do a harness. We have a harness folder and we have another conf called fvcatchesinvariant.conf. And then also more importantly, another spec fvcatchesinvariant.spec. So this doesn't work. And I was originally going to show you why this doesn't work and how it doesn't work. But then it kind of occurred to me that it probably wouldn't make sense to just teach you how to do this wrong. So we're not going to do that, and I'm going to teach you these concepts later. But with that being said, we've now figured out a real basic minimal way to work with Certora, work with rules, and we understand that rules and invariants are different. We haven't really seen how an invariant works, but we have a good idea of what's going on here. So let's do a quick recap of this introduction to formal verification. So formal verification is the process of converting our code into math and proving for some invariant or some property. We worked with two tools that showed us how to actually do formal verification by way of symbolic execution. We work with both Halmos and Certora, and we saw a little bit of control in the video excerpt as well. With Halmos, we can take basically a Foundry fuzz test and just run Halmos on top of it. There are some restrictions, and you'll find that you'll run into some issues when you're trying to do something a little bit more creative and a little bit more difficult, which is where Certora comes in. Certora has a fully featured CVL language that allows us to write formal verification specs, borderline unlimited customization. Certora doesn't make any assumptions about our code base. It assumes we can send value. It assumes storage can be changed. And it tries to keep that in mind when it's trying to prove or disprove some rule or invariant that you give it. We learned how to write a very minimalist, very basic rule. Hey, does hellfunc ever revert? We need to add some preconditions. We checked if it reverted. And then we just had some assert that it verified for us, and it found our edge case of 99. So cool. Now this is a good time to take a break. And if you want to go the extra mile and get even more practice in, the Certora documentation is a great place to start and a great place to look through. So the game plan I have for us for the next couple of lessons here is going to be right here. So number one, we're going to practice doing formal verification using molwad_up. We're going to first do it with Halmos, and then I'm going to show you how to do it in Certora as well. Then we're going to apply this superpower we've just learned to the square root function, and we're going to run into a really interesting problem, and we're going to be very clever with how we actually solve this. And again, we're going to do this with both Halmos and then also Certora. And then finally, I'm going to give you the clue that probably should have tipped you off that there is indeed an issue with the square root function. So spoiler alert, there is an issue in here. And unless you're a savant of knowing how the square root function works, that issue is probably not very clear to you, but there is something in here that probably should have tipped you off. And we'll get to that in a bit. And obviously what's misleading is that these are pretty much always going to pass. So you might be thinking, well, okay, it's close enough to being good, but it's not correct. So we're going to figure out where it's not correct. We're going to find some edge cases and we're going to do some really clever stuff. And then we're going to figure out what should have tipped us off that this is actually not correct. Let's go ahead and let's practice, and we'll practice doing formal verification on our molwad_up function. This way we can feel a lot of assurance that what we're doing is actually correct. And remember, this is the issue here, and I'm going to uncomment it, right? This was the original code base, and this is where the issue is. And we found this with fuzzing. So remember, this is the issue that we found here. So let's see if formal verification can actually catch this as well. So cool. So let's get started practicing with molwad_up and formal verification. So let's go ahead and get started with Halmos here. And if you're following along with the GitHub repo associated with this course, you can find a lot of what we're doing, obviously in the audit data branch, especially in the test codes.t.sol. We're just going to do all of our stuff in this mathmasters.t.sol though. We can actually start again by just looking at the test molwad_up fuzz. Because remember, Halmos is designed to work pretty closely with Foundry. So what we can do is we can actually look at this and say, this actually looks pretty good here. Maybe we could just copy paste this. But actually, this assert equal is not what Halmos looks for. Halmos doesn't look for assert equals. It only works with assert. Assert equal, if you command click it, is actually a function defined in the stdassertions.sol. So this is a custom function that Halmos isn't really familiar with. So instead, what we're going to do is we're going to create a new function called check test molwad_up fuzz. And we're going to pretty much be able to copy paste the whole thing. We're going to remove all these comments because these are kind of annoying. And we're going to just change this to be assert and do a little equal sign here instead of doing this comma up here. And then we're going to get this little underline and we're going to change this to pure. So this looks pretty good. So let's try this. And let's remember the Halmos command that we would do to run this. So we would do Halmos -- function, the name of the function here. And let's try this. Let's see if this works. And now that we have this function set up as a Halmos function with assert instead of assert equal, this will now be formally verified by Halmos. Halmos is intelligent enough to take this, convert it into that SMT language, dump it into the Z3 SMT solver, and then formally verify this. Convert this code base into math and prove this is always the case given these conditions. So we can now run this here. We can do Halmos -- function and then copy paste the name of the function and run this. So what's this? So this is our output. Running one test, master's test, warning, Halmos, counterexample unknown. So did it not complete? Did it complete? What's this? Timeout. Check test molwad fuzz up. Paths 18, time this bounds. Symbolic test result 0 passed, 1 failed. So this actually failed because of this reason right here. There was actually a timeout. It didn't have enough time to finish solving this problem. And this is one of the issues that you can run into with formal verification. Essentially, you can try to formally verify something, but the solver won't have enough time to explore enough paths or convert the math to symbols with enough time. So all of these conditionals in here, whenever we do an if X, if Y, whenever we do in the actual code base, we do a conditional or we do some assembly. Anytime we do something like that, we basically create a new path. And if there are too many paths, we run into this thing called the path explosion problem. Don't worry too much about this for now. Just know that, hey, if the code base is too complex, a formal verification tool might actually not be able to solve it. And this is another reason why fuzzing first can be so important, because sometimes even formal verification will have a hard time and not be able to explore enough paths, or not be able to find a scenario which satisfies or unsatisfies our assert here. However, with this output, we're actually smart enough to know that, okay, this was just a timeout. Is there a command line input that we can use to say, hey, you can go a little bit longer? And there sure is. If we do Halmos -- help, pipe it into less, we look for timeout in here. There's a couple of different timeout commands we can use, and there's actually a whole bunch of different commands we can use. But one of them is going to be solver timeout assertion timeout, where we set the timeout for solving assertion violation conditions. 0 meaning no timeout, and the default is 1000 in milliseconds. So when we ran our command originally, when we ran this command here, we see that it went in 1.74 seconds. So as far as the actual path exploration, it only did 1000 milliseconds to check this out. So what we can do, if we want to say, hey, just keep going forever, is we can add that extra parameter, -- solver timeout assertion 0, and this will tell Halmos, hey, just keep running until you find a solution. Now, similar to fuzzing, this can take a long time. And for some assertions, maybe it takes forever. So this is, again, one of the issues with doing formal verification and fuzzing as well. The difference between fuzzing and formal verification, though, is if this does give us an output, we can be assured that it's binary. It's either right or it's not right. Whereas with fuzzing, if it gives us an output, there's still always going to be a little bit of uncertainty as to whether or not our problem has been solved. Keep in mind, when you run this, this is going to take a long time. So now's a great time to go get a coffee or something, because you're going to let this run, maybe turn on Spotify, YouTube Music, go to the gym, all my usual go take a breakisms, because this is going to take some time to run. Or you can also just assume the output that we get is going to be the same as the output that you're going to get. And after some time, you're going to get a counterexample like this. And I'm actually going to go ahead and cancel the run because, well, we have a counterexample that we can try out now. So we have these two here that Halmos has given us. We can even just take those. We can pop them into here. Boom, we'll grab that. We'll grab this, just like we did with the fuzzing output. We'll grab this and do forge test --mt, paste it in to see if Halmos's output is indeed -vvvv, to see if Halmos did indeed give us a good counterexample, and it sure did. These are not equals. Oh, I should have put assert that they're not equal in there. But yeah, we do indeed see that the logs, the results are different. So Halmos found us a counterexample. Awesome. Thanks so much, Halmos. So we're getting pretty good at working with Halmos, working with this formal verification stuff. Now let's do the exact same thing, but in Certora, and we'll learn a little bit more about some of the different tools that we have additionally in Certora to write our invariant checks. So in the repo associated with this course, there's a Certora folder right inside the tests, but oftentimes you'll actually see people create a new folder right into the root of the directory called Certora, like this. And this is where they're going to put all their files. So let's do something similar to what we did with the SC exploits minimized, but in this Certora file. So just like what we did before, we're going to want to make a comp file and a spec file. So we're going to do molwadup.conf like this, and a molwadup.spec, right? So the conf is the configuration file, and the spec is going to be actually where we write our formal verification. So oftentimes when you find a good configuration file, you can kind of just keep using that one and modify it a little bit for your needs. So you don't actually have to remember all the stuff that goes into the configuration file. So I'm actually just going to copy paste what's in the SC exploits minimized repo for the configuration and just paste it in here, right? And then obviously we're going to do a little toggle word wrap, and we're just going to change these files. So instead of src invariant break, we're going to do, src mathmasters.sol. Let's go ahead, drop this, src/mathmasters.sol. And we're going to run into an issue with doing this, and I'll show you what that is in a second. So same thing. We're going to verify the mathmasters contract, but we're going to use the Certora spec. So we're going to delete all this. So this is going to be at /Certora. slash mol wad up dot spec. Wait for results. We'll do all, rule sanity, basic, optimistic loop true, verification of mol wad. Great. So we have our configuration file. Let's actually write our spec here. We'll do like a little bit of NatSpec up the top. We'll say verification of mol wad up for math masters. In our mathmaster.t.sol, we have this function. And even though Certora has its own language, the CVL, the Certora verification language, we can often take the work that we've done with Foundry already and kind of rewrite it for Certora. So if this is our Halmos form of verification function, or this is what we would use to do fuzzing, we can actually just paste this right into our spec as our starting point. But instead of function, of course, we're going to make this a rule. And we don't need public or pure as part of our rule definitions in Certora. So we're going to tweak this a little bit in just a second. But since we are using this mol wad up, we're going to go ahead and add a methods block, just like we did before. We'll say function, there's a mol wad function, which takes a uint56x, uint56y, and it is external. Or wait, is it external? Mol wad up is actually internal. And it's part of a library instead of a contract. Is that going to work? Well, let's just keep writing it for now. So external returns a uint256, and this is indeed env free, right? We learned before env free has to do with like the message.sender, message.value, etc. Our mol wad up never touches any of that, so we can make this env free. So this could be our spec here, but I'm going to tell you right now, none of this is going to work. And it has to do with this right here. So internal functions on a library or just internal functions, you can't actually formally verify just by calling them outright. One of the most popular ways instead is you want to add them to a harness contract. So a harness contract is basically just going to be a wrapper around our library. Certora can't work with these internal functions. So what we do is we just make an external function that would return exactly what mol wad would be. So maybe we create this in test, maybe we create this in Certora, wherever you want to put it. I'm going to call ours compact codebase sol. You could call it harness or whatever you want to do here. We're going to make this a regular contract, right? So I'm going to do pragma this 0.8.20 contract compact codebase. Again, you'd probably call this like harness or something. And what we're going to do is we're going to go ahead and import mathmasters from /src/mathmasters.sol like this. And in here, we're just going to have a function mol wad up exactly like in our mathmasters. Take a uint256x, uint256y, and make this external pure returns a uint256. And then in here, we're just going to do mathmasters. We're going to do return mathmasters.mol wad up with x and y. And that's it. Let's just make sure this builds with a forge build. See if this compiles correctly. Great. Looks like it does compile correctly. Awesome. So now we have this compact code base, and instead of formally verifying mathmasters, we're going to formally verify compact code base, which is our harness or wrapper for mathmasters. Now, a note on using harnesses. There's this concept in formal verification and with the Certora approver of sound versus unsound. Soundness means any rule violations in the code being verified are guaranteed to be reported by the Certora approver. Unsound approximations may cause real bugs to be missed by the approver and should be used with caution. And it even kind of points it out here, such as loop unrolling or certain kinds of harnessing may cause real bugs to be missed. Essentially, since we are wrapping our library in this external contract, the prover can't reason that this compact code base, that this harness here doesn't affect the return values of this. Maybe some weird odd thing in Solidity makes it so that whenever a library function is wrapped by an external function, some crazy weird stuff happens. So if we do formal verification directly on mathmasters here, if this was like an external function for some reason, and we did formal verification directly on this external function, it would be considered sound. Since we are wrapping it in this harness, it's technically considered unsound, which is still fine. Like it's still formally verified, but it's formally verified in the context of this harness, in the context of this wrapper contract here. Just something to know. So since we can't verify internal functions, we're going to make them external functions. What then we can do, of course, so we can go over to our configuration file. We'll update this to be, instead of source mathmasters.sol, we'll do test compact codebase.sol, and we'll verify compact codebase in /Certora molwattup.spec. So this is going to be molwattup.spec. And this still has the molwattup function. So now instead of calling molwattup on mathmasters, we're going to call molwattup on our compact codebase, which hypothetically returns exactly the same thing that mathmasters returns. So cool. Now there's a couple of issues here. Number one, obviously this 1E18. Instead of 1E18 up at the top, we might do definition WAD returns uint256 equals 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8. And we can put this WAD instead for 1E18. So definitions in CVL, definitions serve as type checked macros, encapsulating commonly used expressions. Oops, and we want to add little parentheses here. And this is going to basically work as our constant variable that you would do in Solidity instead of doing that 1E18 down here. Cool. Next, what else do we need to fix in here? Well, we need to fix a number of things actually. So if at the top, we actually want to get rid of, and we probably should have got rid of it in the Halmos as well. This, instead of being a giant conditional, should be a require, right? It's going to be the precondition for this whole thing to work. The math will only work out if these conditions are true. So instead of an if, I want to get rid of this conditional and turn this into a require. So now a precondition of running our test here is going to be this right here. Now we can go ahead and practice trying to run this spec, which will run this rule here, and it's not going to work, and we'll see very quickly why it doesn't work. But we can run Certora run ./Certora molwattup.conf, and it's going to compile, and we're going to get this error in spec file, variable 2 in 256 has not been declared. Did you forget to use sig for function selector? And we can command click on this, and type uint256.max is also not something that exists in Certora. So instead we can do max_uint or max_uint256. This is what exists instead, but we're going to compile this, and this won't work either. So we'll run this and I'll show you why it won't work either. You're going to get this error in spec file could not type expression comparison of uint256 and mathint failed. So this maxuint256 is of type mathint and not uint256. So if we go to the CVL documentation here, we can go to types, and you can see that like Solidity, CVL is statically typed. There's an overlap between the types supported by Solidity and CVL, but CVL has some additional types. One of these types is going to be the mathint type. And this is essentially a uint256. However, it has no upper bounds, and it can represent an integer of any size. So mathints can never overflow or underflow. This is different, obviously, from a uint256, which can overflow or underflow. So what we want to do then is we want to do some asserts in here. So we want to say, okay, this math uint256 divided by x, in order to do a comparison here, we're going to have to say assert underscore uint256, like this. So basically we're saying max uint256 divided by x, this should always return a uint256. And now if we go ahead and try to run this, we'll get this other error saying right here, contract variable math masters not found. Oh, yep, because it's not masters, it's just molwattup on our compact code base. And let's run this again. And I'm running into these errors on purpose. It is really good to run into these issues so you know how to solve them, right? Okay, found some more errors. Assigning x times y equals blah, blah, blah. To type uint256 may cause overflow. Consider declaring expected to type mathint. So a lot of these typing issues are something that you're going to run into. So the way that I actually worked with this was I made this a mathint so that this is a math int. And then down here, I just said assert uint 256 and wrapped it around expected. We'll run this one more time now. And this time we indeed see connecting to server, and we're running our formal verification spec onto Certora. So I'm going to zoom out a little bit just to show you what this looks like. We basically had to fix some typing in here, but this looks really similar to what we did in Halmos and what we did in Foundry. And this now is what's going to run on our Certora prover. We get a little link that we can command click or copy paste to our prover and see the output. And of course, after a bit of running, we do indeed see, we get an output from our rules here. Let's go check the call trace here. We can see we have an X and Y example that they give us, where we do indeed see we have this assert down here, assert the result equals the expected, and we get a false, and we get these two values in here. So we can do the exact same thing. We can just test Certora by grabbing this, go to the mathmasters.t.sol. Let's find where we tested before. Okay, so this is the X, this is the Y. Boom, like that. Oh, let's actually write the assert now. So we'll do assert, result equals result down. And let's run this forge test --mt, paste that in. And this should still work, even though these are the hex. Solidity and Foundry is smart enough to know how to work with that. And we do indeed see a fail. Oops, I gotta run -vvvv to see the actual outputs here. And boom, we see perfectly that this indeed also fails. So Certora also found us a perfect edge case. Well done, Certora. So, and again, the reason that we were doing this is we wanted to give you a little bit more practice working with Certora and working with Halmos. And I wanted to introduce one more thing to you. As we said before, Certora has both these things called rules and also these things called invariants. Certora also has a keyword invariant, which means something slightly different. And the invariants has its own page in the documentation. You can read a little bit more about this, but this rule that we wrote here could be considered a pretty good invariant. We want to always make sure, no matter what happens in the smart contract, that the library mul_what_up function always equals this right here. So what we could do is we could essentially rewrite this rule as an invariant down here. So instead of rule, now we'll use the keyword invariant. And I'm going to show you exactly how this is so different from what's up here. So we're going to write this rule invariant, check, test, mul_what_up. We'll go like this. And usually, oh, does it have the same word? No, it has a different word. Okay, cool. And then right below this keyword, we're going to write our one-liner to define our property. And this is where we just say, hey, no matter what happens in this contract, this invariant, this property always needs to hold. And this could be as simple as true equals true, and a little semicolon here. So here is what all of your invariants are going to look like. It's going to be the invariant keyword followed by, similar to a function, your property name or your invariant function definition, then your input parameters, and then your single Boolean expression. And then if you have some pre-checks or some preserved block, those will go below the Boolean expression, which we'll talk about in a bit. But in this image here, we have an example of a phenomenally written invariant in Certora. If you have some token whose total supply should never be 0, otherwise your system crashes, all you have to do is write invariant, total supply is never 0, and then right below that, just say the function total supply should never return 0 or never equal 0. And here is really where Certora shines. If you have some invariant that is as simple to quantify in a single Boolean expression like this is all you have to do. And this is the superpower of Certora, where if you have some invariant that's easily defined, you can write it as simple as this. And this is where understanding your invariants is incredibly powerful, because if you understand them, then you can stick them into the Certora prover and mathematically prove or disprove that invariant can be broken. So this is what all of your invariants are going to look like. Now, this leads to some questions like, what's the difference between a rule and an invariant? And the answer is not a lot. All invariants can be rewritten as rules, but not all rules can be rewritten as invariants. Basically, invariants read better than rules, right? In that example here, If you can fit some rule into a single expression, it's much better to write that as an invariant. That's much more readable by us. But yes, at the end of the day, both invariants and rules do the same thing. If the difference between the two is too confusing for you, just say invariants are another way to write rules. But if you can fit a property of your system into a single expression, it's best to have that as an invariant in Certora as opposed to a rule. So as you work with this more, this will start to make more and more sense. Now I'm going to run this just to show you what it would look like. So I'm going to go way up to this Certora run. Let's run this molwadup.conf once again. And this is actually also shows you that you can have multiple rules, multiple invariants in your specs, and Certora will do all of them at the same time. So I'm showing you kind of a number of things. Number one, you can have multiple rules and multiple invariants in the same spec. I'm also showing you, hey, this is what the invariant looks like. So we're getting this output here. Let's go take a look at this and wait for this to complete. You don't have to run this. You can go ahead and just watch what it results for me because it should result in the same thing. So here's the output that we get, and you'll notice a couple things. So number one, if we open up this global problems section, you see it says contract pre-processing step fetched from cache and rule problems, rule verification result fetched from cache. This is pretty safe to ignore. All this essentially means is that some of the contracts and specs that we're using are going to be the same. And since I've been running this a whole bunch while recording, Certora noticed that some of the contracts and specs that I've been using are the same, and therefore just pulled from a cache some of the existing compilation data. So anyways, we see in here, we have obviously the initial rule that we wrote, failing, the env free function static check obviously passing, and then the function that we just added, our invariant, if you will, also passing. Of course, our invariant passing is because we have true equals true, and this obviously is going to always pass. And actually, Certora has this thing called rule sanity, where it actually can check for some of these silly rules. And if we added rule sanity advanced, we'd add a lot of sanity checks. And this would actually fail because Certora would go, hey, that's kind of a really dumb rule for you to have. So I'm going to fail. You should rewrite your invariant. But in any case, we see here that we do indeed pass our invariant down here in the same manner that a rule worked. So invariants really are basically the same as a rule, except for unlike our rules where we have all this stuff defined in here, the invariant is just a single one-liner right underneath the invariant. Now, the line between a rule and invariant can be a little bit gray, and there's some different interpretations with what should be a rule versus what should be an invariant. Because you'll see, we can actually even rewrite our molwad fuzz up to be an invariant. Although we'll have to add something even below this. Because this invariant up here only works so long as this line works. So we have some precondition up here in our rule that enables this invariant to succeed. So down here, we could actually rewrite our test as an invariant, but we're going to have to kind of tweak it. So let's go ahead and rewrite our rule up here as an invariant, and we'll see kind of what the difference between the two is, and it'll give you some insight as to why you should write a rule maybe versus why you should write an invariant. So I'm going to change the name down here to molwadup invariant so we can more clearly know this is an invariant, and we'll do a uint256x, uint256y, exactly the same as what's up here. But still, we don't have a little parentheses or bracket thing. We, again, are just going to have the one-liner of what the invariant is. So what's our invariant going to be? Well, it's going to be molwadup of x and y should equal this whole thing. Equal this. Although this needs to be a uint256, of course. So we'll do assert underscore uint256 to make sure it's a uint256. And then, boom. Put a little semicolon and you're normally done here. However, remember this line only works so long as these preconditions are true. So in Certora, we have this thing called preserved block, where we can say some invariant depends on some other invariant or some external assumptions about the system. Essentially, we can add these preconditions. And this is essentially how we can rewrite invariants to be rules or rewrite rules to be like invariants. But like I was saying, typically you want to have your invariants be some type of one-liner like this, right? Like maybe total supply should never be greater than number of shares of an ERC20 token or something like that. But to write a preserved block, we actually create some brackets underneath the function and we say preserved, and we create another set of brackets. This will be one of the preserved prerequisites that enables this invariant to run. And all we need to do is just copy paste this require, paste it down here. And then we get rid of this little semicolon. So in essence, we're saying this invariant should always hold so long as this precondition or this preserved block holds. So we can now run our molwatup.conf. Once again, we'll run both our invariant and our rule, and these both essentially do the same thing. We can go ahead, go over to the prover, of course, and we'll see both of them once again fail and give us a counterexample as to why each of them failed. And after a few minutes, sure enough, that's indeed what we see. We see the original rule fail, and then we see our invariant fail. We can see why in the call trace here, line 21. Look at some of the variables. It looks like these are two examples it gave us. And if we wanted to, we could once again copy paste these into our Foundry test suite, run them, and we would see that these are also fantastic counterexamples. So we've learned a ton here, and let's do a quick recap of all the stuff we just learned how to do in Certora and with formal verification. Number one, we learned that formally verifying internal functions can be really difficult. So one thing that we can do to get around that is we can use something called a harness. And this is where we have some type of wrapper contract around the functionality that we want. Our compact code base is an example of a formal verification harness where we call molwatup as an external function to mathmasters.molwatup, which is an internal function. In our specs, we can add definitions where we can define different types of variables right in our code bases. We can have rules, which can have preconditions with require, and we additionally want to make sure that all of our variables are of the same type. Certora actually has a number of types equivalent with solidity and their own types as well. For example, a uint256 is going to be different than a math int, where uint256 obviously has a cap size of type uint256.max, whereas a math int has any size. And we want to do some correct conversions between the two. Just like with Halmos or even Foundry, Certora is going to look at the assert keyword in order to verify the correctness or formally verify the functions. We can also do this thing called invariants, where we can make single one-liners about the property of our systems that should always hold. If they need some additional preconditions or tweaks, we can add preserve blocks to make it so. Now, the one last thing I want to do is I want to show you that these are indeed correct. So if we go back into mathmasters.sol and we go ahead and we comment or delete out this line, now that we've done that, our molwatup.conf should prove that, hey, you know what? These are indeed equivalent, right? It should prove that our result is always expected and our invariant always holds. So we'll pull up our prover now that we've commented at that line, and we'll see if this fixes the bug that we ran into. And after a few minutes of waiting, we do indeed see we have our molwatup invariant passing, we have our rule passing, and then obviously our env free check passing. So no errors found by the prover. We have a very nice and wonderful molwatup.spec. And we got a lot more practice using the prover, playing with the prover. Now that we've practiced with molwatup, we've done Halmos, we've done Certora, let's take our learnings over to this square root function. It's time to level things up. Going back over to MathMasters, this behemoth is the monster that we want to tackle. What's going on here? How do we approach this? Let's dive in. So the first thought here is obviously going to say, okay, we have this square root function. Let's just fuzz it against a square root function that we know that works well that isn't in assembly. Well, great thought. The project actually had the exact same thought as we saw. We have a couple of test square root functions right here, where these are just some unit cases picked out of a hat that the developers decided to test. They even have the max uint256 square root in here. They also have test square root fuzz and test square root fuzz soulmate, where there's this function, if we command click it, in the base test.sol, we talked about this a little bit earlier, there's two square root functions. There's uni square root, and then there's this soulmate square root. So for the purpose of this course, we're just going to assume that these are both correct. Obviously, the Uniswap square root is one that's very easy for us to verify, right? Codebase is real simple. We can easily verify whether or not this is right. For the purpose of this course, we're just going to assume that both of these are correct. And so, as the developers should have, they added these square root fuzzings here. Now, like everything that we do here, if we did enough fuzz runs, these would eventually be wrong, right? But if I just run them now, forge test -mt, paste it in, guess what? This fuzz test is pretty much always going to pass, right? Even if we double, triple, quadruple, make this way, way longer, it's going to say, hey, stuff looks pretty good. So we want to formally verify that stuff here indeed looks good. And we're going to first take a bit of a naive approach to doing this. And we could 100% use Halmos, we could 100% use Certora, but let's take kind of what the original approach would be. Well, the original approach, of course, would just be, oh, okay, well, let's formally verify the fuzz test. Let's just do the fuzz test. So let me grab this right here. I already know how to use Halmos. I'm going to use Halmos. Halmos -- function, paste this in here. Let's see how this works. Counterexample unknown. Okay, paths have not been fully explored due to loop unrolling bound of 2. Okay, so there's a loop unrolling bound. So what does that mean? Well, if we go back to our base test, we have this while loop here. Oh, this is kind of tricky. This while loop means if y is substantially large, there's gonna be a lot of while looping. Well, okay, well, let's check with Halmos. Halmos -- help, pipe it into less. Let's see if there's any loop stuff in here. Okay, loop max bound, default is 2. Okay, let's make this number way bigger. Okay, so let's run this again. This time -- loop, and we'll do 1,000. Or something, right? Let's just make this loop way bigger. And you'll notice if you actually run this, you'll be here basically for all of eternity. So this function will take incredibly, incredibly long to run, and probably to the point where it would never finish, right? There's just too many loops in here. Additionally, you could also cancel this. Same thing, run the same test, -- solver timeout assertion 0. And again, this would essentially run for, nearly all of infinity, right? It would be great if that was the easy solution here. So again, we're running into this issue of the path explosion problem. There's way, way, way too much stuff in this function and in the math masters function. There's just way too many paths for the explorer to take, way too many symbols for it to take into account. And we also have this soulmate square root, which is a different assembly implementation of the square root function. And you'll find out if you try it with this, the same issue happens. So that's kind of rough. Well, you might be saying, oh, Patrick, well, we have Certora. No worries. Let's just do it with Certora. Well, okay. Say less, my friend. Great idea. Let's make a new configuration file and spec. We'll call it square root.conf, and then we'll call it square root.spec. And we're just going to grab this conf here, paste it in here. We're going to leave the compact code base. Why? Because MathMaster is still a library and this is still an internal function. So we're going to need a test harness still, no problem. And we'll do square root.spec in here. The rest of these look good. Verification of square root. So now we have our conf. Let's go ahead and make our spec. We can even kind of copy paste some stuff. Let's paste this in. What's our methods block going to be? What are our functions going to be? Let's go to our compact code base, and we're going to need a couple things in here. First off, we're going to need that function uni square root, right? Uint 256y external pure, and then we could actually import this, but I'm just going to do it like this. I'm going to grab it from the base test. So we'll grab this Uniswap square root, paste it in here. And then we're also going to do function mathmasters square root of ChatGPT or GitHub Copilot. That looks pretty good. Uint56x external pure returns. I could do that, but I just want to do this. And I'm just going to say return mathmasters.square root x. Yes. So we have mathmasters square root. We also have the uni square root. So in our spec, we can just add those two functions in here. So we can say we have math masters square root, which takes a uint256. This is going to be external, returns uint256 env free, because we do not care about message.sender, etc. We also have function uni square root uint256 external returns uint256 env free, like so. And all we have to do, Mr. Patrick, is let's just do this. So I'm going to copy paste this test into our spec and modify this. So instead of a function, it is now a rule. We'll say test square root fuzz uni. We'll change this to an actual rule that makes sense. Uni square root matches math masters square root. And we don't need public pure. Assert math master square root like this equals uni square root like that. And ta-da, that looks pretty good. Let's go ahead and run this instead. See if this works. Real minimal form of verification test suite. So let's go ahead and try this. We'll do Certora run /Certora square root .conf, and let's give this a whirl. Let's see what happens. Does that, looks like I forgot to, this needs to be external, not internal. And then, yeah, that one's external. Okay, cool. Now let's try this again. Connecting to server, that's what we like to see. And we get a job here. Perfect. Let's open this up and let's see what Certora gives us for this. So after running this, it looks like this passes, but Halmos timed out. Oh, okay, great. This is so exciting. It seems a little bit too good to be true. What were we doing with this square root.conf again? Optimistic loop is true. What does this optimistic loop do again? Let's go check the docs. Optimistic loop. The Certora prover unrolls loops. If the loop should be executed 3 times, it will copy the code inside of the loop 3 times. After we finish the loop's iterations, we add an assertion to verify we have actually finished running the loop. For example, in a while a is less than b loop, after the loop's unrolling, we add assert a is greater than b. We call this assertion the loop unwind condition. This often changes the assertions of the loop unwind conditions to requirements. That means we ignore all the cases where the loop unwind condition does not hold instead of considering them as a failure. Oh, so this basically means that anytime we see a loop, we unwind it. And let me see, do we have any loops? Yikes, we sure do. So we're basically unwinding this loop, only doing it a couple of times, and then making our assertion with a subset of everything. So we're technically not formally verifying this at all. We're just kind of, yeah, this looks good enough, and saying, hey, it's good to go. Yikes. Okay, that's definitely not what we want. And this is why you should never copy comp files, because sometimes the parameters in here might not be what you want. An optimistic loop here 100% is not what we want. We're getting this output here saying, hey, yep, Uniswap square root is the exact same as math masters. You're good to go. But this isn't true at all. We have this optimistic loop in here set to true, and we don't want this in here. This is an additional parameter when you're very certain that, yeah, doing a loop unwind is the correct thing to do. Again, this would make your form of verification unsound, right? Because you're not truly proving it. You're kind of doing this optimistic, the loop should be good enough. Even in the docs, it says when to use it. When you have loops in your code and are getting a counterexample labeled loop unwind condition, in general, you need this flag whenever the number of loop iterations varies. So for us, we actually don't want to be optimistic with this loop here. We actually do want to get rid of this line and rerun this code base. So we're going to do exactly that. Certora run, Certora square root conf, and let's go ahead and see what we get here. All right, so after running this for a while, we do indeed get an output, and we can see we're getting this timeout issue, kind of exactly the same of what we saw with Halmos. And if we look in here, look in the rules, we see this little timer thing saying, hey, we ran into a timeout issue after 309 seconds. Now, back in our CLI, if we do Certora run -- help, we'll see all the different parameters we can do in here. And we can see we have loop iterations, optimistic loop. These are all the different things we can put in our config file. So is there some parameter we can do to get rid of these timeouts? So there's a whole page in Certora called managing timeouts, and there's a whole lot of different things you can do with timeouts. You can add parameters like the optimistic loop In our scenario, that isn't something that we wanted to do. We can increase how long the prover runs for with different timeout parameters in here. And we basically just say, hey, keep running Certora. Now, for this example, this isn't going to be what we want to do because again, we're going to run into this issue where there's just too many paths and we're never going to be able to actually solve this. And the issue that we're running into, they even talk about right in the Certora docs. This again is that path explosion problem. The number of paths that are given in the path count statistic might seem very high to users. The essential reason for these high number is known as the path explosion problem. The path count is exponentially in the number of nodes and edges in the control flow graph. And there's just way too many situations for Certora or Halmos or really anything to verify programmatically that the Uniswap square root function and the assembly square root function in MathMasters are the same. So we're going to have to do something a little bit more clever. And the Certora docs have some really good approaches that we could take. Mitigation approaches, different flags you can use, but we're going to do something that they talk about down here, which is modular verification. Often it is useful to break up a complex problem into simpler subproblems. This problem is called modularization. And that is how we are going to try to solve this issue. Can we actually verify this square root function with modularization? And what we're going to do here was actually inspired, if we go to the README, was actually inspired by this guy, Zach Obrant, where he did this really cool thing where he actually tried to solve, using formal verification, this exact problem in a bug hunt that he was doing. And he did modularization, and we're going to take the exact same steps that he took to try to verify a similar code base. So let's go ahead and learn how he modularized this up. So if we take a look at our square root function, here's what it looks like. And remember, in our base test, we have two functions that we're going to be comparing against. We have the Uniswap square root, and then we also have the soulmate square root, which looks like this. This hasn't really been one that we've been looking at too much, but if we do look at this soulmate square root code base, we can see something really interesting. Let me show you a side by side of these two different functions. So I'm going to delete some of the comments so this is a little bit easier to read. Now you'll notice something interesting. The first half of these functions are quite different. However, the second half is actually exactly the same. Both are doing these right shifts, these adds, and these divisions. So if we take that the soulmate square root function is correct, what we can do then is we can split our MathMasters square root function into two halves, into this top half and then this bottom half. Ideally, since they both have the same bottom half, their top halves should produce the same result. So yeah, okay, so maybe we're having a hard time verifying this whole thing because this bottom half just creates way too many paths. But maybe the top half is simple enough and not complex enough that we don't run into the path explosion problem. So what if we take that, and I'm going to save these as well. So what if we take that as our inspiration? Well, let's get cracking at what this would look like. So the bottom halves are going to be the same for each one of these. So all we have to do is compare the two top halves. So maybe I'm going to take this top half and we're going to go to the compact code base. And in here, I'm going to create a new function. We're going to say function soulmate top half external pure returns uint256. Oh, it's going to take a uint256x and returns z. And we're just going to paste exactly what soulmate has right in here. And now we're going to create another function called function MathMasters top half. Same thing. We're going to go to MathMasters and we're going to grab the top half of MathMasters in here. Boop, this top half here. Same thing, uint256x, external pure, returns blah, blah, blah. Paste this in here. Returns z, this. This is all wrapped up in assembly. So now ideally, we should be able to compare these two against each other. Wait a minute, Patrick, if we're already doing this, we could probably just do a fuzz test with this. You know what? That's a good idea. You know, why even try doing formal verification when we could just do the fuzz? Let's try turning this into a fuzz test. So maybe in our mathmasters.t.sol, let's scroll up. We could even import compact codebase from /compactcodebase.sol, and we could create a new test function. We could do function test compact fuzz uint256x public. We could say compact code base, compact CC equals new compact code base. This compact code base, we can just compare soulmate top half to mathmasters top half. And we could do a little assert equal CC dot, what is it? Mathmasters top half of X equal, or comma, CC dot soulmate top half of X. Let's see if these, let's see, well, let's first off see if I wrote this test correctly. Let's test these fuzzings and see if we get anything here. Okay, these went ahead and passed. Maybe if I did more fuzz runs, we would actually get this to break, but maybe not. I don't know. I just want to go ahead and keep writing this for a formal verification. So we now have mathmasters top half and soulmate top half. We now have these two functions in our compact code base. So now what we can do is we can take these over to our square root.spec, and let's try this again. So instead of these being our functions, we can now say function, what is it? If we scroll soulmate top half to mathmasters top half. So we say function mathmasters top half, uint256, external returns, uint256, env free, function soulmate top half. GitHub Copilot's got me here. And we have those be our functions in here. Now we can maybe say rule soulmate top half matches mathmasters top half uint256x. Oh, okay. Now this is something that looks pretty easy for us to do. Hopefully it's small and compact enough that we don't run into the path explosion problem. And now we can do assert mathmasters top half of X equals soulmate top half of X. Thank you, GitHub Copilot. And again, this is our entire spec. Remember, we are using this on a test harness, and because of this, this is unsound. We're also doing modular verification where we're not technically verifying the whole thing. We're just verifying part of this. But the idea is if the top halves are different, then that is probably a sign that these two functions do not give the same output. And whoops, actually, sorry, this needs to have this down here. And I forgot a line in the soulmate one as well. Oops, sorry, in the soulmate top half, we also need this line. I forgot to add. And then in the mathmasters, we need this line here. And then the two bottom halves match, right? Because then it's just the Z's and the right shifts. Is that right? Yes. Okay, cool. So we need those two lines. We need this line here. And now the top halves should match up because the second halves are exactly the same. So what we can do then, now that we finally have this, wow, that was so quick to do this actually too. We can finally do Certora run /Certora square root .conf, and let's see what we get. Oh, okay. We have a little error here. It says that these two failed. So let's pop open the prover and see what's up. Take a crack into this. It's saying it sure did fail. Let's see what the rule parameters were. Okay, so this is the output that it gave us where it failed. Okay, well, let's go ahead and run this now in a unit test. So let's go back to mathmasters.t.sol, and let's just copy paste this. Get rid of the x here. We'll say uint256x equals, copy this, paste it in here, and run this now. Now that's not a fuzz test. So hold on, I gotta rename it. Test square root with Certora edge case, clear forge test --mt, paste that in. So it passed. Now here's the sad conclusion of this. So this is indeed a correct edge case of our stripped functions here, right? Soulmate top half and soulmate bottom half. However, it is not an edge case of the square root functions themselves. So we did find a scenario where the two of these top halves did indeed fail, but we would have to go one step further in order to really find an edge case with these square root functions. We would additionally then need to take all these edge cases that Certora gives us and put them as prerequisites into our spec here. We would have to do something like require x does not equal this edge case that we already found because we proved that this one was good. And we would essentially have to keep doing this until we find an edge case where the two top halves don't match, but the bottom half doesn't essentially equate it out, right? So Certora did help us find an edge case, and it did help us find that actually our MathMasters function is wrong. Why is the top half giving us a different response? It wasn't able to tell us exactly what the edge case was. It wasn't able to prove that the square root function is wrong, but it was able to modularly prove that at least the top half of MathMasters is wrong and different from the top half of Soulmate. We can prove that pretty easy if we copy paste this, once again, get rid of the X, paste it here, say X equals the edge case that Certora gave us, and we'll run this forge test -- MT. Oops, I should have changed the name, sorry. I didn't change the name, but yeah, that unit test went ahead and failed. So Certora did correctly find an edge case for the top half, and we did some modular verification where we proved that, there's something wrong with this function. So congratulations. You've written a badass form of verification, and you've done some modular verification where you broke down a very complex problem into a slightly easier problem that we were able to verify. Now, we were not able to verify that the square root function is definitely wrong, but we were able to verify that it potentially is wrong from Soulmate. And in any case, we definitely want to fix that. So this is where we would have to go back into MathMasters and go, where the heck is it getting this wrong? We know it's somewhere in this top half. And this is where I'm going to give you the cheat sheet for the thing that could have or should have tipped you off here. So if we take this decimal here and we do cast to base, paste this in and do hex. The hex of this is a bunch of Fs. So we could essentially then just boop, replace this with all the Fs. Okay, well, what about this one? Let's do the same thing. Boom. Okay, it's also a bunch of Fs. So we could, boop, replace that with Fs. Okay, what about this one? Let's try this. Boop. Okay, this is also a bunch of Fs. Boop. Okay, what about this one? Let's try this one now. Paste it in. Oh, that's not a bunch of Fs. FFFFF2A. Okay, well, what if we replace this with the two Fs, copy this from my MathMasters, put it into our compact code base, wherever that is, that's over here. And now this is OFFFF instead of the wrong thing that it was before, which was like OXFFF2A or whatever it was, right? So now that this is in here, let's see if that was the fix that we needed to match MathMasters to Soulmate. So we're doing some modular verification. We think we fixed the top half, right? We fixed the top half, we think, in our MathMasters top half. Let's give it a moment of truth. And let's finally do a little Certora run here and see what we get. Oh, this is a good sign. No errors found by the prover. Let's open this up. Okay, we see 2 check marks. Okay, that's a good sign. And then if we go finally back to our config file, let's just do a quick check to see there's nothing crazy here. Rule sanity, this definitely won't do anything. Wait for results, looks great. The rest looks great. There's nothing in here that would break our form of verification. So we have just successfully found the final, most important bug in this code base, where this square root function is not right. They put this weird 0FFFF2A instead of the FFFs here. And again, if you want to become a square root Babylonian method wizard, you can look into why the 2A is very different from Soulmate. So we didn't verify that the square root function is wrong per se, but we at least modularly verified that it's not the same as Soulmate, and that could potentially be an issue. If you want to do extra credit and actually formally verify the two of these are exactly the same, and that this square root function was correct or wrong, that will be a great challenge for you to do so. So we went through all of that kind of quickly, and I know there was a ton there. So let's go over what we learned, and most importantly, why we made the decisions that we did. So first off, mathmasters.sol. We were tasked with a very difficult question. Is this square root function correct? It's a ton of assembly, which we learned about, we learned how to do, But there's a lot of really difficult stuff in here, right? Number one, it's using this very unique Babylonian method to find the square root of a function, which might be something totally new. We could 100% walk through this assembly and try to make sense of it, try to see if it is what it's supposed to be doing. And then, to be honest, probably we would have run into the bug here where we would have seen this 2A, this LFFFF 2A is wrong. It's different. But we didn't do that. We decided to take a more testing methodology. We want to be more pragmatic. We want to have our tools catch as many bugs as possible. So we said, okay, how can we actually solve this? And what we did was we first said, okay, well, let's try to just fuzz this. We've done fuzzing before, and we know what soulmate looks like. We have the soulmate function, and we have the Uniswap square root function. Both of these have been tested a whole bunch. It looks like they're either correct or correct enough. Let's just do a fuzzing test suite against it. And that's actually what the developers of this protocol already did. They have test square root fuzz uni and test square root fuzz soulmate. Both of those, when run with a number of runs, actually resulted in passes. These two passed here. So we said, okay, fuzzing passed, but maybe that's not the whole story. Maybe there's an edge case lying secretly in this function. Well, let's go one step further. Let's actually try to formally verify this. And that's what we tried next. We said, okay, you know what? We're going to go into our Certora. We're going to go into our square root.spec. And we tried doing this rule down here where we said, you know what? We're just going to take that exact fuzz test and run it as a formal verification test. And I'm going to tell you right now, like I said before, the soulmate square root form of verification would have given the same results. We originally had the wrong comp. We had optimistic loop equals true in here. Oh my gosh, that's not what we want. Sometimes that's going to be too restrictive. It's going to be too optimistic. We didn't want to be optimistic here. We want to say, prove or disprove this. So we took that out and we ran this, and our solver said, hey, guess what? This is going to run into the path explosion problem. This is just way too complex of a function for the solver to solve in a realistic time, in a realistic universe. So we went back to the drawing board and we said, I wonder if there's another way that we can solve this. And we noticed something very interesting. We noticed back in our base test, if you will, that the soulmate function, the first half kind of does all this wonky stuff, but the second half looks exactly the same as what is in the mathmasters.soul. The second half of these two code bases are exactly the same. So what if we just compare the top half of mathmasters and the top half of soulmate? Surely, if they differ, then there might be an issue with our math masters. So that's what we did. We stuck the top half of both of those functions into our test harness, our compact code base, and we said, let's do some modular verification where we verify at least the top half. And then of course we'd want to verify the bottom half as well, but we found a bug in the top half and that was good enough for us. But we verified that the top half of these actually don't give the same results. And we made a rule in Certora to assert the top half of mathmasters equals the top half of soulmate. And when we ran that in Certora, we did run into an issue and we got an edge case. We found a counter example where the top halves of those two functions, in fact, didn't match. And that led us to think, oh my goodness, there is a bug in this. And that led us to find that And originally, the MathMasters top half had this just kind of random number in here. And when we did some conversion, we did cast to base, paste that in there, hex. We found out, oh, this is a weird hex. What the 2A? Everything else is doing these FFs. Even if you know nothing about the Babylonian method, that might be a signal that, there's something weird going on here. And then when we changed it back and formally verified the two again, this is when Certora finally said, you finally did it. The two of these are the exact same. And now we can know with very high assurance that if soulmate is correct, then our MathMasters square root function is also correct. So there was an absolute ton that we learned in this lesson, and a lot of how to use some of these tools like Certora and Halmos. If you get lost in any of this, be sure to use the documentation because there's a lot of goodies in the documentation. And if you don't like something in documentation, it's open. The documentation is open sourced, so you can always make a pull request on the documentation itself. Now, we have one more formal verification project that we're going to work on. And this next one, we're going to go crazy deep into formal verification. We're going to go crazy deep into working with Certora. So at this point, I want to give you a huge congratulations, because what we're doing right now is super difficult. What we're doing right now isn't easy. This has been a very difficult lesson. Math Master has been a very difficult lesson, right? There's a lot of stuff here that we learned, and there's a lot of tools that we learned, and we learned a lot of different methodologies in Certora. And we're going to learn even more in our final one, the advanced formal verification lesson, the Bad NFT Marketplace, which doesn't look so great in dark mode. You have learned a ton. There's a lot of flexibility in the CVL language to be as expressive as you'd want to be. And that's what makes Certora so powerful. You can do so much with the language, and all of your formal verifications run in the cloud. So you don't even have to worry about your computer being garbage or good. You can just say, hey, Certora, your servers, hopefully they're very good. So we learned an absolute ton. You did phenomenal getting to the end here. And I hope you practiced everything along with us. And if we go back to our mathmasters.t.sol, we scroll to the bottom. We've done everything that we wanted to do. We could have gone ahead and tried to do the square root stuff with Halmos. That's actually what Zach Obrant originally did. I showed you how to do it in Certora, but then we finally learned the clue that should have tipped us off with the OX FFFFF2A, or however many Fs were in there. And this is where, of course, if you're doing an audit report, you would want to do an audit write-up. If you want to learn how to do an audit write-up, go back to the security lesson. We talk about how to do a really badass finding, how to do a great audit report, and do that write-up. In the GitHub repo associated with this course, you can, of course, go to the audit data branch, where we kind of skimped out on the actual report as of recording. We kind of just posted what the bugs were without really good descriptions. However, there are some people who did Codehawks, which was a derivative of what we did here. And there were some absolutely phenomenal write-ups that a lot of people wrote. Highly recommend you check this out, and you check out the people who did these reports, because they are absolutely badass and definitely threats in the security space that you want to look out for. Now's a great time, as you already know, to get some what? To get some coffee, get some ice cream, go on a jog, go to the gym, lift 315 on the bench press. Or not, or even just 10 pounds, or do a push-up, or just stand up. Doing some physical fitness is great for your body, for your mind, and for everything. But whatever kind of break you want to take a break, give your brain a rest, because we've got one more security course with formal verification. This is the advanced formal verification, the Bad NFT Marketplace. And guess what? We're going to do it again. We're going to go even deeper into Certora and learn how to do way more crazy things to formally prove our smart contracts. And once you complete this section, once you complete Bad, the Bad NFT Marketplace, you're going to have skills that, as of recording, maybe 500 people in the whole industry have. Maybe 1,000 if I'm being optimistic. Very, very few people have these skills, and I'm so excited for you to finish Section 3, the Advanced Formal Verification, the Bad NFT Marketplace. Phenomenal job here in Math Masters. You found some amazing bugs. Let's do a quick review of everything we learned here before we finally sign off. To get started, we started by looking at our mathmasters.sol codebase, and we were tasked with, hey, make sure that this codebase is good. Let's do a security review of this codebase. And right from the get-go, we said, hey, custom errors aren't a thing in 0.8.3 of Solidity. They were introduced in 0.8.4. And this is where bots, detectors, and your knowledge of these different compilers is incredibly crucial to making sure that these code bases are secure. We took a look. This mathmasters.sol code base had only 3 functions: molwad, molwad up, and then square root. And it was based on solidity and soulmate. Thank you to the developers who made these for giving the inspiration for this entire section. Their code bases are absolutely baller, and I highly recommend everyone check out their code bases as well if you want to see some phenomenal assembly. We learned about the WAD unit, which was introduced in DAppHub or DappTools and kind of popularized by MakerDAO. And then we actually did some assembly reading. We learned about some of the different functions that you can use in assembly, and we learned even deeper about the free memory pointer. And hey, you probably shouldn't rewrite or overwrite the free memory pointer. We learned even more so how when a contract reverts, how it actually gives you a revert error code. And we noticed, based off of the function selector that it's stored in memory here, that the error code was actually wrong, and it was stored in the free memory pointer for some reason, which is super dangerous, and you probably should never do that. And we got to see, when we actually walked through the Foundry debugger, we got to see what memory looked like, what storage looked like, why we're doing 0x1c, how do all these different functions work? And we just got to see a much lower level usage of assembly. And we used all of our knowledge there to make sure molwad actually worked, which was equivalent to x times y divided by wad, rounded down. Then, with our knowledge, we went over to molwad up, which is the exact same thing as molwad, but rounded up instead of rounded down. And we found out, using our prowess, a combination of manual review and testing and formal verification, to find out that this section right here is erroneous. Why is this here? This shouldn't be here. And we used a couple of different skills to do this. In our mathmasters.t.sol, we looked at some fuzzing, but almost more importantly, we did some formal verification, and we found out there was indeed an edge case where this was wrong. Formal verification proved that there was something weird, something fishy going on with this contract, something fishy going on with this function. And it was this line right here. There's this random is zero going on that we don't need. We learned about Halmos and formal verification. And Halmos is designed to work with Foundry, and we can just do Halmos -- function, check tes up fuzz, or just the name of your function you want to test. Then we said, hey, you know what? Let's level this up. Let's work with Certora. And we wrote a Certora spec for testing the molwad up function, where we had some preconditions, we ran our operations, and then we have an assert. We learned about rules, which are one of the main entry points for our Certora prover. Rules are essentially tests, but for formal verification. We learned what formal verification was and how it is the way to prove or disprove a certain property about your system. We learned how to rewrite these rules as invariants, which are the other key entry point to Certora. Rules and invariants are essentially the tests of Certora and how they start looking at your code base. We learned that invariants in Certora are these one-liners, and if there's some prerequisites that we need, we put them into these preserved blocks. A lot of rules can often be rewritten as invariants, and invariants can often be rewritten as rules. And it's kind of up to you to decide when you want to do what. And like I said, using our prowess, we found out this bug in here. And then additionally, and then once again, we found there was another issue with the overwriting the free memory pointer, using the wrong function selector, etc. And then finally, the square root function, which we took several approaches. We looked at fuzzing, we looked at formal verification, and we said, this is so hard to test. How do we prove that this actually works? And we took a different approach, which was going to be modular verification. So instead of just proving or disproving this outright, we actually broke up the function into just its top halves. And we created what we called our test harness, which is going to be a code base that wraps around the code base that we want to test. And we split up the Soulmate top half and the MathMasters top half and decided to formally compare the two of them because they were small enough problems for our formal verification proofs to check out. Once we did that, we found there was indeed a bug, there was indeed an issue, and on closer inspection, we found there was this weird line here doing OXFFF to A, but it was hidden from us because they use decimals instead of hexadecimals. But Certora was able to catch this, give us the edge case, and then once we fixed it to its correct FF, we reran our formal verification and we modularly proved that the top halves with that fix are indeed the same, giving us some confidence that the square root function at least behaves the exact same as the Soulmate square root function. Once again, that solution was inspired by Zach Obrunt, so a huge thank you there. And I want to give a couple more huge thank yous. Huge thank you to the solidity team, the Soulmate team, Karma for his help on Halmos, and of course to the Certora team for giving me a lot of help on working with the Certora prover, learning the Certora prover, and being able to teach it back to you all. So huge thank you to all these gigabrains. And then obviously a huge thank you to the gigabrains building these tools so that we can have high assurance that our code bases are correct. With all that being said, you know what time it is. It's time for you to take that break, because the Bad NFT Marketplace is the last section of the assembly and formal verification curriculum, and it is a very badass code base, and we're going to learn a lot of really cool stuff with Certora. So, with all that being said, take that break, and I'll see you soon. All right, welcome back to the final module, the final section of the Assembly, EVM, opcodes, and formal verification course, where at the end of this, you're going to be an absolute wizard of assembly and formal verification. And I wanted to bring your attention to Codocs because after this is done, after you get through this final module, this final section here, you're going to be able to come to Codocs and compete in a formal verification contest, write some actual formal verification specs, and potentially get paid to do so. So be sure to look out for those on Codocs because they're going to be a great way to test your formal verification skill sets. And you know, maybe we'll even have some of the first flights. Who knows? But of course, if you're following along, let's go to the GitHub repo associated with this course. If you are on Updraft, it'll be in that GitHub resources. And if you're on YouTube, it'll obviously be on YouTube. If we scroll down in here, we can scroll all the way down to the final one, the Bad NFT Marketplace, and we can come to the code base, which is right here. So we're going to be doing something a little bit different here. And all we're going to be doing is we're going to be writing the Certora, writing the form of verification, and we're going to learn some really badass stuff in here. So let me give you a quick overview of this code base, what it looks like, and what we're going to be doing. So this looks like a pretty traditional code base, right? A pretty traditional Foundry code base. We have some kind of interesting stuff in here where we have some of the opcodes in here, where we have some of the assembly written out. We have a slither config, remappings, we have a makefile, all the regular stuff we would see. We have a test. Oh my goodness, they have unit tests, they have mocks. That's really nice to see. And this is a NFT marketplace, but it's based a little bit off of the Seaport codebase. For those of you who don't know, the Seaport codebase was an OpenSea smart contract NFT marketplace where they actually had two different types of code bases written. One written almost in pure Solidity and one written a ton in Assembly. The reason that they did this was because writing your code bases in Assembly is going to save a lot of gas because you're writing in a lower level language. You get to skip any compiler issues that the compiler actually has. And so what this project has done in this GadBass NFT marketplace is first they created this NFT marketplace.sol. And by they, I mean we, because I wrote this, but they created this NFT marketplace.sol. And all this is it's a minimalistic NFT marketplace. We have a way to list an item on the NFT marketplace where the NFT marketplace actually holds the custody of the NFT. We have a cancel listing function where you can remove your NFT from the marketplace. We have a buy item where you buy the item from the marketplace, update listing where you can update the price, and then withdraw proceeds, which is where you can actually withdraw the proceeds from the different sales of the NFTs that you have. Also, we have this on ERC 721 received so that it can actually accept ERC 721s or NFTs. And that's all it is it's a minimalistic NFT marketplace. Now, what they did was this project actually rewrote this NFT marketplace to be this Bad NFT marketplace, where it's essentially the exact same code base, except for there's a lot of assembly in here to do some of the stuff. So for example, down here, we have, it actually uses assembly to emit the log that somebody actually listed an item. And that's kind of the major difference. We have assembly for the log of cancel listing. We have assembly for buy item. We have assembly for update listing. Withdraw proceeds, pretty much the same. We do a little we do a little raw bytes with on ERC 721 received. And that's kind of the main difference. And what we're trying to show you in this section here is that if somebody takes their Solidity codebase and rewrites it in assembly, you can actually use formal verification to prove the equivalence of these two code bases. We can actually use formal verification to say, hey, the outcome of the functions on the Bad NFT marketplace are going to equal the outcomes on the NFT marketplace.sol. And the reason I want to show you this is because this is what I see as a great way for the future to make incredibly gas efficient smart contracts in the future. You write your original contract in Solidity, you test your Solidity. Solidity is much easier to read, it's much easier to write, and then you rewrite it in assembly and you do some equivalence checking between your assembly and your Solidity reference implementation. This is somewhat similar to what the Seaport codebase did. Now, I will admit that the assembly we wrote in here is kind of simple. right? It's really just events that are the only thing that we replaced with assembly. So there's really not going to be too many bugs in here at all. But learning how to make sure that these are actually equivalent is what we're going to be learning with formal verification in Certora. If you're in the code base here, you can obviously see that there's a Certora folder with configuration files and then obviously specs. That's what we're going to be looking to replicate here. And that's what we are going to write from scratch as a team. So this is going to focus almost solely on the formal verification. And then of course, if you want, you can also walk through the assembly. And to do this, we're going to have two specs. We're going to have a gas bad NFT spec. And before we actually do that, we're going to warm up with this NFT mock.spec. We're going to learn some new stuff about Certora. We're going to get warmed up with this. And then we're finally going to do the gas bad NFT.spec. And this is where we're going to do some formal verification to make sure that the gas bad version, the assembly version of the code base, actually matches the solidity version. And we're going to learn a ton of stuff in here. And once we get done with this, like I said, you're going to be able to participate in some of the CodeHawks formal verification contests where you have to write formal verification specs. You can write formal verification for clients on Certora as well. And just 100 doors open with this skill. So, you ready? Let's do it. To get started, you already know the drill. We're in our opcodes FV repo here, and we're going to be cloning the gas bad NFT Marketplace. Unlike the other ones, there's no audit data branch. There's just main. So we're going to go ahead and get started cloning this. Do git clone, paste it in, code 3 gas bad NFT Marketplace, or open this up in whatever text editor that you prefer. We're going to open this up in here. So one of the first things that we're going to want to do is sulk select, install 0.8.20 if we have not already installed it, and then sulk select use 0.8.20 because that is going to be the solidity version that we're using for this. And what we're going to do to get us started is we're going to go ahead and delete the Certora folder. Why? Well, because you and I, my friend, we are going to be building that from scratch. So let's open up the readme.md. Give this a quick read to see what we need to do to get this set up. So I'm gonna scroll down, blah, blah, blah. I have Foundry. I have Certora CLI already installed. Okay, great. We're gonna run make command. Let's just go check what make does. Let's go in the make file. Make is gonna run all, remove, install, build. Remove looks good, install looks good, build looks good. Let's just check the foundry.toml. There's no FFI in here. That looks pretty good to me. So great. Let's go ahead and run make. Let's get everything installed in here so we can get going. All right, cool. And it's in here. We're updated. Let's do a quick rundown. Let's see what's in here. .env.example. We have a test file with this base test. It looks like this is actually what it's originally doing to try to compare these two. Let's just run this. We'll do a little forage test here. Looks like everything's passing. Cool. And then let's just kind of peruse through this code base here, gas bad NFT Marketplace, and let's take a look at this assembly here. So this is going to be using assembly to emit logs. And this is actually a pretty classic finding in a lot of competitive audits if you're doing some type of gas competitive audit. Using assembly to emit logs is often a little bit more gas efficient. They're using the log4 EVM opcode, which we can look up in here, append log record with 4 topics. We can look at what this actually does. So this takes 1, 2, 3, 4, 5, 6. So byte offset in the memory in bytes, byte size to copy. Let's see what it's doing. Okay, so start at 0 in memory, do 32 bytes, and it looks like right before we start at 0, price is a uint 256, so that's going to be 32 bytes, so that makes sense. So the first topic in all logs is always going to be the hash, basically the function signature of the event. So it looks like this is exactly that. Then topic 2, topic 3, and topic 4 is going to be caller, NFT address, and token ID. And this is where we'd want to double check that these are emitting the correct event if we were doing an audit. So caller is some assembly to get the message.sender. So that's correct. NFT address, token ID, and then price is going to be what's on the end. So again, byte offset in memory and bytes, byte size to copy. So after all your topics, it'll stick on the end whatever you have put in memory for, the size of memory you've said. I didn't explain that very well. Since in our log4, we're saying start at the 0th byte in memory, go to the 32nd byte, grab whatever's in there and stick it at the end of our log. And that's going to be our price because that's just what we stored in memory. All of our events are basically going to be looking like this from this assembly, which is cool. So since that's most of our assembly, right? If we walk through all these, it looks like that's pretty much like event, event down here. And then we just have kind of this bytes 4, which returns this function selector, which we could verify. We probably already know that this shouldn't have any effect on anything. And whenever we run our Certora formal verification, we should know, hey, these should pretty much all match. There's a very low chance that the assembly is going to screw something else up. Now, of course, we could have screwed up the assembly, and that's what we could formally verify for, but that's not what we're going to be focusing on. So that's just like a quick walkthrough of the actual differences here. It's just this assembly bits. But now that we have the Git repo, we've done a little bit of a walkthrough of the code. If you want to take some time to walk through it some more, feel free. It's a pretty minimalistic NFT smart contract. Let's go ahead and let's actually build some formal verification. So, and in the README, I'm even going to scroll up to the top. We're going to make a little game plan for what we're going to be doing here. So number one, we're going to warm up by verifying some stats of our NFT mock. And then number two, going to formally verify a lot of stuff for the Bad NFT Marketplace. And in particular, what we're going to be formally verifying is some of these events, because like I said, we do want to formally verify some of these events. So number one, we want to verify, anytime a mapping is updated, we emit an event. So in here, we have all this mapping up here, S listings, S proceeds, and we want to be able to verify, hey, anytime, no matter what, anytime one of these are updated, this assembly kicks off correctly. Is there a scenario where we screwed this up? Did we screw up the assembly somewhere? So we want to verify that. Guess what? We can formally verify that. What else? Calling any function on the Bad Marketplace or the NFT Marketplace, they end in the same state. So we want to make sure, we want to do this equivalence test. So we want to make sure that the NFT Marketplace and the gas marketplace are exactly the same except for gas differences. So guess what? We can formally verify this as well. So these are going to be the two main things we want to formally verify for. And just these two things here, we're going to learn a ton about Certora and how to do really clever things with Certora. And this is something that you would want to know how to do for projects who are doing a setup like this, where they have a solidity reference and then they have a more gas efficient assembly or huff or whatever reference. We're going to teach you how to build this formal verification pipeline and do some really clever creative stuff so you can have unlimited customization and flexibility when it comes to doing this. And I want to warm up, like I said, with our NFT mock because I want to give you some more practice with working with Certora, because guess what? Repetition is the mother of skill, and we're going to make you skillful. So let's do this. So to get started, we're going to look at this NFT mock.sol, and we're going to verify a couple of things in here. Actually, I should have wrote this over here. And for our NFT mock, we're going to do these three things. We're going to make sure the total supply is never negative. When we mint an NFT, we mint exactly one mock. And then we're going to do some sanity checks, again, just to warm up, give you more practice. Right, so we have this mint function. We're going to make sure it mints exactly 1, and the total supply is never negative. So that's what we're going to go ahead and do. So, the first thing that we're going to want to do, create a new file, Certora, like so. We're going to want to make sure that we export our Certora key, like that. Want to make sure that's there. And in here, we're going to make 2 folders. New folder, we're going to make a conf or configuration file folder, and then a spec for all our actual specs. Let's start by creating an NFT mock.conf. This will be our NFT mock configuration file. And then we'll also make NFT mock.spec. And to get some practice with this, let's actually write out the configuration file ourselves. So in here, first we want to identify the files that Certora is going to have access to. And it's going to have access to the ./test /mocks/ that's really nice, NFT mock.sol, and that's really it. What are we going to verify? Well, we're going to verify the NFT mock contract. Again, you don't have to be this explicit, but I like being this explicit. That's going to be at Certora /spec/NFT mock.spec. Like that. We're going to say wait for results. We're going to say all. And let's just do message for now. Message verification of NFT mock. We're probably going to change this pretty soon, add some more custom stuff in here, but this is just what we're going to do for now. And just to make sure that we're even connected, let's actually bump this up to number 1. Let's do some sanity checks, right? So let's create our spec now. Say verification of NFT mock. Let's do a little bit of sanity checks here. So we'll do a little rule, sanity, and we'll just say satisfy true. That's it. And so this obviously is going to be correct. But let's do Certora run /Certora as spec NFT mock.spec. Oops, sorry, not .spec. Do conf NFT mock.conf. Let's just see that this actually works. Now I'm going to run the Certora prover a lot. And the Certora prover takes a lot of time to run. So if you're saying, like, I don't care, Patrick, just like, let me see the outcome, no worries. I'm going to show you the outcome of running the Certora prover. So if you want to get the experience for yourself for what the Certora prover outputs when you change some config or something, I highly recommend you do so. And I highly recommend you run the Certora prover pretty often so that you can get a good feel for what everything looks like. However, you don't have to run it as often as I do because I run it pretty often. And of course, this passes because it's kind of a stupid rule because it's, it's real easy. But I wanted to show you this again because if in our conf here, we add rule sanity basic, and we run this again, Certora will actually give us an error and say, hey, you big dummy, obviously this is going to be true. Why don't you write better specs? And we want Certora to tell us that because we want to write better specs. And even though our output says, hey, no errors found by the prover, if we scroll up, we see we violated the sanity check here, where it's saying, hey, dumb rule, stupid rule, you violated it. This obviously is going to pass. So that's where this rule sanity can help us out in giving us some context. So it's good to have some rule sanities in here and read the outputs down there. So now let's create some of those rules or invariants that we were going to play with. So we did a little sanity check. We're going to play with this some more, but let's actually do this. Total supply is never negative. And this is one that's perfect for an invariant. It is one function that should never ever be negative, and Certora can go all over the place looking at all of our stuff to make sure that this is the case. If we look at our NFT mock.sol, we have this total supply function, which if we command click it, it says all tokens.length, and all tokens is our array at the top, and it's a unit 256. There should never, ever, ever be a scenario where this is negative. And it's pretty easy to look at this contract and be like, well, yeah, duh, like that's the case. If total supply is returning all tokens.length, obviously it's never going to be negative. This is going to be good practice for us to write these specs. So in here, this is a perfect use case for writing an invariant, which, as we know, we've learned that we could actually write it as a rule as well. But this is going to be a quick one-liner, right? So total supply is not negative, like this. And then in here, we can just say, oops, we do the same thing where we say total supply is greater than or equal to 0. Of course, we're going to need our methods block. Methods like this. Function total supply. External returns uint 256 env free. Like so. And let's just comment out our rule sanity for now. We're going to come back to it later. Now let's go ahead. We'll rerun this. with Certora run, or you can use make, whatever you want to use. And let's see how we get on. This is a great example of how simple some of these invariants can be. If you figure out your invariant and you can put it into a little one-liner like this, that is fantastic. That's what we want to do. And to me, right here, this is the power of Certora. I didn't have to do any setup. I didn't have to do any contract deployments, nothing. I just said, hey, that total supply function better always be greater than or equal to 0. And to me, the ease of writing an invariant like this is so helpful that it makes the user experience really, really nice. So really, really love this. To me, this is probably one of the best reasons why to use Certora right here. So after we run this one actually failed. Prover found violations. What the? Oh my goodness. It failed. Well, why did it fail? And if we go into the call trace, we can see a whole bunch of stuff that it did. So it took our storage state with the NFT mock and havocked everything, right? What does havoc do again? Well, it just makes all this stuff super random. So some of the different all tokens it made random. At the spaces it made random. All tokens index, balances made random. Own tokens. It just havocked and randomized everything. And on the right here, we see the counterexample. And we get this prover found violations. Total supply is not negative. Safe transfer from. That's kind of weird. What's going on here? Okay, so we click into this. We scroll down. We see unwinding condition in a loop. I feel like we've seen this before. Maybe in the Certora docs. If we paste this in here, what do we get? Loop unrolling. Oh, this was to do with the loop unrolling. Okay. We actually ran into this before again. This is when you have loops in your code that are getting a counterexample labeled loop unwind condition. So do we want to add this back in though? What's the actual loop? Okay, let's click on this. Let's look at the actual call trace down here. Looks like we're calling check. Looks like we're calling check ERC721 received. Then we're doing this if 2.code.length is greater than 0. And then we have this unknown loop source code. Okay. I think I know why this is happening. So if we go into our NFT mock.sol, we look at this code base, the ERC721, we command click into there, and let's look for this check on ERC721 received. It does this if 2.code.length is greater than 0. Try 2.on ERC20 received, message sender, blah, blah, blah. It tries to do this. And in making this call, it goes, oh, well, I don't know what code could be at this 2. So the code at this 2 could essentially be anything. So you can actually even see that here, this internal context message sender. We have this global state, kind of is havocing all this stuff. And it's not sure what's going on. So doing this call, it's like, all right, well, this could do anything. So we could just keep looping, keeping calling this. And it goes, oh, we ran into a loop. Break. So this is where we might go, you know what, for this invariant, maybe we do turn that optimistic loop back on so we don't run into this. And this is where you want to be a little bit sensitive with when you turn this on, when you turn this off, etc. So for us here, we're going to turn this optimistic loop check back on. Optimistic loop. We're going to say true because in our actual code base, right, in our actual ERC721.sol, we don't have any loops, right? If we do a little for like that, there's no like for loops in here. We know there's no actual loops. There's no actual assembly. This is Open Zeppelin. So we're going to feel pretty confident to make the optimistic loop here true so we can get past this error. Now doing so, sure, it'll make this unsound, but we think we're going to be pretty happy running this here. So let's run this again now that we have optimistic loop set to true, and we will see what we get. And after we run this one, we'll see we actually get this to pass. We go over to the prover, do a little refresh. We can see that these have actually passed. Prover is smart enough to know on these. However, once again, and you don't have to run this, if we change the rule sanity to basic and then run this again one more time, let's see what happens. on the Certora UI, you'll see this kind of weird sanity failed yellow thing. This is basically, again, Certora telling us, hey, obviously this is going to pass. This is kind of a silly check here. Total supply can't be negative. It's a uint 256 based off the length of an array. That's kind of a really silly rule. So this is Certora, again, this sanity check kind of helping us out. For now, I'm going to keep this as none, just so that we can write different specs to teach different stuff, right? So cool. Another example of a variant. Here's what it would look like. If we have this rule on, it goes, hey, this is kind of a stupid check, etc. So now let's do, oh, I actually wanted to put one more in here. Sorry. We're also going to do a parametric form of verification example, and I'll show you what that means in a minute. But so total supply is never negative. We learned that this was an example of a sanity check because obviously it's always going to be true. Let's do a much harder one. Minting, calling the mint function always mints exactly one NFT. Let's do this. Let's go to the spec. And this is clearly going to be a rule because we're saying if you do this thing, this other thing should happen. We could convert this into an invariant, but I think this will be much better to just have a rule. So we'll say rule minting mints one NFT, like so. So we're probably going to need to have the mint function in here. So let's scroll on up. Let's add the mint function. So we'll say function mint like this. This is external, right? If we go to the NFT mock, get the mint function here. Great. And again, we could put env free. We could put it in the rule, whatever we want to do here. So for us, we're going to follow the arrange act assert testing framework. So let's go ahead and arrange this test here. So let's just keep it not as env free just to practice working with envs. So the first thing we're going to need to do env e. This says, okay, e is now going to represent all of the environments of calling this mint function that we haven't added yet. We'll say address minter. There will be some minter address in here. And then we'll require that e.message.value equals 0. This is basically equivalent to having this be env free, well, to some extent. And then we'll also require e.message.sender equals minter. So this way, whenever we call this form of verification, we're basically saying the message.sender is always going to be this address minter. Cool. Now, what we're going to do to make sure only one NFT is minted, we're going to get the balance before. We're going to get the balance of, and this is where we're going to do function balance of, and what is the, takes an address. This is definitely external, returns uint 256. This is definitely env free because it's a view function. And then down here, we can say uint 256 balance before. This could also be a math int like that, but let's do uint 256 equals nft.balance of the minter. And this is pretty much all the setup we're going to need to do. Now we get to act. And if we want to interact with the current contract, right, in our configuration file, this is going to be the NFT mock. Here we can just say current contract.mint. And whenever you work with a non-env free function, the first argument that you pass to it has to be the E, or has to be some environment. So we're going to pass E. And then finally, we can do our assert. So we're going to say assert nft.balance of minter. It's going to be equal to balance before plus 1. Now we could do this, but it's probably better to not use uint 256s here. Why? Well, because balance before as a uint 256 has a cap. So it's probably better to make these math ints after all, because this plus 1 would basically overflow. So we can go ahead and we can do math int like this. And then down here, we say to math int. This is how you convert to math int. And then additionally, we can also write a little assertion error code. If it doesn't do what we want to do, we can say only one NFT should be minted. Now, if we want, we can comment this one out because we've already kind of practiced it a lot. And now we can test out our new rule that we just created. So let's give this a whirl. Boom. Let's run this and see what we get. Oops, NFT, oh, sorry, not NFT dot. Although if you look in the GitHub repo at the top, we have using NFT mock as NFT. And similar to Solidity, you can actually rename different contracts you're working with in here. And then if you want to be a little bit more explicit, so then you could do like nft.balance of. We're not going to do that. We're just going to do directly with the contracts. Let's run this again. And we wait for the server to get going. And we can see that after running this, we do indeed get some passes, but we did a good job. Cool. Let's keep going. And now we're going to do a parametric example. So we're going to create a rule known as a parametric rule. A parametric rule is a rule that calls an ambiguous method, either using a method variable or using an overloaded function name. The Certora approver will generate a separate report for each possible instantiation of the method. This really just means any rule that contains an undefined method variable. So any rule, could even be rule sanity, where all of a sudden it's just method f. This is now a parametric rule. So this method type is we're saying we have this object f that's of type method. And with this f thing, it means we could call any function selector, etc., just with this f thing. All we would need to do is add env and call data arg, and then we could say f e arg like this. So we're saying we're calling any method using any environment, any message.sender, any message.value with any lump of call data. And this is the most minimal example of a sanity rule. We have any random method with any random environment, any random call data, and here's how we call it. And this is really powerful because we can do some really cool stuff with parametric methods like this. So what I could do is I could create a rule where I say there's no change to total supply, right? And in here I could do, I could do method f right in here, define one, but I actually kind of like to do method f as a parameter up here. And in here, I'll say U256 total supply before equals total supply, like so. env call data arg, f e arg, and then we could say assert total supply equals the total supply before, comma, total supply should not change. So this could make for a pretty decent invariant as opposed to a rule here, but I want to show you that this is what a parametric rule could look like. We are passing any method f, and we're saying we have the total supply before. We call any method at all, and we want to make sure that the total supply doesn't change. And what's cool about this is it's very similar to the stateful fuzzing that we did before. Because what Certora is going to do is it's going to set up the contract to have havoc storage and be in random states and say, no matter what state it's in, if you call a function, if you start with a total supply and then you call a function, the total supply should still be exactly the same. Now, we obviously know that this should be false, right? Because NFT mock.sol has this mint function, and when you call mint, it increases the total supply of the ERC 721. But this is how we can make super, super customizable rules saying any method, you call any method like this, passing any environment with any call data, and we want to make sure the total supply doesn't change. So let's go ahead and run this, and you will see, of course, this fails, and we'll see why it fails. But let's go ahead and comment this rule out so that the only rule in here is our no change to total supply, our parametric function, which will, of course, fail. Our parametric rule, not parametric function, sorry, which will, of course, fail. Now, of course, when this finished, we see no change to total supply. We have a little transfer from here, or safe transfer from, and we can see some of the different functions that actually violated this. Looks like somehow safe transfer from violated this. That's kind of interesting. Maybe check ERC20 on received called mint again. That's probably what it's doing. It's saying, hey, if I call safe transfer from and we call ERC 721 received, we could call mint or transfer from again. Okay, that actually does make sense. So we see that failed. We see safe transfer from failed. We see mint obviously failed, right? And if we click on the call trace, we can see it called NFT mock.mint. We scroll down. Obviously, it increased the all tokens. We called safe mint. This increased the global state storage balances, NFT mock. All tokens is now 11. That means total supply has increased. Transfer from because of that fallback function. So this was a great example of a parametric rule that's actually going to fail. But we actually saw it go through and actually run through this on all these functions in the contract, all of these functions in here, which is incredibly powerful. And we get to work with all the different methods in the contract. Nice. So we learned a little bit here. And again, I wanted to warm you up here, introduce you to these parametric functions, because we're going to get a little bit more complicated when we actually go over to verify the Bad NFT Marketplace. So let's do a quick recap of what we learned here before going over there. We watched another example with invariants, and especially we learned about different type of rule sanities, which said, hey, this rule is kind of stupid. Maybe you don't want to do this rule. It's a tautology. It's a very obvious use case, etc. The sanity one down here, hey, satisfy true. This is just always going to be true. Are you sure you want to do that? And then we learned this is kind of what we look for when we're doing invariants though. These real simple one-liners, there's no preserve block. This is some beautiful syntax that we could just drop into our protocols very easily that have well-defined invariants, and we love to see this. We did another example of a very basic, very simple rule where we worked with the environment E. We did some requires, we learned about the current contract, and we added some error codes to our asserts. Finally, we learned about a new thing, parametric rules, which are any rules with this method F, right? We also learned about this call data arg type. Like we said before, there's a number of different types in CVL, including mathint, method, and call data args, which we just learned about. The storage type, which we haven't used at all, but that's another type that we have as well, where we can see what storage looks like. The env type, which we definitely learned about. And then uninterpreted sorts are used to represent unknown types, which we haven't worked with either. But we did a really basic parametric rule with rule sanity here. And then finally, we did a more complex parametric rule, which obviously failed, but really just to show off the power of what a parametric rule can do. Now that we've gone through a little bit of this verification testing, I'm just going to comment everything out just in case we accidentally run this, although we shouldn't. Now we're going to finally move over to verifying the Bad NFT Marketplace. Let's do it. So let's create a new file, gasbad.spec, and we'll do gasbad.conf, like this. So I'm going to copy paste the configuration from gasbad.spec over to here. And I'm just going to cheat a little bit. And I'm going to tell you, I am going to be using the optimistic loop is going to be true. We're going to put rule sanity on basic. Now that we've played with it a little bit, we do want this here. Verification of gasbad, wait for results, yes. Verify is going to be gasbad NFT Marketplace. And this is going to be in Certora spec gasbad.spec. And there's actually going to be a few files in here. So we want to get src/gasbad NFT marketplace.sol, the gasbad NFT marketplace. We want to be comparing this marketplace to the regular marketplace. So we're also going to want src/NFT marketplace.sol, the NFT marketplace. And then additionally, we're going to want to work with some NFTs. So we're going to say the test/mocks/NFT mock.sol, NFT mock. So these are all the contracts we're going to grab, and here's what we're going to verify. We're going to use the optimistic loop, the rule sanity basic, and we're probably going to add one more prover arg in here in a little bit, but we'll get to that when we get to it. So now let's go down to the gas spec. Let's do a little comment here to get started. Verification of Bad NFT Marketplace, like this. Cool. And let's go over to our README, figure out what we need to be formally verifying. Let's do it. All right, so the first one, anytime a mapping is updated, we emit an event. Whoa, that sounds kind of hard. How do we figure this one out? Can we even do this? Patrick, you're picking a very difficult thing here. We definitely can do this, but we're gonna have to learn about a couple of new things here. And the first thing that we need to learn about is this thing called ghosts or ghost variables. So ghosts are a way of defining additional variables for use during verification. These variables are often used to communicate information between rules and hooks, which, guess what? We're going to learn about hooks in a bit, and define deterministic function summaries, which, Guess what? We're going to learn about those too. So if we scroll down in the docs, we have some context about declaring ghost variables. And we want to mark them as ghost variables because we're saying, hey, this is a variable that we're using specifically for Certora. It's a variable we're using to keep track of something. So the way we can initialize variables is we can just say ghost uint256 x, like that. But wait a minute, what are we trying to do again? Anytime a mapping is updated, we emit an event. So we could probably track the amount of times that one of these mappings gets updated. So where do we have, okay, so we have S listings. So maybe we just track whenever this gets updated, which this is a storage variable. Can we track that? Yes, we can. Don't worry, I'll teach you in a second. So we're gonna say ghost. We're gonna make this actually a math int instead of a uint256. This is a ghost variable and we don't really care if it's a uint256 or a math int or whatever. It's just much easier for this ghost to be a math int. We'll call this listing updates count. And we're going to use this to count anytime this S listings mapping is updated. So this is what we're going to be using to do that. And this isn't quite right, and we'll get to that in a minute. But this is what we're going to use to do that. How do we actually count how often this is updated? Or is there a way to do that? Well, maybe we figure out a way to listen for list item, but that doesn't sound very formally verificatable. That doesn't really even make sense. Is there a way for us to literally just say anytime the storage variables of S listing are updated, we call it out and we do something? And sure enough, there is. So Certora has this thing called hooks, which are down here in the documentation. So hooks are used to attach CVL code to certain low-level operations, such as loads and stores to specific storage variables. That sounds perfect. What we can do with a hook is basically we say, hey, anytime a certain variable has an sStore action happen to it, an sStore action happen to its storage slot, do something. Oh, well, that actually sounds perfect. So let's create that. So let's do hook sStore. And as of right now, this is the syntax. Yeah, the capital kind of bothers me. But we'll say the S underscore listings variable, right? Because this is the name, S listings. Anytime S listings has an S store, so anytime this is updated, and we do a little bit of CVL syntax in here, we say the key is going to be an address, NFT address, right? Because in here, it's address, NFT address. So this is the key. So we say key, address, NFT address. And then the second key, because it's a mapping in a mapping, is going to be a uint256 token ID. So we'll say key uint256 token ID, and that returns a listing. However, listings are structs. And Certora doesn't do super hot with structs, but it works great with our primitive types, like a uint256 or an address. So we would then need to say .price or .address, whatever we want. It doesn't really matter. If one of them gets updated, we are happy. So we're going to do .price. So anytime this is stored, this price is of type uint256, and we're going to call it price, although we're not going to use this variable at all. We then just say storage, because our hook is exclusively for storage. Wow. So that hook looks pretty ugly. Let me break this down a little bit. So you can have a hook for pretty much any EVM opcode, right? So we're just doing store. But you could do gas price, block hash, timestamp, literally anything in here. Once you pick the opcode you want to look for, you can pick the variable that is associated with that opcode. And then you say, okay, this is going to be updated with some type, and we'll call it price. So if this mapping got stored with maybe the number 7, this variable price would now be what's in here, right? So I can make this like dog or whatever I wanted. And then in the hook, I could work with dog, right? Or 7 or whatever I wanted. Now, we don't even have to have this in here. We could just leave it blank, but I think it's nice to put in here anyways. And then additionally, this store hook is known as a store pattern. And all store and load patterns must end with storage. So we have to just put this keyword storage in here. Let me do a little toggle word wrap. So it has to end with storage here. This could also be like sload. So anytime somebody reads from this, I would need to update this, but anytime somebody reads from this, it would need to end with storage. So store, boom, storage. So now that we have this hook, basically anytime this storage variable changes anytime sStore is called on this storage variable, what do we want to do? Well, we can say listing updates count equals listing updates count plus 1. So now we are keeping track of how often slistings is updated. So anytime this is updated, we're going to increment the count. And now all we have to do is check that the number of events emitted equals the listing updates count. Now we could probably have a more clever ghost variable where instead of just keeping a list of the count, we actually keep a ghost array of the different prices or dog or whatever. Let's put this back to price, of the different prices that have actually been updated, and make sure that price is in the actual event if we want to be really good with it. But this is a learning lesson, so we're going to be a little bit simpler here. I will say though, something like this should probably exist on every single smart contract that exists. We should be running a really generic formal verification script where anytime a storage variable is updated, we emit an event. So there's your alpha right now. You can go out and write formal verification test suites, at least just looking to see and make sure that everyone emits events no matter what. That would be a great world. This is going to be our listing updates count. Additionally, we should probably also count the number of events that we emit. Same thing, right? Now that we kind of know the setup, let's do the same thing. So let's do ghost math int. We'll call this log4 count because we know what in here we have log4. All the events are being emitted with this log4. So we'll just count the number of these log4s that get emitted. So we'll say log4 count, and we'll create another hook. So we'll say hook, and this time it's going to be log4 because we're just going to say anytime the log4 opcode gets emitted, we're going to do something. Now this hook is going to look a little bit different. For this hook, we're going to have the different variables on the stack saved in our form of verification test suite. The offset, length, topic 1, topic 2, topic 3, etc. So actually for us, we can just copy paste this whole thing and paste it like so, because this always has to be what this hook looks like. And inside of here, we're just going to put log4 count equals log4 count plus 1, like so. Great. Now, if we were to create a rule which does some stuff and storage is updated, this actually would all fail. This wouldn't work here. Listing updates count would not actually update as such. It would not start from 0, and neither would log4 count. And the reason for that is, unlike in Solidity, our ghost variables are not initialized to 0, right? They don't start off like this. We actually have to initialize them using the init state keyword. So when it comes to writing your ghost variables, you need to create what's called an initial state axiom. So there's these two keywords we're going to learn about, both init state and axiom. This init state keyword sets the initial state to be whatever you want it to be. And then the axiom keyword says this is going to be something that always must hold true, which might be a little bit confusing, but axioms are CVL expressions that the tool will use to then assume are true about the ghost. And then init state refers to the initial state of the ghost. So in here, instead of having listing updates count like this, we would need to do init state listing update count equals 0. And you could do this, but we need to tell Certora, hey, make this always true. And we just say axiom. Init state axiom listing state updates count equals 0. So this is kind of the equivalent of saying, hey, the initial state will be 0 and then require such to be true. So this axiom kind of works like a require in this sense. So, or excuse me, not equals, not set to 0, equals 0. Because this axiom is basically acting like a require around this listing updates count, saying the initial state is listing state equals 0, and then require that to be true. So that's essentially what this is doing. And we're going to want to do the same thing for our log4 count, init state, axiom, log4 count equals 0. Now, when we do this, Certora will start both of these at 0 and make sure that they start at 0, essentially. So this is how you set the initial values for our ghost variables. If you want to see what happens in Certora, if you don't do this, go ahead and get rid of this and put it back to normal, and you'll see you get kind of wonky results. But okay, cool. So now we have two hooks that track anytime sStore is called for this mapping. We probably would do this again for our other mapping, maybe our other variables in the mapping. And we have a hook where anytime log4 is called, we go ahead and we update this log4 count. So we're updating both of these. So essentially we're tracking anytime this mapping is updated and anytime we emit a log4. And using this knowledge, we're going to say, hey, anytime storage is updated, an event should be emitted. And we're keeping track of that. So now what we have to do is obviously write the rule or invariant to check this. So we'll create a little, I want to do headers rules like this. Grab this because that looks very nice. Rules. Pop this over here. And we'll create a rule or invariant for this. Now, this is again why Certora is so nice. Now that we've set these up to always update these two variables for whenever storage or an event is emitted, what we can do is we can just turn this into a very simple invariant. We don't have to do any weird setup. We can say invariant anytime mapping updated emit event like this. And we can just say listing updates count must always be less than or equal to log4 count. And the reason we're doing less than or equal is because maybe we emit log4 for different reasons. Maybe we emit it for updating different storage variables. So there should never be a scenario where we update our storage here more than we emit an event. Like I was saying before, this is kind of the easier approach to doing this. Realistically, we would want to say anytime storage is updated, also check to see if log4 was emitted. But for simplicity, this is how I wanted to show you this. So this should be valid and this should hold. But let's see what happens when we actually run this. So we're going to run this. This is our invariant. We're basically checking that the number of times we emit this storage variable is less than or equal to the number of times we called the log4 opcode. So let's do this. Certora run Certora conf gasbad.conf. And we're going to this up. It's giving us some warnings saying, hey, you don't actually need to write the name of the file, but I like to because that's what I like to do. And it says gasbad.conf here that we're running. And let's see what we get. So after running this, after running our invariant here, we actually get an error on Certora. So let's go ahead and let's look through this and figure out why. So it looks like we're getting errors on all of these. Let's go check the call trace. Oops. Let's go check the rule here. Looks like NFT Marketplace, buy item, list item, cancel item, withdraw proceeds. Looks like these are all violating it. Looks like for some reason withdraw mock is violating these. Bad NFT Marketplace is violating these as well. Looks like, so basically this is telling us there's a function in each one of our contracts that's violating our invariant here. So it's saying there's a scenario where we do a storage update without emitting a log. So let's go ahead and dig into the logs to figure out why this is happening. And let's click this one. Yeah, Bad NFT Marketplace list item. This is one that we want to emit an event, and it's saying, hey, it's potentially not emitting an event here or not emitting enough events. So we'll click on this list item right here. And let's go through the call trace a little bit and understand what went down. So the global state was set up. Storage state balances, sure, whatever. Storage state, we don't care. It can be kind of whatever it wants. Balances also don't really matter. And the ghost states, wait, count -1, log4 count -1. What? Hold on. We said the initial state for both of these should be 0. So why are they being havocked to -1? And what's this havoc mean again? So the definition of havoc, according to the glossary, is going to be, in some cases, the Certora prover should assume that some variables change in an unknown way or can change. For example, an external function on an unknown contract may have an arbitrary side effect on the state of a third contract. In this case, we say the variable was havocked. And there's some havoc summaries that we'll talk about in a bit. So what this is saying here is that, sure, the ghost states were initially set to 0. However, some other function in any of these contracts could have changed what our ghost variables are set to. And Certora can't reason about effectively what these other functions can do. So Certora goes, you know what? We're just going to set them to something kind of random where we can find an edge case. So our two ghost states, yes, they did actually start as 0. However, Certora is telling us that during the call trace that it found a counterexample, some other function could have potentially changed these. So since Certora doesn't know what they could have been changed to, it says, you know what, we're just going to havoc it. We're going to say these could be really anything that we want, and I'm going to use that to find a counterexample. This actually was a question that I had to sync with the Certora team. Why is my ghost variable havoced when it has an axiom? I said the exact same thing. Certora team answered it with basically exactly what I just said. And I guess this is a little spoiler alert on how we're going to change our code base. But in any case, okay, so having them both start at -1 probably won't be an issue anyways, right? So let's keep walking through the call trace, seeing what else happens. All right, there's a little bit of a setup here. Assume invariant in pre-state. Yep, -1 is indeed less than or equal to log4 count. So great. Obviously that's going to hold. Now check effects of step taken by one of the functions. So this is where this is going to be their counterexample. And so this is them saying, hey, something in this list item transaction caused the invariant to be broken. So let's read where there was an issue. So each one of these steps is going to be a step in calling the function. So we have a sender of the transfer, and then they actually go through some of the lines of code and evaluate the branches, evaluate the different possibilities. And if we scroll down in here, we can even see the apply hook store, right? So we have this Bad NFT Marketplace's S listing is updated because we updated storage. And if you even click on this, it says, hey, ghost red listing updates count is -1. It gets assigned to -1 + 1, which ends up having this listing updates count updated to 0. And that's what we want to see, and that's good. So then there's a store. This is the actual storage that happens. And Certora is able to see storage happened with price, storage happened with seller. And then we also applied our hook log, right? Our log4. So we did indeed emit an event. So right back in our NFT marketplace.sol, right? List item. We're basically going through this list item function, caught this, and it said, okay, we updated storage here. And now it's even saying, oh, you even emitted an event. And sorry, this is actually on the Bad marketplace here, where this assembly is happening. And it says, oh, cool. Yeah, you did indeed do a log4 here. So, okay. And we updated our ghost parameters, right? Ghost assignment, log4 count equals log4 count + 1. So now it's 0. So great. So we did indeed update the log4 count. So what's the issue here? Why are we getting a invariant break here? So next we do this little safe transfer. What is this default havoc? So in the Certora guide, in the Certora documentation, they talk about an example very similar to this. If we look up default havoc in parentheses, there's a little example in here, and it says, here we see that calls to the transfer from and balance of function are marked with default havoc. This means that the prover lets the call to transfer from to change the balances any way it likes. In fact, calls to asset.balanceOf are also unresolved, so the prover can choose any return value that causes a counterexample. So what's happening here is we're seeing this safe transfer from, and we'll talk about auto summaries in a minute. We're seeing this safe transfer from, and Certora is going, oh, this safe transfer from function can actually do a lot of stuff. When we call list item, we're calling transfer from on some random address. The Certora approver goes, hey, you're calling transfer from on some random address. That random address hypothetically could call any function in the Bad NFT Marketplace. So because the prover looks at this and goes, well, any NFT contract could have their transfer from function be anything, that means it could affect our contract in ways that we don't understand. So it says, because of that, we're going to havoc all non-persistent ghosts. Ghosts are havoced, and we're going to havoc storage. We're going to havoc basically anything because we're making this external call and we can't prove what it will or will not do. And this is good. We want this. We want the prover to say, hey, is there any scenario where something makes a mistake? And Certora goes, hey, you're making this weird external call to a contract we don't know about. It could have random arbitrary side effects. So guess what? All non-persistent ghosts were havocked. And this is where, after this line, our two ghost variables, back over here, our two ghost variables, according to Certora, are now literally anything. Because we're calling this external function could do some reentrancy stuff. It could do literally anything. So it says, great, everything's havocked. And because everything's havocked, as we scroll down to the bottom, we now get assert invariant in post state, ghost red, where updates count is greater than log4 count. Because of this safe transfer from, Certora said, we're going to make these random. And since it could make them random, listing updates count could be greater than the log4 count. So that's how this is ruined. We call this external random safe transfer from Certora havocks or randomizes our variables here. And there's a scenario where it just randomizes the listing updates count to be greater than the log4 count, breaking our invariant. So are we doomed? Is there a way to write a better form of verification spec? Well, there sure is. There's actually a number of things we can do. Right in here, one of the things it says is all non-persistent ghosts were havocked. So there's a key word in Certora ghosts called persistent, which allows ghost variables to survive havocks. Instead of having our ghosts look like this, we can instead say persistent ghost and run it like this. If you have persistent ghosts, this makes it so that anytime there's a havoc, anytime there's a weird randomization thing, just keep your ghost variables as they are. And if we reran our Certora tool, I already reran it, so I'm not going to show you, we would indeed pass. Like this would be great. Like anytime mapping updated, emit event. Awesome. So this would be one way to write our form of verification. However, obviously, this would be a bit unsound. And again, you're starting to see how much you have to think about when you do write these form of verification specs. Persistent would solve the issue, but it would also mean that these external calls to safe transfer from could update storage, and we're ignoring it. So having these be persistent means that anytime there's a havoc example or your smart contract could do something with unknown side effects, these ghost variables would ignore that. But oftentimes we don't want to just make these persistent. Oftentimes this is kind of a cheap, easy workaround. So we're not going to do that. But that is one way that you could do. So we could do that, but it really looks like it's seeing this safe transfer from function and it's going, hey, safe transfer from can do anything. So havoc, right? Now, this is actually really good because safe transfer from could do anything. Maybe we want to tell Certora, hey, yeah, we know safe transfer from could do anything, but for the purpose of this prover here, maybe it does everything, but assume it can only do one specific thing, or assume that we've already defined what this safe transfer from can do. And this is where we get into method summaries. So we kind of have already touched on the methods block. We haven't made one for this yet, but we're going to. The methods block is actually even more important than we originally thought it was. So we haven't written any methods yet. We're just saying, hey, do whatever you want to this and track the storage and the logs. But there's actually two types of method blocks that you can have. You can have non-summary declarations and summary declarations. So when we worked with our NFT mock.spec, these were considered non-summary declarations. A non-summary declaration just means use the function as defined in the code base. However, sometimes the functions of the code base could be too complex. For example, maybe total supply does some crazy math with some crazy while loop, but it's really just always going to return a positive number or something. Sometimes the functions are only called by one or two contracts. Sometimes we just want to make more assumptions for the prover so that it can run, so that we avoid maybe like a path explosion problem. So when we make non-summary declarations, we're basically saying, hey, this is a function, use it in all its glory, do whatever you want with it. But additionally, we can make summary declarations, and these are incredibly powerful. We basically say, hey, instead of using total supply as how it's defined in the contract, we're going to replace total supply with something else completely. So maybe if total supply was kind of this crazy, hard to understand function, we could just say, hey, anytime you call total supply, it should always return 1. And now this is what's called a summary declaration. We've now told Certora, hey, yes, there's this total supply function, but it should always return 1. So these summary declarations basically allow us to say, yep, there's this function, but we want you to do something else with it instead. And in the documentation for the methods block, there's a lot of different types of summaries. The most important ones are going to be view summaries, havoc summaries, dispatcher summaries, auto summaries, and function summaries. And this is probably one of the most important pages in the Certora documentation in my mind, is how to actually work with these methods and these method blocks. Now, not only are there different ways to summarize functions, there's also different ways to enter, call, or invoke functions. So far, we've just been assuming that the contracts that we're verifying, we're going to exactly call the functions inside of those contracts. However, there are other ways that you can tell Certora how to interact with any function in your entire system. We've already seen some basic methods, the basic syntax, but there's a couple of different types of entries that we actually haven't seen. So we've been doing our methods block pretty minimalist, but there's actually a ton of different things that you can do in here. So we have exact entries where we pick exactly a function, like what we've done with total supply. But additionally, we can do wildcard entries. Whenever we say total supply here, we're secretly saying current contract dot total supply. And all of these are assumed exact entries just with current contract appended to them. But these could be wildcard entries with an underscore on here as well. Adding wildcard entries would mean that this function declaration applies to any contract with the total supply function. And we could even add a summary declaration on this to say always returns 1, which would mean any contract that has a total supply function should always return 1. So now we have a summary declaration and a wildcard function declaration. I'm saying kind of a lot of words here, but I think I trust you understand the gist here. We can have catch-all entries, which almost do the opposite. We could say maybe current contract, I don't know, you'd want to do this, dot underscore external returns always 1. And this would mean that no matter what contract you're working with, every single function should just return 1, which would be kind of a silly one to do, but that's something we could do. So that would be an example of a catch-all entry. We have visibility modifiers, which we understand. We can work with different visibilities. Free, we've talked about. We can say a function is optional. And there's just several other ways we can create a method in our methods block. But let's focus on these summaries, these summary declarations. For any function where there's this little arrow piece here that recognizes a function as being a summary declaration. We're saying, hey, yeah, we know total supply does something, but let's replace it with something else. And there's a ton of different things that we can do in here. For us, we actually already looked at some of these different view summaries, like we played with always a lot, but we could have it be constant, per Cali constant, or non-det, which stands for non-deterministic. If you have a really complex function and you don't want the prover to have to run into the path explosion problem, you can just say, hey, it's a non-deterministic result. Boom, you would just add this as the function summary. And now total supply, according to the prover, would just return borderline random stuff. So those are the view summaries. Okay, what about the havoc summaries? You can have havoc all, which is the most conservative type. And this just says, hey, this total supply function can do literally anything. Havoc everything every time this total supply is called. The havoc all approximation is sound, but it can be incredibly restrictive, right? Because if you're saying this total supply function can do anything, I mean, that's great because we're being incredibly conservative. We're saying, oh, any function can do anything, but we're going to run into issues where it becomes very difficult to prove anything, because if we just tell the prover, hey, anything can do anything, we run into some issues there. Havoc ECF, on the other hand, just says, hey, this function could almost do anything, except it can't re-enter the function. And that's often very helpful, especially if we have functions that are non-reentrant. And then we have dispatcher summaries. And these are going to be the solution that we actually use to solve this issue about default havoc, which again, we could have solved with the persistent keyword, but we're going to use this dispatcher to actually solve this issue that we're running into. A dispatcher summary just has dispatcher true or dispatcher false. That's it. That's what a dispatcher summary is. Dispatcher true just means that this total supply function, no matter who calls it, can only do stuff as defined by some other contract. That was probably a terrible explanation. So let's go actually back to the gas pad spec to show you what I mean. So let's make a methods block here, and let's create a function, and we'll do safe transfer from function, which takes an address, and EU256, and we'll make it external. So this is the function that our Certora report was running into. Safe transfer from address EU256, safe transfer from address EU256. If we make this dispatcher true, this means that only the known contract instances are considered, which means that we can only assume things about the safe transfer from function if it's defined somewhere else. So if we have this line, instead of Certora going safe transfer from could do literally anything, if dispatcher is true, it'll say, okay, I need to look through the currently known about contracts and find the different safe transfer from functions in there and see what those do. This safe transfer from actually can't do anything. It can only do whatever's defined in these known contracts. If we have this to be false, Certora goes up, safe transfer from can do literally anything. But if we have it as true, so what Certora is going to do is going to go, oh, okay, this is true. Okay, let me look for function safe transfer from. Okay, it looks like it's defined in mock ERC 721.sol. Oh, wait, I don't know about mock ERC 721.sol. I only know about these three contracts. Okay, well, does NFT mock have this? Okay, it's ERC 721 enumerable. Safe. Okay, it's an ERC 721. Okay, so there is a safe transfer from here. So I'm going to use this as the function declaration. Is there anything else in here? It looks through the list of known contracts, looks for safe transfer from function declarations, and says, I'm going to use one of these implementations as the safe transfer from function. So, no, there was a mouthful. So dispatcher true means safe transfer from can't do anything in the world. It can only do what any of the safe transfer from function definitions in any of the known contracts has. So if contract A has a safe transfer from, or contract B has a safe transfer from, Certora can go, okay, it's either going to do A or B, and I need to tread accordingly. So hopefully that makes sense. And you'll see in a second, trust me, you'll see in a second where we actually get this to fix our issue and why it makes sense. So just stay with me here. And additionally, actually, now that we're learning about summaries, you see in here that we have this auto summary. The auto summaries is going to be basically where anytime there's a method that's called, Certora automatically adds this auto summary to it. And the auto summary basically does exactly what you would think it would do, where it just automatically tries to pick what the function should do. So view and peer methods use the non-deterministic approximation, and they don't change anything on state. Calls to library methods and delegate calls are assumed to change the caller's storage in an arbitrary way. All other calls and constructors are considered Havoc ECF. So when you see this auto summary here, since this is all other calls, it just automatically applies the Havoc ECF. So that's why this says default Havoc, because auto is defaulting this to Havoc over here. Again, if that's a little bit confusing, don't worry about these. Don't worry too much about these quite yet. Let's just focus on the task at hand, shall we? So back in here, right now, us defining this method as such, we're basically saying current contract dot safe transfer from is going to have this dispatcher summary, meaning that safe transfer can't just do anything. It can only do this true thing. Now, the issue here is that the gas bad NFT Marketplace.sol isn't the one actually calling transfer. It's this ERC 721.safe transfer from. So saying current contract.safe transfer from dispatcher true actually doesn't do anything, because current contract is going to be gas bad NFT Marketplace, and gas bad NFT Marketplace is then going to call safe transfer from. So we want to tell Certora to have any contract that calls safe transfer from should not be default Havoc, but you should pull from an already existing implementation of known contracts. In our gasbad.conf, we're passing nftmock.sol. nftmock.sol has an example of safe transfer from, so use nftmock.sol. So since dispatcher is true, we're basically saying use nftmock.safe transfer from for all safe transfer from calls, no matter what. If there was like an NFT mock 2 contract that also had safe transfer from, this line here would tell Certora to use nftmock.safeTransferFrom or nftmock2.safeTransferFrom. It would say use either or, but since we only have safeTransferFrom defined in our NFT mock, we're telling Certora, hey, just use the NFT mock. Now we're adding some assumptions onto our system with this, right? We're assuming that the NFTs that we're going to be interacting with are not going to mess with storage. Maybe that's a bad assumption. Maybe after we write all this, we should write another invariant that says external contract calls can't mess with storage of this contract. But for now, we're going to have this be our catch-all, and we're going to assume we're working with NFTs with a simple or basic transfer from function. And I know I said a lot here, so let's run this, see what we get, and then we'll do a quick recap of what we just learned. So in here, we're going to do Certora run once again, and we'll see what happens with the prover now that we've said, hey, don't havoc safe transfer from. Use a safe transfer from implementation that is in your list of known contracts. And I'll give you a hint, we will run into an issue. All right, so after running this, it looks like we still get an error. Now that we know a little bit more about the prover, maybe you can guess why. So let's walk through this. Let's see where this error is. Let's open this up so we can see it a little bit better. Okay, we have buy item. Let's scroll down in here. Everything looks pretty good so far. Now for safe transfer from, we now see dispatcher instead. Okay, so let's look in here. Okay, NFT mock.safe transfer from, right? So now, since we have dispatcher be true, it says, hey, anytime we see safe transfer, we're going to call the safe transfer from of the NFT mock because that is a contract that the prover knows about. Okay, very cool, Certora. Okay, next. Okay, it's going to evaluate some branches and stuff. Okay, whatever. NFT mock.safe transfer from. Cool. Okay, clickety click. Let's keep opening these up. Oh, good. There's so many branches in here. Ghost states. Okay, let's click into this branch. Let's click into this branch. Oh my goodness. Okay, it looks like nothing weird happened there. Let's look in here. Let's keep opening up these branches. That looks fine. Oh, there's so many branches. Okay, there's an approve. Okay, what else? Okay, there's an apply hook. Okay, cool. Okay, evaluate branch. Okay, here's another one. Okay, context. Aha, we found a default havoc. So this is pretty much often what you're going to be looking for when you do run into these errors. You want to find, obviously when you scroll to the bottom, we have assert invariant in post state, listing updates count is 1, and log4 count is 0. So we want to find where did this update in extra time or where did this not update, and it should have. And we can scroll back up, and oftentimes finding a default havoc is a great way to find it. And we found ours in this internal ERC71 _ check on ERC721 received from Bad NFT Marketplace. And we have this on ERC721 received default havoc. And because we havocked, all non-persistent ghosts were havocked. So that's telling us somewhere in our NFT mock, there's going to be this on ERC721 received function that it's havocking. And you might be like, Patrick, what the hell are you talking about? Just real quickly again. So our Bad NFT Marketplace is going to call buy item. That's what we're calling in Certora. This buy item function, right? Buy item will call the safe transfer from on some random address, but we're dispatching it. So it's going to go, okay, let's use the NFT mock implementation of safe transfer from. So it goes, great. We're going to call safe transfer from on our NFT mock, which we have defined here, which will then call this check on ERC721 received function, right? This check ERC721 received function, which will then call this on ERC721 received function, which we know this too is our Bad NFT Marketplace. But according to Certora, this is some random address calling some random ERC721 receive function. So guess what Certora is going to do? It's going to havoc. It's going to Wreck-It Ralph havoc. So we want to be able to tell Certora, hey, this random address is us. Only call the on ERC21 receive function that is implemented in the Bad NFT, which, as we know, is going to be this static return down here. So what can we do? Well, we can do exactly what we just did. We go, okay, it's assuming this on ERC721 receive function can do anything. let's make it so that it can only do on ERC 721 received of a defined function. And we could say function underscore dot on ERC 721 received. Let's see what the address uint256 bytes, address uint256 bytes, external. We could do a bunch of stuff here. We could say dispatcher true. And if we put dispatcher true, it would probably set all on ERC 721 receives to what's in the Bad NFT Marketplace. We could also use one of our other summary blocks as well, because this is going to be a view or a pure. So we could say always constant, per Callee constant, or non-deterministic. So maybe we just go, hey, you know what? This is just going to always return 1. And either one should work and allow us to get past this bug. But remember, when we add these in, we're making some assumptions about our system now. We're saying the safe transfer function is going to be a basic safe transfer from function. And we're also saying on ERC 721 received is going to always return some static variable. But let's run this one more time and see if we get past all these issues. After running this, looks like this failed too. Well, the good thing is now we're getting really good at reading Certora prover issues. So let's go in here again. Let's clickety-click. Okay, Bad NFT Marketplace. Withdraw proceeds has an issue. Okay, let's minimize this. Let's open up the call trace and let's see what happened. So global state. Okay, ghosts were havocked to 0. Okay, that's cool. Setup, assume invariant. Looks like the invariant pre-state was good. Now check effects of a step taken by one of the functions. So let's scroll down here. Let's look for a havoc or an issue. Aha, okay. Bad NFT Marketplace calls payable message.sender.call. Well, of course this havocked because call can literally do anything, right? So in our Bad NFT Marketplace, in here, we did a call somewhere. Where did we do the call? In withdraw proceeds, we're doing call right here. And of course, call can literally be anything. So our smart contract goes, since call could literally do anything, it could re-enter this function and do some crazy stuff. We're going to havoc everything. And since we havocked everything, we scroll on down, assert invariant in post state, listing update was 1, log for count is 0 because we havocked. All non-persistent ghosts were havocked. So that gave us an issue. Okay, well, at least we're getting a lot better at solving these issues quickly and figuring out why some of our form of verification is breaking. What can we do here? Well, again, if we wanted to, we could say, you know what, screw it. I'm just going to make these ghosts persistent. But it's great if we're way more explicit because at least when we define our methods block like this will tell us what our assumptions are. We're assuming something about safe transfer from. We're assuming something about on ERC 721 received. However, if we just do persistent like this, it's really hard to tell what we're assuming. So this is going to be a much better written spec than just using persistent because we know what our assumptions about the code base are. So how do we solve this one where calls are even havocked? What could we do there? Could we do function underscore dot call? Well, no, that wouldn't make sense because call isn't defined as a function. Like call is a low level of the actual language. And this is where we can use one of the prover args. So back in the Certora docs, we scroll up to this, we can look up prover args like this. And the CLI or the config file has this thing called prover args, where we can add a ton more different types of arguments into our config file. And I highly recommend you check these out to see what a lot of these do. One of the prover args is going to be optimistic fallback. So the optimistic fallback prover arg determines whether to optimistically assume unresolved external calls with an empty input buffer can make arbitrary changes to all states. So this is essentially, if we set prover arg's optimistic fallback to true, this would tell Certora, hey, next time you see a call like this, just assume it cannot make arbitrary updates to our code base. And if we want that, all we'd have to do is open up our gasbad.conf, and down here we would say prover args dash optimistic fallback true. So anything you put in this little prover args list here would be the same as if you put it directly in the command line. So we have prover args optimistic true. We have a dispatcher summary for a safe transfer from. we have an always summary for our on ERC 721 received, which could also be a dispatcher summary. And now we're going to say, okay, if you see some type of fallback function, just assume it's not going to re-enter this contract and cause a whole bunch of random storage to change. So now that we have all of these defined, let's run this one more time. Oops, unless I forgot the comma here. Now let's do this. Okay, cool. And here's the output. So now we're getting somewhere, but we have this sanity failed here, right? And remember, this is because in our conf, we have rule sanity basic. So if we go into here, if we go to rule problems, we see vacuity check failed. This again means that what? Total absence of matter, emptiness, total lack of ideas, emptiness of mind. I always think that that's really funny whenever I read the definition of vacuity and it's like, oh, you have a total emptiness of mind. I feel like Certora is low-key throwing hands on my intellect here. Vacuity refers to the state where we have a spec reported to be correct by the prover, even for assertions that are obviously wrong. Basically, an assertion in the spec is effectively not checked because no input satisfies all requirements defined in the spec. So the vacuity check here isn't saying that you're stupid. It's actually just saying an assertion in the spec that isn't checked because no input satisfies all requirements defined by the spec. So this check failing for being vacuous is failing because why? This is where debugging these sanity checks can actually be kind of tricky. Because looking at this, we say, okay, update listings is good. It's actually not a stupid check. Withdraw, all these functions are good except for list item. For some reason, list item is failing. Why is list item failing? Well, it's not failing. It's just saying, hey, this is a really silly check. And if we click on this, unlike a failed rule, there's actually no call trace that we can kind of debug. So debugging these kind of checks can be really difficult. But actually, if we go into the documentation, these are actually really important because these could tell us, hey, maybe we have some prerequisite that never can hit. And so like your rule doesn't make any sense. For example, require X does not equal X, assert false, will never be able to be reached, right? Because there's no input X that will satisfy X does not equal X. When we get these, we do want to figure out, okay, why did we get these? However, I have gone through this several times and gone over this, and I can tell you why right now. On ERC 721 received, we have this as set to always returning 1. However, if we go to on ERC 721 received and we look at the spec, it should return a bytes 4. So we are kind of assigning this summary here, and our function summary is saying always return 1, which is not a bytes 4. So then the question is, okay, well, Patrick, why is it only on the list item? You know, withdraw looks good, buy item looks good, cancel item looks good. Why is it only on the list item? Well, if we go back to our code base here, list item is the only one where we call safe transfer from that would call what? That would call our on ERC 721 received. So instead, we want to take one more step. We want to make this also dispatcher true. And I wanted to show you how some of these sanity checks can be very difficult to debug. And we should have used dispatcher equals true for this as well. Now we pull this back up, we run this again, and we finally have a passing invariant here where all of our contracts, gas bad, NFT Marketplace, and NFT Mock are all passing. So we learned a lot already. Let's do a quick summary of what we've learned so far because yeah, we've learned a lot. Number one, we learned how to make ghost variables. And these are variables that are considered part of the contract. However, they're for the purpose of working with Certora. And in order to initialize them, we need to say init state axiom. If we want these ghost variables to not ever get havocked, because anytime a random thing happens, they can get havocked, we need to make them persistent ghost variables like that. We learned about hooks, where we can take different opcodes in the EVM and say, anytime this opcode happens on this storage slot or with these parameters, do something. And for us, the do something was update our ghost variables. We did a hook for log and for store. We said anytime log4 gets called, increase the count. Anytime store gets called, increase the count. And then finally, we did another invariant using our ghost variables. And this is an example of a very simple, beautifully simple invariant. Hey, anytime you update that listings storage variable, you better also emit a log. There should never be a time where there are more listing updates than there are logs. Fantastic. We learned a little bit more about the rule sanity. I know we've talked about this briefly several times, but we learned a little bit more about how it can help you write better rules. We learned about the prover args for the optimistic fallback. Anytime you do a call, the prover goes up, this can do anything, we better havoc, and we need to figure out how to get around that. One of the biggest things that I'm trying to drill into here is that this prover, and this is what it's good for, is going to look for any opportunity to say, hey, this is undefined functionality, or we're not sure what this does. We're going to havoc everything and make random stuff happen. And now that we're in a random state, looks like we can indeed break this invariant. And this is how the symbolic execution of Certora works. It tries to symbolize everything. And if it goes, this variable here can be anything, you havoc, and you have to figure out if you broke something in your formal verification spec, or if you actually have an issue in your code base. So we're learning an absolute ton here. Now let's put all of our knowledge together and let's drill this in with a final rule that we are going to define, which is going to be a lot of fun here. So let's do our final rule. Our final rule here is going to be calling any function should result in, let me zoom in a little bit, each contract having the same state. So this is going to be what we are really using Certora for here. The whole purpose of using Certora was the fact that we have a reference contract, which is going to be our NFT Marketplace, and then a more gas efficient one, gas bad NFT Marketplace. And we want to write some formal verification proof that says no matter what function you call, if you were to call it on NFT Marketplace or gas bad NFT Marketplace, both contracts should essentially end up with the same state or the same solution. And this is going to be an incredibly powerful rule that we're going to write here. And this is going to be a parametric rule. So like we were saying before, parametric rules are going to be rules that contain an undefined method variables. Right, and here we have our rule here. Let me put a little bit of extra space down here. And if we just have method f, ta-da, this now becomes a parametric rule. And now an important note actually about parameters in here versus parameters in here. So you can actually have parameters either in the parentheses of the function definition or inside of the body. And it actually doesn't matter where you put them. They're going to be randomized either way. I asked this question as well. What's the difference between putting variables as rule parameters versus in the rule body? So either method f up here or method in the body. Is there a difference? And the answer is no, there is no difference. The only difference is if you want to add filters, and we'll talk about filters in a second. So this is like method f, env, address k, or address k. You can put them up there, or you can do address k in here. It does not matter. It only matters for filtering. Simply because we have a method f in here, this is now a parametric rule. So what are we going to do in here? What's this rule going to look like? Well, we're going to do a couple things. We're going to call the same function on the NFT Marketplace and gas bad. And then we're going to compare the getter functions to conclude that the contracts are still the same. So if we look up gas bad NFT Marketplace, so at the bottom we have get listing and get proceeds. So we'll compare calling the two of these functions. We could 100% compare storage slots, but since we're using assembly, maybe we don't want to compare storage slots because the assembly we use could put them in different storage slots. So all that's really important is that these getters return the exact same results. And so how are we going to do that? Well, we're going to pass into this rule a method variable, call that method, like I said, on both of these two contracts, and then compare to make sure they're the same. So pretty much exactly what I just said. So let's go ahead and do this. But before we do this, I do want to show you what a filtered rule is and what they look like. So normally, whenever you have a rule with a method f, like I was saying before, you can actually filter this rule or method. So this method f is going to be any function on this code base. So like I said before, if I do f, if I make env like this, and then f of e, excuse me, actually, and call data args, e args, this little bit of Certora says we're calling some function f, which can have any call data in any environment, and we'll call it. However, with our methods, we can also filter them down. Filters allow you to prevent verification of parametric rules on certain methods, and it can be a little bit less computationally expensive than using a require statement to ignore counterexamples for a method. So using filter is going to be similar to doing like require, maybe f dot selector, for example, equals some function selector, right? So filters are just going to be a little bit easier for the Certora approver to work with. And the syntax for filtered functions is going to be filtered like this, and then the function, and we could do like even function dot selector, or what else? There's function dot is view, function dot selector. There's a lot of attributes that go along with these function types. So we could say function dot selector equals, ox, whatever, some function selector we want to be here. And that's how we would filter them out. Basically, filters are just requires for Certora. But we're not going to use filters because we would want to make sure that two of our function selectors match, and the filters block doesn't have access to the different input parameters, so you actually can't compare two method inputs to each other. So we are just going to use the require after all. So we want some method f, and we want to call it on both the NFT Marketplace and gas bad. So I can go ahead and set this rule up saying, okay, there's some env. And remember, I could put the env up here if I wanted. It would be the same as putting it in the body, but we're going to do it like this. Some env, some call data args, and then we go args. But remember, this only calls it on the current contract, right? So us just calling f right here is the same as saying current contract.f. And Certora will go through all the different contracts and run this rule on them. We actually want to run this rule on both the gas bad NFT Marketplace and the NFT Marketplace, and we want to compare the results of the two. So this is where, at the top, we're going to go ahead and add this using line. So we'll say using gas bad NFT Marketplace as gas bad NFT Marketplace, and then using NFT Marketplace as NFT Marketplace. And now what we can do is we can say we're going to call gas bad NFT Marketplace.f and NFT Marketplace.f args, like so. So now we're going to be calling this exact same function on both gas bad NFT Marketplace and NFT Marketplace to compare the two of them. Or this is what we would normally do, except according to the documentation, it is an error to call the same method variable on two different contracts. So we actually want to create two different method variables. So instead of saying method f and using f on both of these, we're also going to say method f2 like this. And for NFT Marketplace, we're going to have it use f2 here with the same e and the same args. Now, the thing is, we still want f2 and f to be the same function. So to make sure that f and f2 are the same, we're going to say require f.selector equals f2.selector. And this is basically the same thing as doing a filter anyways, except for this one actually works. So great. So we have a require, we have some parameters here, and this is going to be our act we're setting up here. Let's get the before and after of the NFT Marketplace. So we want them to both be in the same state. So let's make sure that for both of these contracts, the get listing and get proceeds start in the exact same state. So to do that, we're going to need to add some stuff. We're going to need to add some address, listing address. We're going to need to add a uint256 token ID, right? Because we need NFT address, token ID, and a seller. Let's do address seller like this. And we're going to want to call get proceeds and get listing. So we're going to need to go up to our methods block and add these in here. So function, actually, you just kind of copy this whole thing. The listing returns, we don't need the view function. We do need returns. Listing memory. Oh, that's kind of weird. So listing is a struct. How do we get our code base here to know about the listing? Well, what we can do is, since gas bad and NFT Marketplace both import this INFT Marketplace with this struct, we can just use this as a base class and say INFT Marketplace.listing. So this is how we'll get Certora to know what the makeup of this struct looks like. And this, of course, is going to be env free, right? Because it's a view function. I'll even zoom out a little bit so you can see it like that. And then we'll also want to grab get proceeds, which is a little bit simpler. We'll put that right underneath. Get proceeds, address seller, external. We don't need a view. Returns uint 256 semicolon. So cool. So now we have get proceeds. We have get listing. Down in the bottom here, we can do a little require to make sure these are the same. So we'll say require gas bad marketplace dot get proceeds seeds. Oh, and since get proceeds is also env free, we don't need an env actually, so we probably don't need an enve at all. Excuse me. And this should equal the NFT marketplace dot get proceeds seller, like so. And even though this is env free, we are going to have to put the E variable in here, and you'll see why in just a minute. But for now, we're going to leave it as blank, but you'll see. And then also, we need to require the gas bad NFT, excuse me, gas bad marketplace. Is that what we called it? Gas bad NFT marketplace, excuse me. Gas bad NFT marketplace, gas bad NFT marketplace dot get listing. This is also env free, so we'll say listing ADDR token ID dot price equals. And again, we do the dot price because Certora doesn't really understand structs, so we have to give it a type it understands. Price is a uint 256 inside of that struct, and this should equal the NFT marketplace dot get listing ADDR token ID, like so. And then we copy paste this. Oops. Dot price, excuse me. Then we copy paste this and we do dot seller, like that. If I zoom out, it'll look like this, but I'm going to stay a little bit zoomed in. So, okay, cool. So we're making sure that all of these view functions return the same values prior to the start. And then after the same function gets called on both contracts, we'll say, okay, now we can assert that all of these are still equal. So I'm actually just going to copy all these requires, and I'm going to change these all to asserts now. Because now that we've done the same function to both, it shouldn't matter. These view functions should always return the same thing. Just because we did some crazy gas optimizations to the gas bad NFT marketplace doesn't mean it should differ from our NFT marketplace representation. Cool. So let's give this a whirl, right? Let's try to run this. Let's see what happens. Variable E has not been declared. Oh, E. Whoops. Okay, I do need E. Sorry, I need E because we do want our random methods to have access to E. So we'll add that back in, run this again. And so now you'll see, I told you we were going to run into this error that, hey, what does it say? Missing environment parameter to non-env free function. Wait, what? How's that so? Get proceeds. We said it's env free up here, right? But remember, this is equivalent to saying current contract dot get proceeds. And down here, we're doing gas bad NFT marketplace dot get proceeds. So we would have to add this E in here, or up here we could say gas bad NFT marketplace dot get proceeds. But then we'd also have to do NFT marketplace dot get proceeds. So it might just be a little bit easier. For us to write, for us to add the E in here. And that's what we're going to do. We're going to add the E in here for all of these. E. And let's run this again. And cool, we're getting an output. All right, and now that that's done, we get an output that looks like this. And it says, oh, we have a violation here. Prover found violations. A lot of these calls gave some type of violation. If we scroll down to the bottom, it doesn't tell us what it was. So let's pop over to the prover. The env free func static check passed. Obviously our anytime mapping updated emit event passed because we fixed it. But we have the calling any function should result in each contract having the same state. Gave us this sanity check failed. And if we click into it, we can see on a number of the different functions, we're getting this sanity check failed. We see for withdraw proceeds, on ERC 721 received, get proceeds, buy item, get listing, update listing, cancel listing, update listing, withdraw proceeds. Oh my God, everything was, oh wait, on ERC 721 received gets verified. Oh, that's weird. Okay, well, update listing, cancel listing, okay, blah, blah, blah. Oh, this update listing passed. Wait, didn't we just have one that failed or was considered Vasquez? Yeah, we did. NFT Marketplace.update listing. This one was Vasquez, update listing, and buy item. So if we go in here, it looks like we get this sanity failed for a lot of these, right? And we can see exactly what the methods that were given as parameters in here. So we have NFT Marketplace that withdraw proceeds and on ERC 721 received. Well, of course, this isn't going to pass. Right in here, we have a require that says the two function selectors should be the same. So instead of this being ignored, we get this sanity failed. And this is where if we had the filtered, these would have been filtered out, but because it's a require, down here instead, Certora still shows them. This, I guess, could be an improvement, but basically they're saying, hey, these two functions don't fulfill this require, so this won't work. And you'd see pretty easily if you get rid of this require and you rerun this, a lot of these will actually fail because of this same reason. So it's doing a lot of these compares between these two different functions that have different function selectors. But if we scroll down in here, we do get check marks for what we want. So all the check marks here, NFT Marketplace.ERC 721 receive and gasbad.ERC 721 received do get a check mark. Oh, well, let's keep scrolling. What are the other check marks? Okay, update listed is being compared against update listing, and that also gets a check mark. Okay, keep going. Let's see. What else? Okay. Get listing and get listing. Obviously, those passed. Buy item and buy item. Obviously, this passes as well, etc. So here we actually are verifying what we want to verify, but Certora is adding these runs in here as well. Maybe there's something in our spec that we could update so that it doesn't add those. We could probably hard code these selectors so that instead of saying require these selectors are equal, we require the selectors are from a certain subset of our methods list or something like that. But in any case, it looks like even though this is getting this sanity failed, this is indeed doing what we want it to be doing. And then of course, all we would need to do to get those errors to go away is in our config here, we would just change this to none. You obviously want to be really careful about doing this because maybe you have some dumb rule in here that passes when it shouldn't, but this might be a good case where we set this to none and then boom, all of these would then pass because we don't have this sanity check in here anymore. And this is indeed checking what we want it to check. So what's really cool about this is one of the major hurdles to rewriting your code bases in Assembly or Huff or anything like that is, oh my goodness, I'm so nervous that if we rewrite this in Assembly, we're going to break the functionality. However, what is incredibly badass and what is incredibly cool is that with Certora, with this formal verification, we can just say, no problem, let's compare the functionality of the two and compare the view functions before and after on any function call. And this way, we can do an equivalence check essentially between these two contracts. So I really want to drill this in on how cool this is, okay? I really want to drill this in. We are saying that no matter what, the NFT Marketplace will perform exactly the same as the Assembly optimized GasBad NFT Marketplace, and we have formally verified it as such. We've mathematically proved that when any function is called, no matter what state the contract starts in, it will end up in the exact same state. Now, keep in mind though, we do have some assumptions here. We do have these two being big assumptions, and maybe these are assumptions that you don't want to have. Maybe you don't want to say that these two are already enabled because, of course, these would be the functions that do have some type of reentrancy. So you could do some modular verification here where you say, hey, I want to prove in a different spec that reentrancy isn't possible. Because again, if we get rid of these summaries here in these functions, Certora will havoc this and say, oh, there's some crazy stuff here. So what's beautiful is we've proven this so long as these two assumptions are held. And that is incredibly powerful. We've just learned a ton and we've written two beautiful formal verification specs. And even if you don't think that they're beautiful, you've just learned an absolute ton on how to write formal verification tests, how to mathematically prove stuff, and the likes. So let's do a quick recap of all the stuff we learned because we drilled a lot of stuff into you. So number one, we have our gasbad.conf where we imported all these files and we said we're going to verify our gasbad.spec. We had the rule sanity as none sometimes and as basic sometimes, and we got to see the prover say, hey, this rule might not make sense, and how to optimize for it. We learned about prover args and how we can tweak a lot of the assumptions that we make about our formal verification. And whenever we see any rules in our configuration file, we should immediately know, okay, there are some assumptions being made for this formal verification process. And we want to always keep that in mind when we do formal verification. What are the assumptions that we have about the system? What are we actually formally proving? Should we make our formal verification more or less strict? So we have some assumptions here about optimistic loops and optimistic fallback. We learned about different summaries, in particular the dispatcher summary, but we also learned about always one. We learned about the different havoc summaries. We learned that summaries are essentially a way to say, hey, take this function and just replace it with whatever functionality that we want over here. Normally, whenever we define a function in our methods block, it's equivalent to doing current contract.getListing. However, we could do a little underscore and say, this is almost like a catch-all, and say this is a wildcard, and say that anytime you see a transfer from happen, any call at all, this is going to be, the function summary is going to be what it does. So we're saying anytime anything calls safe transfer from, it's only going to be from our NFT mock safe transfer from, because that is the only place in our entire list of files that has this defined. On ERC 721 is going to be something similar. It can only be from the NFT mock or from our Bad NFT Marketplace because they have this function defined. We played again with env free. We learned how to get a response type from a struct in our methods block as well. We learned about ghost variables and how in order for them to start, we need to give them an initial state and an axiom and set it as kind of similar to what a require statement would look like. These kind of act like variables in our contracts, where anytime some havoc happens, they will get changed. And if we want to say, make these havoc proof, we would say they are persistent to make them havoc proof. Havocing is one of the most important processes in the Certora system. If it can find a loophole, if it can find a way to say, oh, you can do anything here, it will do as such. And that doing anything is called havocing. And havocing your ghost variables means that Certora will try to set them to a variable that will break your invariant or rule. We learned that anytime we update anything in storage or do any opcode, we can use a Certora hook to do some custom action based off of that opcode. And we saw how to do it with store and for log4. We built a beautifully minimalistic invariant here where we just counted the number of listing updates, the number of storage updates, and the number of logs that were emitted and said, hey, there better be at least as many logs as there are storage updates. And then finally, we had this really badass parametric function built here with two different methods, f and f2, where they had the same function selector, and we verified that no matter the starting state, as long as these two contracts, Bad and the NFT Marketplace, as long as they start in the exact same state, no matter what function you call on them, so long as it's the same function, they will end up in the exact same state. And that, my friends, is how we as a community are going to reduce gas in the future. I guess quick tangent, I envision the future, especially with AI helping us write smart contracts, where we write a very readable smart contract in Solidity, and then we rewrite it in Huff or Assembly or raw opcodes, and then we do some equivalence testing with formal verification to prove, yes, indeed, these are the same. Obviously, if you want to do this, you're going to have to spend a little bit more time, but the results are you can have incredibly performant smart contracts. I'll leave it up to you to do so. And with that, my friends, we've come to the end of the Assembly, EVM opcodes, and formal verification course. This was kind of quick, but it was definitely not easy. But you've learned so much along the way. So with all this knowledge, I want you to make sure you pop over to your GitHub. Well, delete all your tabs first of all. You pop over to your GitHub and you make sure to push your projects up here, because your GitHub is really what a lot of these companies are looking for when hiring. And add all this stuff to your Codehack security portfolio or your Cypher security portfolio or just your name security portfolio so people can say, wow, look at all this amazing work this person has done. Projects are absolutely essential for getting careers, and they're essential for you learning and growing. Now that you've gone through this whole thing, there's a number of things that you can and should do. Number one, Codehawks. Just full stop. You should check out Codehawks. Go to the contest and participate. For security researchers, we are additionally going to have formal verification contests on Codehawks as well, where you can practice doing exactly what we just learned in here with our gas Bad NFT Marketplace with Certora, but you can also get paid for it on Codehawks. And this is how you'll improve your skills and continue to get better. As an industry, we're about to usher in a new age of security where we have a lot of well-trained smart contract researchers like yourself. And developers and smart contract researchers like yourself pushing the boundaries are how we're going to get there and how we're going to make Web3 so much better. And you are going to do incredibly well along the way because you've taken this course. So I would love you all to do one more thing. If you are on Twitter, if you're on Farcaster, etc., tweet at us. Give a little @, say hi at Cypher and Updraft. Thank you for X, Y, and Z. Here's what I loved, here's what I hated, and here are the projects that I'm working on now. We absolutely love working with developers and getting feedback on how we can improve and seeing you on your journeys to become successful smart contract developers, security researchers, and just technical people in Web3. Looking forward to you on Twitter, on Farcaster, on name your other social media here, and especially excited to see you on Cypher and Codehawks and see your progress here. And of course, if you're on the GitHub repo associated with this course, we have some more links on where do I go now, what you can start looking into, what you can start doing, where you can learn more, different disclosures and sponsors, etc. So with all this being said, congratulations. Now's a great time to go get a coffee, get some ice cream, or go lift, or go to the gym. You've just learned an absolute ton, and I'm excited to see you apply this knowledge and do very well in Web3. This is Patrick Collins. Let's get froggy. Great job, and signing out.